memorable way in our story of Earth. 4.45 billion years ago, when Earth was a mere 100 billion years old, much of the surface was already hardened with a thin layer of black basaltic crust that floated on a deep ocean of magma and peridotite. Before basalt, it was impossible for any topographic feature to rise significantly above the mean elevation. The magma crystal mush simply wasn't strong enough to hold up the mountain. That situation changed with the production of basalt. Basalt has an average density of 3 grams per cubic centimeter, about 3 times the density of water. That value is about 10% less than the density of the peridotite and its parent magma, more than 3.3 grams per cubic centimeter. Consequently, a floating mass of basalt can have about 10% of its mass above the surface of the heavier magma. For example, a floating mass of basalt 10 kilometers thick will typically form a topographic high more than a kilometer above the magma ocean. And tapered features such as a volcanic cone could easily have risen more than 2 kilometers above the mean. Rather quickly, Earth's surface began to become more varied as a result of this density difference. It's fun to imagine what Earth looked like from space. For example, from the safe distance of the surface of the young moon. Black, with red highlights, must have dominated. Earth's basaltic crust was black, but it was broken by long, curving red cracks and localized luminous highlights where fountaining volcanoes and magma flows broke the surface. Those volcanoes must have generated lots of volatiles along with plumes of dirty white ash-laden steam, so some of the surface would have been obscured by the growing atmosphere. This ancient version of our home planet is unfamiliar and hostile. You would not have been able to survive in such an alien and violent landscape. Meteors up to kilometers across frequently bombarded the surface. These space bombs cracked the basaltic crust and splattered chunks of rocks and blobs of magma across the surrounding plains. There must have been thousands of volcanic cones all across the globe, each belching out steam and other volatiles. But there was no trace of free oxygen in the atmosphere. Added to this harsh environment were the severe consequences of the nearby moon. That hovering world, slowly receding, but still less than a tenth of today's Earth-Moon distance, would have generated globe-spanning magma tides. The surface, especially around the equator, must have repeatedly cracked and buckled, opening fissures that delayed formation of a solid surface. The moon's uncomfortable proximity also meant that Earth continued to rotate much more rapidly than today. The consequent short days, less than 6 hours long, were accompanied by cyclonic storms and megatornadoes much more severe than anything experienced today. In spite of these tumultuous surface effects, the deeper interior was settling down into a more or less steady state. Peridotite formed by the fractional crystallization of olivine and pyroxene. Basalt formed by the partial melting of peridotite, and the very crystals, rocks, and melts rose or sank depending on their relative densities. The partially molten interior separated into volumes of distinctive chemical compositions. Silicate-rich zones that would ultimately become the continents, the ocean floor, and the underlying layers of deep crust and upper mantle. These processes of chemical separation foreshadowed subsequent segregations of elements into the oceans and atmosphere, and ultimately into plants and animals. All of these processes of elemental selection and concentration, and they've all continued right up to today. In all of these earliest stages of Earth's evolution, heat was the principal agent of change. Heat caused the entire planet to melt, and thus divided the denser iron core from the less dense silicate mantle and crust. Volcanism, also driven by heat, separated the volatiles that would eventually become oceans and atmosphere in the rocks. Earth's earliest history is marked by a succession of heat-driven element separations. It was because of heat that Earth spent a brief part of its infancy as a blackened, basalt-covered world. But that phase couldn't last long on a volatile-rich planet. The globe was about to be enveloped by a new volcano-born layer of general picture of Earth's initial cooling and the subsequent release of volatiles to form the atmosphere and oceans. But much of what we deduce boils down to informed speculation based on lab experiments and computer models. Hardly any rocks are known to have survived from the Hadean Eon. Before examining the early origins and evolutions of the ocean, we should make an inventory of what we don't know. The collective evidence of astronomy and moon rocks suggests that the moon formed by a giant impact. Yet we aren't sure the exact timing of that event, nor do we know the details of Thea's final trajectory. We can imagine the rain of incandescent silicate droplets that must have followed the big thwack, but we don't know how long it took to cool Earth's superheated surface. We're equally uncertain about the fast-changing orbital dynamics of the young Earth-Moon system. How fast did the moon recede, and Earth therefore slow its frenetic rotation? By the same token, scientists are unsure when the oceans first formed, or where they formed, or what they looked like. We can deduce a general picture of Earth's initial cooling and the subsequent release of volatiles to form the atmosphere and ocean, but much of what we deduce boils down to informed speculation based on lab experiments and computer models. Hardly any rocks are known to have survived from that early period, but there are some pretty convincing ideas out there, and I want to give you a version of the story that's probably now. With active volcanism,
defended many theories as to their origins. What is crystal clear is that liquid water covers nearly 70% of Earth's surface. Every molecule of water cycles in a continuous waltz, exchanging heat, influencing climate, coming and going. This unique hydrogen-oxygen compound has transformed Earth's surface through erosion, weathering, transport, and ultimately, life.
We've come a considerable way in our story of Earth. 4.45 billion years ago, when Earth was a mere 100 million years old, much of the surface was already hardened with a thin layer of black basaltic crust that floated on a deep ocean of magma and peridotite. Before basalt, it was impossible for any topographic feature to rise significantly above the mean elevation. The magma crystal mush simply wasn't strong enough to hold up a mountain. That situation changed with the production of basalt. Basalt has an average density of 3 grams per cubic centimeter, about 3 times the density of water. That value is about 10% less than the density of the peridotite and its parent magma, more than 3.3 grams per cubic centimeter. Consequently, a floating mass of basalt can have about 10% of its mass above the surface of the heavier magma. For example, a floating mass of basalt 10 kilometers thick will typically form a topographic high more than a kilometer above the magma ocean. And tapered features such as a volcanic cone could easily have risen more than 2 kilometers above the mean. Rather quickly, Earth's surface began to become more varied as a result of this density difference. It's fun to imagine what Earth looked like from space. For example, in the safe distance of the surface of the young moon. Black, with red highlights, must have dominated. Earth's basaltic crust was black, but it was broken by long, curving red cracks and localized luminous highlights where fountaining volcanoes and magma flows broke the surface. Those volcanoes must have generated lots of volatiles along with plumes of dirty white ash-laden steam, so some of the surface would have been obscured by the growing atmosphere. This ancient version of our home planet is unfamiliar and hostile. You would not have been able to survive in such an alien and violent landscape. Meteors up to kilometers across frequently bombarded the surface. These space bombs cracked the basaltic crust and splattered chunks of rocks and blobs of magma across the surrounding plains. There must have been thousands of volcanic cones all across the globe, each belching out steam and other volatiles. But there was no trace of free oxygen in the atmosphere. Added to this harsh environment were the severe consequences of the nearby moon. That hovering world, slowly receding, but still less than a tenth of today's Earth-Moon distance, would have generated globe-spanning magma tides. The surface, especially around the equator, must have repeatedly cracked and buckled, opening fissures that delayed formation of a solid surface. The moon's uncomfortable proximity also meant that Earth continued to rotate much more rapidly than today. The consequent short days, less than 6 hours long, were accompanied by cyclonic storms and megatornadoes much more severe than anything experienced today. In spite of these tumultuous surface effects, the deeper interior was settling down into a more or less steady state. Peridotite formed by the fractional crystallization of olivine and pyroxene. Basalt formed by the partial melting of peridotite. And the very crystals, rocks, and melts rose or sank depending on their relative densities. The partially molten interior separated into volumes of distinctive chemical compositions. Silicate-rich zones that would ultimately become the continents, the ocean floor, and the underlying layers of deep crust and upper mantle. These processes of chemical separation foreshadowed subsequent segregations of elements into the oceans and atmosphere, and ultimately into plants and animals. all of these processes of elemental selection and concentration, and they've all continued right up to today. In all of these earliest stages of Earth evolution, heat was the principal agent of change. Heat caused the entire planet to melt, and thus divided the denser iron core from the less dense silicate mantle and crust. Volcanism, also driven by heat, separated the volatiles that would eventually become oceans and atmosphere from the rocks. Earth's earliest history is marked by a succession of heat-driven element separations. It was because of heat that Earth spent a brief part of its infancy as a blackened, basalt-covered world. But that phase couldn't last long on a volatile-rich planet. The globe was about to be enveloped by a new volcano-born layer of brilliant blue. We can deduce a general picture of Earth's initial cooling and the subsequent release of volatiles to form the atmosphere and oceans. But much of what we deduce boils down to informed speculation based on lab experiments and computer models. Hardly any rocks are known to have survived from the Hadean Eon. Before examining the early origins and evolutions of the ocean, we should make an inventory of what we don't know. The collective evidence of astronomy and moon rocks suggests that the moon formed by a giant impact. Yet we aren't sure the exact timing of that event, nor do we know the details of Thea's final trajectory. We can imagine the rain of incandescent silicate droplets that must have followed the big thwack, but we don't know how long it took to cool Earth's superheated surface. We're equally uncertain about the fast-changing orbital dynamics of the young Earth-Moon system. How fast did the moon recede, and Earth therefore slow its frenetic rotation? By the same token, scientists are unsure when the oceans first formed, or where they formed, or what they looked like. We can deduce a general picture of Earth's initial cooling and the subsequent release of volatiles to form the atmosphere and ocean, but much of what we deduce boils down to informed speculation based on lab experiments and computer models. Hardly any rocks are known to have survived from that early period, but there are some pretty convincing ideas out there, and I want to give you a version of the story that's probably as good as any for now. One thing is very clear. With active volcanism and abundant volatiles, Earth could not remain black and dry for long. Thundering volcanic vents blasted hot nitrogen, carbon dioxide, water vapor into the thickening atmosphere at rates of many millions of tons per day. The atmophile elements and compounds, the atoms and molecules that are gases in our atmosphere, were the same atoms and molecules that formed all the different ices of the former solar nebula. In fact, they're the exact same atoms that you're breathing right now as you listen to this lecture. They're the atoms that contribute to all the tissues of your body. And those volatiles have played many roles throughout Earth history, including in the rapidly evolving Hadean Earth. Hot water played several crucial roles in the evolution of rocks and minerals. Water and carbon dioxide mixed with magma, which lowered the melting temperature of the rock significantly and turned the liquid rock into a superheated soup that more quickly ascended to the surface. Once that water saturated magma came close enough to the surface, all the dissolved gases transformed rapidly and violently from liquid to expanding gas. The resultant massive volcanic explosions were like mountain-scale replicas of a shaken, warm soda can. Rocks and magma and ash were blasted across the countryside. Water-rich fluids associated with magmas played another key role. They dissolved and concentrated all sorts of rare elements that don't find a ready home in the common rock-forming silicates. If you look at the periodic table, you see the light elements lithium, beryllium, boron. They were concentrated in the hot liquid water phase. Many of the elements that form common salt-like minerals also entered the aqueous phase, sodium and chlorine, as well as fluorine, sulfur, potassium. So were rare metal elements like silver, gold, and uranium, and many more that would eventually become concentrated in the world's great ore bodies. As bodies of water accumulated in larger and larger volumes, water began to shape the surface in ways that volcanoes and meteorites never could. Roaring rivers cut deep valleys, while crashing waves ate away at shorelines. Water thus became the principal agent of rock erosion, which produced Earth's first sandy beaches, along with ever thicker accumulations of near-shore sediment wedges. water quickly became the chief architect of Earth's surface. This focus on water, on oceans and atmospheres, can appear to reflect a rather anthropocentric view. Water is volumetrically a trivial fraction of the whole planet. All the oceans today represent only about 0.02% of Earth's total mass. And the atmosphere is much less than that, about 1 part in a million of its bulk. But the oceans and atmospheres have always exerted, and they continue to exert, disproportionately great influences on our planet. H2O, as much as any chemical, makes Earth what it is today. So, let's take a step back and review the character and properties of the 5 principal elements that contribute most to Earth's outermost layers: the ocean and the atmosphere. These are not the big 6 elements that predominate in the mass of the planet as a whole. Only oxygen is important enough to be in both groups. Instead, the 5 elements here are hydrogen, oxygen, nitrogen, carbon, and sulfur. All assume important and rather different roles as Earth's mobile gaseous components. All 5 of these elements are produced abundantly in large stars, so all are common in the cosmos and are widely dispersed in supernova explosions. All 5 of those elements are important in the most primitive Ci carbonaceous chondrite meteorites that formed more than 4.56 billion years ago in the solar nebula. Now recall, the average composition of Ci chondrite meteorites is similar to that of Earth as a whole. The major lithophile and siderophile elements, oxygen, silicon, aluminum, magnesium, calcium, iron, remarkably similar in relative proportions, and that goes for numerous less common elements as well. But even a casual glance at the composition of Ci chondrites proves that Earth is a highly depleted planet in volatile elements. For example, these most primitive chondrites average more than 3% carbon, but if you add up all Earth's known carbon reservoirs, it's less than 0.1%. Either there's a vast and hidden deep carbon reservoir, or most of it's been lost. Similarly, the average Ci chondrite holds as much as 100 times more water compared to the bulk composition of Earth. This kind of extreme compositional disparity points to the early era of solar nebula distillation. Most of the volatiles that must have originally occurred in the vicinity of the rocky planets were blown by the solar wind to the orbital distance of Jupiter and beyond. The key to understanding how Earth diverged from blasted and inhospitable worlds like Mercury and the Moon lies in its peripatetic volatiles. We can be confident that the next phase of Earth history, it's becoming a blue planet, rested on the behavior of water. Yet, understanding the detailed history of the oceans and atmospheres is extremely challenging. That's because essentially nothing remains from Earth's first 500 million years. None of Earth's volatiles survives in an unaltered state. All the water, the nitrogen, the carbon, the sulfur have been recycled over and over again, countless thousands of times, because the same atoms are used over and over again. If the atoms have been recycled so often, what possible clues could have survived? Again, the most primitive chondrite meteorites are a useful quantitative starting point, and we do have a modest store of rocks and mineral samples from Earth's first billion years as well. Those data, coupled with all the ancient meteorites and lunar samples, inform speculations. Equally important are the distinctive physical and chemical characteristics of the volatile elements and their molecules. 4 ingredients: nitrogen, carbon, sulfur, and water are potentially the most important volatile elements. Nitrogen is the easiest to deal with because it's a chemically inert gas that rarely forms minerals. Nitrogen plays no significant role in the formation of rocks, and it concentrates in the atmosphere. Indeed, that 7th element of the periodic table only had important chemical roles since the rise of life, which cycles nitrogen in ways that were unknown during the first billion years of Earth history. Carbon and sulfur, likewise, will come into much greater prominence after the origin of life in a billion years. So of the 4 principal volatile ingredients, water has played the longest central role. Water water's many roles in Earth history are a consequence of the distinctive chemical and physical properties of H2O, the oxide of hydrogen. Hydrogen is the first element of the periodic table, while oxygen is the eighth. Neither element has a magic number of electrons, so two hydrogen atoms share their electrons with one oxygen. The result is the V-shaped H2O molecule with a larger oxygen atom flanked by two smaller hydrogen bumps, an arrangement not unlike Mickey Mouse's ears. Given oxygen's propensity as an electron acceptor, it borrows the two electrons from the two hydrogen atoms and thus develops a slightly negative charge. The two hydrogen atoms develop a correspondingly slight positive charge. An important consequence is that water molecules are polar. They have a positive and negative electric charge ends, and that polarity accounts for many of water's distinctive properties and behaviors. Water is an excellent solvent because the positive and negative ends can exert strong electrostatic forces that tend to pull apart other molecules. That's why table salt, sugar, many other chemicals dissolve so rapidly in water. It's also why the oceans are salty. Rocks can take a long time to partially dissolve, but over an accumulated millions of years, ocean water has become enriched in virtually the entire periodic table of the elements. It's just hard to imagine how much is dissolved in the ocean, but think about gold. Every cubic mile of salty ocean water contains 11 kilograms of gold. That's more than $500,000 worth at recent prices. In fact, we don't have the technology to extract the gold, and if we did, the price of gold would probably drop pretty fast. The amazing ability of water to dissolve and transport other chemical compounds is what makes it such an ideal medium for the origins and evolution of life. All known life on Earth, and some researchers argue that all possible life in the cosmos is dependent on water. The polarity of water molecules dramatically affects the properties of both liquid and ice. Water molecules bond strongly to each other as the positive side of one water molecule attracts the negative side of other molecules. As a result, ice is unusually strong for a molecular solid. You probably know that if you've ever slipped while ice skating. Ice also has an unusually high melting temperature for a small molecule. Ice won't melt until 32 degrees Fahrenheit, compared to minus 108 degrees for solid ammonia, that's NH3, minus 109 degrees for solid carbon dioxide or dry ice, and minus 297 degrees Fahrenheit for methane or natural gas, that's CH4. Another consequence of water's unusually strong intermolecular forces is its high surface tension, which is a fascinating property that allows small insects literally to walk on water. Surface tension also facilitates capillary action. That's the ability of water to rise up against the force of gravity through the stems of vascular plants. That's why trees can grow to heights hundreds of feet above the land, even though they don't have a water pumping system. Yet another phenomenon related to surface tension is rounded raindrops, which are drawn into their shape by the strong mutual attraction of water molecules. Raindrops are absolutely vital to maintaining Earth's unusually rapid water cycle. It turns out that non-polar molecules like methane and carbon dioxide can't form droplets as easily. So they would probably just float in the atmosphere as a fine, pervasive mist. Rain might be unlikely on a planet without polar atmospheric molecules. So the cycling of volatiles would probably be much slower and certainly very different in character. Strong bonding between water molecules leads to yet another of water's curious and critical properties. Turns out that liquid water is 10% denser than solid ice. That's odd. In almost every other known chemical compound, the solid state is denser, so crystals sink in their liquid. That situation is intuitively logical because a repeated packing of the same molecules in a crystal contrasts with a more random distribution in a liquid. One analogy is the way you might store shoe boxes in the back room of a shoe store. It saves a lot of volume if you stack everything in neat rows. A random pile, like chaotically tumbling molecules in a liquid, would always seem to occupy more volume, but that's not the case with water. The V-shaped H2O molecules actually pack more efficiently in their random liquid state than orderly ice crystals. And important consequences follow. Whether it's an ice cube in your drink or a frozen ice layer on a pond or river, the ice floats. Were it not for this curious trait, many bodies of water would freeze from the bottom to the top, rather than forming a relatively thin surface layer of ice, and many bodies would thus freeze solid bottom to top. One could imagine that aquatic life would be severely challenged in cold regions of such a frozen world, and the vital water cycle would certainly come to a screeching halt once everything was solid. And here's another really interesting characteristic of water, even so-called pure water. It isn't ever pure H2O, no matter how carefully you might filter or distill water. It's never made entirely of H2O molecules. Inevitably, a very small fraction of those 3 atom units break apart into 2 smaller units. They're positively charged hydrogen ions, or hydrons. Those are simply H plus ions, which are nothing more than individual protons without any electrons attached. And there are also negatively charged hydroxyl groups, or OH minus molecules. Now, because hydrons have positive charges, the hydrons quickly latch on to the more negative oxygen end of water molecules to produce H3O plus hydronium ions. So, pure water at room temperature has negative hydroxyls and positive hydroniums. And these components have to occur in equal concentrations to maintain the totally neutral electric charge. That's a requirement of any liquid. Turns out that the concentration of positive hydronium and negative hydroxyl groups is about 1 part in 10 million. In chemical terms, that's 10 to the minus 7th, or 1/10 millionth of a mole of hydroxyl and hydronium per liter of water. This arcane concentration measurement is usually reported as a power of hydrogen, or pH, of 7. Now, 7 is admittedly a nice round number of convenient size, but this definition of pH is frustratingly obscure. pH is the negative logarithm of the hydrogen ion concentration expressed in moles of H plus per liter of solution. Okay, when describing any body of water, and Earth's oceans are a prime example, a major focus is the bulk composition, both the pH and the salt content. Turns out that these 2 chemical properties are closely related. Water readily dissolves lots of impurities, some of which carry a positive electrical charge, like the electron donor elements sodium, which forms sodium plus 1 ions, and calcium, which forms calcium plus 2 ions. Other electron acceptor elements or molecules have negative electrical charges. Common examples are chlorine, which forms chlorine minus 1 ions, and also carbonate ions. That's CO3 groups with a minus 2 charge. An important rule of thumb is that the net electrical charge of any bulk water solution has to be 0. There has to be an exact balance between the total number of positive charges and negative charges. In pure water at room conditions, the requisite 10 to the minus 7th mole of positive hydronium ions is exactly matched by 10 to the minus 7th moles of negative hydroxyl ions. But the balance can be achieved in other ways. In an acid, there are more hydroniums than hydroxyls. The excess positive hydronium ions are matched by negative ions like chlorine. That's what happens in hydrochloric acid, for example. Similarly, in bases, excess negative hydroxyl ions are balanced by positive ions like sodium or potassium, or calcium, magnesium. The resulting molecules are called hydroxides. For example, sodium hydroxide, and they are some of the most common bases in chemistry. The strength of an acid or a base can be quantified on that arcane pH scale. Values of pH less than 7 indicate acidic solutions, those with more H3O plus than OH minus, more hydroniums than hydroxyls. A slightly acidic solution with pH 6, which is quite typical of untreated tap water in many localities, has 10 times more hydronium ions than the neutral solution at pH 7. Then increasingly strong acids include coffee, that's about pH 5 with 100 times more hydronium. Then there's vinegar or acetic acid at pH 3 that has 10,000 times more hydronium, and lemon juice with citric acid at pH 2 with 100,000 times more hydroniums. And we can do the exact same kind of survey for common bases, all of which have more hydroxyls than hydroniums, and that's pH values greater than 7. Baking soda, it has an informal chemical name of sodium bicarbonate, but it's really sodium hydrogen carbonate, and it has a pH of about 8.5. The common antacid, milk of magnesia, it's magnesium hydroxide. It has a pH equal to 10, and household ammonia cleaners can have pH in excess of 12. And we'll see throughout this course the changing pH and salinity of Earth's ancient oceans remains topics of debate. Water is among the most abundant chemicals in the universe. It seems like almost everywhere we look, we find more. Ground-based telescopic observations can be tricky at times, since water in our own atmosphere can get in the way. But really, concentrated deposits of H2O in space stand out. Such is the case with one distant galaxy-sized object, a quasar named APM 08279 plus 5255, which has a giant black hole at its center. Judging from its immense distance from Earth, this quasar is 12 billion light years away. So we're seeing the object as it appeared during the first 2 billion years of the universe. This quasar is the wettest known place in the cosmos. It has an estimated 140 trillion times all the water in our oceans. Now, it's admittedly galaxy-sized, but that's an immense amount of very old water. It proves that water has been a ubiquitous chemical in the universe for almost its entire history. Astronomers have also found lots of younger and smaller water concentrations in space. Some objects, like those in the Kuiper Belt and other distant parts of our solar system, reveal an icy surface by their distinctive spectral signature. One telltale sign is a weak absorption of infrared radiation with wavelengths of about 1/10,000,000th of an inch. This absorption provides a spectroscopic fingerprint that indicates many comets. Some asteroids also incorporate significant amounts of ice or snow. All of the gas giant planets hold significant stores of water vapor in their dense atmospheres, and Saturn's bright rings are made principally of water ice. And we've seen that Jupiter's large moons, Europa and Callisto, may well have thick ice coatings over even deeper encircling oceans of water. The situation at first glance seems quite different for the terrestrial planets. Mercury appears desiccated. It's too close to the sun for surface water to remain, except for small amounts in the shadowed craters near the sunless poles. Venus probably had some water early on, but today it appears to be almost totally devoid in near-surface H2O. Its atmosphere is superheated carbon dioxide and lacks water. The story of Mars is much more complicated. There's no question that Mars had quite a bit of water locked into its white polar ice caps. Those features expand and recede along with a 687-day cycle of Martian seasons. The ice caps are easily seen from Earth, so astronomers have long speculated that the red planet might be a wet world, even a living world. In the 1870s, during one particularly close approach of Mars to Earth, the Italian astronomer Giovanni Schiaparelli documented several dark, linear features which he interpreted as natural, possibly water-bearing channels, canali in Italian. However, the English translation of Schiaparelli's descriptions erroneously called them canals, and that word has an implication of high-tech, engineered structures. Well, the idea of an intelligent, extinct Martian race took on a life of its own. The most famous Mars life enthusiast was a Harvard-trained astronomer, Percival Lowell. In the 1890s, he became obsessed by Schiaparelli's discoveries. He was a wealthy person. He was wealthy enough to construct a private observatory in Flagstaff, Arizona, the Lowell Observatory, where he devoted decades to the study of Mars. Using a state-of-the-art 24-inch telescope under generally clear Arizona skies, Percival Lowell imagined he could resolve an elaborate network of canals stretching from the presumably ice-covered poles all the way to the dry equator. He translated his findings into 3 immensely popular books. First came Mars in 1895, then Mars and its canals in 1906, and finally Mars as the abode of life in 1908. In these books, Lowell goes so far as to describe the last desperate technological masterpiece of a now lost, water-starved race. You can imagine how Lowell's fanciful findings fueled a lot of science fiction stories and novels. The most famous is H.G. Wells' 1898 classic, The War of the Worlds. But this kind of speculation did not convince the scientific community that Mars is wet, much less that it's living. It's almost impossible to prove there is water on Mars with an Earth-based telescope. That's why NASA has played such a major role in our growing understanding of the red planet. Space exploration of Mars began with a flurry of sophisticated flyby missions, starting with Mariner 4, which sped past Mars in 1965, and then orbiters. The first Mars orbiter was Mariner 9 in 1971, and then landers, starting with Viking, which landed on Mars in 1976. Even with these advances, there was no definitive evidence for any extensive Martian water repositories. The first unambiguous evidence for polar water ice came with the Viking missions, which made spectral measurements in the late 1970s. But it was only since 2000 when a combination of Mars orbiting satellites and analytical machines on the Phoenix lander, the Spirit, and Opportunity rovers that the true vast extent of water and the nature of its repositories of Mars has been revealed. And so in the next lecture, we'll discover how the latest round of NASA missions and other research projects have dramatically changed our understanding of water throughout the inner solar system, from Mars to our moon to Earth itself. How much water is there? In particular, how much water is on Mars and the moon? Where is that water, and how accessible is it to future colonists? For Mars, answers to those questions are now coming from a succession of amazing Mars orbiters and landers, most courtesy of NASA. One of the most important discoveries about Mars, a finding that has only come into focus in the early 21st century, is that Mars has a lot of water, most of which occurs as subsurface permafrost and maybe some groundwater in deeper zones where it's warm. These hidden repositories are potentially huge, and they're for the most part isolated from the dry outermost layer. The first substantive hints the true extent of subsurface water came from the Mars Odyssey. That's a spacecraft in 2002. Mars Odyssey carried a sophisticated neutron spectrometer, which measures neutrons that are dislodged when cosmic rays encounter hydrogen near the Martian surface. In this case, hydrogen means either water or else hydrous minerals like clays, which require water to form. The Mars Odyssey instrument package detected such neutrons from a wide swath of the Martian surface, from high latitudes near the poles to the equator. However, the form of water, liquid, or ice, or a hydrous mineral couldn't be resolved. Then in 2007, NASA's Mars Reconnaissance Orbiter offered a much higher resolution picture of the buried water by employing ground-penetrating radar. That technique records reflected pulses of microwave radiation, which can be used to distinguish layers of rock from water or ice in the outer 1,000 feet of the Martian surface. Rock is much more reflective of microwaves than water or ice. If microwaves penetrate more deeply, as measured by increasing times until the reflection is recorded by the orbiter, then more ice is present. These pioneering measurements pointed to a vast glacier-scale underground accumulations of water ice in the mid-southern latitudes, and more recent similar measurements by the European Space Agency's Mars Express Orbiter point to deep ice across much of the planet. There are places near the South Polar Ice Cap, for example, with ice-rich zones more than 1,500 feet thick. It now appears that Mars has enough near-subsurface frozen water to form a globe-spanning ocean hundreds of feet deep. NASA's Phoenix lander and its amazing two rovers, Spirit and Opportunity, fed scientists the most wonderful data for years beyond their projected lifetimes. And they detected a variety of such mineral evidence. And then NASA's amazing Curiosity rover began doing the same. Water-rich clay minerals, which suggest rock weathering in the presence of water, turn out to be rather common in the near-surface environment of Mars. Much of the near-surface hydrogen-rich material observed by Mars Odyssey's neutron experiments were probably clay minerals. Equally compelling are so-called evaporite minerals, which are characteristic of dried-up lakes or oceans. A variety of these minerals, notably flat deposits of distinctive sulfates, point to dried-up bodies of water. And opal is a poorly crystallized variety of quartz that typically forms in wet sediment, common in the ocean floor. It's also found on Mars. There's much more evidence for water at the local and planetary scales, evidence that water once flowed freely across the sculpted Martian surface. The highest resolution photographs of the Martian surface, for example, those obtained by telescopic cameras on NASA's Mars Global Surveyor and Mars Reconnaissance Orbiter, they're amazing. They reveal clear signs of rivers, ancient boulder-strewn branching valleys and systems of gullies, teardrop-shaped islands and ancient riverbeds, water-induced slumping features on steep hillsides, and even complex braided stream channels. All of these landforms are diagnostic of flowing water. What's more, many of those features cut through layers of sediment reminiscent of earth deposits laid down in shallow lakes or seas. There's even a suggestion of a global high water mark, where such a body of water may have left ancient beach-like terraces. These characteristic landforms girdle the northern hemisphere of Mars, which happens to be topographically quite a bit lower than the southern hemisphere. Some planetary scientists conclude that one continuous ocean covered most of the northern latitudes, more than a third of the Martian surface, to an average depth of 1,800 feet. If that's true, it's quite possible that Mars may have been a blue, ocean-covered, life-giving planet many millions of years before Earth. By the way, whatever water Mars has left, it's a lot less than the way it started. Gravity, or I should say rather the lack of gravity, is the culprit. Mars is too small to hold on to its hydrogen. Water molecules evaporate, but they're a bit too massive to just fly off into space. The trouble is that cosmic rays split the water into two, into one OH molecule and one hydrogen atom, and that isolated hydrogen atom can fly off into space. Over a span of billions of years, Mars has lost a lot of hydrogen, and that translates directly to losing a lot of water. Only the water locked deep beneath the surface is immune from this kind of loss. Let's shift our focus to Earth's moon. Mars may have a lot of water, and it may have once had a lot more, but the moon appears to have always been a dry place. By conventional wisdom, it's bone dry. In fact, it's a lot drier because bone retains a significant amount of water even when it's bleached white in the desert sun. Several lines of evidence support this contention of a dry moon. For one thing, Earth-based telescopes find no characteristic infrared absorption. Even more convincing, the Apollo moon rocks had no traces of water, at least according to the analytical capabilities of the 1970s. The fact that iron metal persists on the lunar surface for 4 billion years is yet another indication that there's not even a trace of corrosive water. But you know, conventional wisdom is a funny thing. Sometimes someone will come along and challenge what most other people think is true. And every so often, we learn something quite new in the process. That's what happened with the story of lunar water. Not one, but two new findings provide convincing evidence that the moon is not as dry as we once thought. Spacecraft observations of the moon's surface provide one line of evidence that's not too surprising. We know that comets must slam into the moon from time to time. And when they do, some water must be added to the surface. A lot of that water must gradually escape back into space, but if a comet strikes near one of the moon's poles, then some ice could concentrate in a perpetually dark crater floor. The the coldest places on the moon surface. Temperatures never get close to the melting point of water, so ice could persist. The first hints of such crater floor ice came from a single flyby of the Clementine mission in 1994. Radar measurements were consistent with deposits of water ice, though a lot of planetary scientists were unconvinced. The Lunar Prospector spacecraft, employing neutron spectroscopy 4 years later, detected significant concentrations of hydrogen atoms, a sign of either water ice or hydrous minerals near the poles. That result also raised objections. After all, there must be a significant accumulation of hydrogen ions implanted in the lunar soil by billions of years of the sun's solar wind. That could be a more likely source of this signal. Now, fast forward a decade. Some NASA scientists had the neat idea of smashing the big upper stage of an Atlas rocket, that's a 30-foot-long, 2-ton chunk of metal, into one of those craters near the pole, and then looking at the impact debris for signs of water. The consequent mission, the Lunar Crater Observation and Sensing Satellite, NASA called it the CROSS because NASA loves acronyms. Anyway, they targeted a shadowed south polar crater called Cabeus. The impact took place on October 9th, 2009, and it produced a fair-sized plume of dust and debris visible in Earth-based telescopes. The bottom line, there was a small but significant amount of water. All of this renewed interest in lunar water led to yet another discovery, this time in old data. Roger Clark of the United States Geological Survey re-examined decade-old data collected during a lunar flyby on August 19, 1999 by the Cassini-Huygens mission, which was on a 5-year journey to study Saturn. It turns out that Cassini's infrared camera had picked up clear evidence of lunar water. That fingerprint-like absorption feature in the infrared spectrum. At the time, he didn't follow up because everyone knew the moon was dry. And those discoveries by Lacrosse and Cassini were further reinforced by another mission, this one, the Indian Chandrayaan #1 spacecraft, which conducted its own infrared observations of the lunar surface. 3 different studies, complementary data from Lacrosse, from Cassini, from the Indian mission, appeared together in the October 23, 2009 issue of Science. And then there were findings, which I'll get to in a minute, that the Apollo moon rocks contained previously undetected water. And that suggested the moon's total water might be even greater. Based on this flood of data, there can be no question that there's water on the moon. It's true, this water may be only a minor constituent of the otherwise volatile poor moon, but even a small quantity of water might be a tremendous asset for future moon colonists who might employ sunlight to split ice into life-sustaining oxygen and energy-rich hydrogen. Lunar orbiter and flyby missions proved that there's water on the moon. What are those apparently dry Apollo moon rocks and soils? In the 1970s, the most sensitive analytical methods then available detected no trace of water. But analytical methods have improved by leaps and bounds. 3 decades after the Apollo missions, my colleague Eric Howry and his co-workers at the Carnegie Institution employed one of these new techniques. Colorful green glass beads, most no larger than a pinhead, are among the commonest constituents of lunar soils. These tiny, revealing objects are a consequence of violent surface volcanism that must have atomized magma in explosive eruptions billions of years ago. That kind of explosive volcanism implies there must have been a significant component of expanding volatiles, and water is certainly the most likely choice. The idea that the glass beads might contain water wasn't new. Decades earlier, several other scientists had analyzed lunar glass beads looking for water, but it's not easy to see traces of hydrogen. The detection limit in the 1970s was perhaps 100 parts per million water, and that value required analysis of many glass spheres at the same time. At that level of precision, the glass appeared to be dry. Eric Howry has access to much more sensitive instruments. An ion microprobe. This technique, not available to the first generation of scientists who study moon rocks, is ideally suited for detecting trace amounts of hydrogen. The ion probe employs a narrow, high-energy beam of atoms that focuses onto a sample and measures the atoms that are blasted off. With this amazing machine, Haury measures water concentrations as low as 1 part per million. And he can make these measurements on sample areas as small as a millionth of an inch. Here's what Haury and his coworkers did that was so clever. They mounted and polished a variety of spherical glass beads so that their circular cross-sections were revealed in the ion probe. That sample preparation meant that they could scan across the beads and measure the water content from rim to core. They found the outer rims to be extremely dry, with only a few parts per million water, just as you might expect from the results of earlier bulk analyses. What was really new and exciting about Haury's analysis was that the centers of the largest beads hold as much as 100 parts per million water. Now, that amount may not sound like much, but what's preserved in the glass beads must be only a tiny fraction of the water that was originally there. For one thing, a great deal of water certainly boiled off during the original volcanic eruption, and a lot more water has gradually evaporated into space over billions of subsequent years of lunar history. That's why the rims of the lunar glass beads are so much drier than their cores. Most of the original water has been lost, but based on what remains, Haury and colleagues calculate that the magma's original water content may have been as high as 750 parts per million. That's a lot of water. In fact, it's comparable to the water content of many volcanic rocks on Earth. And it's more than enough water to drive explosive volcanism. What's more, if that much water drove explosive volcanism on the moon billions of years ago, then a lot of water must still be stored somewhere deep inside the moon today. The discovery of significant water on both Mars and the moon is exciting and points to an abundance of water throughout our solar system. Nevertheless, Earth remains the one and only ocean-bound world in our vicinity. So how much water does Earth hold? What forms does it assume? Where does it reside? How does it move? This story is complicated, and it's constantly being updated. As recently as the 1990s, most scientists thought the oceans were by far the largest repository of water on Earth, storing about 96% of all the accessible inventory. Ice caps and glaciers are a distant second, accounting for about 3% today, though that figure may have risen to 5 or 6% with the peak advance of glaciers during the Ice Age. Groundwater, including all of the near subsurface water that fills aquifers, as well as the more widely dispersed deep water, represents 1%, and all the lakes, the rivers, the streams, the ponds, the atmosphere combined count for no more than about 1/100% of Earth's available water. This near-surface water is constantly moving from one reservoir to another on scales of days to millions of years. Water molecules evaporate from the oceans. They fall as rain into lakes and rivers. They penetrate the ground into aquifers and become locked in ice at the poles. Great ocean currents, rivers of warmer and cooler water, transport huge volumes of water from equator to the poles and back, while prevailing winds sweep rain clouds from oceans to continents. Human actions alter nature's water cycle by pumping immense quantities of deep water to the surface to sustain agriculture, for example in the semi-arid Southwest. In this way, ancient aquifers are being drained, mined of their water at unsustainable rates. Earth's water cycles without end. Some molecules temporarily break apart into hydronium and hydroxyl ions, but they quickly recombine into new water molecules with new atomic companions. Other water molecules undergo chemical reactions in deep ocean zones of serpentinization when basalt turns into clays, or in soils to become part of Earth's storehouse of crustal clay minerals. Life has also evolved to become an essential part of Earth's near-surface water cycle. Plants absorb carbon dioxide, water molecules, and sunlight in the process of photosynthesis to manufacture their roots, stems, leaves, fruit. Then, when animals eat those nutrient-rich plant tissues, respiration converts them back to carbon dioxide, and water. Such near-surface processes are in plain view and relatively easy to study. But what of Earth's deep interior? Is there any water in the mantle or in the core? And does that water play any role at all in the more familiar water cycle at the surface? These questions came into sharp focus in the mid-1980s when mineralogists and petrologists began to consider the global scale water cycle. Surface water can't be the whole story. Some water-rich magmas that reach the surface in explosive eruptions come from tens or even hundreds of kilometers down. Some minerals that crystallize deep inside our planet hold tiny water-rich fluid inclusions. Scientists concluded that we were missing a deep and largely hidden part of the water cycle. This deep water that affects volcanism must be locked primarily into one of two reservoirs. On the one hand, there must be some kind of widely distributed fluid phase, which is sampled in those fluid inclusions. The volumes can't be huge because any big volumes of fluid would appear in detailed seismic surveys of shallow zones. Alternatively, many scientists have focused on the possibility that common mantle minerals, olivine, pyroxene, garnet, as well as their denser deep earth variants, might incorporate small amounts of water under mantle conditions. Consequently, in the 1990s, the investigation of water contained in nominally anhydrous minerals became a major focus of high-pressure mineralogy. And I think it's safe to say that everyone was surprised by the astonishing results. What experimentalists found was that it's relatively easy for many common magnesium silicate minerals to incorporate hydrogen atoms. That's the mineralogical equivalent of water because hydrogen atoms bound to oxygen offered by the silicates of these minerals. We were all surprised to learn that minerals that are variably dry in the shallow crust can become wet in the mantle. Let's look at the example of olivine, the first silicate to crystallize as the magma ocean cooled. Olivine is a key ingredient of peridotite and many other igneous rocks, so a little bit of water in olivine could represent a lot of water in Earth. The experiments are conceptually simple. Start with a sample of powdered olivine in a gold tube, add water, heat while squeezing. Experimental petrologists pressurize samples to hundreds of thousands of times atmospheric pressure and simultaneously heat to temperatures approaching 2,000 degrees Celsius. To accomplish such extreme conditions, far, far beyond what Hat Yoder's bomb could attain, scientists have designed and built a new generation of massive metal presses to concentrate tons of force on tiny samples. The experimental assembly is rather intricate and exploits three nested stages. Each stage is made of several hard anvils that surround and squeeze the next, so it focuses immense pressures on smaller and smaller volumes. The first stage is a pair of giant parallel metal plates like a vise, with one plate above and the other below the sample. Those plates are set in a big press that can push down with a force of thousands of tons. The second stage, inserted between the plates, consists of 6 interlocking hardened steel anvils, 3 above and 3 below. This second stage is engineered in such a way that as the big press pushes down, the 6 anvils press uniformly against the 6 square sides of a cube, about 3 inches across. This cube holds the third stage. That third stage is a cube broken into 8 smaller cubes, each a kind of anvil in its own right. These 8 anvils are machined from tough tungsten carbide. Each one is a cube about 1.5 inches across, with one tiny corner cut and polished to form a triangular facet. Those 8 faceted corners, the anvils of the third stage, all face inward. In this way, they define an inner sample holder that has an 8-faced octahedral shape about 1/2 inch across. That sample holder itself is a complex assembly. There's a central metal capsule that seals in powdered mineral plus water. That capsule has to be surrounded by an electrical heater and wires to measure temperature and a deformable octahedron-shaped liner so all the reactants don't squirt out the sides. Generating hundreds of thousands of atmospheres is only half the battle. The sample also has to be cooked to carefully controlled temperatures much higher than any oven. There's no way to use coils of platinum wire like Cat Yoder did. In fact, heating samples requires a fascinating two-stage heater. First, there's a little cylinder of pure carbon in the form of graphite. That cylinder surrounds the sample. It turns out that graphite makes a pretty good electrical resistance heater. You put a modest current through the cylinder and it heats up to 1,000 degrees Celsius. Ironically, above 1,000 degrees and at high pressure, the graphite transforms to diamond. So there needs to be a second cylinder inside the graphite made of chromite. That little heater kicks in above 1,000 degrees and can sustain temperatures of about 2,000 degrees Celsius. Okay, that's a really complicated assembly. But if everything goes well, if the desired pressure is reached and the high target temperature is sustained, if the temperature sensor doesn't break, if the sample doesn't leak out, then it's possible to duplicate conditions of Earth's mantle. It's possible to see if water can be stored in deep minerals. Even if the experiments are successful, how do you measure a few parts per million water in an otherwise dry sample? Eric Howry's ion probe is certainly one option. It has high sensitivity, has terrific spatial resolution. If you can find trace amounts of water in lunar volcanic glass, then the high-pressure experimental samples should be no problem. Another option is infrared spectroscopy, the kind that astronomers and lunar orbiters use to reveal characteristic bonds between oxygen and hydrogen. The trouble with these techniques is that a single minute fluid inclusion, a pocket of water too small to see with a microscope, can yield a false hydrogen signal in such sensitive measurements. And there's always the possibility that water trapped at very high pressure might somehow leak out as the pressure is released. That uncertainty leads us to a second alternative experimental approach for generating extreme conditions in the laboratory, a device called the diamond anvil cell. The diamond cell generates high pressures by squeezing two gem diamonds together. Take 2 half-carat brilliant cut diamonds, the kind in most engagement rings. Polish down the sharp points, or what you might call the bottom of the diamonds. That gives you 2 flat circular surfaces, maybe a 1/20th of an inch across as the anvil faces. It's important to mount the diamonds as precisely parallel as possible in a metal vise. The sample chamber is nothing more than a thin piece of metal with a tiny hole, but the hole is centered over the opposing diamond anvils. It's relatively easy to load sample chambers with mineral powders and water and then close up the cell and squeeze it. Even a modest force in the diamonds generates tremendous pressure because the pressure is simply the force divided by the area, and the area of the anvils is very small. This kind of diamond anvil cell has reached the world record highest sustained pressure equal to more than 3 million times atmospheric pressure. That's just shy of the 3.5 million atmosphere pressure at the center of Earth. Perhaps the most appealing aspect of the diamond anvil cell, even more important than the extreme pressure range, is that you can look through your diamonds and see your pressurized samples. So many different analytical techniques can be used to probe the sample at pressure. It's also relatively easy to heat the sample to deep Earth conditions, for example, with a high-powered laser that shines through the transparent diamond anvils. In this case, scientists can change temperature and pressure and look for the characteristic changes in the infrared absorption spectrum that point to newly formed bonds between hydrogen and oxygen. Those bonds alter the way that the mineral absorbs light so they can watch water entering the mineral structure at high pressure. These diamond anvil cell experiments took a while to catch on, but when they did, scientists quickly found a whole lineup of minerals that can store deep water, and many of these minerals are surprises. Olivine, pyroxene are typically dry. They hold no more than 100 parts per million water in the lower crust, but if pressures and temperatures are increased to mantle conditions of 100,000 atmospheres, 1,500 degrees Celsius, olivine transforms to the different, denser Wodsleyite structure, which we now know can incorporate an astonishing 3% water. That's 30,000 parts per million. It turns out there's an ideal small hole in the Wodsleyite crystal structure where a little hydrogen atom can attach to an oxygen atom. Wodsleyite is thought to be the most abundant mineral in Earth's transition zone from about 400 to 600 kilometers deep. So the transition zone, that relatively narrow layer between the upper mantle and lower mantle, may be the wettest place in the planet, or at least rather the most hydrogen-rich place. It may hold the equivalent of 9 times all the water in the ocean. Similar experiments on minerals of the lower mantle find that the most abundant minerals are much less waterlogged, with much lower hydrogen content. But what those minerals lack in hydrogen concentration, they make up for in huge volumes. Half of Earth's total volume is lower mantle silicates. So best estimates are that they may hold another 16 times the hydrogen in all of Earth's oceans. There could be a lot more hydrogen locked in the core, as hydrogen easily bonds to iron at very high pressure and temperature. Consequently, by one recent estimate, Earth's deep interior may store as much as 80 oceans worth of water. At first blush, it would seem unlikely that Earth's deep water cycle has anything at all to do with the surface. Certainly the hydrogen atoms in the mantle and core would seem to be permanently locked away, but that's not quite true. Earth is a dynamic planet with long-term cycles of convection, plate tectonics that can really mix things up. We'll explore plate tectonics and its influence on mineral evolution in more detail in lectures 24 and 25, but for now it's sufficient to note the two ongoing processes: subduction, by which old crust is swallowed up by the mantle, and volcanism, by which mantle material generates new crust, have tremendous effects on the water cycle. Every year, huge volumes of wet rock descend into the mantle in so-called subduction zones, mostly at the margins of the oceans. And every year, new wet magma ascends from the mantle, both at places where new crust is formed, at places like the Mid-Atlantic Ridge, and above subduction zones in the kind of volatile-rich explosive volcano exemplified by Mount St. Helens in Washington State, which literally blew its top on May 18th, 1980, and killed 57 people in the process. Such explosive volcanism, which occurs around the world, especially along the Ring of Fire around the Pacific Ocean, points to an active exchange of water from the mantle to the surface. It's tricky to be sure of the total volume of this exchange between the surface and the deep interior, but by one thoughtful estimate, all the water in Earth's oceans is completely recycled through the mantle about once every 300 million years. That means over the 4.5 billion year history of Earth, the average hydrogen atom in the oceans today could have made the journey to the deep interior and back a dozen times. Earth scientists have been pretty successful at cataloging the volatiles on Earth today. We certainly have a good handle on the gaseous elements, the inert gases, helium, neon, and argon, and the equally inert dinitrogen molecules that make up most of the atmosphere. These elements are rarely locked in mineral hosts, so the atmosphere represents a dominant repository for them. We now have a much better idea of the total hydrogen budget as well. Carbon is a different story. Much less is known, but there's a new effort called the Deep Carbon Observatory that I'll tell you about in lecture 39 that's trying to correct that situation. So all in all, it's not difficult to account for sources of Earth's modern oceans and atmosphere. Earth accumulated plenty of volatiles during its accretion from the solar nebula. Indeed, conservative estimates place Earth's original volatile budget at perhaps 100 times greater than modern levels. So the principal challenge in modeling Earth's volatile history may be figuring out how so much was lost. In the next lecture, we'll see how minerals, particularly the difference in near-surface mineralogy of Earth and the Moon, provide important clues about what happened to all the water. Where is Earth's missing water? The oceans hold a lot of water, but they represent only a minuscule fraction of what would be found in a similar mass of volatile-rich CI chondrites, the most primitive carbon-rich type. recent findings suggest lots of water might be stored at depths, perhaps 80 times the water found in all the oceans. But even that prodigious amount of water pales beside the multiples more of water that meteorites suggest must once have been there. Some things we know. In the earliest days on Earth, volatiles were released in huge quantities from the deep interior as mega volcanoes pumped water, carbon dioxide, nitrogen, and other gases into a rapidly thickening atmosphere. It's likely that within a few million years, Earth's atmosphere became many times denser than that of the modern world. Water would have rained down onto the cooling surface, possibly forming wide, shallow seas near the poles within the first few tens of millions of years. Earth's axis of rotation probably did not yet have its current tilt, so there would have been no change of seasons. And then came that big thwack which blasted all the atmosphere, the incipient oceans, away. Almost every molecule of water and air that had found its way to the surface was lost to space, with remnants initially sequestered in ways we are only beginning to detect on the moon. For Earth, the impact of Theia was like a giant reset button, back to square one, with a globe encircling magma ocean and absolutely no atmosphere, no oceans. We don't know how much of Earth's carbon dioxide, nitrogen, water, other volatiles were lost in that catastrophic event, but it must have been a lot. For another 500 million years, hundreds of smaller scale impacts, objects from 10 to 100 kilometers in diameter, caused disruptions. Each of those events vaporized more of the oceans and may have ejected significantly large quantities of volatiles into space. Following the moon-forming event, but still within Earth's first 100 million years, let's say 4.45 billion years ago, water vapor had become a significant part of the atmosphere. Somewhat like Jupiter today, Earth's rapid rotation produced severe wind shears and violent weather. Thickening, turbulent, dark clouds were accompanied by howling winds, shattering lightning, unceasing torrential rain. As the surface of this storm-lashed land gradually cooled and hardened, low-lying basins gradually filled with water. What would become the oceans slowly formed. And perhaps you can imagine what it was like, with volcanoes everywhere, magma pouring out onto the surface. For a time, the expanding ponds and lakes must have caused a global sauna, surface waters penetrating cracks and fissures where it contacted the hot rocks below and returned to the surface as gargantuan geysers of roaring steam, superheated water. One important consequence of these intense water-rock reactions was to speed up crustal cooling, which led to the accumulation of even deeper lakes than seas, ultimately oceans. Rocks older than 3 billion years are rare on Earth, and we don't know the exact timing of the first oceans formations, but provocative evidence is now emerging in the form of Earth's oldest crystals. One important locality for such ancient deposits is the desolate and arid sheep ranching district of Western Australia known as the Jack Hills. The Jack Hills hold layers of sediments formed from the accumulation of sand-sized mineral grains of rock and other minerals that eroded from much older rock formations and have long since weathered away. A minute fraction of those historic sand grains, less than 1 in a million, consists of the mineral zircon, zirconium silicate, which has the distinct advantage of being one of the most resilient of all minerals. The lustrous red zircon grains from the Jack Hills are smaller than the period at the end of a sentence. They must have formed, as zircon crystals do today, as a minor accessory mineral in igneous rocks that contained modest amounts of that rare element, number 40, zirconium. But zirconium is too big to fit easily into the crystal structures of common minerals, pyroxenes, olivine, feldspars. So as those minerals crystallize from magma and the proportion of solid increases, zirconium becomes concentrated in the remaining hot melt. Eventually, at the tail end of solidification of the magma, tiny zircon crystals form. Zircon crystals may be easy to overlook, but they have the brilliance and fire of diamond and provide provide a unique source of insight about early Earth. For one thing, unless zircon crystals are remelted and destroyed by heat, they last almost forever, far longer than Earth history. Zircon crystals have a high melting point, comparable to two of the earliest minerals, hibonite and spinel. It's not unusual for a single crystal of zircon to erode from the igneous host where it first crystallized, then get incorporated as a grain in sandstone, then erode from that sandstone to another again and again and again for billions of years. It's possible for one zircon grain to be recycled through a dozen different sedimentary rock formations. Zircon crystals are also valuable for understanding Earth history because they tell time. They readily incorporate the radioactive element uranium, which sometimes substitutes for as much as 1% of zircon's atoms. Uranium-238 has a half-life of about 4.5 billion years, so once a zircon crystal forms, its uranium atoms begin to decay to produce lead atoms. Half the uranium atoms transform on average every 4.5 billion years. That ratio of dwindling parental uranium atoms to the growing daughter lead atoms provides an accurate estimate of the zircon crystal's age. Zircon provides yet another important line of evidence about its past. 2 of every 3 atoms in zircon are oxygen. And oxygen isotopes can provide information about the crystal's temperature of formation. We saw when discussing the Big Thwack that one line of evidence regarding the moon's formation history was its distinctive ratio of oxygen's stable isotopes. It turns out that Earth and the moon have identical ratios of oxygen-16 to oxygen-18. That isotopic similarity implies that both bodies formed using materials a similar distance from the sun in the same orbital space at about the same temperature. In a similar line of reasoning, the ratio of oxygen-16 to oxygen-18 in a zircon crystal points to the temperature at which it grew. Samples enriched in the heavier oxygen-18 isotope point to a cooler temperature of formation. For igneous rocks, the temperature revealed by oxygen isotopes is potentially a sensitive indicator of the magma's water content, because lots of water can lower the temperature at which zircon crystals form. In addition, water near Earth's surface tends to be even more enriched in heavy oxygen-18. That's why zircon crystals with unusually high oxygen-18 are interpreted as having interacted with surface water. So, why am I taking this digression to talk about zircon crystals? The reason is that zircon crystals are like little time capsules. They survive billions of years. They endure many cycles of erosion and deposition, and they can preserve details of the age, the temperature, and the water content of their original environment. It's amazing that all that information can be obtained from a crystal that you can't even see without a microscope. And what do we find? First, the Jack Hill zircon crystals are really old. Many are more than 4 billion years old, and the core of one remarkable ancient sand grain clocks in at 4.4 billion years. That grain also has about 1 billion years of additional growth layers on the outside, so it's been through a lot. That oldest zircon crystal, which is the oldest known solid fragment of Earth, has an unusually high concentration of the heavy oxygen isotope. Some scientists use that data to conclude that when Earth was only about 150 million years old, that's 4.4 billion years ago, the surface was already relatively cool and wet, so that implies there must have been oceans. Not all experts agree. For one thing, zircon crystals can be incredibly complicated. Interpretations of Earth history are confused by the concentric layers of younger overgrowths that mantle that 4.4 billion year old grain, as well as virtually all other zircon grains from the Jack Hills. It's common for one single grain to display 1 billion year range of ages from its core to its rim, and the ratios of oxygen isotopes are correspondingly variable. It's always possible that the older core has been altered during more recent episodes of crystal growth. If so, then the inferred characteristics of Earth's ancient surface might be wrong. That zircon story is still being studied, it's still being discussed, and we can be sure that more of these ancient crystals will be found to shed new light. But whatever the outcome of those debates, most experts agree that relatively shortly after Earth's formation, probably no more than 100 to 200 million years after the moon's formation, Earth had become a water world with an almost continuous, kilometer-deep encircling ocean. From space, Earth would have appeared as a deep blue marble, swirled with clouds and the frequent cyclonic storms, but predominantly a beautiful blue. By the way, the ocean's deep color, that blue color, arises from basic optics. Sunlight bathes Earth's surface in all the rainbow colors, reds, yellows, greens, blues, yet water absorbs primarily the red and orange wavelength of the spectrum. Our eyes perceive that dominance of the scattered blue wavelength of light. And what of the land? Was there any? Where was it? Today, continents cover almost a third of Earth's surface, but in the Hadean Eon, the first 500 million years of our planet, continents hadn't formed. The principal reason why some of us conclude that Earth was almost completely covered by one primordial ocean is that the hidden magma ocean wasn't strong enough to support much basalt topography. Great mountain ranges had not yet formed, so Earth was close to spherical. On such a world, lacking highs and lows, water would cover everything in one relatively shallow body. There must have been some land, but it was primarily in the form of isolated volcanic cones that poked above the waves. There may have been thousands of such landforms, but individual cones would rarely have exceeded a few tens of kilometers in diameter. Each was bounded by a rubbly black beach. These black, smoking islands, randomly dotting the globe, provided the only solid features to break the beautiful blue monotony. What was that first ocean like? Was it hot? Probably a lot hotter than today's ocean, given the global magma ocean beneath. Was it salty? Again, probably yes. Salt is the most distinctive property of ocean water today. But it might seem logical that Earth's first ocean started out with few dissolved chemicals, as fresh water. In fact, recent evidence suggests that the early oceans quickly became much saltier than it is today. That's because sodium chloride and other salts readily dissolve in hot water. Fluid rock interactions on the Hadean Earth must have extracted much of the available salts quite rapidly. Now today, as much as half of Earth's sodium chloride may be tied up in underground salt domes and other evaporite deposits that formed when ancient salty seas dried up. So a lot of salt is locked in thick layers deep underground. But during Earth's first half-billion years, there were no large salt deposits because there were no continents. The conclusion is that salinity of the first oceans may have been twice that of the modern world. And what are the ocean's pH? Was the Hadean Ocean acidic? Was it basic? The answer may lie with atmospheric carbon dioxide, which coupled with salinity controls the ocean's pH. Most experts agree that CO2 content of the early atmosphere was at least hundreds, if not thousands of times higher than today. Right now we're at about 400 parts per million carbon dioxide, though that level is rising every year. Much more CO2 in Hadean air meant much more CO2 in the water as well. The connection to pH lies in the tendency of CO2 to combine with rainwater to form carbonate, H2CO3. In the ocean, this carbonate partly breaks in two to hydrogen ions, which quickly combine with oxygen to form hydronium ions. Those are the H3O plus ions, plus so-called bicarbonate ions, which are actually just an HC3O minus group. That reaction means a net addition of hydrogen ions. And by definition, that's an increase in acidity, perhaps driving the oceans to a pH as low as 5.5. Such acidic conditions have a chain of consequences. For example, acids accelerate the weathering of basalt and other rocks, which adds even more salts to an already salty ocean. There's one additional big wrinkle associated with early Earth and its globe-encircling ocean, and that has to do with the sun. According to a growing body of astronomical observations and astrophysical calculations, a star like our sun undergoes a very slow brightening over its 10 billion year lifetime. By current estimates, the young sun 4.4 billion years ago was only about 70% of its current brightness. That's a lot less solar energy hitting Earth. What's more, this state persisted for at least another 1.5 billion years. If the sun were suddenly to dim today by that extreme amount, 20% or more, then Earth would rapidly go into a disastrous ice age, perhaps freezing solid from poles almost to the equator. Most life would die. Only the most resilient organisms, primarily deep subsurface microbial life and animals living around active hydrothermal zones associated with volcanoes, would survive such a catastrophic climate change. So, did Earth freeze over? And if not, why not? Evidence for abundant surface water at least as far back as 3.5 billion years is unambiguous. Geologists find substantial layers of water-deposited sediments from both shallow and deep water environments. What's more, fossil evidence reveals that life began and thrived at that time, but that the ocean remained liquid. A much hotter Earth must have helped. It took a long time for the primordial magma ocean to cool, and there was a lot of hot molten rock and other volcanic activity to keep the surface warm. It was as if the entire ocean was sitting on a big hot plate. But that wasn't enough to keep things unfrozen for 500 million years. The leading hypothesis to explain the faint sun paradox, but has been until relatively recently the textbook explanation, is an exaggerated greenhouse warming, an effect caused by the extremely high atmospheric concentrations of carbon dioxide. Those are the same high CO2 concentrations that probably cause the oceans to be acidic. One problem with this scenario is that the mineralogy of rocks surviving from between 3 and 4 billion years ago is lacking in much of the iron carbonate rocks, which should have formed under a thick carbon dioxide atmosphere. A second clever idea is that Earth in its early black, then blue phases must have absorbed much more of the sun's energy than the surface does today. Oceans absorb more sunlight than land. And that effect very likely exaggerated long ago by relatively high concentrations of iron in the earliest oceans, iron that would later be locked up in other molecules. That increased solar absorption might also have been enhanced by relative lack of light-scattering clouds. See, today, many clouds are nucleated by plant-generated particles and chemicals, dust, the effect of mountain ranges. Billions of years ago, there were no plants. There was no biological dust, and there was no mountain range to speak of to trigger cloud formation. Yet another hypothesis, one that's gaining a lot of traction, suggests that the early atmosphere had a significant concentration of methane, CH4. Methane could affect global climate in at least two ways. First, it's a potent greenhouse gas. Molecule for molecule, methane is much more effective than carbon dioxide. In addition, high in the atmosphere, methane exposed to ultraviolet radiation would have undergone chemical reactions that synthesized a rich variety of organic molecules, including possible building blocks of life. And some of those organic molecules could have caused a thick, heat-trapping, smog-like haze, possibly even transforming the blue Earth into a distinctly orange world, reminiscent of Saturn's big moon Titan. In any case, even though we don't have a complete picture of why Earth remained wet and unfrozen under the ancient faint sun, we have more than enough explanations to keep us busy with more research. With the formation of Earth's black crust and the birth by volcano of the global ocean and atmosphere, we have come to stage 3 of Earth's mineral evolution. Up to this point, minerals have formed before the planet as a whole. First, a dozen minerals in the cooling envelopes of big stars. Then stage 1 with 60 or more minerals that condensed in primitive chondrites. And stage 2 with about 250 mineral species from planetesimals that experienced differentiation and alteration by heat, water, impacts. All of those minerals still fall to Earth and the other planets and moons of our inner solar system. all of those 250 species have been present continuously at or near the surface of Earth since the crust first hardened. But the third stage of mineral evolution requires a planet-sized body. This makes possible the crystallization of peridotite, the partial melting of peridotite to form basalt, and the production of residual melts and other fluids concentrated in rare elements that had not previously played much of a role in mineral evolution. All terrestrial planets, as well as Earth's big moon, participated at least part of the way in this next stage. In all these rocky bodies, magmas produced new kinds of silicates, including the chain silicate group from amphiboles. Silicate minerals in the familiar garnet group are a good example, since they are found in minor quantities across many kinds of rocks. New minerals of the elements titanium, manganese, sulfur, chlorine also are likely to have formed. All told, igneous processes may have resulted in another 100 species, for a grand total of perhaps 350 minerals. And that's it for Mercury, and probably the moon as well. The moon might differ in some way because of its early collision with Earth, but we haven't found any other mineral-forming processes that would have diversified those relatively small, dry worlds on their own. There simply wasn't enough internal heat. There wasn't enough water to drive the cycles of melting and freezing that are so critical to separating and concentrating elements. My colleagues and I estimate that all the mineral diversity that would ever be on the moon and Mercury was achieved more than 4 billion years ago. The story for Earth and Mars is quite different. Those planets are a lot wetter than Mercury or the moon, or Venus for that matter. And this difference caused a divergence in their mineral evolution. Water enhances mineral formation in at least 3 ways. First, as we've seen, water dissolves a variety of elements and thus holds the potential to transport those elements from one place to another. In addition, water greatly lowers the melting point of rocks, which means a planet's inner heat can accomplish more in the way of partial melting and fractionating rocks. And finally, a huge number of mineral species on Earth incorporate water. Almost 60% of all known mineral species are hydrous, so a wet planet can make a much greater diversity of mineral species than a dry one. What we find is that fluids are the real key to mineral evolution of stage 3, and even stages 4 and 5, both of which we'll discuss in later lectures. New minerals arise when dozens of different elements that initially are extremely rare become concentrated in one fluid or another, and that fluid phase could be the molten magma, or it could be a hot, water-rich liquid, or it could be something more exotic, enriched in sulfur or carbon. It just needs to be a fluid that separates from the magma or the solid rock. A part per million uranium, or beryllium, or a part per billion mercury or cesium simply cannot form a separate mineral. But if you repeatedly concentrate those elements into a fluid, hot, salty brine, for example, then you can achieve concentration factors of 1 billion times or more. That's exactly what happened on Earth, and to a lesser extent on Mars. Let's look at Mars first, since it's the smaller planet and has less heat to play with. Abundant evidence reveals that Mars was a water world early in its history. A shallow ocean probably covered most of the northern hemisphere to an average depth of perhaps approaching a kilometer. Given all the volcanism on Mars, there must have been widespread active hydrothermal zones, places where hot water flowed through cracks and fissures of the crust and altered and dissolved the basaltic veneer. One immediate consequence was the formation of a salty ocean and the consequent production of evaporite minerals along the Martian ocean margins. As on Earth, sodium chloride, the mineral halite, would have been a major evaporite mineral. Lustrous cubic crystals would have blanketed shorelines as the salty ocean dried up and waned. Salt is soft, and much of those deposits will by now have eroded away, or perhaps lie buried under layers of sandy sediment, but common salt is surely there. Dozens of other evaporite minerals, though less abundant than sodium chloride, would also have formed. It's likely that Mars also has potassium chloride, what geologists call sylvite, Chlorides combining both magnesium and potassium were certainly there too, as were numerous hydrated variants. Hydrated minerals are those that incorporate a few molecules of water in their crystal structure. A good example is a soft potassium magnesium chloride like carnallite, with potassium magnesium 3 chlorines and 6 H2O molecules. Recent Mars missions have identified abundant sulfate minerals as well. And here the mineral diversity really begins to skyrocket. Take the magnesium sulfate minerals, for example. These minerals include the electron donor element magnesium, which gives away 2 electrons, and an electron acceptor called sulfate, with a central sulfur atom surrounded by 4 oxygen atoms. That sulfate group accepts 2 electrons, so it has a -2 charge. The core of these magnesium sulfate minerals is thus a 1-to-1 ratio of magnesium to sulfate. Virtually all of the magnesium sulfate minerals, and there are more than 50 of them, also incorporate water. Perhaps the most familiar of these is epsomite, also known as Epsom salt, with 7 molecules of water. But there are also kieserite with 1 molecule of water, a 1-to-1 ratio of magnesium sulfate, cranswickite and starkeyite both with 4, pentahydrate with 5, hexahydrate with 6, and meridianite with 11 molecules of water for every MgSO4 molecule. Meridianite was not correctly described or given its current name until 2007. It's only stable below 2 degrees Celsius, or about 36 degrees Fahrenheit. So it's most commonly found in icy brines. Meridianite was sampled from a frozen pond in British Columbia, but it was named after the Meridiani Plana, the meridian plains of Mars, because of the strong presumption that this particular magnesium sulfate was going to be discovered there. Other electron donors also form sulfates. Potassium sulfate is arcanite, while sodium sulfate is thenardite, and there are dozens more hydrated forms as well. There are also lots of sulfates with mixed electron donors, combinations of sodium, potassium, magnesium, and others. 2 of these probable sulfate minerals are water-free: a sodium magnesium sulfate called Van't Hoffite, and a potassium magnesium sulfite called Langbenite. And there are dozens of hydrated sulfites, some of which also have chlorine. Perhaps the most important and distinctive sulfate mineral on Mars, however, is the potassium iron sulfate called jarosite. The formula is 1 potassium, 3 irons, 2 sulfates, and then 6 OH groups. On Earth, jarosite often forms in places where old mine dumps rich in sulfide minerals contaminate local ponds or streams. It's a signature mineral for acid mine drainage. The presence of jarosite has been confirmed on Mars by a variety of spectroscopic techniques and is highly suggestive not only of an evaporitic environment, but also one that's extremely acidic. That acidic environment probably resulted from the high carbon dioxide content of the atmosphere. All told, the near-surface environment of Mars may have dozens of different evaporite minerals, none of which would have played any significant role in the first 2 stages of mineral evolution. The oceans of Mars and early Earth have led to many other water-rich minerals as well. Prominent among these would have been a significant number of hydroxide minerals, minerals in which OH groups bond to electron donor elements like magnesium, aluminum, or iron. We've already met the magnesium hydroxide brucite when we discussed serpentinization in the achondrites. But now there are also aluminum hydroxides such as diaspore and gibbsite, iron hydroxides such as ferrihydrate and goethite, and manganese hydroxides such as manganite and pyrochromite. Moreover, combined with later changes on Earth, water will eventually go on to create thousands of hydrated minerals, including water-rich variants of most of the minerals we've met so far. That's because water, with its positive and negative charged sides, can bind to almost everything. The planet-wide igneous processes of stage 3 make it easy to incorporate water into a variety of crystal structures, and later changes on Earth allow many more water-rich minerals to be created. we've seen is that on a water-rich world, like Mars or Earth, there are likely to be lots of hydrated mineral species. Of all the groups of hydrated minerals, none is more important on Mars, on Earth, than the clay minerals. Clay minerals tell an amazing story and have played a key role in the near-surface transformations of both Mars and Earth. We'll be meeting these important minerals again and again, starting in the next lecture, where we will wrap up our look at stage 3, hydrated minerals created in the context of planet-wide volcanism, and we'll turn to granite, an abundant stage 4 rock that first leads to the formation of continents, microcontinents on Earth.
For 500,000 years, Earth has been a water world. But below the surface, something is happening. Heat from below and water above actively drive the planet into a fourth stage of mineral evolution. Black basalt partially melts to produce hard gray granite. Because granite is much less dense, the granite floats on basalt, like corks on water. These masses of granite become the cores of continents and the beginnings of dry land.
The principal focus of this lecture is the fascinating way that heat and water led to the formation of granite and numerous associated new minerals. Before the origin of life, internal heat and abundant water were to be the two principal forces driving planetary mineral evolution. To look at the role of water, let's return to Mars and what are perhaps the most distinctive water-bearing minerals at the surface of any wet planet, the clay minerals. I have to admit that clay minerals are poorly defined. They're a rather broad class of minerals that don't have a precise definition, but I guarantee that you know a clay mineral when you see or feel one. Soil made of dry clay is very hard and difficult to crush by hand, while powdered clay is very smooth. But when wet clays occur, they're sticky, they feel smooth, and you see that it changes colors. That's why the Native Americans could use clays as paint. Sometimes they're red, they can be orange, green, browns, or even black. The familiar look and feel of clay are explained by two key formal criteria for identifying clay minerals. First, at a minimum, all clay minerals are extremely fine-grained, with typical particle sizes of about 1 micron. That's about 1/1,000,000th of a meter, or a few 10,000ths of an inch across. There aren't many materials in our everyday lives that feature such tiny particles. Sand grains typically have diameters that are 100 to 1,000 times greater, meaning the volume of a typical sand grain is more than 1,000,000 times that of a clay particle. Even dust grains are much, much bigger. The only thing comparable might be talcum powder, which just happens to be the clay mineral talc. The incredibly tiny grain size means that it's almost impossible to see any individual clay crystallites in a light microscope. That makes clay minerals tough to describe and to classify. This fine-grained character also helps to explain one of the most familiar properties of clays, namely their behavior when they're wet. If you've ever used wet clay to make pottery or had to walk across a stretch of wet, clay-rich soil, you'll know what I mean. It's sticky, it's clayey stuff. It can be extremely slippery when it's wet as well. I remember one amazing geology field trip in Montana when a group of us were walking across a terrain of clay-rich mounds, and it began to rain. So this entire field area became like this sticky quagmire, but it was so much fun. We'd all try to climb to the top of these low rounded hills. They're maybe 20 feet high and pretty steep. And it was almost impossible to do it. We had to claw at the clay, and every few inches we'd go up and then we'd slide back a few inches almost as far. But if you made it to the top, you could slide down the hill on your back and get this great slippery ride. And by the time the rainstorm was over, we were all just covered with this thick gray clay from head to toe. It was a mess, and it was so much fun. I still see friends who are now distinguished professors at prestigious universities, and we just laugh like kids about that experience. So, extremely small grain size. That's one of the characteristics of every clay mineral. But that's not enough. Even dust in the lunar regolith can be comparably small, but there's no known clay minerals on the moon. So the second essential characteristic is that all valid clay minerals have to have a layered atomic structure with silicate tetrahedra linked in flat sheets. In other words, clays are members of the layer silicate structural group. These layers are what allow clays to be so slippery. Recall the essential features of layer silicates. First, the key building block is a 5-atom group with a central silicon atom surrounded by a tetrahedron of 4 oxygen atoms. These tetrahedra have the neat ability of sharing corners with each other so that you can have structures with chains or rings or layers or frameworks. So in clay minerals, which are all layered silicates, there are layers of 6 membered rings of tetrahedra, like little 3-sided pyramids with all the points facing in the same direction. Now, those tetrahedra can be linked to other kinds of atomic layers in a rich variety of ways. We'll come back to the clay minerals in more detail in several upcoming lectures, but let's take a quick look at the most important clay layer structures. The simplest clay minerals, including serpentine with magnesium and kaolinite with aluminum, feature a single tetrahedral layer bonded to a so-called octahedral layer. The octahedral layer features 7 atom units with one central magnesium or aluminum atom, and each of those atoms is surrounded by 6 oxygen atoms. These octahedra share edges with each other to make a uniform flat layer. This 2-layer sequence of a tetrahedral sheet bonded to an octahedral sheet is the thinnest possible kind of clay mineral. Serpentine and kaolinite have this repeated structure that's only 7.7 billionths of a meter thick. These layers of alternating molecules are only a little thicker than the layers of carbon atoms that we discussed for graphite. Now, 4.5 billion years ago, there certainly must have been lots of serpentine on both Earth and Mars. That's because serpentinization, that's the metamorphism of rocks involving water, was such a dominant process when hot water circulated through basalt. The magnesium silicate minerals in basalt reacted with hot water to produce clays and other new minerals. It's also possible to make thicker layers with an octahedral layer sandwiched between 2 tetrahedral layers. For example, that sequence is about 1/1000th of a meter thick, and it's found in lots of different clay minerals, and all the mica minerals as well. And some of those clay minerals might have contributed to the near-surface mineralogy of ancient Mars as well. The most familiar example of those common clay minerals is talc. It's a hydrated magnesium silicate. That's the mineral of talcum powder. And another common clay is pyrophyllite, which has aluminum in place of magnesium. And then there's even thicker sequences in which that whole 3-layer sandwich of a tetrahedral, then octahedral, then another tetrahedral layer alternates with a single octahedral layer. And that leads to a clay mineral such as chlorite with a repeat distance of 1.4 billionths of a meter. Chlorite is almost as soft as talc and produces a green powder when scratched with a fingernail. But those are only some of the building blocks. You see, different kinds of clay layers, serpentine and talc and chlorite, can easily stack on top of each other, so it's common to get complicated mixed layer minerals with almost random sequences of layers. Virtually every clay is different, so the study of clay minerals is a very specialized branch of mineralogy. Clay mineralogists even have their own society, they have their own journals. And one of the exciting discoveries of recent Mars missions is that the surface of Mars is just covered with clay minerals. Satellites in orbit around the planet measure the way light is reflected off the surface, the way that certain wavelengths are reflected and other wavelengths are absorbed. This is what's known as a reflectance spectrum, and clay minerals have distinctive reflectance spectra. In fact, each major group of clay minerals has a slightly different spectrum, so planetary scientists now have mapped large areas of the Martian surface according to the dominant kind of clay. All told, by adding up all the hydrous minerals that might have formed on Mars, that's the hydrated evaporite minerals like sulfates, the hydroxides, the clay minerals, there might be an additional 150 minerals that couldn't have formed on dry Mercury or the Moon. So we have a dozen minerals, then 60 chondrite minerals in stage 1, we have 250 minerals in stage 2, and all the way to 350 minerals on Mercury or the Moon. And then add 150 water-rich minerals, and we're up to 500 stage 3 minerals on Mars and Earth. But that's where Earth and Mars part company, because Earth is a much larger planet, and it has a lot more internal heat. Earth's extra heat added to water equals more mineral diversity. Earth was about to double in mineral diversity, and that's what I refer to as stage 4 of mineral evolution, the formation of granite and the origins of the continents. When we think of Earth, we envision the planet of today, a planet of amazing contrast. Earth is about 1/3 land, 2/3 water. From space, you see a melange of colors, oceans of blue with brown and green continents and swirling white clouds. But 4.4 billion years ago, I suspect that things were different. I imagine lots of scattered black volcano cones forming islands, which were the only places where dry land poked above the blue shallow oceans. The big difference between then and now is continents. A continent is defined as a large volume of rock at Earth's surface that's less dense than the underlying formations, and therefore floats much higher than the surrounding crust. On Earth today, there are 6 or 7 continents, depending on how you count. There's North and South America, Africa, Antarctica, Australia, and Europe, plus Asia. In fact, Eurasia is one big continent. Sometimes it's called a supercontinent, but that's a misleading name for Eurasia, given what counts as supercontinents earlier in Earth history. In any case, about 1/3 of Earth's surface is taken up by the continents. But that hasn't always been true. Very early in Earth's history, there were no continents, and it must have taken a long time to build them up. The growth of continents was a huge step in the episodic differentiation of Earth into zones of distinct composition and character. Differentiation was a sequence of chemical and physical processes that began long before Earth formed. Over and over, the chemical elements that once formed our solar nebula have been separated and concentrated into new zones. At the biggest scale of the solar system, the inner rocky planets Mercury, Venus, Earth, and Mars became concentrated in such elements as magnesium, iron, silicon, and of course, oxygen, as intense solar winds swept gaseous hydrogen and helium away from the heavier elements. Those lighter elements became concentrated in the distant domain of the gas giant planets, Jupiter, Saturn, Uranus, and Neptune. So the rock-forming elements were separated from the lightest gases. Then, on Earth, the dense metallic elements, iron and nickel, separated by gravity to the core, while Earth's mantle became correspondingly enriched in magnesium silicates. Recall that the main rock type in the mantle is peridotite, named for the magnesium silicate olivine, or peridot in its gemstone form. The chemical formula of olivine is Mg2SiO4, so the bulk mantle composition is about 2:1 magnesium oxide to silicon oxide, with smaller amounts of calcium and aluminum. That means the mantle is on average about 1/3 silicon oxide. The next big stage of element separation occurred when peridotite was partially melted in the mantle to produce basalt. The resulting basaltic magma is relatively enriched in calcium, aluminum, and silicon. And recall that the dominant minerals in basalt are pyroxene and feldspar. These minerals have about a 1-to-1 ratio of silicon oxide to magnesium oxide, plus calcium plus aluminum. So basalt is about 50% silicon oxide. That's compared to about 33% silicon oxide for peridotite. Basalt's also about 10% less dense than peridotite, so basalt magma rises to the surface to make the first crust. Another episode of element separation occurred when basalt erupted explosively onto Earth's surface. Water and other volatiles quickly separated from the basaltic magma as superheated steam and other gases. These gases cooled to form the first oceans and the atmosphere. So Earth became even more layered: solids, liquids, gases, and each layer had its own chemical composition. The story of continent formation, which is also the story of granite, repeated this fruitful history of element separation and concentration through heating. As the outermost crust of black basalt cooled and hardened, it created a lid-like cover that trapped Earth's inner heat. Inevitably, as the basalt crust thickened and was heated more and more, it began to partially melt, just as peridotite had partially melted before. Now this wet crustal basalt, as it was reheated from below, started to melt at relatively low temperatures. Water lowered that initial melting temperature to perhaps as cool as 1200 degrees Fahrenheit. As with peridotite, basalt didn't melt all at once. As heat built up, the percent of basalt melting gradually increased. First, just a few percent, then 10%, eventually up to 20 or 25% partial melting. And again, in an echo of the way peridotite melts, the resulting magma was quite different in composition for the basalt that was melting. Most strikingly, this new melt was much, much richer in the element silicon, as much as 65 or even 70% silicon oxide, compared to 33% in peridotite and 50% in basalt. This partial melt also concentrated the alkali elements, sodium and potassium. Those elements are in the first column of the periodic table, and they are enthusiastic electron-donating elements. Recall that sodium readily gives up an electron to chlorine in common table salt, or sodium chloride. This new silicon-rich magma was at least 10% less dense than the basalt from which it was produced, so the magma inevitably pushed its way toward the surface, forming an entirely new kind of crustal rock called granite. Granite is so familiar. It's the rugged, gray building stone of countertops and of continents. 4 mineral species dominate virtually all granites. Feldspars, which are mineral with an alkali element plus aluminum and silicon, are the most abundant. They come in 2 principal varieties, one with more potassium, the other with more sodium. These feldspar minerals would have combined in granites to give Earth's earliest granites their monotonous grayish white color. Almost as abundant in many granites is the mineral quartz, which forms clear, colorless crystals of pure silicon dioxide. Quartz grains are among the most resilient minerals on Earth, so weathering of granites would have produced Earth's first white, sandy beaches. Most granites also hold a few percent of one or more dark, iron-bearing minerals. Look closely at a polished granite countertop, and you'll see blocky pyroxene grains, or sheet-like mica flakes, or elongate amphibole crystals. Now, a key characteristic of the magma that form granites is its ability to incorporate water in a hot fluid that also selectively concentrates dozens of rare trace elements: beryllium, lithium, uranium, zirconium, tantalum, boron, cesium, rubidium, many, many more. The presence of all these rarer elements in concentrated form often leads to scattered tiny grains of new, relatively rare minerals. And we'll learn some of the amazing mineralogical consequences of those element concentrations later in this lecture. For now, a good example of a mineralogical novelty is zircon, which concentrates the rare element zirconium. Recall from the last lecture how those little red zircon crystals were extracted from old sediments from the Jack Hills of Australia. Those special crystals provide evidence for early ocean 4.4 billion years ago. And those tiny zircons also point to granite formation at that early stage because they have the distinctive heavy oxygen isotope signature of a cool and wet origin. What's more, some rare zircon crystals seem to have inner inclusions of quartz, and that's a mineral that was hardly ever formed before granite. That's why lots of experts suggest that the quartz-bearing zircon crystals are the last surviving remnants of the earliest granite crust, the earliest traces of continents. Up until the formation of granite, Earth was pretty much like its planetary neighbors, Mercury, Venus, and Mars. All those bodies must have started with something like an iron core and a peridotite mantle, and all produced copious amounts of basalt that formed their black crusts. But with a partial melting of basalt and the formation of lots of granite, we see the first really significant divergence of Earth from those other inner planets. You see, granite formation not only requires a lot of basalt near the surface, but it also requires a lot of internal heat to remelt the basalt. Mars and Mercury are simply too small. They don't have enough heat. It's likely that relatively small volumes of granite have been produced on Mars and Mercury, but nothing like the deeply rooted granite continents of Earth. Now, Venus is a lot larger and has correspondingly more inner heat than Mars and Mercury, but Venus also appears to be a lot drier than Earth. That means it's harder to melt basalt and harder to produce much granite. So Earth really does seem to be a mineralogically unique world in our solar system. The rise of granite on Earth caused a number of profound changes, not the least of which was the landscape. Black basalt, which formed Earth's primordial crust, was constantly softened by heat from below. With its average density about 3 times that of water, it never could support much topography. It's true that a few of the most actively growing volcanoes might have built mountains that rose a mile or more above the ocean. But there were probably no great mountain ranges, nor were there any extremely deep ocean basins before the rise of continents. Granite changed that. Granite has a significantly lower average density of about 2.7 times the density of water. That means that granite floats on basalt and on peridotite. It can pile up in great mounds, rising miles above the surface, like an iceberg floating on water. Your everyday experience with ice drinks makes the point. Ice is 10% less dense than water, so about 10% of an ice cube's or an iceberg's volume sticks out of the water. And if the piece of ice has a tapered shape, then significantly more than 10% of its height can poke above the water. Indeed, a 200-foot tall iceberg will often have 30 or more feet exposed above the water's surface. That's the tip of the iceberg. By the exact same token, granite is typically about 10% less dense than the basalt on which it rests. So as fresh granite piles up on top of the partially melted basalt crust, the granite forms mountains. These mountains are simply iceberg-like protrusions. A mile-thick granite body floating up basalt might produce a small mound that rises almost 1,000 feet above the mean level of the salted crust. By the way, the average height of Earth's solid surface today is about 2 miles below sea level. Over time, as more granite accumulates to thicknesses of many miles, big mountain ranges, miles high, can form simply by this kind of buoyancy. Today, the Rocky Mountain chain of western North America has granite roots as much as 40 miles deep, and corresponding mountain peaks that are almost 3 miles above sea level. Think about the forces that might cause a mountain range to form. A mountain is a huge thing, typically several cubic miles of rock rising way above the surrounding landscape, so you need a really big force to counter gravity. Geologists see 2 basic ways to do it. The one that's more often invoked today is lateral tectonics. If 2 great masses of rock are pushed together from the sides, they sort of smoosh up and they form a mountain change. That's one of the key ideas of the theory of plate tectonics, which we'll meet in lectures 24 and 25. But early in Earth history, it's not obvious how big lateral forces would have been generated. The crust was simply too thin and hot and plastic, at least according to a lot of current thinking. So we have to resort to a different kind of mountain building by vertical tectonics. Back in the late 1960s, when I took my first geology courses at the Massachusetts Institute of Technology, this power of buoyancy in driving all kinds of geological change was still textbook orthodoxy. I still remember we used a 1965 edition of the richly illustrated classic textbook, Principles of Physical Geology by British geologist Arthur Holmes. Geology called this buoyancy of some less dense rocks on top of more dense rocks isostasy. We learned about the driving force of vertical tectonics, that is mountain building by buoyancy. The way a granite mountain rose up was called isostatic readjustment. And I love the neat little woodcut that was used in that and most other textbooks, virtually unchanged from 19th century geology texts. It showed a line of little rectangular wooden blocks at different heights floating in water. In the woodcut, the taller blocks projected higher out of the water, just like a mountain. We also read the conventional wisdom of how ocean basins gradually fill with thick layers of sediments, how those sediments melted to form more granites, how new mountains rose up in their place. And I have to say, it all made perfect sense to us. It was a compelling explanation, even if it was only partly true. So how early did granite formation begin? It seems logical that pretty early in Earth's history, perhaps within the first 100 million years, some modest-sized land masses that were rooted by buoyant masses of gray granite must have begun to form. After all, there was a lot of basalt crust, there was a lot of heat to partially melt that basalt. The oceans weren't very deep, so a mass of granite didn't have to rise very high to poke above the waves. I imagine those first isolated bits of continent, they must have been utterly barren. They were certainly windswept, and their coastlines would have been battered by intense waves. As the granite slowly eroded, rock fragments of quartz and feldspar gradually accumulated to form meager sandy beaches. In my imagination, those earliest granite islands on Earth were isolated, only a few hundred kilometers across, and probably low and rounded in profile. Earth's first continental fragments gave no hint at the scale of the continents to come. So, Earth's surface gradually became more interesting with both black volcanic cones, gray granite islands. But how did the early Earth shift from a predominantly volcano-dotted basalted world to a planet with wide, gray, granitic continents? By what process do lonely granite islands expand to the kind of hemisphere-spanning land masses that we see on the globe today? At this early time, with predominantly vertical mountain building, no obvious mechanism could have caused isolated granite masses to coalesce into expanses of dry land the size of today's continents. You know, one of the most enjoyable aspects of the earth science is creative storytelling. Geologists have never been shy in inventing clever stories, and a good idea can gain traction even if the supporting evidence is sparse. Among the more intriguing ideas to emerge in recent years suggests that giant impacts played a central role in continent formation during Earth's first billion years. And here's how it works. For at least a billion years after the moon-forming impact of Theia, there must have been huge impacts from time to time. There were dozens of huge asteroids, up to 100 miles across, that were left over from the time of planet formation. And from time to time, they smacked into Earth. So imagine a scenario 4 billion years ago. You have a hot plume of upwelling magma rising to the surface beneath a young ocean crust. Many dozens, if not hundreds of such hot, buoyant magma plumes must have risen from Earth's deep interior. That's the most efficient way to transfer Earth's inner heat, by the efficient process of convection. And above each of these plumes, there were megavolcanoes that erupted huge amounts of basaltic lava along with water vapor and other gases. Simultaneously, all that heat caused significant remelting of basalt crust and generated a lot of granite that thickened the land. We can scarcely imagine the catastrophe as a 50-mile diameter asteroid slammed into a cluster of volcanoes above a mantle plume. The impact would have eradicated every trace of land within a radius of 300 miles, a vast area simply obliterated. The impact would have caused a giant bowl-shaped lake of magma that would have showered the adjacent surface thousands of miles around with immense blobs of magma and blocks of shattered rock. This unimaginable cosmic insult would have blocked the rising mantle plume. That mantle plume had to find a new path to the surface. Now, here's the cleverest aspect of this purely hypothetical model, which posits an acceleration of early continent development. You see, the mantle plume was diverted. In many instances, that diverted plume would probably have taken a sideways detour and thus heated another patch of ocean crust. That would have created a new cluster of volcanic islands, somewhere adjacent to the asteroid crater. But every once in a while, such a plume must have found itself shifted beneath a mini continent of granite. And once a plume was positioned beneath such a thick, heat-trapping lid of granite overlying basalt, that new heat source would probably have partially melted even more basalt to produce granite in abundance, and that new granite would have expanded and thickened the land in a way that accelerated the formation of continents. Now, admittedly, this story is untestable by direct experiment, but it makes a lot of sense. I think it's probably part of Earth's earliest continent-forming narrative, and 1 billion years of that kind of near-surface processing would have generated an ever-increasing inventory of volcanic ocean islands with complex intermixing of basalt and granite cores. Heat worked its magic. Ever so gradually, the gray land arose from the sea as big islands may have covered a few percent of Earth's surface by 3.5 billion years ago. Nevertheless, no continent-sized landmasses had yet formed. But then, along came plate tectonics, and almost everything changed. Throughout this lecture, Earth's vast store of inner heat has been a central theme. That heat arose from two major sources. First was the great amount of heat released as all those planetesimals and asteroids and comets converted their gravitational potential energy into heat. Calculations showed that the total heat released by this process was more than enough to melt the entire planet from core to crust. And added to that was an amount of heat almost as great from all the radioactive elements that were swept up in the formation process. We still have a lot of radioactive uranium and thorium and potassium and other long-lived radioactive elements. But early on, there was a lot more, including all sort of short-lived radioactive elements that dumped huge amounts of heat into the planet's interior. So that was enough to melt the planet through and through, all over again. Through Earth history, a lot of that heat energy has gradually escaped into space, and Earth has cooled accordingly. But there's still a lot of inner heat. This heat is what causes rocks to partially melt, for peridotite to produce basalt, and for basalt to produce granite. And that's not the end of the mineral forming sequence. Even granites too can partially melt, and when granite melts, it can concentrate fluids rich in the most incredible variety of rare elements. Granites lead, and will lead us to the next lecture, to the rocks that mineralogists dream about, to the amazing rocks called pegmatites. The central theme of this course is the story of Earth, but it's also the story of Earth materials. All kinds of materials, from rocks and minerals to the oceans and atmosphere. Have you ever noticed the amazing diversity of materials all around us? Look closely at a pair of your sneakers or a backpack. There are probably dozens of different kinds of fibers and metals and plastics. You'll find nylon and polyethylene, aluminum alloys, Velcro. Go into a hardware store. You'll find hundreds of other specialized materials like paints, glues, lubricants, sealants, pesticides, fertilizers, all sorts of chemicals for cleaning and polishing. an astonishing range of metal alloys. Walk into a drugstore or a grocery store, and there are literally thousands of other chemical products. Cosmetics, bug sprays, pharmaceuticals, deodorants, sunblock, petroleum jelly, margarine, cooking oils, not to mention all kind of paper and plastic products and packaging as well. By contrast, imagine yourself back 200 years to a time when the United States was a young nation with ambitions for expansion to the West. What materials did our pioneer ancestors have to work with? It's hard to imagine that time when the typical general store probably had no more than about 100 different kinds of materials. Wood, leather, bone, rocks, natural fibers were the most obvious, and there were maybe 8 or 10 different kinds of metals: iron, brass, tin, copper, silver, some gold, for example, and you could have obtained a few kinds of dyes, glues, oils, and paints as well. But it was nothing like today's material world. One of the keys to all this material diversity of our modern society is the process known as refining. That's the process of separating and concentrating useful chemicals from complex mixtures like petroleum. The commonest method of refining involves a tall distillation column that's hotter at the bottom, cooler at the top. And you've probably driven by chemical refineries with what looks like forests of these columns, many with a bright flame burning at the top. Petroleum is an incredibly complex mixture of tens of thousands of different kinds of organic chemicals all mixed together. So the first step in refining petroleum is to inject that sticky black goo near the hot bottom of a column, and only the most viscous components of petroleum, that's the asphalt, the tar, they remain liquid and they flow out of the bottom of that column. Everything else vaporizes, and that's the key to distillation. And the vapor rises to the cooler part of the tower. And so a succession of chemicals condenses out and flows into waiting receptacles. Candle wax comes out as a liquid in the lower part of the column. Then heating oil condenses a little higher, and kerosene, jet fuel, gasoline, butane, propane, and ultimately natural gas the higher and cooler you go. There are lots of additional steps in the production of most chemicals, but this kind of separation by distillation is the first step. In this sense, human activities today mimic what Earth has been doing for more than 4.5 billion years. Earth is like a giant still that's hotter in the center, cooler on the outside, and that temperature gradient distills all the elements of the periodic table. The sequence of rock types that we've seen so far: first peridotite, then peridotite partially melting to form basalt, and then basalt partially melting to form granite. That illustrates the point. And think about it from the mineral evolution point of view. Early in the history of the universe, there were only a dozen or so different minerals. Then came about 60 primary minerals in the chondrite meteorites, and more than 250 minerals as chondrites clumped together and were subjected to differentiation and alteration by water, heat, impacts. And even after Earth formed and the surface cooled, there probably weren't more than about 500 different kinds of minerals. So just like the early days of the United States, the number of different materials on Earth was rather limited. Now, pegmatites. They represent one more case, and an extreme one at that, of distillation. The definition of pegmatite is somewhat fuzzy, but basically a pegmatite is an igneous rock with a mass of large crystals that forms near the end of the cooling process, usually the cooling of granite. Whereas the grains in granite are visible but small, in pegmatites the grains are by definition at least half an inch in size, and often as large as your fist. And because pegmatites represent the very last stages of crystallization, when sufficient water is present, they tend to concentrate all of the strange and rare chemical elements that don't easily fit anywhere else. And that means that pegmatites can form hundreds of rare minerals that simply don't occur anywhere else. In fact, with the advent of pegmatites, the mineral richness of Earth may have doubled from about 500 to about 1,000 different mineral species. The key to understanding pegmatites is to see where elements fit comfortably into crystal structures. You see, there are lots of elements that don't form minerals in peridotite, or in basalt, or in granite. And as you go from one of these rock types to the next, these so-called incompatible elements just keep getting more concentrated in the residual fluid, the part that doesn't solidify. The key to understanding pegmatites is seeing what elements don't fit easily anywhere else. Which ones are left over at the very end of the cooling process. As the residual liquid cools in a pocket, usually inside a larger body of granite, beautiful crystals of exotic minerals can grow to immense sizes. Topaz, tourmaline, aquamarine, and other gems are found in these pegmatites. Hundreds of new mineral species formed in these rocks. As granite slowly cools, all of its principal elements gradually crystallize out as part of quartz and feldspar, the dominant minerals of granite. Quartz, which is silicon dioxide, concentrates silicon and nothing else. In quartz, there's only one kind of site for a metal atom. That's where silicon lives. It's surrounded by 4 oxygen atoms and has a charge of +4. And there's really no other element in the periodic table that can substitute easily for silicon. Look at the periodic table. We need to find a small atom, one in the first few rows that can adopt a +4 valence and is 4 coordinated with oxygen. Okay, in the first few rows of the periodic table, the only atoms that consume a +4 valence are in the 5th column. Carbon, element 6, the element above silicon, is too small. It only bonds to 2 or maybe 3 oxygen atoms, never 4. Germanium, the element below silicon, is too large for 4 coordination with oxygen. In fact, germanium almost always is found in 6 coordination. So quartz is often quite pure, and even when it has minor impurities, that doesn't help with finding a home where other elements concentrate. Okay, then there's the feldspar group of minerals. Feldspar includes silicon, just as in quartz. Then there's also aluminum, which also occurs in 4 coordination with oxygen and has a valence of +3. Now, aluminum can be replaced by a couple of other elements. The common element iron in its +3 valence state is one minor substitute. A little bit of iron in feldspar gives many granites their pinkish color. It's the same color as rust. And then there's the rarer element boron, which occurs right above aluminum in the periodic table. Boron is really too small to fit easily into the feldspar structure, but a small amount sometimes winds up there. Directly below aluminum in the periodic table is gallium, another rare element that can also enter feldspar in small amounts. It's really a bit too large to fit comfortably, though. The other key elements in the feldspars of granite are the alkali metals sodium and potassium in the first column of the periodic table. These elements always have a +1 valence state, and they reside in fairly large sites with more than 6 oxygen neighbors. And as you might expect, a few other elements can substitute. If you look at the periodic table, the first column, the next largest alkali element is rubidium, which can snuggle into feldspar, though it's pretty tight. The smallest alkali is lithium, element 3, and that really is too small. It's also common to find some calcium or even some barium from the second column. So, unlike quartz, feldspar can incorporate perhaps 9 or even 10 elements in all. The only other common minerals in granite are the little dark specks you see in a polished granite countertop. They can be any of several common minerals, including pyroxene, mica, amphibole, or garnet that hold the elements iron and magnesium. And if the granite has a small amount of the element zirconium, you might get tiny red crystals of zircon. If the granite holds any titanium, you might get crystals of the yellowish mineral sphene. But most of the other rare elements in the periodic table are incompatible. They simply don't have a comfortable bonding environment in any common rock-forming minerals. These incompatible elements become highly concentrated in residual liquids. For example, the water-rich liquids left over as granite crystallizes. And that's the secret of pegmatites. Let's look at this very last stage of a cooling granite body. As with all cooling magmas, granite cooling involves the formation of crystals, which can then separate from the leftover melt. In this case, the quartz, feldspar, dark minerals crystallize together to form the solid granite, which surrounds surrounds pockets of hot liquid that's very concentrated in water, plus the major elements of granite and possibly some of those incompatible elements. Those pockets can be anywhere from a few inches in diameter to many feet across. And in a few special cases, the leftover fluids concentrate in central chambers more than 100 feet across. It's those pockets and chambers that produce the biggest crystals on Earth and those rare exotic minerals. Let's follow the crystallization of one of these special bodies, what's known as a complex pegmatite. A pegmatite is really a very general term for any igneous rock that crystallizes into really big crystals. By the way, the mineralogical community has benefited tremendously from the studies of specialists who devoted their careers to studying pegmatites. Of special note is Professor David London of the University of Oklahoma, who has spent 3 decades of research and who recently contributed a magnificent volume summarizing what we know and don't know about pegmatites. His book, called simply Pegmatites, was published in 2008 by the Mineralogical Association of Canada, where some of the world's most important pegmatites are located. David London and other experts describe pegmatites in terms of a crystallization sequence in which some minerals appear before others. This sequence is shown most dramatically in places where the pegmatite-forming fluids gradually migrate away from the host granite. So you get a series of mineral zones as the fluids migrate and cool, and progressively get even more concentrated in rare elements. This process really is a kind of geological counterpart to distillation. The first big crystals to form are always quartz and feldspar, just like in the original granite, but without the black magnesium iron minerals. What you see in a rock outcrop are places where the fine-grained speckled granite host surrounds what were clearly pockets that got filled with much larger grains. You often see veins of coarse quartz and feldspar linking different pockets, so it's easy to imagine how there was a kind of plumbing system for those late melts. Typically, these first assemblages of coarse crystals are barren pegmatites. They don't have any of the rare minerals, just quartz and feldspar, and maybe some big flat crystals of mica. One mineralogical novelty of these barren pegmatites is a curious intergrowth of quartz and feldspar called graphic granite. Graphic granite occurs when 2 large crystals, one of clear quartz and one of white feldspar, grow simultaneously and then become intertwined. The result is a fascinating rock that looks like it carries a coded message in some strange alphabet. Graphic granite is just one of the many mineralogical wonders that's unique to pegmatites. However, graphic granite's not what causes mineral collectors to flock to pegmatites. The first of the rare pegmatite minerals occur in the next zone where the element beryllium concentrates. Beryllium is element 4 of the periodic table. It occurs at the top of the second column, right above the important rock-forming elements magnesium and calcium. And like magnesium and calcium, beryllium is always found in its divalent state. It forms ions with a +2 charge. Now, you might think that beryllium would simply follow magnesium and calcium and enter such common minerals as pyroxene and olivine, where those elements reside in sites surrounded by 6 oxygen atoms. But beryllium is just too small to fill those structures. It always occurs in crystal structures surrounded by only 4 oxygen atoms. In fact, beryllium is the only element that has the combination of +2 charge and 4 coordination with oxygen. That's why beryllium forms more than 100 different minerals, and most are pretty rare. If there's a significant amount of beryllium around, it has to form its own mineral. Now, here you might ask why there isn't a lot of beryllium around. After all, it's element number 4, coming after hydrogen, helium, and lithium. Shouldn't it have formed abundantly in stars? Well, the trick is in the isotopes. Hydrogen fuses to form a lot of helium-4, but beryllium-8 is unstable. So helium fusion in stars pretty much skips over beryllium and forms lots of carbon-12 instead. Supernovas don't stop to make any of the lightest elements either, so there just isn't a lot of beryllium in the universe. The only stable isotope is beryllium-9, which is what you find on Earth. But it's just 3 parts per million in the crust. That's less than 1,000th of a percent of the crust. Beryllium is only the 48th most abundant element, and that's why it doesn't play a big role in most rocks. But beryllium is economically important because it has a number of highly specialized technological uses. For example, because it's so lightweight, and also because it's transparent to X-rays. Beryllium forms its own minerals only when it becomes sufficiently concentrated in those very late-stage pegmatite fluids, typically about 100 parts per million. So that's at least a 30-fold concentration. That's when beautiful beryllium minerals begin to crystallize. By far the most important and familiar beryllium mineral is beryl. It's a beryllium aluminum silicate with the formula Be3Al2Si6O18. Not only is beryl the most important ore of beryllium, but you've also admired this mineral in its beautiful green and blue-colored forms, which are the gemstones emerald and aquamarine. For such a rare element, the formation of big beryllium crystals in six-sided prisms is quite remarkable. They can grow to be more than a foot long. The history of beryllium minerals on Earth tells us a huge amount about mineral evolution in general. My friend and colleague Edward Grew, who is a professor at the University of Maine in Orono, is the world's expert on these minerals. So in 2008, I challenged him to think about when the first beryllium minerals appeared on Earth. He then proceeded to do an absolutely remarkable study of the ages of every one of the 106 known beryllium minerals. What Ed Grew found is that the oldest known beryllium minerals, crystals of beryl found in Australia, formed in pegmatites only about 3 billion years ago. Now, it's possible there are much older examples that haven't been found or that may have eroded away long ago, but it's clear that beryllium minerals were much, much rarer early in Earth's history than they are today. What's more, almost all of the other 100+ beryllium minerals formed within the last 1.8 billion years. The take-home message is clear. It took more than 1 billion years of processing of crustal materials to sufficiently concentrate beryllium into fluids that can produce beryl and other beryllium minerals. It takes time, and it takes a lot of fluid-rock interactions. The reasonable conclusion is that such processes simply cannot occur on a relatively dry planet like Mercury or on the Moon. And they can't occur on a small planet like Mars that doesn't have enough internal heat to generate lots of granite. In fact, with the possible exception of Venus, Earth is probably the only planet in our solar system with all the conditions necessary to make beryllium minerals, as well as hundreds of other rare pegmatite minerals of other exotic elements. The next rare element to form minerals after beryllium in many pegmatites are the twin elements niobium and tantalum. These two elements, numbers 41 and 73 in the periodic table respectively, are found in the 5th column. Both are scarce at concentrations of much less than a part per million in the crust, but they do have a few specialized commercial uses, notably as an alloying agent in corrosion-resistant steels. Niobium and tantalum have remarkably similar chemical properties. In their metallic state, both elements are very inert at low temperature. In fact, tantalum is sometimes used in surgical implants. And both elements adopt an unusual +5 ionic charge in minerals, and they prefer big crystal sites with at least 6 surrounding oxygen atoms. No other elements have this combination of characteristics. So niobium and tantalum tend to form their own distinctive minerals. Indeed, there are dozens of unusual niobium-tantalum minerals found in complex pegmatites, and these minerals constitute the principal ores. By the way, in the niobium-tantalum-rich zones of some unusual pegmatites, you can also find concentrations of the heavy elements tin and uranium, which are commercially valuable and form their own pegmatite minerals. Pegmatites don't constitute the principal ores of these elements, but some pegmatites are sufficiently enriched to be mined for tin and uranium along with niobium and tantalum. And then we come to lithium. That's element number 3 of the periodic table. Lithium, like beryllium, is a lot rarer in nature than you might expect from its prominent position in the periodic table. It's in column 1, right below the most abundant element, hydrogen. And it's just above the common rock-forming element, sodium, of sodium chloride or table salt fame. But lithium is present in the crust at only about 20 parts per million. And it must be concentrated in the late-stage fluids more than 100-fold before it can begin to form its own distinctive minerals. That's because lithium is the only common element with a +1 charge that's comfortable in 6 coordination with oxygen, what we've called octahedral coordination, because the 6 oxygen atoms form a tiny 8-sided octahedron. Now this situation leads to an intriguing crystal chemical trick. The commonest minerals with atoms in 6 coordination with oxygen are magnesium, iron, silicates like olivine or pyroxene. In those minerals, the octahedral magnesium and iron atoms have a +2 charge. But if there's a lot of lithium and aluminum around, as there is in many complex pegmatites, then you can substitute one lithium atom with a charge of +1 and one aluminum atom with a charge of +3 for 2 iron or magnesium atoms, each with a charge of +2. That's called a coupled substitution, and it's a guiding principle in lithium minerals. When lithium does achieve a sufficient concentration, the results can be remarkable. One of the most important ore minerals of lithium is spodumene, a lithium aluminum silicate with a composition LiAlSi2O6 that occurs in immense crystals that can approach 30 feet in length in some pegmatite bodies. Spodumene is a pyroxene, just like the magnesium silicate called enstatite, which is MgSiO3. But in spodumene, every pair of magnesium atoms is replaced by lithium plus aluminum. By the way, in its purple form, spodumene is used as the gemstone called kunzite, and in its rare green form, it's a gemstone called trifate. That trick of substituting lithium plus aluminum for 2 magnesium atoms means there are lots of other lithium minerals as well, and the most abundant ones are all aluminosilicates. There's the purple lithium mica called lepidolite, which is just beautiful. There are also the rather ordinary-looking grayish-white minerals petalite and eucryptite. In fact, that name eucryptite literally means well hidden, with the same Greek root as in the word encryption. Eucryptite looks almost exactly like quartz, so it's easily overlooked in pegmatites. There are a few other unusual elements that can become concentrated in pegmatite. One of the most important in terms of sheer mineral diversity is phosphorus, element 15 in the periodic table. Now, phosphorus is an extremely important element in nature. It's the 11th most abundant of all the crustal elements at about 0.1%. So phosphorus is relatively common, at least compared to the other pegmatophile elements we've been talking about. The calcium phosphate mineral apatite is widely present in crustal rocks. In fact, it's the reference mineral for number 5 on the Mohs hardness scale. Phosphorus is also a key element in life. For example, phosphorus oxygen clusters called phosphates form part of the backbone of the genetic molecules DNA and RNA. And our cells have energy transported by a triphosphate called ATP. Phosphorus has unique crystal chemical behavior because it most commonly gives away 5 electrons to become a +5 ion, but it's so small an atom that it can only attach to 4 surrounding oxygen atoms. And here we have a new phenomenon because that cluster of a central phosphorus atom and 4 surrounding oxygen atoms is nonetheless so stable and rigid that it behaves like a separate molecular building block, a 5-atom PO4 group with a -3 charge. This cluster is the phosphate ion, and it is the essential building block of all of the hundreds of phosphate minerals. So when phosphorus becomes concentrated in a pegmatite along with all those other more exotic elements, you suddenly get hundreds of new kinds of phosphate minerals that simply don't occur anywhere else on Earth and probably don't occur anywhere else in our solar system. There are beryllium phosphates, and niobium tantalum phosphates, and uranium phosphates, and lots of lithium phosphates. Many of these minerals are extremely rare, forming only tiny crystals that only the most experienced mineral collectors can identify on site. Some of these minerals form as colorful microscopic crystals in tiny open pockets, which reveal that at the very last stages of cooling pegmatite, some of the minerals form from a hot vapor, and probably not as a liquid. And then we come to boron, element 5. It's yet another distinctive and relatively rare mineral forming element. At only 1/20% of Earth's crust, boron is not a major rock former, but it does tend to concentrate into one of the most fascinating minerals in nature, or rather the group of minerals called tourmaline. Like lithium and beryllium, boron is unique in terms of its crystal chemistry. It's the only element that has a +3 charge, and and typically occurs in 3 coordination with oxygen. Tiny BO3 triangular clusters of atoms lead to numerous unique minerals, but the tourmaline group dominates in pegmatites and many other kinds of rocks as well. As we saw when discussing minerals in lecture 4, the complex tourmaline crystal structure has all sorts of atom sites, room for alkali metals and divalent atoms in 6 coordination, and silicate and aluminum and more. In fact, more than 50 different chemical elements can find some kind of home in the accommodating tourmaline structure. That's why there are almost 20 different categories of tourmaline minerals and literally thousands of compositional variants. Tourmaline's individual crystals can grow and change composition at the same time, a phenomenon called zoning, and those zones can be different colors. Now, most tourmaline crystals are black, but when they incorporate other sorts of elements, you get these triangular prismatic crystals, roughly triangular in cross-section. They can be absolutely gorgeous. Some of the most amazing and beautiful crystals in nature are zoned tourmalines. You may have seen the varieties sold as watermelon tourmaline with a pink interior and green ends. And there are blue tourmalines, and there are red tourmalines and yellow tourmalines, and all sorts of amazing zone varieties. I think my very favorite tourmaline specimen, and it's hard to choose a favorite, is the famous candelabra from the Pala mine in California. That specimen of the Smithsonian Institution has 3 big watermelon tourmaline crystals standing in a row, surrounded by other beautiful crystals of quartz and feldspar. That specimen epitomizes what collectors love about pegmatites. But I've saved the most amazing example of a pegmatite mineral for last. Cesium, element 55, is one of the rarest elements in nature to form its own mineral. Cesium is in the first column of the periodic table, like the much more common elements lithium, sodium, and potassium. Cesium represents only about 2 atoms per million in Earth's crust, and yet in certain complex pegmatites, you can find crystals of the mineral pollucite, cesium, aluminum, silicate. In order to form a pollucite crystal, the fluid concentration has to rise from 2 parts per million to at least 40,000 parts per million. That means 4% cesium is needed. That's because at lower concentrations, cesium follows other alkali elements as a minor element in feldspar and mica. So there needs to be a concentration mechanism by a factor of at least 20,000. But what is most amazing is that in some pegmatites, there are individual masses of pollucite crystals more than 30 feet across. How's that possible? David London estimates that those pollucite crystals represent the concentration of cesium by fluid rock interactions of a volume of crust approaching 10,000 cubic miles. And that is what's so special about pegmatites, and how pegmatites and the unique mineralogy may distinguish Earth from all other planets. Earth is an engine of mineral diversification. It may have taken 1 billion years or more to distill our planet to the point where beryl and tourmaline and pollucite can form. But now what treasures lie in wait for the keen-eyed collector. And yet, as extraordinary as pegmatites may be, that whole ensemble of diversifying minerals is also moving across and plunging deep into the surface of Earth. Next time, we'll trace discoveries leading to the realization that Earth's continents move, and that Earth's rocks travel from deep inside the planet to the surface again and again in a round trip we call the rock cycle. Great scientific discoveries often require decades, if not centuries, of painstaking observations and data collection. It's rare that a big new idea springs forth from only one mind, or that a new point of view takes root quickly. So it was with the discovery of plate tectonics, which we now recognize as Earth's dominant geological process. Indeed, the establishment of plate tectonics is in many ways a scientific story that spans most of modern science. In this lecture, we're going to look at work leading up to plate tectonics, which was anticipated by at least 4 centuries of research. The once heretical ideas that entire continents somehow shift across the globe came only into sharp and convincing focus during what became an international rush of discoveries in the 1960s. But science reaches a tipping point. Once the mass of evidence piled up, geology went through one of the most rapid paradigm shifts in the history of science. That's why, within just a few years of my undergraduate courses at MIT, every geology textbook had to be completely rewritten. In a blink of an eye, lateral tectonics replaced vertical tectonics. The earth science community quickly came to realize that lateral movement of tectonic plates plays the central role in such diverse phenomena as global climate, vertebrate evolution, ore deposits, continent formation, and the diversification of the mineral kingdom. I suppose that in some respects, some lines of evidence against vertical tectonics, that is, mountain building by buoyancy, should have been pretty obvious. In North America, we look to the Rocky Mountains as our grandest range, and it's not so difficult to imagine buoyancy playing the key role in their uplift. But the Rockies only rise about 14,000 feet at their tallest points. They're absolutely dwarfed by the 5.5-mile height of Mount Everest and the rest of the mighty Himalayan range. It's even harder to imagine the greatest ocean depths, but think about this. The oceans average about 2 miles deep, yet Earth's deepest ocean trench, which is located off the Mariana Islands in the South Pacific, plunges to an astonishing 7 miles. How could such an extreme depth be maintained on a planet ruled by nothing more than gravitational rise and fall? Such an extreme depth could not possibly be sustained by buoyancy alone. So we have to conclude that vertical tectonics can't be the whole story. There have been subtle hints pointing to lateral tectonics, the vital role of sideways motion driven by heat as opposed to gravity in Earth's geological evolution. The first striking evidence came with the charting by 15th century explorers who collectively produced the first accurate maps of the coastlines of the New World. By the early 1600s, the rough outlines were delineated, and the striking conformity of the east coast of the Americas and the western shores of Europe and Africa were obvious to anyone who looked. Many details are mirrored on opposite sides of the Atlantic. Both continental margins have a broadly S-shaped contour. Embayments on one side match the coastal bumps on the other. The suggestive curl of South America's tip fits the southern end of Africa. It all looks like the fit of 2 jigsaw puzzle pieces. Early attempts to explain such matching features were unsuccessful, if not downright bizarre. Harvard University astronomer William Henry Pickering enthusiastically supported George Darwin's fission origin of the moon as a molten blob hurled into space from a rapidly spinning Earth. So he suggested that the Atlantic Ocean opened wide on one side of Earth in response to the moon being ripped from the Pacific Ocean on the opposite side. Others thought they glimpsed the mighty hand of God in that great Atlantic S-shape. They speculated that the Atlantic coastlines were the shores of Noah's flood. The deluge was unleashed a few thousand years ago to create the great ocean and, as the Bible says, divide the lands. Systematic surveys of rocks, minerals, and fossils might have helped resolve the question. But 400 years ago, the field we call geology hadn't even been named, much less pursued in any systematic way. The very practical economic pursuits of mining and agriculture, not science per se, were the driving forces behind the earliest geological surveys of the late 18th century. What's more, these surveys were strictly state and national affairs. Almost no attempt was made to match up geological formations across political boundaries, and there was no thought that the riches of one principality could be linked in any coherent way to those of any other unless a particularly valuable deposit straddled the territory of 2 nations. Prior to plate tectonics, gold was quite literally where you found it. So you can imagine that attempts to match up geological features across the great expanse of the Atlantic Ocean between South Africa and Brazil, for example, or the USA and Spain was not of much interest. So even after the field of geology got its name in the 18th century and began to be pursued as a science, most geologists weren't thinking about correlating features across oceans. Nevertheless, I find it really surprising that the very first detailed transatlantic geological comparisons were made by a meteorologist. It was the German scientist Alfred Wegener. He spent a good part of his career in the Arctic. In fact, he died there on the Greenland ice sheet during a heroic winter rescue mission. Most of Wegener's professional life was devoted to the origins of weather and climate, hence his interest in the climate-sensitive Arctic. However, Wegener's most memorable and lasting work by far related to what has been called continental drift, which is a pioneering and much maligned contribution to lateral tectonics. His inspiration for this odd digression into geology occurred during World War I. Alfred Wegener was serving as a reserve lieutenant in the German army when he was shot through the neck during the Belgian campaign. He was relieved of further frontline duty and thus was given a chance to devote his convalescence to study. Like many scholars who came before him, Wegener was struck by the evident fit of the Americas with Europe and Africa across the Atlantic Ocean. Some had simply dismissed the fit as coincidence, but Wegener cast a wider field of view and realized that similar continental matches could be seen in the coastlines of East Africa, Antarctica, India, and Australia. In fact, it turns out that all of Earth's continents can be rather easily clustered together to make one supercontinent, which he dubbed Pangaea. Wegener also realized that one could test the hypothesis that the continents were all once joined together by looking for identical marginal features. He and others cataloged evidence from the recently published geological surveys of coastal regions of Europe, Africa, the Americas. These treatises, published in many languages by many independent authors, point to numerous intriguing correlations across the wide Atlantic Ocean. Among the most obvious correlations are great mining districts, such as the extensive stream-hosted alluvial diamond fields of Brazil and Africa. These economically important zones form a single large deposit when the continents are juxtaposed. There are also many examples of similar distinctive fossils on both sides of the Atlantic. Rock layers holding the distinctive fossil fern Glossopteris line up almost exactly, as do other beds with unusual fossil trilobites and early vertebrates. Wegener detailed these observations and argued that such geological and paleontological correlations can't be simple coincidence. Now, Wegener wasn't shy about promoting his ideas. The continental drift hypothesis first appeared in print in 1950, and he kept expanding and elaborating on the idea. 3 subsequent German editions were published, each one much more detailed than the last, and there was also a widely available 1924 English translation entitled The Origins of the Continents and Oceans. And then many other editions in various languages followed. The continental drift hypothesis gathered some interest and support. As more data came in, so did some support for the idea that continents were once joined together and later drifted apart. In 1917, for example, a committee of paleontologists cataloged more than a dozen instances of distinctive fossil-bearing strata matching up across the oceans. Now, they proposed that there was once some sort of land bridge between the continents, now washed away. More support came from South African geologist Alexander Du Toit, who was especially enamored of Wegener's ideas. He was able to obtain a grant from the Carnegie Institution, that's the same institution that supports my lab, and then he visited Eastern South America, recorded more examples of transoceanic matchups, and published his work in 1927 and 1937. So, some scientists took Wegener pretty seriously. In spite of the growing evidence that the two sides of the Atlantic somehow match up, most members of the earth science community were unpersuaded. And there was a good reason for this. Newton's first law of motion tells us that nothing happens without a force. So if continents were somehow drifting apart, then there must be a huge force at work. Wegener simply had no answer for that objection. In fact, his default suggestion was merely that continents somehow cut a path to the even harder underlying rock of Earth's crust. Well, without a reasonable mechanism for continental drift, most geologists were openly contemptuous of the idea. Until an epic global-scale force could be clearly established, continental drift was just doomed to be another crackpot idea by a geological amateur. And there are some pretty brutal quotes from this era. One of the milder ones came from Cambridge physicist Harold Jeffreys, who summed up the British viewpoint in 1923 when he wrote that, quote, "The physical causes that Wegener offers are ridiculously inadequate." And leading geologists in America were equally unconvinced and perhaps less restrained in their rhetoric. Roland T. Chamberlain of the University of Chicago's Geology Department mocked continental drift at a 1926 symposium on the subject. He said, "Wegener's hypothesis in general is of the footloose type, in that it takes considerable liberty with our globe and is less bound by restrictions or tied down by ugly facts than most of its rival theories. If we are to believe Wegener's hypothesis, we must forget everything that has been learned in the last 70 years and start all over." Not everyone was so dismissive, but the ideas of some of Wegener's supporters were sufficiently wacky to generate more negative than positive feedback. The key was to come up with some kind of novel mechanism for continental shifts. One amusing school of thought posited that Earth is shrinking, perhaps because it's slowly cooling and thus contracting, or maybe by the collapse of gas-filled chambers in Earth's deep interior. It doesn't really make sense if you think about it, but the proposal was that portions of Earth's surface gradually fall inward like a broken archway. So if the continents once were linked by land bridges, as some paleontologists proposed based on fossils, then you could imagine continuous solid land from the eastern coasts of Africa and Asia all the way to the western coast of the Americas. And when that great archway collapsed, what remained was today's Atlantic Ocean. But this model simply doesn't work. The basic geometry of a sphere, first set down by Euclid thousands of years ago, shows that while a simple archway can collapse, there's no way that a volume of continental rocks covering an area the size of the Atlantic Ocean could collapse into anything. So another group of Earth scientists proposed the exact opposite hypothesis, that Earth has been expanding and continues to expand to this day. Somehow, according to this scenario, Earth inflates like a balloon over geological time. And it must have inflated a lot. The expanding Earth community points to a time hundreds of millions of years ago when the entire surface was covered only in continental crust. This thin, brittle crust had to crack and split apart as Earth inflated. In fact, if you play an animation of a supposedly expanding Earth backwards, then you do arrive at a remarkable point when all the diverse continents slide neatly together to cover almost a perfect sphere. That's about 3/5 the size of our modern planet. But finding a reasonable mechanism to expand Earth over hundreds of millions of years has proven to be a serious drawback. Some scientists have invoked the steady internal pressure of expanding gases, but it's really hard to imagine how to trap that much gas beneath the surface. Others point to possible gradual phase transitions of some minerals from more dense to less dense forms. Here's how that idea works. Earth's interior is filled with extremely dense mineral phases. Some minerals are more than twice as dense as those on the surface. Now, that's quite reasonable. We know, for example, that the high-pressure diamond form of pure carbon is about twice as dense as the low-pressure graphite form. Moreover, some high-pressure minerals are less stable than their lower-pressure counterparts. So if Earth formed with a lot of high-pressure minerals, and if some of those minerals started to transform, then Earth's total volume has to increase. What's more, as Earth gets larger, the pressure in the mantle and the core gradually lessens because more mass is farther from the center, and the force of gravity is correspondingly less, which means that more minerals can transform to their less dense, larger volume minerals. And that keeps driving Earth's expansion. This hypothesis has never been a mainstream idea, but it does have real staying power. If you were a scientist who thought the geological and topographic matchups across the Atlantic Ocean are real, then you needed some kind of explanation. And before there was any other viable mechanism for forming the Atlantic, the expanding Earth hypothesis was about as plausible as you were going to get. A significant number of prominent Earth scientists seriously considered expansion from the 1920s to as late as the 1960s. And even today, there's still an active, if marginalized, community of expanding Earth enthusiasts hold conferences and they publish journals. Nevertheless, most scientists gladly abandon any notion of a shrinking or expanding Earth as soon as a compelling new idea took its place, and that idea was plate tectonics. This leads us to a fundamental point about geology. Technology is great. There's no way modern Earth science could have made the advances and discoveries it has without technology. But at its very core, geology is about the solid stuff that forms our planet. Everything we know of Earth ultimately comes from the testimony of the rocks and minerals. As we learn more and more about esoteric approaches to Earth sciences, ion probes, mass spectrometers, gas chromatography, magnetometers, it's easy to lose sight of the fundamental importance of the rocks themselves and of trekking to remote locations across the globe to retrieve samples, document their geological context. No matter how sophisticated our labs might become, there is simply no substitute for the arduous, often dangerous, utterly exhilarating study of our planet in the field. And what we find all across the globe are three basic kinds of rocks: igneous, sedimentary, and metamorphic rocks, which collectively make up Earth's great cycle of rock formation. Think about what we've learned about rocks on earliest Earth. When Earth formed, there were no rocks anywhere. During Earth's initial accretion, and certainly again following the impact of Theia, Earth was entirely molten. It was a glowing magma ball orbiting the sun with no solid land, no oceans of water, no atmosphere, but as surface temperatures dropped below the melting point of rocks, a black crust solidified, much as that first layer of ice forms in a pond in winter. Those first solid rocks at Earth's surface were examples of igneous rocks, rocks that form from the hot, molten state. Basalt is an igneous rock, as is granite. Igneous rocks come in two principal types, both of which we've met frequently in Earth's early stages. Volcanic rocks, or extrusive rocks, form quickly at Earth's surface as magma solidifies in air. These are by far the most spectacular of all rock-forming events, with red-hot fountains and flows of lava oozing down the slopes of growing volcanic cones. Basalt comes to the surface in this way, crystallizing quickly into small grains. Similarly, if the raw materials for granite erupt to the surface, they can produce a fine-grained material called rhyolite. Volcanic rocks also include accumulations of ash, cinders, other debris that can travel long distances in the air before they settle into layers at the surface. You may recall recent events in Iceland or Alaska, or Mount Etna in Italy, where volcanic ash disrupted air travel. The second major type of igneous rocks harden underground, typically forming larger grains, and are called intrusive rocks. You can imagine how in the vicinity of a volcano there are reservoirs of magma underground, and some of that magma solidifies before it gets to the surface. So, for example, basalt often exploits underground cracks near volcanoes to form vertical breaks called dikes, and horizontal or slanted layers or sheets of igneous rock called sills. The raw materials for basalt also crystallize more slowly underground, producing a more coarse-grained intrusive rock called gabbro. A great example is the Palisades on the Hudson River near New York City, which formed in this way. Less dense than basalt or gabbro, granite is perhaps the most common intrusive rock in Earth's continental crust. Granite is tough, is valued as a building and ornamental stone. New England is particularly famous for its many fine granite quarries. Earth's first crust was composed almost entirely of igneous rocks. But sedimentary rocks, the second of our three major groups, account for 2/3 of all rocks exposed on Earth's surface today. They form wherever fragments of other rocks accumulate into layers. You can imagine that process occurring on early Earth. When the first rains began to fall on the first igneous rocks, the process of weathering began. Small mineral grains were washed off those recently hardened volcanic rocks, basalt and granite. Lots of grains, quartz, feldspar, pyroxene, and the occasional tiny red zircon. They flowed down through streams and rivers, were laid down into layers in shallow lakes and on the ocean floor. Weathering also occurred by chemically dissolving rocks and by the mechanical action of water freezing in cracks. Over time, thick layers of sediment accumulated, especially in big fan-like deltas at the mouths of rivers. These sediment layers can reach incredible thicknesses in many places on Earth right now, like the Mississippi River Delta that extends into the Gulf of Mexico. Sediments are miles deep. Sediments start as loosely consolidated grains, just like the sand at the beach. But when sediments are buried deep, the temperature and pressure increases, and hot water flows through the sand and silt layers, dissolving and redepositing glue-like chemicals. All that pressure, the heat, the effects of mineral-laden water welded the bits of sediment together into new layered rocks. Depending on the grain size, we have conglomerate with big pebbles, or sandstone with medium-sized grains, or shale and mudstone made of finer-grained silt and clays. And when lots of dead plant matter accumulate, you can get sedimentary deposits of peat or of coal. Every sedimentary rock tells an amazing story. Some very uniform sedimentary rocks form at the base of a single mountain or cliff from one kind of rock. That's common on volcanic islands like Hawaii, where a lot of the sand on a black beach comes from weathering of basalt. But at other places, the collection of sand grains accumulates from many different localities. Imagine the big delta at the mouth of the Mississippi River. Those grains come from cliffs in Minnesota, valleys in Pennsylvania, mountains in Texas, more. The same way the sediments deposited near the mouth of the Colorado River carry bits of history for much of the North American West. A great and relaxing way to get an appreciation of sedimentary rocks is at the beach. Just pick up a handful of sand, and you'll see every grain is different. Some are light colored, others dark. Some are smooth, others angular. And think how each grain once was part of a far away rock. As that rock weathered away, that grain was chipped off, carried to your hand by wind, by water. Eventually, probably millions of years from now, the sand you hold in your hand will be transformed into solid rock. Indeed, the story of a single sand grain provides a good metaphor for the way that all Earth's atoms are recycled. Those atoms are always shifting around, but it's always the same matter, recycling over and over again. So far, all the sedimentary rocks I've mentioned form from tiny particles, or sediments. But many sedimentary rocks form directly by chemical precipitation from water. One familiar example is salt deposits from a dried up salty lake. There are places where immense layers of salt have accumulated. Some of those have been mined for centuries, for table salt. But lots of other chemicals can form rocks by precipitation. The most common of these is limestone, which forms from calcium carbonate. Early in Earth's history, carbonate minerals were deposited directly from the ocean. Later, by contrast, most carbonate was formed by living sea creatures, especially corals, so most big limestone formations are clear signs of life. In fact, limestone often holds beautiful fossils of ancient animals that lived near those coral reefs. Wherever you travel around the world, you're likely to encounter many common varieties of sedimentary rock. They're really easy to spot in road cuts and outcrops because of the distinctive layered appearance. In fact, some of the most amazing scenic places in North America, Bryce and Zion National Parks, the Grand Canyon, the Canadian Rockies, many other places feature spectacular sedimentary rock formations. The rich variety of metamorphic rocks encompasses the third great group of rocks on Earth. As igneous or sedimentary rocks are slowly buried deep, they're subjected to intense heat and pressure, and they can transform into new kinds of rocks. For example, shale or mudstone will turn into layers of brittle, hard slate. That's a kind of rock sometimes used for roofing shingles or old school blackboards. At even higher temperatures and pressure, slate transforms into phyllite, which has more luster, and then into beautiful banded schists, and ultimately gneisses, which often have crystals of garnets and other high-pressure minerals. You can recognize road cuts and outcrops of these metamorphic rocks because they look like a giant cross-section of a swirled marble cake. Sandstone quartz also metamorphoses when it is exposed to high temperature and pressure. The original sand grains can fuse into a solid mass known as quartzite. And when a limestone is subjected to high pressure and temperature, it can transform into marble. If you you ever travel the roads of Vermont, chances are you'll pass an outcrop or a road cut of distinctive greenish white cast, a rock with intricate bands and swirls. Marbles take a high polish and have been prized for many centuries by sculptors and architects. Igneous, sedimentary, metamorphic rocks all participate in the rock cycle. Igneous rocks, once formed, can be weathered to form sedimentary rocks, or they can undergo metamorphism. Layers of sedimentary rocks can also be transformed into metamorphic rocks. And all three kinds of rocks can be partially melted and reformed as new igneous rocks. In this way, the rock cycle never ceases. There's one more crucial aspect to understanding the rock cycle, and that's time. It often takes immense spans of time, hundreds of millions of years, to make new rocks or transform them. This discovery of deep time was made more than 200 years ago by the Scottish geologist James Hutton, who lived in Edinburgh from 1726 to 1797, and who's often called the founder of modern geology. James Hutton reached his great insight near the town of Jedburgh, where spectacular sea cliffs reveal vertical layers of rock overlain by horizontal layers. Now, how could such a sequence have occurred? Hutton studied these remarkable cliffs, and he realized that he was seeing the end product of a long chain of events. The obvious first step must have been that a sequence of sediments was deposited in the normal way as horizontal flat layers, one on top of another. Step two, those layers had to be buried sufficiently deep that hot mineral-rich fluids cemented them into sedimentary rocks. Then third, some kind of tectonic activity must have disrupted those layers, pushing them from the sides, thus breaking and folding them until they were tilted nearly vertically. And after that, third step, those vertical layers of rocks had to be lifted up and eroded down to create a new surface with a vertical base exposed. That's step four, but we're only halfway done. After still more tectonic activity, the vertical beds of rock found themselves at the bottom of an ocean or a shallow sea, so rocks had to sink or else sea levels had to rise. And then another sequence of sediment layers was deposited on top of the older contorted rocks. And then those sediments had to be buried and turned into solid rock. And finally, another episode of uplift and erosion has brought the rocks to the surface where the ocean is eroding a steep cliff and exposing everything to Hutton's view. Well, Hutton not only recognized this complex sequence of events, he also realized that all those processes, sedimentation, burial, uplift, tectonic forces, more, they're acting today, albeit very slowly. He concluded that the same geological forces must have been operating for an almost unimaginably long time. Each step of the formation process must have taken tens to hundreds of millions of years. In order for a formation like the one at Jedburgh to exist, Earth had to exist not for thousands of years or even hundreds of thousands of years, but for many hundreds of millions of years. Thanks to Hutton and his successors, we now know that Earth's age is more than 4.5 billion years, and the existence of structures like the one at Jedburgh become comprehensible. In the words of Hutton himself, the testimony of the rocks offer no vestige of a beginning, no prospect of an end. Hutton had captured a crucial feature of what we call the rock cycle, where surface rocks are ceaselessly broken down and become the raw materials for creation of new rocks. And once we combine the ideas of this lecture, continental drift, and Earth's great rock cycle, and the power of deep time, we're ready to explore the force that unifies all of these observations and provides Earth's mightiest agent of change, plate tectonics.
Volcanic eruptions and other natural phenomena remind us that Earth is a dynamic, evolving planet. Over geological time, the heat from Earth's core drives slabs, called tectonic plates, to shift around on the surface. As a result, oceans open and close. This is stage 5 of mineral evolution, where new minerals appear that are rare or absent elsewhere in the solar system.
Following the global disruptions of World War II, Earth scientists were once again poised to tackle the big question of how mountains and oceans form. As I noted in the last lecture, technological developments provided the new key evidence. In fact, it was two developments in anti-submarine warfare, both declassified and adopted by oceanographers in the 1950s, that led directly to transformative discoveries about the dynamic Earth. The first key advance was sonar, which employs the echoes of sound waves to measure distance and direction. This is technology that's more than a century old, and it's certainly familiar to anyone who's enjoyed any of the stylish Hollywood submarine movies. The sonar sends out a ping, and that brief sound is answered a short while later by a softer echoing ping. In naval warfare, that sound wave is bounced off the solid hull of a hidden submarine. And have you ever noticed how the effect on the audiences is quite different depending on whether the movie's point of view is inside the submarine or on the deck of a destroyer? Anyway, you have that tension building effect. Ping, 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 ping. The faster the echoes come, the closer the submarine. The exact same concept has also been put to scientific use in the study of the ocean floor topography. That's critical not just to science, but also to the Navy, whose submarines need to navigate in the deep ocean. And even the deepest hidden ocean mountains and valleys can be observed and mapped with sound waves. Even before sonar, there were hints that the floor of the mid-Atlantic had great mountains. In the 1870s, British scientists employed relatively crude deep water soundings aboard HMS Challenger, and the first echo sounding technology was developed for iceberg detection following the 1912 Titanic disaster. And then sonar saw rapid improvement during World War I in an effort to track German submarines. So scientific applications began with ocean floor mapping in the 1920s, and that's when it became clear that great mountain ranges lay hidden beneath all of Earth's ocean. But just as oceanographers were coming to grips with the implications of submerged mountain range, along came the Great Depression and the looming World War, and oceanographic research was all but stopped. The Second World War began a new generation of high-sensitivity sonar detectors. After the war, not only could oceanographers map the ocean floor topography, but they could also measure sound waves reflected from deeply buried rock layers to get a sense of ocean floor geology. The most general topographic features of the Atlantic Ocean were quickly confirmed. The continental shelves extend up to hundreds of miles away from the present Atlantic coastlines. They deepen gradually farther from shore and then reach a steep edge where depths suddenly increase to an abyssal plain 2 miles deep and 1,000 miles across. That distinctive feature is much wider and flatter than anything on dry land. Oceanographers also confirm that the Atlantic is divided right down the middle by a huge mountain range called the Mid-Atlantic Ridge, so those findings agreed with earlier results. What was new was the discovery that the ocean crust is significantly thinner than continental crust. Now, geologists have predicted that the ocean crust would be thinner than continents, and that the ocean crust would thin gradually the farther you got from the continental shelf. What they found instead was an abrupt change from tens of miles of crust beneath the continents. The ocean crust only about 5 or 6 miles thick, and the transition was extremely sharp between continental and oceanic crust. The sonar operators sailed back and forth across the Atlantic dozens of times, and each transect gave the same result. Hidden beneath the ocean, right down the middle of the Atlantic Ocean, there's a dramatic mountain change more than 10,000 miles long. It's the largest mountain chain on Earth. And the shape of the range is unmistakable. It has the exact same sweeping S-curve of the continental coasts. Even more dramatic was the newly discovered fit of the continents. If you use the submerged continental shelves as the edges, then the resulting match between continent shapes is uncanny, almost as if you fit the pieces of a broken china plate back together. Scientists couldn't possibly dismiss this evidence as a coincidence. And then, as more detailed traverses of the center peaks of the Mid-Atlantic Ridge were completed, new patterns emerged. These are no ordinary mountains. Now, you've seen pictures of the Rockies or Himalayas. These mountain chains have a jagged line of high peaks right along the center. By contrast, the very center line of the Mid-Atlantic Ridge turns out to be a wide trough-like rift valley. This is a distinctive feature. It's about 20 miles wide and more than a mile deeper than the adjacent sides of the valley to the east and the west. And there's another really curious aspect to the ridge. It doesn't follow a smooth, continuous curve north to south. Instead, over and over again, the Rift Valley is sharply offset by hundreds of miles to the east or to the west, as if someone had taken the whole ridge and cut it with a knife and then shifted the pieces. These offsets, called transform faults, give the entire ridge a jagged and broken appearance. No one knew what was going on. It would have been so easy for these rather esoteric findings to be lost in the arcane oceanographic literature. There were, after all, hundreds of amazing post-war scientific discoveries in physics and chemistry and biology, and in a very real sense, it was all just data. But there's an important point in science. It's not just what you discover, it's how you promote those discoveries, and often that means it's how you visualize your data. Turns out that the lead investigators in the Ocean Floor Topography Project were especially gifted publicists. Bruce Hazen, no relation to me, and Marie Tharp were those creative marine scientists working at Columbia University's Lamont Geological Observatory. They devised a dramatic new topographic map of Earth's surface, one that looked beneath the ocean's surface. They followed the convention of other topographic maps representing elevations with a series of colors and shades. Now, it's been traditional to show higher elevations on land by gradations in color from greens and yellows to browns and ultimately white for the highest, coldest mountain elevations. In that way, all Earth's big mountain ranges stand out on the globe. Hazen and Tharp use the exact same trick by employing varying shades and hues of blue. So the Mid-Atlantic Ridge and other deep sea features clearly stand out, and they appear absolutely monumental on a global scale. They also used a great trick by centering their exquisite map right on the Atlantic. In this view, those identical shapes of coastlines in the Mid-Atlantic Ridge are highlighted in an unforgettable way. It's amazing how powerful one visual image can be. By the 1960s, thanks to the National Geographic, just about everyone had seen Hazen and Tharp's iconic map. And whatever the cause, the link between continents across the wide Atlantic was obvious to everyone. I want to share a personal story about the impact of their map. When I enrolled in geology at MIT as a freshman in the fall of 1966, I didn't know anyone in the department. So I was surprised to find that some of the most senior faculty members were quite respectful, and they went out of their way to shake my hand. Well, I didn't know it then, but I suspect it has to do with the fact that Bruce Hazen's last name, which is spelled H-E-E-Z-E-N, is pronounced just like my last name, Hazen. And you see, in science, distinguished pedigrees can have a real advantage. And some of those faculty members must have made a connection, whether it was conscious or unconscious, between Bruce Hazen and Bob Hazen. Anyway, that gives you a sense of how influential Bruce Hazen and Marie Tharp had become only a decade after the publication of their first map in 1957. It's not surprising the revelations of the shape and geology of the Mid-Atlantic Ridge, as well as discoveries of similar undersea volcanic ridges in the Indian Ocean and the East Pacific, caused scientists to revisit the possibility of continental drift. Now, everyone knows that the continents aren't drifting, but geologists were much more inclined to search for some kind of force that could shuffle Earth's surface. The 1950s were a particularly heady time in earth sciences. Discovery followed new discovery, and the new data kept confounding the experts. In 1956, Hazen and his boss at Columbia University's Lamont Laboratory, seismologist Maurice Ewing, found a remarkable connection between a 34,000-mile-long pattern of small ocean floor earthquakes extending around the globe and the positions of ocean floor ridges. Clearly, rift valleys and earthquakes earthquakes are related, and that suggests that ridges are dynamic, changeable features. The rocks dredged from the ocean floor has also surprised many geologists, some of whom had predicted that the Mid-Atlantic Ridge was a typical mountain range, perhaps capped by marine limestone like the Canadian Rockies. But collections of rocks along the ridge and from some of Atlantic's many islands were invariably dominated by volcanic basalt. And the ages of the basalt were surprisingly young. The ocean floor has a thin veneer of soft sediments, but the ocean's crust is made almost entirely of basalt. Stretching more than 2,500 miles from east to west, basalt forms the ocean crust of the Atlantic Ocean. And if you use dating techniques based on decay rates of radioactive elements like uranium, there's a very simple pattern in the rock ages. All basalt samples collected from the Rift Valley itself are recent, never more than about 1 million years old. And the farther you move east or west for the central Rift Valley, the older the basalt becomes. The rocks near the continental margins are typically more than 100 million years old. And that's a real mystery. Why should rocks near the Mid-Atlantic Ridge be so young, while rocks near the continents are old? It's logical to conclude that the Mid-Atlantic Ridge is a line of active volcanoes where new basaltic crust is being generated, but that still doesn't explain where those much older rocks at the ocean margins come from. Okay, the new data that clinched the discovery of plate tectonics relied on a second submarine hunting technology called the magnetometer. Submarines of the Second World War were big hunks of iron-rich metal alloys, and that means they're magnetic. Magnetometers have been known for a long time, but a new type of sensitive magnetic detectors were deployed by submarine hunting airplanes that could measure the anomaly of a nearby enemy submarine. So, after the war, geophysicists improved the sensitivity of those magnetometers so they could detect extremely small changes in magnetic fields on the ocean floor. So instruments were towed behind an oceanographic ship just above the sea bottom, where they studied ocean floor basalt. Okay, here's the story. Basalt always carries a weak magnetic signal because it contains small crystals of magnetite, a magnetic iron oxide mineral. When basalt magma cools, the magnetite crystals lock in the orientation of Earth's magnetic field, just like tiny compass needles frozen in ice. So ocean floor basalt preserves the orientation of Earth's magnetic field at the time when the rock hardened. There's now a big subdiscipline of geology devoted to this field. It's called paleomagnetism. So in the 1950s, oceanographers began to drag magnetometers across the seafloor, and they found something really striking. They found a totally unexpected magnetic pattern of long north-south trending stripes. All the basalt right at the ridges and rift valleys in both the Atlantic and the Pacific have a normal magnetic orientation. The little magnetic crystals point in a direction close to today's north magnetic pole. But when they went a few miles east or west of the rift valleys, the magnetic signal flips around by 180 degrees. The north magnetic pole of these basalts is pointing in the opposite direction of its present position. The north pole of these rocks is where the south pole is supposed to be. And it gets more confusing because if you sail a few more miles in either direction, the magnetic field flips 180 degrees again to the correct orientation. And there are dozens of these reversals on any given transect moving away from the rift valleys. Okay, there are three key facts. First, rocks with flipped magnetic fields occur in long, narrow, north-south trending bands that exactly parallel the ridges. In the places where the central rift valley is offset by transform faults, so are the magnetic bands. Second, whatever pattern appears on one side of the rift valley, the exact same pattern is mirrored on the other side. Magnetic stripes are symmetrical about the ridge axis. And third, ages of basalt from ridge systems around the world confirm that the magnetic reversals are global events, and they can serve as a kind of ocean floor timeline. What do these three facts imply? First, Earth's magnetic field is extremely variable. Every 500,000 years on average, for at least 150 million years, the magnetic field is flipped 180 degrees. The last major major reversal was our current polarity was about 780,000 years ago, though recent work also suggests a very brief reversal back and forth took place during the last ice age about 41,000 years ago. How can this happen? The magnetic field arises from convection at Earth's liquid iron outer core, so that convection must vary chaotically from time to time. Earth's rotation usually stabilizes this convection, so magnetic poles usually align close to the rotation axis, but the motions of liquid metal in the core can become unstable, and the poles can flip, perhaps in the span of a century or less. Second, mid-ocean ridges must produce an inch or two of new basaltic crust every year. As new lava solidifies at the ridge, older crust moves sideways, both east and west, like conveyor belts in two opposite directions, so the Atlantic grows maybe 2 inches wider every year, which means it takes roughly 30,000 years to produce a mile of new crust. And if you play Earth's tape backwards, 150 million years, the Atlantic didn't exist. Just as Wegener proposed almost a century ago, the Americas and Europe plus Africa must have been locked together. Evidence piled up from every ridge system around the globe, and in a remarkably fast transformation, all sorts of specialists in geology, geophysics, geochemistry, paleontology, and more began to talk to each other in ways they had never talked before. Seafloor spreading, as it was called, integrated efforts in earth science. A flood of publications shifted the collective mindset of geologists, and by the mid-1960s, most were convinced that continents are moving. How can anyone deny that the Atlantic Ocean has been opening for more than 100 million years? Seafloor spreading raised one obvious unanswered question. If new crust is being generated at an incredible rate of a mile-wide swath every 30,000 years along more than 30,000 miles of mid-ocean ridges, how does it all fit? Is Earth really growing larger, as Bruce Hazen advocated for a while? Otherwise, the crust has to go somewhere. Seismologists solved that problem thanks to new global arrays of seismometers that were put in place to monitor nuclear weapons testing. During the Cold War with Russia, we needed to be able to verify nuclear treaties, and continuous seismic monitoring was the key. The result was the worldwide standard seismographic network, which combined 120 stations around the world. This seismic array could tell the exact locations, depths, magnitudes, and motions of small earthquakes or big explosions anywhere on Earth. And geophysicists reaped the benefits because they could sense thousands of previously undetectable small earthquakes and see global patterns that just weren't possible to track otherwise. It turns out that most earthquakes occur along narrow, curving lines of intense seismic activity, particularly at mid-ocean ridges and along some continental margins, for example, around the Pacific Ocean's notorious Ring of Fire. Geologists knew that relatively shallow earthquakes often occur just offshore, not far from deep trenches and on the ocean floor. And deeper earthquakes often strike farther and farther inland from the coast. And some of the deepest known earthquakes occur under chains of dangerous, explosive volcanoes like Mount St. Helens in Washington state. Those volcanoes are usually located many miles inland, far from the coast. By the late 1960s, it was clear that there are important connections among trenches, earthquakes, and volcanoes. The shallowest quakes occur exactly at deep ocean trenches, which are the deepest places on Earth's surface. And earthquake depths increase away from the trenches. This pattern of deeper and deeper quakes reveals that huge slabs of ocean crust are moving down into the mantle along subduction zones. Old basaltic crust is colder and denser than the hot mantle, so subducting slabs are swallowed up, and this rigid subducting basalt buckles the adjacent crust downward to form trenches. It's a simple equation. Every square mile of new crust made at ocean ridges is balanced by a square mile of old crust lost at a subduction zone. So it was that plate tectonics, the new paradigm of the earth sciences, was born. Earth's surface is formed from a dozen shifting plates, each a cold and brittle slab of crust and upper mantle, each only a few tens of miles thick, but hundreds to thousands of miles wide. Plate boundaries are defined by ocean ridges and subduction zones. These thin, rigid plates easily slide across the hotter, softer mantle rocks. That's how continents can drift. Look at a map of Earth. One large plate is defined by the Pacific Ocean's Ring of Fire. Antarctica and its surrounding seas comprise another plate. North and South America are on two big plates that extend westward from the Mid-Atlantic Ridge all the way to the Pacific coasts, and the Eurasian plate extends eastward from the Mid-Atlantic Ridge to the Pacific coast of East Asia. The African plate is especially intriguing because it's beginning to split apart. A new rift valley is forming that traverses the equator, stretching from Ethiopia in the north down to Tanzania in the south. So someday Africa will wind up as two plates, and a new ocean will start to grow in between. Ocean ridges make new basalt, while subduction zones swallow up old crust. But there's a problem, because Earth is a sphere. On a sphere, some moving plates have to scrape against each other at long, scar-like features called transform faults. You've probably heard of the San Andreas Fault, which causes many of the big California earthquakes. Every day, more stress builds up along this transform fault because the North American plate moves to the southeast relative to the Pacific plate. I still haven't addressed the original objection of Wegener. What epic forces drive plate motions? The answer is to be found in Earth's inner heat. The second law of thermodynamics demands that heat must flow from hotter to cooler objects by one of three familiar mechanisms: conduction, convection, or radiation. Rocks and magmas don't conduct heat very well over large distances, nor do they allow much heat transfer by radiation. But long-range convection is possible, because at high temperature, rocks become soft and plastic. Over millions of years, rocks deform, they ooze, they flow. Hot, buoyant rocks gradually rise toward the surface, even as cooler, dense rocks sink. These motions set up great convection cells thousands of miles across, motions that drive plate tectonics. After all, even the biggest continent is a tiny, tiny thing compared to Earth's mantle. Shifting continents are like scum on the surface of a pot of boiling soup. The rate of convection is vast. It may take 100 million years or more for a single turn of the convection cell, which is exactly the same time required for opening and closing oceans. Think back to Earth's earliest time, 4 billion years ago. We imagine that mantle convection back then must have been a chaotic, swirling hodgepodge. There were dozens of hot mantle plumes rising like a lava lamp, carrying hot melts of low density and disorganized pulses and plumes to the surface. And isolated dense chunks of colder crust must have sunk into the interior. But lateral tectonics, plate tectonics, wasn't yet a global organized cycle. Over the next billion years, mantle convection became more orderly. Many smaller convection cells consolidated into a handful of majestic cycles, each thousands of miles across. Where these convection cells rose to the surface, new seafloor ridges rose up. Where convection cells cycled back into Earth, subduction zones formed. Earth, in cross-section, might have looked like a collection of sideways whirlpools, with each swirling rotation taking 100 million years. Thanks to plate tectonics, Earth's surface evolved, and the topography became more extreme. Giant mountain ridges of basalt grew at the diverging boundaries of ocean ridges. Deep, gash-like trenches were formed where old crust plunged downward at subduction zones. Subduction also accelerated the production of granite and the growth of continents. That because the wet, subducted basalt began to heat up and melt. Not completely, mind you, but perhaps 20 or 30%. And this partial melt rose back to the surface as granite. Granite floats. That's the key to making continents. Granitic melt slowly, inevitably rises to form near-surface rock masses. Countless granite islands have formed by this continuous process, and plate tectonics not only produces granite island chains, but also assembles them into continents. That's because low-density granite won't subduct. Basalt easily sinks into the mantle, but granite is like a floating scum. So imagine a subducting plate of basalt crust that's unsinkable, has unsinkable granite islands on it. As the basalt subducts, the islands remain at the surface to form a strip of land immediately above the subduction zone. After tens of millions of years, lots of granite islands pile up to form wider and wider strips, while new volumes of granite melt rise above the subducting zone. In this way, a continent forms from lots of smaller granite islands. Plate tectonics transformed the Earth sciences. In the dark ages of vertical tectonics, every geological discipline was more or less separate. Paleontologists had no need to talk to oceanographers. Research on volcanoes seemed unrelated to ore geology, and geophysicists were unconcerned with life's origins and evolution. Now, plate tectonics has unified everything about Earth. Earth is an amazingly complex, integrated system where every component affects and in turn is affected by every other. Nowhere is this interconnectedness more obvious than in Earth's mineral evolution, where plate tectonics is a great driver of mineral diversity on Earth. The most notable mineralogical effects were associated with extensive hydrothermal processing of the upper mantle and crust. Subduction zones in particular are sites of lots of mineral action. As cold, wet slabs subduct, they partially melt, they release lots of water in the process. That hot water rises toward the surface, in the process interacting with vast volumes of Earth's upper mantle and crust. Hot water strips out all sorts of rare and widely dispersed elements. It's a lot like the formation of pegmatites that we saw 2 lectures ago, but at a much greater scale. These hydrothermal processes of subduction zones reworked literally millions of cubic miles of Earth's outer layers and concentrated immense quantities of metal in the first episodes of massive sulfide ore bodies. Massive sulfide deposits and their associated precious metal concentrations are truly awe-inspiring. The largest mines can hold as much as 10 million metric tons of copper. Hot water concentrates copper, lead, zinc, nickel, gold, silver, many other metals, along with sulfur. When the fluids near the surface cool, all these metals precipitate out as new minerals, primarily groups of metal ore minerals called sulfides and sulfosalts. Only about a dozen different minerals form the major ore reserves, but literally hundreds of other minerals occur as accessories. And many of these are found only in this kind of rich, massive sulfide deposit. The oldest such massive sulfide deposits are found in 3.5 billion-year-old formations in Australia, and they speak to a time when plate tectonics was just getting started. North America is especially rich in younger sulfide ore bodies, with major mining operations in several western states. Plate tectonics led to lots of other mineralizing events. The new kinds of volcanoes above subduction zones involve magmas that can interact with the surrounding rock, what geologists call the country rock, in very complex ways. So you can get magmas enriched in alkalis like sodium, potassium, or calcium, or carbon. Each can in turn lead to some fascinating new minerals. One whole series of minerals that are relatively high in sodium and potassium, but low in silicon, produce new suites of minerals like sodalite and lazurite, which sometimes occur in a beautiful blue form known as lapis lazuli. Now, we can't tell for sure, but it's likely that the first sodalite and all sorts of related minerals, low in silicon, first appeared around this time. And yet another mineralogical consequence of plate tectonics was the uplift and subsequent exposure of rocks that had experienced very high pressure metamorphism. In some places, a very rapid subduction, a wedge of buoyant crustal rocks can be driven down deep, as much as 50 miles down, only to pop back up to the surface. And by pop, I mean a process that only takes a few million years. The high pressures and temperatures can produce distinct new minerals through extreme metamorphism. Quartz, for example, is observed to transform not just to quartzite, but to an even denser form called coesite. And feldspar can transform to the lustrous hard mineral jadeite, which is one of several prized minerals that's used in Asia as jade. In fact, there are perhaps 20 distinctive high-pressure minerals that only reach Earth's surface through subduction-related processes. With plate tectonics we've reached the 5th stage out of 10 in Earth's mineral evolution. We started with a dozen minerals, then increased to 60 primary minerals and chondrites, and up to 250 different species and all the varied kinds of meteorites. The next stage of igneous processing yielded 350 minerals on the dry moon and Mercury, perhaps 500 minerals on wet Mars. Then the advent of granites on Earth, and especially the novelty of pegmatite minerals, up the total to 1,000. And with plate tectonics, we add perhaps 500 more for a grand total of about 1,500 minerals on Earth by roughly 3 billion years ago. But Earth did not remain stuck at 1,500. Something else had been happening over that same period, something that would eventually take over and drive mineral and planetary evolution for the rest of Earth's history. Our planet, having attained roughly 1,500 minerals, it also provided a home for the origins of life. The story of Earth is the story of incessant change. Our planetary home has been an engine of change for more than 4.5 billion years. For the first 100 or 200 million years of Earth's history, the most dramatic of those changes would have taken place at or near the crusty, black, and sparkling blue sunlit surface. The rain of asteroids and comets, the impact of Theia, rising mantle plumes, cooling of the surface, formation of oceans, were just a few of those changes. But rather quickly, in a geological sense, certainly within the first 500 million years, Earth's mantle got into the act and took over the leading, albeit behind the scenes, role. Earth's mantle is an 1,800-mile thick zone that holds roughly 2/3 of Earth's mass and heat energy. So perhaps it's not surprising that dramatic and irreversible transformations driven by heat ultimately arise from the mantle. So it was that granite landmasses arose, literally from the mantle. Unlike dense black basalt, those first barren granite landscapes floated on the surface, and they appeared whitish gray. That's the color that results from blending colorless quartz and tan or buff feldspar. Now, if you could travel back in time to that ancient world of 4 billion years ago, you'd spot some topographic features that were more or less familiar. You could stand on solid land, on the beginnings of continents. There would be jagged hills and steep walled valleys without a trace of vegetation. In fact, it would appear not unlike some rugged coastlines of the high Arctic today. Like today, you'd probably have to endure periods of violent weather, wind and rain, punctuated by days of sunny blue or maybe orangish skies and puffy white clouds. You could rest by the cool blue ocean. You could lie on the first sandy beaches with their countless grains of resistant pale quartz grains eroded from the gray granite, with a sprinkling of durable red zircon crystals thrown in. Of course, you'd suffocate and die in a few short minutes in that dense atmosphere of nitrogen and carbon dioxide. That's an atmosphere without the slightest whiff of life-giving oxygen. It's important to put these developments in context. Early formation of protocontinents, which were the first landmasses to be constructed of sturdy granite, was just a sideshow in the sweep of Earth's evolutionary story. You might think of those first granite terrains as something like growing gray scabs on what was otherwise a pretty monotonous basalt crust. True, there were growing blue oceans, but those oceans were floored by a pretty much homogeneous black skin. Now, basalt could never rise very far above the ocean waves, but granite, which formed by deep heating and partial melting of basalt, could form mountains, chains of them miles high. Still, those rafts of granite floated to the surface much the way scum floats to the top of a pot of boiling soup bones. It's ironic that what we perceive in our anthropocentric view as the solid Earth is really a kind of geological afterthought. So our planet, at its 500 millionth birthday, was really a rather ordinary, rocky world. True, it was a little larger and a lot wetter than most of its neighbors in our solar system, but there wasn't much to distinguish it yet. Earth had big volcanoes, but so did several of the other planets and moons. Earth had a globe-spanning ocean, but it's likely that Mars did as well, at least in the first half-billion years. And it now appears that Jupiter's big moons, Europa and Callisto, those are the second and third of the four so-called Galilean moons that you can see with a small telescope. They appear to be covered by water ice with an underlying ocean, perhaps 50 or more miles deep. So they have a bigger percentage of water than Earth. Mantle plumes and convections played a big role in shaping Earth's surface, but in those early years, certainly Venus and very possibly Mars had their own versions of mantle convection and tectonics. And bulk chemistry, it didn't make Earth special either. All of the rocky planets and moons have basalt crusts. The same few elements, silicon, magnesium, iron, oxygen, they dominated the composition of all these worlds. Planet Earth had reasonable supplies of the life-giving elements carbon and nitrogen, sulfur, but so did the other interterrestrial planets. In fact, by almost any measure you could devise, our home planet early in its history, 4 billion years ago, would have appeared to the unbiased observer to be a rather ordinary planet. In spite of these initial similarities, Earth would soon become utterly unique among all the known worlds, not just of our solar system, but of any place we've yet observed in the cosmos. Now, I have to admit that Earth was already unique in a couple of respects. First, no other solar system planet or moon had experienced such radical change since its formation, especially in the violent formation of the moon. But that great transformative event was different only in its epic scale, not in its nature, for every world suffered big impacts. Second, every known planet has such a large, no other known planet has such a large moon relative to its own size. A moon that during Earth's early history was also much closer than it is today. But what was to become the most dynamic engine of planetary change? The one characteristic that sets Earth apart from every other known place in space was yet to occur. Of all known worlds, only Earth became alive. That singular feature, the origin of life, and the subsequent evolution of the biosphere distinguishes Earth from all of the other known planets and moons. That's a simple statement. Earth is unique because of life. But what exactly does it mean to be alive? How do we define this familiar phenomenon that makes Earth so very different from all the rest of the known universe? If you were put on the spot and asked to define life, you might think for a moment and then start to describe life as a number of distinctive and interconnected traits and behaviors. Life seems to differ from non-life in a number of ways. Life always has a complex structure. Life is somehow linked to the ability to grow, to adapt, and often, but not always, to move. Life makes copies of itself, so reproduction has to be part of the story. And then we might talk about the ability to evolve through mutation and selection. We might also point to a variety of distinctive cellular traits, a membrane, for example, with an inside and an outside, or perhaps we'd cite the long strands of the critical genetic molecule DNA. And we could keep going with more and more specific attributes of life, but no matter how long that list of traits, there will always be exceptions. Plant spores can lie dormant for thousands of years. Red blood cells don't have DNA. Mules don't reproduce. So perhaps the chemistry of life could provide a better foundation for defining life. After all living things are basically organized molecular systems. They undergo all sorts of chemical reactions, many of remarkable complexity and coordination. The most basic unit of every known life form is the cell, an intricate assemblage of molecules that are separated by a flexible cell membrane from the environment. Cells are remarkably well adapted assemblages of chemicals that have evolved two codependent means of self-preservation. Metabolism, by which cells take in energy and raw materials to grow and reproduce, and genetics, by which cells store and pass on all the information required to make more cells. Together, metabolism and genetics, with would seem to distinguish living organisms from the non-living environment. Okay, let's look at these two critical, all the varied chemical reactions used by all different kinds of life forms to convert chemicals and energy into more cells. Now, by chemicals, I mean essential atoms and molecules. And by energy, I mean chemical energy from the environment or light coming from the sun. In this respect, cells are just like tiny chemical factories. They take in the necessary molecular raw materials and fuel, and they use those resources to move, to repair, to grow, from time to time, reproduce. The analogy to a chemical factory is actually rather nuanced. In cells, the chemical reactions are exquisitely controlled, as opposed, for example, to a raging fire. That means the reactions are regulated by a variety of positive and negative feedbacks that keep metabolism in check. Of course, metabolism by itself isn't sufficient to define life. That's because cells, quite unlike the non-living environment, carry information in the form of molecules of deoxyribose nucleic acid. That's DNA. DNA has the remarkable ability to copy and pass molecular information and how to make and maintain cells from one generation to the next. What's more, that genetic information is typically copied with a few scattered errors or mutations. And while mutations are often harmful, they also can confer adaptability to a population of dividing cells. By promoting chemical novelty, mutations introduce innovations that, under times of stress and change, may enable a population of cells to adapt and to compete successfully against other populations that are less able to change. This plasticity of populations of cells instills the ability to survive during stressful times of environmental change, or perhaps to radiate into otherwise inhospitable new environmental niches. As hard as it may be to define life, metabolism and genetics must together play roles in any successful definition. And still, in spite of centuries of study by literally millions of life scientists, biologists have simply not been able to come up with one universally accepted definition of life. A lot of us in the origins of life field think that a panel sponsored by NASA's exobiology program probably came the closest. That group was given the charge in 1994 to define what characteristics would allow us to claim the discovery of life on other worlds. The panel was chaired by Gerald Joyce of the Scripps Research Institute in La Jolla, California. Joyce and his colleagues agreed on a rather streamlined one-sentence definition. They initially said, life is a self-sustaining chemical system capable of undergoing Darwinian evolution. Now, to put this effort in context, Jerry Joyce is one of the leaders in attempts to make life in the laboratory. That's a field known as synthetic biology in the origins of life community. And synthetic biology recently achieved this benchmark in Joyce's own lab. It was really quite a remarkable breakthrough. In Joyce's test tube-based system, he incorporated thousands of diverse interacting molecules that are both self-sustaining and evolving, at least in one sense of the word evolution. You see, all the evolution in Joyce's closed system is limited to changes in the relative proportions of a very large, but nevertheless limited suite of molecules. Depending on the changing conditions he imposes, different temperature or acidity might be examples of those changes. His complicated process only makes exact copies of the same diverse molecules that have been present from the very start of the experiment. And here's a really remarkable part of this story. Joyce could have announced to the world that he had devised the first self-replicating chemical system that evolves. That's the first life, according to his own NASA panel's definition. But instead, he realized that a chemical system that simply churns out more and more exact copies, even if the proportions of those different molecules change over time, is ultimately not much more interesting than a kind of molecular Xerox machine that spits out random copies. This exact copy scenario is quite different from natural living systems, which have the ability to mutate and thus change over time and potentially do completely new things. Joyce's lab system lacked the essential ability to explore new environments, to adapt to environmental change, to perform new tasks, This collection of molecules was ill-suited to compete with new neighbors for resources. So rather than claim the historic feat of synthesizing life in the lab, Joyce has revised his NASA definition to include one more trait, the characteristic of novelty. So now the definition of life reads, life is a self-sustaining chemical system capable of incorporating novelty and undergoing Darwinian evolution. This definition of life provides hints regarding the challenge of understanding life's ancient origins. We have to figure out how a non-living planet somehow invented those two intertwined traits of metabolism and genetics. And as you might expect, there's more than one point of view among scientists working in this topic. And one thing we tend to agree, most origins of life researchers adhere to the idea that emergence of life was an inevitable geochemical process. Okay, so what does that mean? It's clear that Earth had all the essential raw materials. We had lots of water in the oceans, we had key chemicals in the atmosphere, there were vast supplies of rocks and minerals that were rich in all the elements of life, that is, carbon, oxygen, hydrogen, nitrogen, sulfur, and phosphorus. Earth was also rich in sources of energy. There was the sun's radiation, though that was not the most likely source early on, as we'll see. More significant, I think, was Earth's inner heat. The thermal energy provided a ubiquitous, reliable source, though it's certainly possible that lightning and radioactivity, meteor impacts, and many other forms of energy contributed as well. And that's one reason why there are at least as many different theories of origins of life as there are different sources of elements and energy. Everyone agrees on a few aspects of life's origin. For one thing, carbon must have played a leading role. Carbon is by far the most versatile element of the periodic table. No other element can match carbon in the variety of its molecular designs and functions. Carbon has the ability to bond to itself and to most other elements, especially the biologically important hydrogen, oxygen, nitrogen, and sulfur. Carbon typically forms up to 4 bonds at once, which can be arranged into long chains of atoms, or interlocked rings, or complex branching arrangements, or almost any other imaginable shape. That's how carbon helps to form the backbones of all sorts of biological molecules, including proteins, carbohydrates, fats, oils, DNA, RNA. No other element has the potential to fulfill the twin defining characteristics of life, the ability to make copies and the ability to evolve. Carbon's unique chemical character explains why it's the central element of life, and it has become the dominant element of modern chemical technology. Think about all the carbon-based materials around you, all the food and pharmaceuticals you consume. Every structure of your body and the bodies of every other living organism is made from carbon-based molecules. So-called organic chemicals, those with carbon, hydrogen, and other molecules of life, are all around us in paints, glues, dyes, plastics. They're in natural fibers of your clothes and the rubber soles of your shoes, in the pages and ink of every newspaper and book. All the varieties of fossil fuels, coal, oil, natural gas, gasoline. As important as carbon was in the story of life's origins, it was by no means the only factor. The transition from geochemistry to biochemistry also must have relied on water, on heat energy, and very likely the chemical energy of rocks. This was a chemical process that also required lots of time, perhaps many millions of years. Science isn't yet able to say exactly how or when life emerged, but we are able to point to some basic principles. One guiding principle of my own research and other research at dozens of laboratories around the world is that the origins of life must have occurred as a sequence of steps. Each step added chemical complexity to the evolving biological world. First, you have to synthesize the small carbon-based molecules from which all organisms are formed. Those are the most basic building blocks of life. But these small carbon molecules are much less dense than the minerals we've been discussing so far, with values clustered around the density of water. Now, water floats on top of Earth's rocks because it's less dense than the rocks. And the same is true of these small carbon-based molecules. Indeed, the lightest would have floated on the water's surface like alcohol, or even into the atmosphere like methane. but larger carbon molecules would sink and settle to whatever rocks and water meet. Then you must concentrate and organize those small molecules into life's essential structures, the membranes, the polymers, other functional components of a cell. Ultimately, at some point, the collection of molecules had to start making copies of itself, and they also had to devise a means to pass genetic information from one generation to the next. And once molecules could self-replicate and mutate, then evolution by Darwinian natural selection took over. That's how life must have emerged. By far the best understood step in the origins of life was the synthesis of life's small molecular building blocks, including sugars, amino acids, lipids, more. All of these essential chemicals are based on carbon, and all of them are known to form just about anywhere that a source of energy interacts with simple gas molecules like carbon dioxide and water. Life's raw materials must have formed in all sorts of environments, where lightning pierced the atmosphere, for example, or where volcanic heat boiled the ocean from below, or even where ultraviolet radiation bathed molecular clouds in deep space. It's likely that Earth's first ocean, more than 4 billion years ago, became increasingly concentrated in the molecules of life. After all, biomolecules must have rained from the skies in the form of carbon-rich meteorites, and they rose from the depths of deep volcanic zones. Scientists began to get a handle on these processes in the early 1950s with what surely remains to this day as the single most famous experiment in biogenesis. The two lead characters in this drama, Nobel Prize-winning chemist Harold Urey, a professor at the University of Chicago, and Stanley Miller, his graduate student. They designed a rather simple and quite elegant tabletop experiment. It consisted of a pair of glass bulbs a few inches in diameter, connected to each other by a loop of tubing. In one bulb was a small pool of heated water, and the other a mixture of gases exposed to little electric sparks. The idea was to simulate early Earth, with the hot water representing oceans, the gas mixture representing the atmosphere laced by lightning. It only took a few days for the confined, colorless water to become first pink, then brown, with a complex mix of organic molecules. As the experiment progressed, the transparent glass around the electrodes became smeared with the sticky, black, organic sludge. What Miller found after analyzing the colorful mixture was an abundance of amino acids, lipids, carbohydrates, and other building blocks of life. He made headlines around the world with his 1953 paper in the journal Science that announced the key findings. Turns out Harold Urey modestly refused to be a co-author in that paper because everyone would assume the Nobel Prize winner was the brains behind the experiment. Well, whether or not that was in fact true, Miller's career was made. Dozens of other chemists soon flocked to the study of origin of life chemistry. Well, some details of the original experiment have been called into question. The exact combination of gases used in the original Miller-Urey experiment may not have been an exact analog of early Earth's atmosphere, nor were the electric sparks an adequate simulation of lightning. Nevertheless, thousands of subsequent experimental variations on the Miller-Urey theme have established beyond any doubt that early Earth must have been an engine of organic synthesis. Life's essential molecules abounded. That problem was basically solved, or so many scientists thought. Indeed, Miller's spark experiment may have been too successful. Many in the field mistakenly thought that the origins mystery was largely solved. Turns out that the initial enthusiasm for Miller-Urey discoveries may have come at a considerable price. You see, Miller's experiment was masterful. It placed origins of life research solidly in the domain of organic chemists. Miller and Urey established the leading paradigm that life emerged from a prebiotic soup of organic molecules formed by lightning. It was all so simple, but few experimentalists during the 1950s had considered the absolute staggering complexities of geochemical environments. Think about nature. You have daily cycles, night, day, hot, cold, wet, dry, and more. All of these cycles are key to natural environments. Real geochemical environments also display a range of natural gradients. There are gradients in temperature, for example, when volcanic magma contacts cold ocean water, or gradients in salinity as freshwater streams flow into the salty ocean. And geochemical environments also have rocks and minerals. None of Miller's experiments incorporated rocks and minerals. And along with rocks and minerals comes real chemical complexity with dozens of major and minor and trace elements, and also reactive energetic mineral surfaces. Miller and coworkers simply assumed that Earth's sunlit surface was all that was needed for life's origin, and so they spent decades ignoring what early Earth was really like. As it was, Stanley Miller's influence was immense, and for almost 30 years, he and his growing number of followers had the dominant influence on the origins of life community. On the one hand, origins of life research became an established field. With new journals, there were honors, there were awards. The Millerites, as they were called, received new sources of government funding. In fact, it wasn't until 1987 and the discovery of deep-sea communities of organisms at the so-called black smoker ecosystems that an alternative to the Miller origins paradigm emerged to challenge the primordial soup model. The idea was that in those deep zones of total darkness, mineral-rich fluids react with hot volcanic crust. Ocean floor geysers jet scalding water into the frigid ocean. A constant rain of microscopic minerals creates a kind of black smoke of reactive particles. And an amazing quantity of life abounds in those remarkable places. And that life is not fueled by the sun or lightning, but rather by chemical energy at the interface between crust and ocean. Miller and his followers hated the idea that these deep, dark, volcanic environments might have fostered life, and they did whatever they could to squelch the hypothesis. They gave negative reviews to any manuscript or grant proposal that even suggested a deep volcanic origin of life. This battle over origins paradigms has a lot to say about the way science is done. It's easy to understand why the Miller-Urey process created such a following. It resulted in a synthetic suite of biomolecules that are stunningly similar to the chemicals life actually uses. In many ways, the Miller-Urey mixture of amino acids and carbohydrates and lipids looks like a well-balanced diet. That's why Harold Urey is said to have quipped, "If God didn't do it this way, then he missed a good bet." It's okay to take sides in such a scientific argument, but there's some reason to believe that some followers of Stanley Miller may have taken things a little bit farther than typically by systematically suppressing competing ideas. While I was writing Genesis, which was my previous book on scientists' effort to understand life's origin, several leading origins of life researchers told me that their grants were denied, their papers were rejected, their careers suffered because of the pervasive influence of this point of view. That situation persisted at least until the mid-1990s. But a shift in opinion began with that startling 1987 discovery of living black smokers. And the shift was accelerated because of the powerful influence and the expanding ambitions of NASA. That's because NASA wants to discover life on other worlds. Now, the discovery of black smokers underscored a growing awareness that microbial life thrives in all sorts of extreme environments, in many places where previous generations of scientists wouldn't have dreamed of looking. These amazing organisms, which are collectively known as extremophiles, have radiated into all sorts of astonishing environments. Microbes have been discovered in extremely acidic streams that flow from old mine waste dumps, and in boiling pools above volcanic zones. Microbes have been found living inside frozen Antarctic ice and rocks in Antarctica, and they persist on stratospheric dust particles miles above Earth's surface, where they're blasted by ultraviolet radiation. And then there are really amazing deep microbial ecosystems that extend many miles beneath Earth's surface. This deep cellular life lives in narrow cracks and fissures underground. They subsist on a meager diet of chemical energy associated with minerals. And all of these microbes, integrated over the huge volume of Earth's crust, may account for a significant fraction of Earth's total biomass. In fact, subsurface life may approach the mass of all the trees, the elephants, ants, people combined. And from NASA's point of view, this is good news, because if life can survive in such extremes, especially in deep environments that were protected from impacts from asteroids and comets, then life could have originated in deep, hot zones. And if life originated in deep environments on Earth, then it could have originated in the deep environments of other worlds as well. That's why NASA, whose annual budget depends, at least in part, on the prospect of great discovery, embraced research into the possibility of deep origins of life. On the one hand, if life has to arise by a Miller-Urey scenario, with biomolecules formed in the lightning-laced atmosphere of an ocean-covered world, then our own home planet Earth, and very possibly Mars in its first 500 million years, are really the only plausible places where life could emerge. So there are only two living worlds within our reach, and we're living on one of them. On the other hand, if life can emerge from the deep, black, hot domain of an undersea volcanic zone, then lots of other solar system bodies suddenly become tempting places for exploration. Think about those nearby worlds. Even today, Mars must have deep hydrothermal zones, so it's possible that microbes live there even now. And several of Jupiter's moons are also ripe for biological investigation. Europa and Callisto are both thought to have deep, ice-covered oceans. There's also Saturn's Earth-sized moon, Titan, which is known to be rich in organic molecules and must have warm, wet zones in its interior. It's even possible that some of the larger asteroids, some of which are hundreds of miles in diameter, might have life-producing zones in their deep interiors. So the possibility of life arising deep in our planet has led NASA into planning new missions to many other bodies in our solar system. That intriguing prospect that life might have come from the deep, hot vents remains one of the most exciting frontiers in origins research, and it epitomizes how much we have to learn about the story of Earth. But in any case, the progression from the first small carbon-based molecules all the way to living microbes requires more. Next time, we'll discuss ways that simple carbon molecules could assemble into the bigger molecules of biology itself. The quest to understand the origins of life has been a respected scientific pursuit for more than 60 years. Stanley Miller and Harold Urey of the University of Chicago were pioneers in origins experiment, and their work was followed by new contributions from hundreds of researchers around the world. In that context, our team at the Carnegie Institution is a relative latecomer to origins research, but I want to tell you about some of our work, not only because it's more recent, but also because it's a good example of research to understand the second step in life's origin, that is, the arrival of big biomolecules. We did our very first NASA-sponsored experiments back in 1996, when we decided to investigate the possible roles of deep organic synthesis on the ocean floor in dynamic black smoker regimes. Those are zones of high temperatures and pressures, which are exactly what the Geophysical Lab is famous for. In many ways, our strategy was like that of Stanley Miller. Like him, we subjected chemical mixtures of plausible atmospheric gases to energetic conditions. In our case, we used heat and chemically reactive mineral surfaces, which is exactly what's found in deep volcanic zones. And just like Miller, we synthesized amino acids and lipids and other molecules of the kind used by biology. And these weren't random or chance findings. Our results have been duplicated and extended in many other labs, showing beyond any doubt that it's easy to synthesize most of life's molecules under conditions that are found across the globe, in the pressure cooker conditions of the shallow crust. The elements of life are all there. Volcanic gases contain carbon, and nitrogen. They react easily with many different common rocks and seawater to form just about all of life's molecular building blocks. And what I find especially appealing, our experiments use the relatively gentle energy associated with oxidation and reduction chemical reactions, not unlike rusting iron or caramelizing sugar. Those are the same kinds of chemical reaction that life itself uses in metabolism. And they are in stark contrast to the violent effects of lightning or ultraviolet radiation. It's certainly true that lightning bolts can facilitate the synthesis of some small biomolecules, but lightning just as easily rips molecules apart, destroying what it made before. That's why many researchers think it makes a lot of sense for Earth to have made prebiotic molecules with chemical reactions more or less in the identical way that cells do it today. Miller and his followers were initially convinced that hot volcanic zones would destroy rather than form biomolecules. But as more and more data have come in, it seems that the sources of life's molecular building blocks may be all of the above. Every early environment with an energy source and a supply of small carbon-bearing molecules probably generated amino acids and sugar and lipids and other key building blocks of life. Lightning works, ultraviolet radiation works, black smoker environments and other deep hot zones also work. More biomolecules formed during impacts of asteroids and comets. Still more from exposure to cosmic rays and sunlight. Key organic molecules even form in the kind of space-bound molecular clouds that gave rise to our solar system. Those are places where microscopic particles of dust and ice are bathed in ultraviolet radiation. Earth was made from that dust, and literally tons of organic-rich pre-solar dust still rains down on Earth's surface every year. So it's clear that the molecules for building life litter the cosmos. The first step in life's origins, the synthesis of the fundamental biomolecules, is for the most part solved. It's easy to make amino acids and lipids and sugars. Indeed, the problem is making too much, or rather, making too many different kinds. A fundamental attribute of life is chemical parsimony. Only a relatively few small molecules are used by life. But nature manufactures millions. That's why the second emergent stage in the origin of life seems to have been the selection, concentration, and assembly of molecules from the complex but dilute prebiotic soup into life's macromolecules. Those macromolecules include structures that enclose the cell and promote its chemical reactions and carry genetic information. We suspect that two complementary processes likely played a role. First, self-assembly, and then template-directed synthesis. Let's consider self-assembly first. Oftentimes, elongated molecules with a skinny backbone of carbon atoms clump together spontaneously. These chemicals, including molecules that form the encapsulating membranes of cells, are called lipids. They self-assemble into cell-sized spheres because one molecular end is attracted to water, the other end is repelled by water. If you place huge numbers of these molecules into water, they find each other. They form a remarkable double layer with water-hating ends pointing inward, away from the water, and water-loving ends pointing outward in contact with water. Every known plausible source of biomolecules, Miller-Urey, volcanic vents, tidal ponds, deep space, all form lipid molecules that self-assemble in water. Experiments that demonstrate this behavior are easy, and they've led to most origin scientists agreeing that lipid self-assembly must have played a key role in life's origins. But self-assembly can't possibly be the whole story, because most of the familiar biological molecules don't self-organize. Sugars and amino acids, for example, they tend to dissolve in water and remain there in solution. But there is a simple and effective way out. These molecules can become concentrated and neatly arrayed on the protective, orderly surfaces of different mineral crystals. So these days, the principal experimental program for many, including my own research team, is studying how life's molecular building blocks absorb onto the surfaces of virtually every natural mineral, including all of the common rock-forming minerals in the major rock types like basalt and granite. We've investigated olivine, feldspar, pyroxene, quartz, and more. In every case, amino acids and sugars are selectively pulled out of the solution and array themselves on the mineral surfaces. And there's more. When several molecules compete for the same surface, we find really interesting behaviors. So in one set of experiments, we exposed mineral surfaces to 4 different kinds of sugar molecule, each with 5 carbon atoms: arabinose, lysose, ribose, and xylose. These 4 sugars have the exact same chemical composition, but the atoms are arranged in slightly different ways. And what we find is that ribose invariably is absorbed much more strongly, and the ribose is the one that life uses in the critical molecule RNA and in other functions as well. So here we have an easy way to concentrate ribose from the prebiotic soup. And in other experiments, we find that when various amino acids are added to a solution and exposed to mineral surfaces, those molecules often cooperate and yield complex surface structures that appear to promote even more molecular absorption and perhaps more organization as well. It's easy to conclude from these experiments that wherever the diverse molecules in the prebiotic soup contacted minerals, the result was highly concentrated arrangements of life's molecules: sugars, amino acids, lipids, the building blocks of DNA. So that's an effective mechanism for achieving those critical steps of selecting and concentrating, and maybe even templating more complex structures from the formless broth. I have to take a moment here to provide a warning. I think it's just an inevitable fact of life that all of us, including origin of life researchers and all other scientists, see the world in a distorted way, through eyes that are biased by what we know best. Scientists always seem to gravitate to models that highlight their own particular scientific specialty. So it's not surprising that organic chemist Stanley Miller and his many colleagues saw life's origins as essentially a problem in organic chemistry. But geochemists, by contrast, tend to focus on the much more intricate kinds of origin scenarios that involve all the messy geochemical variables like temperature and pressure and chemically complex rocks in equally complex environments with cycles and fluxes and gradients. And then you have experts in those membrane-forming lipid molecules who promote the lipid world as the first example of self-replication, and experts who study DNA and RNA and who gravitate to self-replicating RNA as the model to beat. And Origins of Life field has attracted specialists in other areas: viruses, metabolism, clays, the deep underground biosphere. And they all have their own training and prejudices as well. It's human nature. We all do it. No one gets a PhD degree in origins of life. So everyone focuses on what they know best. And we all see the origins problem through a lens distorted by that selective knowledge. I'm no different. I'm trained in mineralogy, so it's not hard to guess where my origins of life biases probably lie. I'm inclined by training and by experience to look for minerals to play a number of central roles in life's origins. But I'm certainly not the first origins researcher to come to that conclusion. After all, what raw materials were there? You have the atmosphere, the oceans, rocks, and minerals. And it's very hard to imagine any fully developed origin scenario that doesn't rely on all 3: the gases, the liquids, and the solids. In fact, virtually all biologists who have spent any time at all with the origins problem agree. They all eventually gravitate to minerals because any origins of life scenario involving only oceans and atmosphere just runs into insurmountable problems when it comes to selecting and concentrating life's molecules. Nothing matches the solid crystalline surfaces of minerals and their ability to select, concentrate, and organize molecules. Turns out that understanding the selection and concentration of lipids or sugars or amino acids is not that difficult. In some cases, as with lipids, self-organization works perfectly well. In others, mineral surfaces get the job done. But there is one really difficult, knotty problem where the solution isn't so obvious. Biochemical processes are intricate, with complexly interwoven cycles and mind-boggling networks of molecular reactions. The only way for these layered chemical processes to work is for each molecule to have just the right size and shape and chemical reactivity. The origin of life is at heart a problem of finding the right molecule for each biochemical job. In this context, shape is destiny. Each molecule must have exactly the right shape. And that requirement leads us to what perhaps is the most daunting challenge in molecular selection, the pervasive handedness of life, or chirality. You see, many of life's most critical molecules come in mirror image pairs, left-handed versions and right-handed versions, just like your two hands. These chiral pairs of molecules are identical and interchangeable in most respects. Chiral molecules have the same chemical formulas. They have the same melting and boiling points. They look the same color, the same luster. They have the same magnetic properties, the same electrical conductivity. But left-handed and right-handed molecules have different shapes. They appear similar, but the shapes can't be superimposed. Now that's a familiar characteristic to us because we've all had the experience of trying to put a left-handed glove on our right hand or a right-handed shoe on our left foot. And have you ever tried to use a left-handed bowling ball if you're right-handed? So here's how this situation affects origins of life models. Turns out that most experiments that synthesize biomolecules, hydrothermal experiments or Miller-Urey experiments, or experiments that mimic deep space, all of them produce more or less equal amounts of left and right-handed molecules. What's more, most natural processes treat left and right-handed molecules exactly the same way. So it seems that the natural world, at least the non-living natural world, is for the most part indifferent to the distinction between left and right. Life, on the other hand, has structures so demanding that it is utterly dependent on finding molecules of the correct shape. If you need a left-handed amino acid, a right-handed amino acid molecule simply will not do. Our research team decided to tackle this knotty question of how life somehow selected left-handed amino acids almost exclusively over right, and right-handed sugars over left in a global environment that didn't seem to care about handedness. Focused on minerals, we've been exploring the possibility that handed mineral surfaces were the starring players in selecting handed molecules. And if that's true, the minerals might have been even more critical than we previously thought in the origins of life. I began these experiments in the year 2000 when my colleagues and I realized what was at the time quite a startling revelation, but is now, in retrospect, pretty obvious. Turns out that chiral mineral surfaces are absolutely everywhere in nature. Every rock, every soil is dominated by mineral surfaces on which atoms are arranged such that the places where molecules attach, tiny molecular scale handholds, if you will, are chiral. Some attachment surfaces are left-handed and some are right-handed. We find that the distribution of these left and right-handed mineral surfaces are statistically equal proportions. And we conclude that Earth, on both regional and global scales, isn't biased one way or another for left or right. But every individual molecule is either left-handed or right-handed. So those molecules do care where they wind up. You can learn more about those experiments in my great courses offering on the origins of life. In short, our years of experiments have shown that left-handed molecules can be concentrated on one set of crystal surfaces, while right-handed molecules tend to concentrate just as strongly on the mirror image sets of mineral surfaces. In that way, each chiral surface becomes a tiny experiment in molecular selection and organization. This discovery was greeted with a lot of interest, but it doesn't come close to explaining the origins of life. My colleagues and I suspect that life's origin occurred on a chiral mineral surface, where just the right combination of small molecules was selected, concentrated, organized into a system that could promote copies of itself. This event occurred at a microscopic scale on 1 tiny place on one small mineral grain. And I doubt that any laboratory experiment with minerals and molecules is likely to reproduce that exact historical event. After all, there are thousands of different kinds of mineral surfaces and millions of small organic molecules. It took a planet like Earth with countless trillions of minute mineral surfaces, each surface bathed in the molecule-rich organic soup, and miniature chemical experiments were repeated over and over again for hundreds of millions of years. In this model, the origin of life becomes an experiment in what's known as combinatorial chemistry. Just try countless trillions of experiments and see what works. That's very possible on a big, old planet like Earth, which must have eventually tested virtually every combination of small molecules somewhere, sometime. Only the tiniest fraction of all possible molecular combinations would have displayed useful self-assembly into biostructures, or developed an orderly binding to mineral surfaces, or experienced greater stability at high temperatures and pressures. Only the tiniest fraction would have learned to self-replicate and grow. No one yet knows, and we may never know exactly what combination of molecules and mineral surfaces led to the first lifelike assemblage of chemicals. But we're now learning the guiding principles of molecular selection and organization. It's now certain that biomolecules were synthesized in abundance. It's equally certain that some of those molecules formed larger and larger clusters. One principle that has emerged from our experiments is that electric charge played a big role. Some molecules carry a slightly positive electric charge. Others have a slightly negative charge. And quite a few interesting molecules, including water, are polar. That is, they have both a slightly positive and a negative end to the same molecule. In a similar fashion, mineral surfaces have charged surfaces. Some mineral surfaces are slightly positive, some are slightly negative, and sometimes the mineral will have both positive and negative regions on its surface. The result of all these charged regions of molecules and surfaces is that they can organize spontaneously as positive electric charge attracts negative electric charge. The details of this kind of prebiotic self-organization are still very much a frontier of origin research, but it's clear that self-assembly has to have occurred on early Earth in virtually every wet, chemically diverse environment. The first two steps in life's origin are pretty well understood, at least in principle. Biomolecules like amino acids, sugars, lipids, they're manufactured abundantly in all sorts of prebiotic environments. Earth's surface had all the raw materials it needed, and those raw materials could be assembled in complementary ways through self-assembly, by selection on mineral surfaces, some of which were chiral, and by intricate combinations of those two processes. But arrays of molecules, no matter how intricately they might be patterned, can't be said to be alive unless they can make copies of themselves. And here we come to what remains the biggest hurdle to understanding the origins of life. How did a collection of lifeless molecules become organized in such a way that it could make copies of itself? What was the first self-replicating system of molecules? Life's most distinctive characteristic is self-replication. One collection of molecules becomes two becomes four, doubling again and again in geometric expansion. In some cases, we can work backwards by mimicking what life does so well. Scientists have devised clever experiments that replicate portions of plausible reproductive cycles, but no one has been able to create a lab system that takes in small food molecules and makes copies of much bigger molecules. This is a huge challenge. We know that at some point in Earth history, at some specific time and location, probably in a volume smaller than a dust grain, an organized collection of molecules began to copy itself while using other molecules in the environment as food. So try to imagine Earth 4 billion years ago, when it was about 500 million years old. It was surrounded by an ocean with a very dilute broth of organic molecules. It had an unimaginably vast surface area of reactive minerals with many chiral crystal faces. What What's more, Earth had hundreds of millions of years during which it could conduct chemical experiments in all kinds of geochemical environments with varying temperature and pressure, salinity, acidity. Most of those molecular experiments, indeed almost all of those random experiments, did nothing at all of interest. Most combinations of molecules displayed no useful function. But over 500 million years, I estimate that there were something on the order of 10 to the 50th or 10 to the 60th power of different molecular experiments. That's a trillion, 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 trillion different experiments in the origins of life. That's what a big planet with lots of time gives you. Only an infinitesimally small fraction of those molecular experiments on mineral surfaces did anything useful by producing some kind of organized structure with some kind of enhanced function. Maybe stronger surface attachment, or a way to attract more molecules to the local community, or perhaps the tendency to destroy competing molecular species. And at some time, someplace, a collection of surface-bound molecules discovered the ability to make copies of itself. And then imagine how quickly the natural world would have rewarded such an innovation. Once self-replicating molecules took hold, they could rapidly take over, infesting every habitable crack and fissure on the globe. Let's take a couple of steps back. First, why would any collection of molecules spontaneously start making copies of itself? And why would that ability confer some kind of advantage? I think the answer lies at the heart of why evolution is such a powerful force. Evolution seems to be a universal feature of the cosmos. We see complex evolving systems all around us in the emergence of the varied elements and isotopes form the stars, in the evolution of minerals, which is such a central theme of this course, in the evolution of biomolecules, and in the origins and evolution of life. In all of these cases and many more, the twin evolutionary pillars are variation and selection. First, all of these systems evolved because they display vast number of different possible configurations. The nuclear particles, protons and neutrons, can come together in millions of different arrangements, of which a few are the stable elements and isotopes. Carbon, hydrogen, and oxygen are flexible and abundant atoms that can adopt an almost infinite number of different arrangements, of which the familiar biomolecules are particularly stable examples. And those biomolecules can adopt a combinatorially vast number of structures. Those are all examples of variation. These natural systems display tremendous potential variation because they're made up of lots of smaller components that can be arranged in vast numbers of different configurations. The second and equally essential attribute of all evolving systems is selection. If all possible configurations are equally probable, then evolution couldn't happen. But you just have a mess. In these systems, though, it turns out that some configurations are much more likely to survive than others. In the case of protons and neutrons, only a few arrangements are stable. That is, they aren't radioactive and spontaneously disintegrate. The same thing for organic molecules. Most atomic arrangements spontaneously break apart, and that's of course true for collections of molecules. That's selection. What survives the first cut is what is stable. But collections of molecules have the potential for even more powerful selection. For a collection of molecules to be stable, it has to first survive. But now imagine a vast prebiotic collection of hundreds of thousands of different more or less stable molecules, all of which are made of carbon, hydrogen, oxygen, nitrogen, maybe with some sulfur or phosphorus thrown in. And that's not an unreasonable estimate of diversity. Prebiotic synthesis, like Stanley Miller's experiment, and natural samples, for example, what we find in meteorites, display this high degree of molecular diversity. But it's easy to imagine that not all molecules are equally suited for survival. Some molecules are relatively unstable, and so they decompose. Any unstable molecule is quickly eliminated from the competition. Other molecules probably clumped together into useless, tar-like black masses which floated away or sank to the ocean floor. Those molecules could play no further role. But some small fraction of molecules must have proved to be especially stable. and that stability was surely enhanced when they bound themselves to others of their kind or to a stable mineral surface. All sorts of molecular interactions further refined the prebiotic mix. Some groups of molecules cooperated with each other to attach to various mineral surfaces in ways that individual molecules could not, thus enhancing the survival of the group. Other small molecules must have acted as catalysts that enhanced survival in two ways. Some chemical species promoted stability by catalyzing the formation of new chemical bonds, while others accelerated the destruction of molecular species by breaking their bonds. In this way, the molecular soup was inexorably refined. For a time, perhaps for hundreds of millions of years, the prebiotic soup was refined in these varied ways. But being the most stable molecule is not always the best way to ensure survival. Ultimately, security in the prebiotic soup was to be found not by eliminating the competition or just surviving. The ultimate guarantee of survival went to that precocious collection of molecules that learned to self-replicate. That's because self-replication increases the concentration of the winners while gradually consuming, that is, eating the competition. And it's even better than that, because in the natural world, mistakes are made. Self-replication can't be perfect every time. So mutant versions of the self-replicating molecules pop up from time to time. And while most of those mutants, at best, have no effect on the system, and at worst, are going to slow down or halt reproduction, once in a while, a lucky mutant will be better at the self-replication trick. It might replicate faster, or be more energy efficient, or perhaps be able to work its chemical magic in different environments, where it's hotter or saltier or more acidic. So self-replicating systems have the potential to evolve into new systems that do the tasks of life even better. But while we observe all kinds of evolving systems all around us, from elements to minerals to molecules, most of those evolving systems don't include self-replication. That's what distinguishes living systems from the rest of the natural world. And it's also life's greatest advantage. Reproduction is a profound invention. But how did it happen? How can lifeless molecules begin to make copies of themselves? No one knows for sure, but three competing models are now vying as scientists attempt to describe the first living systems of molecules. The origin of reproduction is the greatest unanswered question in efforts to understand the origins of life on Earth. Reproduction is the hallmark of life. Every proposed definition of life has to include self-replication, and that's why so much emphasis is placed on figuring out what was the first collection of molecules that could make copies of itself. Three different models have been in competition to describe that first self-replicating system. They are the reverse citric acid cycle, autocatalytic networks, and self-replicating RNA. Let's take a look at these three ideas. By far the simplest of these three models, and consequently the scenario that many researchers prefer, is based on a very well-known cycle of a few small molecules called the citric acid cycle. Now, you may have heard of this cycle by one of its other names. It's sometimes called the Krebs cycle or the TCA cycle, and you may have learned about it, how it works in a high school biology class. The idea here is to build up bigger molecules from smaller pieces. Start with acetic acid, which is only 2 carbon atoms, and react the acetic acid with carbon dioxide, that's CO2, to form pyruvic acid with 3 carbon atoms. Then pyruvic acid undergoes a second reaction with CO2 to make oxaloacetic acid with a backbone of 4 carbon atoms. These initial reactions are followed by other simple chemical reactions that produce progressively larger molecules, up to citric acid, which has 6 carbon atoms. So far, we've just been adding small molecules to make bigger and bigger molecules, but this cycle becomes self-replicating because the citric acid molecule splits into 2 pieces. 2 smaller molecules, one of which is acetic acid, the other oxaloacetic acid. Those 2 smaller molecules are both part of the original cycle. So now you have 2 cycles going. One started with acetic acid, the other with oxaloacetic acid. And in that way, 1 cycle of molecules becomes 2, 2 cycles becomes 4, and so on. This elegant reproducing cycle of a few small molecules has something else going for it. It turns out that it's easy to synthesize many of life's essential building blocks, including amino acids and sugars, by simple chemical reactions with the core molecules of the citric acid cycle. For example, just take a molecule of pyruvic acid, add ammonia, that's a nitrogen atom surrounded by a triangle of 3 hydrogen atoms, and you get the essential amino acid alanine. And many other important molecules of life can be made in 2 or 3 steps by such simple reactions. One of the most convincing arguments in favor of the TCA cycle as the first self-replicating system is that it's obviously very ancient. It's a kind of biomolecular fossil, if you will. Just about every known living cell on Earth has the citric acid cycle buried deep inside, so some of us suspect it's a primordial characteristic that may have descended from the very first life form. Now, it's important to remember that such a molecular cycle by itself is not alive. But the citric acid cycle does have the potential to make countless copies of one set of molecules by using other chemicals in the environment as food. By the way, there's one more fascinating aspect of the TCA cycle that I think points to its very early origins. Today, every step of the TCA cycle is helped along by a protein molecule called an enzyme. Those enzymes speed up the reaction rates, sometimes by 1,000,000 times or more. Well, it turns out that all of these enzymes have at their very core a tiny cluster of atoms, typically iron or nickel plus sulfur. That atom cluster helps to shuffle electrons, which is the key to all chemical reactions. And what's amazing is that those clusters look like tiny bits of iron and nickel sulfide minerals that we know were present on early Earth, especially in deep volcanic zones. So some of us wonder if these minerals triggered the first TCA cycle. And enzymes came later as a way to make the cycle run faster. The citric acid cycle, with just a dozen key molecules forming a self-replicating loop, is the simplest model of molecular reproduction in play right now. At the opposite extreme of chemical complexity, we find a competing model called the self-replicating autocatalytic network. This is a self-organizing model of life's origins that was championed by Stuart Kauffman, who is a pioneer in studies of complex systems. Kauffman conducted groundbreaking theoretical studies at the famed Santa Fe Institute in New Mexico. Okay, here's the idea. It's likely that the prebiotic soup grew richer and richer in its variety of organic molecules. It may have eventually incorporated hundreds of thousands of different kinds of small carbon-based molecules from different sources, including meteorites, Miller-Urey processes, hydrothermal vents, and more. And at some point, when organic molecules became concentrated, for example, in a drying tidal pool, some of those carbon-based chemicals would have triggered more reactions that made more new kinds of molecules. At the same time, other reactions would have accelerated the breakdown of less stable molecular species. And you can picture the result. The concentrations of some molecules increase while others decrease. Kauffman's idea of an autocatalytic network takes this idea to an extreme. He says there would develop a collection of molecules, maybe 1,000 or even 10,000 different species working in concert that favor the synthesis and stability of themselves while they accelerate the destruction of any molecule that isn't in that network. This is the molecular equivalent of the rich get richer, with some lucky molecules in the network, but most out. It would be difficult to claim that such a molecular network is alive. But think about its properties. The network does make copies of itself. It uses its surroundings to gain energy and food. It grows. It's far more complex in its chemical activities than most non-living chemical systems. Now, a principal objection to Kaufman's autocatalytic network idea is that it's really untestable. Even if you knew in advance what 1,000 or 10,000 different molecules to include in the cycle, and even if you could afford to buy all of those chemicals and run the experiment, there's no analytical technique that could be used to monitor the relative proportions of all those chemical species. And at this point, no one has a clue as to what chemicals to use. Ask Kaufman, he says, well, that's for the chemists to figure out. So, as intriguing as his idea might be, and it might really be the way life got started, no one is about to prove it anytime soon. Okay, there's a third origin of life scenario called the RNA world that's clearly the front runner. It's the one idea probably favored by most biologically trained origin researchers. The RNA world model is based on a molecule that is, at least for now, hypothetical. It's a molecule of the genetic chemical RNA that's learned to make copies of itself. Now, to understand why this RNA world scenario appeals to biologists, we need to think about the two most critical functions of life. Remember, first there's metabolism, which means making and assembling life's molecules into cell, and then there's genetics, which is transferring information on how to make life's molecules from one generation to the next. In modern cells, it's the complexly folded proteins that run metabolism. But the ladder-like molecule DNA stores and copies the information needed to make more proteins. It's a chicken versus the egg problem because the protein molecules assemble the DNA, but DNA is necessary to assemble the proteins. So, which came first? And it turns out that RNA may be able to do both jobs at once. RNA is an elegant polymer. It's a long strand made from numerous individual molecules called nucleotides. The nucleotides come in 4 different types designated A, C, G, and U that line up like beads on a string or letters in a sentence. You can construct any imaginable sequence from RNA letters just like a coded message. And it turns out these RNA letters hold genetic information in exactly the same way as DNA. So RNA can fulfill the role of DNA. At the same time, RNA has the ability to fold up into complex shapes that have the ability to catalyze some biological reactions. And that's just what proteins do. In fact, it's now known that RNA molecules play key roles in assembling all proteins. So in RNA, we have a molecule that does both key tasks, carrying genetic information and catalyzing protein formation. Of all life's diverse molecules, RNA is the only one that seems to do it all. Hence, this RNA world has attracted a lot of supporters, and RNA experts often dominate at origin of life meetings. But there are problems. Foremost among them, no one seems to be able to come up with any chemical mechanism to produce RNA nucleotides, much less to produce the vast numbers of different strands of RNA required to generate some random kind of self-replicating RNA molecule. But let's say, just for argument, that a plausible way to make RNA in nature did exist, and that lots of strands of RNA were assembled. Almost all of those varied strands would have done absolutely nothing. They might have simply survived or gradually degraded. So the assumption has to be that a select few strands possess some kind of survival mechanism. Perhaps they folded up to become more stable, or maybe they latched on to a secure mineral surface and were protected, or maybe they accelerated the destruction of other rival molecules. Such behaviors would be familiar examples of the struggle for molecular competition in the prebiotic soup. The central and as yet unproven assumption of the RNA world hypothesis is that one of these vast number of prebiotic RNA strands learned the useful trick of how to make copies of itself. It became a self-replicating molecule. This idea is unproven, but it may not be so far-fetched. After all, strands of RNA are a lot like strands of DNA, which we know is able to make copies of itself, and RNA, like DNA, can incorporate mistakes, and this RNA is easily mutated. So even if the first self-replicating RNA molecule was inefficient or sloppy, it would have quickly found itself competing against all sorts of slight variants of itself. And some of those mutants inevitably would have been a little more efficient at making copies, a little faster, or with a little less energy, or maybe in a warmer or saltier or sunnier environment. And I have to confess that an RNA molecule that could do all that, make copies of itself while evolving, would seem to fulfill all of the minimum requirements for life. That so-called naked RNA molecule is a self-sustaining chemical system capable of incorporating novelty and undergoing Darwinian evolution. It's likely to have taken a long, long time, maybe hundreds of millions of years, for that first crudely self-replicating molecular system to emerge. Take your pick. A relatively simple TCA cycle, or a complex autocatalytic network, or maybe self-replicating RNA, or something we haven't thought of yet. But Earth had vast amounts of time and surface area with which to try out different chemical combinations. So it's plausible that versions of all three would have been given a chance. Unimaginable numbers of different molecular combinations were being tried out on trillions of varied mineral surfaces across almost 200 million square miles of Earth's wet surface for many millions of years. That's combinatorial chemistry that we could never repeat in our laboratories. And all it took was for just one of those inconceivably immense numbers of molecular combinations someplace, sometime, to work. Some combination of molecules learned to make copies of itself. That was the moment of life's origin, the moment when everything changed. And here we come to the fourth and final step in life's origins. Recall that making the small biomolecules like amino acids and sugars came first. Then was the selection and assembly of those molecules into larger structures, and ultimately a collection of molecules became self-replicating. But how exactly can a collection of molecules evolve? What is the natural process that would drive such a phenomenon? And here we can be confident that we know the answer and understand the mechanism. The answer lies in selection. That's the driving force behind all evolving systems. We live in a world that rewards certain essential functions related to survival. In such a world, the molecules that are most functional will always be the ones most likely to survive. And molecules that don't make the grade are doomed to be eliminated. The power of natural selection, whether for molecules or living creatures, is not just idle conjecture. Experiments now being conducted in the Boston-based laboratory of Harvard biologist Jack Szostak have demonstrated over and over again the power of selection in molecular evolution. Let me tell you about a typical experiment. Szostak's team begins with a random mixture in water of about 100 trillion different RNA sequences. That's a 1 with 14 zeros, a lot of different RNA strands. Each of those RNA molecules consists of a random 100-letter string of the 4 genetic letters A, C, G, and U. And that means that each molecule in that immense collection folds up differently into a different shape. So the entire collection of 100 trillion molecules is confronted with a task. For example, they're exposed to another molecule with a distinctive shape. And those distinctive molecules are attached to little beads. So you have a beaker with coated beads, and then a water solution with 100 trillion RNA molecules. Now, the vast majority of RNA strands will do absolutely nothing. They'll just continue floating around in the solution. But a tiny fraction of the RNAs will bond tightly to the target molecule. These target molecules dangle out into the RNA-rich solution like little hooks. Think of it as Velcro that latches onto just the right kind of material. So almost all RNA molecules have the wrong shapes and can't interact, but a few of the original RNAs stick tight. And that's why selection is so powerful. It rewards molecules that work, and you can enhance the process by cycling. So Shostak's team throws out the old solution that still has almost 100 trillion different RNA strands that didn't stick. And then they carefully recover the few RNA strands that did stick because of those fortuitous shapes. They use a few standard tricks of genetic technology to prepare a new batch of 100 trillion RNA strands. But this time, every one of the new strands is a sloppy copy of one of the old strands that stuck. So these are mutant strands that are offspring of one of those original few functional strands. And here's the power of selection and variation. By repeating these simple steps, we generate a new population of functional RNA strands. But some of these second generation variants happen to bind much, much better than any strand in the first generation. And if you repeat the whole process a few more times, the resultant RNA strands keep getting better and better at binding until the very best mutants have the maximum possible binding to the target molecule. These RNA strands achieve a kind of perfection. You could not engineer a better molecule for that function. The whole experiment in Shostak's lab takes a few days. It's less than a week to transform from random strands to a perfect binding molecule. If you were to ask a team of the world's most brilliant chemists with the most powerful computers to design such a functional RNA molecule from scratch, they would find the task to be virtually impossible. We simply do not have a method to predict how a long RNA strand will fold up, nor can we predict how it might attach to other complexly shaped molecules. And here we have an important message for those who would deny the power of evolution. Evolution by natural selection is the fastest, the most demonstrably reliable path to attaining function. By contrast, intelligent design of biomolecule structures from scratch is immensely more complicated. Engineering is unlikely to be either fast or even functional. And contrary to some criticisms, there's nothing random about selection. Selection always picks the configuration that works, which leads some to say that if God created life, she is smart enough to have used evolution. We certainly don't yet know all the details, but somewhere, sometime in Earth's first billion years, a collection of molecules learned that self-replicating trick. It's clear that any collection of molecules with even the slightest useful function had an advantage in the prebiotic soup. But no function was more valuable than the advantage conferred upon groups of molecules that could make copies of themselves. Such a self-replicating system ensured its own survival by producing more or less identical offspring. The molecular copying process must have been messy. So some of those molecular copies were mutants. Most mutations were lethal or conferred no significant advantage, but a few fortuitous alterations allowed offspring to outshine their parents. The system evolved through chance copying errors. Whatever the original self-replicating molecules might have been, some offspring tolerated more extreme conditions of pressure or heat, acid, salt. Some replicated faster, or they found new sources of food, or were more ruthless in destroying less fit molecules. It's likely that some molecules enjoyed even greater advantages by binding to protective mineral surfaces or finding refuge within a safe encapsulating membrane. The first self-replicating molecules, they were without competition, and so it's likely that they engulfed all of Earth's nutrient-rich zones in a geological instant. It's hard to imagine any microscopic object engulfing Earth. But consider this. Just for argument, say that the first self-replicating molecule was pretty inefficient. It took a full week to duplicate just once. By contrast, many modern microbes can replicate in a matter of minutes. But let's say a week. So week after week, 2 molecules become 4, 4 becomes 8, 8 becomes 16, and so forth. At that leisurely rate, it would have taken about a half a year to form a clump of 100 million self-replicating molecules. You'd barely be able to see such a molecular cluster. It would take another 20 weeks or so for the mass of molecules to fill a thimble. And continuing at this rate, it would take another 20 weeks for all life to fill a good-sized bathtub. So we're up to maybe a year and a half after the first self-replicating set of molecules appeared, and you'd be hard-pressed to see any change of any sort on planet Earth. Yet at this point, things changed fast. Continued doubling every week would produce remarkable transformations. After 20 more weeks, miles of life-infested waters would have appeared along the coasts, or in an inland lake, or perhaps a deep-sea environment. And it would take only 2 years, if you assume that a single initial collection of molecules doubled every week, for Earth to hold 1 million cubic kilometers of living stuff. And in just a few more weeks, doubling every week, you'd have enough biomass to fill the entire Mediterranean Sea. So life, once begun, may have spread quickly, but those earliest life forms were primitive in the extreme. The simplest single-cell organisms had not developed the complicated mechanisms to harvest sunlight. They probably survived on the chemical energy of nearby minerals, and they can't have had much effect on Earth's geology. There were no great changes in the near-surface distribution of rocks, for example, nor were there any new mineral species attributable to life. Now, it is likely that some biologically mediated rock formations occurred. In some of Earth's oldest surviving rocks, we find distinctive localized red and black banded iron-rich formations and shoreline-hugging carbonate reefs. These early signs of life, some dating back more than 3.5 billion years, are found in remote parts of Australia, South Africa, Canada. It's evident that some microbes were able to modify their environments by producing layers of minerals. But the key here is that those minerals would have formed anyway, albeit much more slowly. Life simply learned to accelerate the production of minerals, and in the process, the cells got chemical energy they needed to survive. In this sense, the earliest life forms were like catalysts or enzymes that speeded up favorable chemical reaction. Before exploring the dramatic changes that life gradually imposed on Earth, let's step back and think about the context of life's origin in the bigger planetary picture. In contrast to later stages of living Earth, when life transformed the surface time and time again, as far as we know, that first molecular life made little mark. In fact, we're not even sure when life began. Detailed studies of Earth's most ancient sedimentary rocks, which were laid down in shallow oceans or lake environments about 3.5 billion years ago, preserve what are unmistakable fossils of microbes. We see dome-like rocky structures called stromatolites, typically a few inches to a few feet across. And they form when microbes deposited one thin layer after another of minerals in shallow reef-like settings. There's also ample evidence that microbial mats covered parts of the sandy shoreline where they consolidated and patterned sand in tidal zones, much as they do today. There are even a few places where what look like actual microbe fossils have been preserved as microscopic carbon-rich spheres. These fossils aren't all that spectacular, but you can sometimes convince yourself that they have distinctive cell walls, but no older fossils, at least none that are incontrovertible, have been found. There are traces of carbon and other critical bioelements in some altered rocks as old as 3.85 billion years ago. But those tantalizing chemicals by no means have convinced the geological community of life. So, how long ago did life arise? Here the answer depends as much on philosophy as science. If you harbor belief that life is a cosmic imperative, that it emerges early and often on any viable planet or moon, then you'd probably start with the hypothesis of a stable biosphere very early, perhaps as early as 4.4 billion years ago. That's within Earth's first 150 million years. After all the key ingredients were there. Oceans, atmosphere, energy, perhaps as many as 500 different minerals, those from stage 3, and small carbon molecules. There's no doubt that the giant impacts of asteroids and comets would have challenged life. Perhaps the hardy microbes that learned to live hot and deep in protected rocky homes beneath the ocean floor were the best survivors. And if you think that life's origins are easy, then perhaps life came into being more than once, maybe many times before Earth settled down. And if that's so, then those 3.5 billion year old fossils represent an ecosystem that had been evolving for almost 1 billion years. On the other hand, if you incline toward the opinion that life's origins are difficult and correspondingly rare in the cosmos, then an origin date closer to 3.5 billion years would seem to be more likely. Perhaps life is so very unlikely that it took 1 billion years of chemical experiments, a bigger repertoire of minerals, maybe 1,000 minerals or more, and trillions of different mineral molecule interactions throughout hundreds of millions of cubic miles of ocean crust before just the right combination occurred. It's possible that those few fossil remains from 3.5 billion years ago mark the true beginnings of the biosphere. My best guess is it's somewhere in between. That life began in an interval from about 4 billion years ago, when most intensive asteroid bombardment slowed down, to 3.8 billion years, when we start to see some pretty convincing isotopic evidence that life was influencing the surface environment. So I want you to imagine yourself back to that ancient Earth, to a time some 4 billion years ago. Earth's surface was unbelievably hostile. The weather was probably hot and steamy, maybe hotter than any place on Earth today. Ultraviolet radiation hit Earth with full force because no ozone layer yet existed to block it. The globe was largely ocean covered, but giant volcanoes were everywhere, above and below the water's surface. They spewed noxious gases like smelly hydrogen sulfide into the atmosphere. Impacts of meteors the size of city blocks and larger still were a common occurrence. Comets also crashed through the atmosphere, pulverized the surface. What land there was mostly barren black basalt, perhaps with growing areas of gray granite. It's very possible that the world of 4 billion years ago was utterly lifeless. If you could time travel and stand on one of those ancient, active volcanic islands, perhaps on a black lava beach with shallow tidal pools, you'd see nothing alive. Chemical analysis of the water might reveal nothing but a dilute solution of organic compounds and salts. If you could then skip forward a couple 100 million years to about 3.8 billion years ago and visit the same kind of spot, I doubt if much would have appeared to change. The volcanoes are still violent, though perhaps a little less intense than before. Meteorite impacts are still common, though at a somewhat slower rate, with fewer really big hits. And Earth's surface is a little bit cooler. But now, if you could scrutinize the tidal pools, you'd see a kind of cloudiness, maybe a surface scum that wasn't there before, maybe even rounded mounds of carbonate minerals. Under a microscope, you might see tiny ancestral forms of bacteria or archaea swarming in the water. So the changes were subtle at first, but those microscopic specks of life were the harbingers of incredible global change. Details of the origin of life remain a mystery. But what is known, and what we've also seen in mineral evolution, for instance in the creation of Earth's pegmatites and the rare minerals they make possible, is the role of deep time. Given a span of time almost impossibly beyond our own experience, plus an entire planet of sufficiently varied raw materials, it becomes possible for trillions and trillions of different combinations of molecules to each have their moment in the sun, or maybe in the hydrothermal vent, as the case may be. And such an enormously vast process of selection can eventually allow previously impossible behaviors to emerge. Indeed, if life could begin on Earth by a purely natural process of molecular selection, then life could also begin by similarly vast processes on any of the presumed billions of Earth-like planets circling other stars throughout our galaxy, not to mention the billions of other galaxies that lie beyond the Milky Way. Given the unimaginable profusion of stars and planets, it seems almost inconceivable that we are alone in the universe. Since writing my book, The Story of Earth, I've often been asked to name the single most transformative event in Earth's history. And there's no question that life was it. For no other event before or since life's origin led to such dramatic and irreversible changes in our beautiful planet.
Life emerged on Earth over 3.5 billion years ago, at a time when oceans still covered most of the world, where basalt, volcanoes, and protocontinents of granite represented the only land. A simple, single-cell form of life now inhabited our world, and it radiated and diversified in that form for the next billion years.
Life is irrevocably transformed every facet of Earth's near-surface environment. The most obvious changes have occurred in the oceans and atmosphere, but life has radically altered the rocks and minerals as well. Those big changes took a lot of time. For a billion years or more after the innovation of that first living microbe, Earth's surface hadn't changed in any significant way. It is true that new varieties of microbes probably formed brownish or purplish scums along some coastlines. It's even possible that there were patches of greenish slime that populated shallow ponds and bays as a few pioneering cells began to experiment with ways to capture the sun's energy. But 3.5 billion years ago, the continents were still totally barren. No plants decorated the rocky landscape, and there certainly weren't any animals of any sort. If you were suddenly transported to that alien, anoxic world, you would still die quickly. Earth at age 1 billion years, or roughly 3.5 billion years ago, was at a major transition point in our planet's history. A lot has happened to set Earth on its path to the modern world we know. The oceans and atmosphere had formed, though they were very different from the oceans and atmosphere today. Plate tectonics was just getting started, and the first continents were being assembled, though they were much smaller in total landmass compared to our time. And the first life had emerged, though it consisted entirely of microscopic cells. In many senses, then, Earth was well on its way to becoming what it would become. But there's something special that sets Earth at 3.5 billion years apart from earlier times, at least for those of us in the Earth sciences. That's because at about 3.5 billion years, we begin to see a significant rock record. For the first time in Earth's long history, large-scale deposits of rock survive. These revealing fragments of the early crust are called cratons, which are very old, very stable, buoyant pieces of continents that represent ancient large islands and mini-continents. Cratons are generally more than 2 billion years old, and some may be closer to 4 billion years old. A handful of cratons in North America, Africa, and Australia form the very hearts of continents, and they preserve the oldest rocks on Earth. I can't overstate how important these cratons and their amazing rocks are to our growing understanding of Earth history. Evidence for what happened during Earth's first few 100 million years is incredibly sparse. A few isolated zircon grains, no larger than a piece of sand, date from those early years. Those are the oldest known fragments of our planet. We also have meteorites and moon rocks, which provide some clues about the early stages of our solar system. Indeed, the moon rocks document quite a bit about what was happening in our neck of the woods during the first billion years or so. And someday, when we revisit the moon, we might be lucky enough to find fragments of Earth's earliest crust that were blasted into space and landed on the moon as Earth meteorites. But there's nothing like actual rocks in outcrops that you can walk on, that you can hammer and drill and take chunky specimens back to the lab for analysis. I want to take a look at some of those earliest available rocks to give you a sense of what they tell us about Earth in those early days of the living world. But let's start by getting comfortable with the time scale that geologists use to pinpoint different episodes in Earth's history. The geologic time scale is, of course, a work constantly in progress. It divides Earth history into major transitions as that imperfect history is known at a given time. But we keep learning more. And it turns out that many of Earth's most transformative events probably don't correspond exactly to any boundary in the current timeline. So it wouldn't surprise me at all if the names and dates will be changed sometime in the future. Of course, that'll cause all sorts of confusion in the geological literature, just stuck with the current version. In any case, Earth history is first divided into 4 major eons. The earliest, and consequently the least understood, is the Hadean eon, literally the hellish time extending from Earth's formation through about 4.03 billion years ago. By convention, the Hadean eon is defined as the time from which no rock formations are known. A couple of years ago, that number was 3.85 billion years, but as of today, the Hadean eon ends at 4.03 billion years because that's now the oldest known rock formation on Earth. So the Hadean is a shifting definition, and it's probably just a matter of time before some even older rock is found. For example, there are now claims, much disputed claims I should add, that a little outcrop along Hudson Bay in Canada is as much as 4.2 billion years old. And there are those zircon crystals that date back to 4.4 billion years. So the demarcation of the Hadean eon is really pretty arbitrary. It's possible that life emerged at about 3.85 billion years, but could have been hundreds of millions of years earlier or later. We simply don't know. What is true is that the rock record is extremely sparse prior to 3.85 billion, perhaps no more than a few acres of total exposure on Earth. That means we have essentially no direct information regarding Earth's Hadean surface. Virtually everything we do know comes from inference and analogy. So that's the mysterious Hadean eon. Next comes the Archean eon, which spans the period from 4.03 to 2.5 billion years. That's almost a third of Earth history. The Archean eon is further divided into 4 eras, and I have to confess that these 4 subdivisions seem really arbitrary to me. There's the Eoarchean era. Eo means dawn, from 4.03 to 3.6 billion years. There are only a very few small outcrops from that interval, notably 4.03 billion year rocks from Canada and outcrops as old as 3.85 billion years along the southwestern coast of Greenland and Isua and Achilea Island. And there are also some rocks about 3.6 billion years old in central Canada. In any case, those oldest Eoarchean rocks are all pretty altered by heat and pressure. They've been metamorphosed in such a way as to mask what the original rocks might have been. It's not even clear in most cases whether the rocks were sediments or from volcanoes. One exception, and an incredibly important discovery, are the oldest of the so-called banded iron formations, or BIFs. These iron-rich rocks must have formed on the ocean floor, where iron-rich minerals were deposited in layers. The rocks are quite distinctive and beautiful, with alternating bands of red hematite and black magnetite, which are both iron oxide minerals. These banded iron formations tell the story of a time when there were shallow oceans, margins, and iron-rich seas. It's also possible that microbes played an important role in the formation of the BIFs by pulling the iron out of solution and forming those uniform layers. So it's entirely possible that these rocks represent some of the earliest signs of life as old as 3.85 billion years. The Paleoarchean era comes next. It rather arbitrarily spans 400 million years, from 3.6 to 3.2 billion years. Now, neither of those endpoints is associated with any obvious major events in Earth history. However, this is the time span when the first major pieces of crust, the first real surviving cratons, date from. Pieces of the Paleoarchean crust, hundreds of miles across, are found in central Canada, in North America, in South Africa, and in Western Australia. The oldest unambiguous fossil structures, stromatolites at about 3.5 billion years from South Africa and Australia, come from this time as well. By the way, the scientific community doesn't always use the official timeline. It's amusing to me that many experts on Earth's first billion years now call the time before 3.5 billion years as simply early Earth. So they define 3.5 billion as the real dividing line between Earth's adolescence and young adulthood. Then comes the Mesoarchean era, another 400 million year chunk from 3.2 to 2.8 billion. In this interval, we find increasing volumes of preserved rocks and more cratons, so it's clear that continents were being assembled. This is also the interval for which there's growing evidence that modern plate tectonics probably took over in a global scale, organized way from the vertical plume-driven tectonics of before, forming the first large continent by around 3.1 billion years ago. And global scale plate tectonics came what may have been the first instance of all the continents coming together to form a single supercontinent. If so, then 2.8 billion years may not be such an arbitrary date after all. The idea is that plate tectonics causes land masses to shuffle this way and that across the globe. And from time to time, two continents collide and suture together. You can get hints of these collisions from a couple of sources. For one thing, every time two continents collide, they form a mountain chain, just like the Himalayas today. Also, any molten rock will freeze in the orientation of Earth's magnetic field when it cools. So you can sometimes tease out the orientation and even the latitude of ancient rocks when they formed. That's the field called paleomagnetism we touched on when we were discussing plate tectonics. The bottom line is that it appears about 2.8 billion years ago, all the continents clumped together to form one gigantic supercontinent called Kennerland, which was surrounded by an even more gigantic super ocean. We're going to come back to examine this supercontinent cycle in several lectures from now, in lecture 35. Suffice it to say that Earth at 2.8 billion years was acting very differently than it did a billion years earlier, at the start of the Archean Eon. And the fourth and final segment of the Archean Eon is the Neo-Archean era, the 300 million year interval between 2.8 and 2.5 billion years ago. Here again, the rock record becomes more complete, more nuanced. Kennerland continued to assemble, perhaps for 200 million years, leading to more mountain building. When mountain building came the formation of lots of new rocks through melting and reworking of what came before. So we actually have a fair amount of interesting Neo-Archean mineralization, including some huge ore deposits in Australia, Africa, Canada, Europe, associated with rocks of this age. Unlike the previous eras, the bounding ages of the Neo-Archean era may have some significance to Earth history. We've seen that 2.8 billion years may correspond to the beginning of the first supercontinent assembly, when new mountain ranges started to form and the geography of the globe took on an entirely new character. And as we'll see in the coming lectures, 2.5 billion is about the time when the most important atmospheric change in history took place. That was the rise of oxygen through the invention of oxygen-producing photosynthesis. Okay, let me run briefly through the rest of the geological timescale, and we'll come back to this each time we enter a new time interval. The third of Earth's four grand eons is the Proterozoic eon, which embraces more than 40% of history, from 2.5 billion to 542 million years. So 2.5 billion years is roughly when oxygenic photosynthesis got going, and you can probably guess that 542 million years is not an arbitrary cutoff date. It does represent a significant innovation in life when the first big pulse of mineralized shells occurs in the fossil record. And we'll come back to that point. Proterozoic eon is divided into three eras, and here the division really does seem arbitrary, even unfortunate, as there are big transitions that are simply not represented by this time scale at all. Anyway, there's the Paleoproterozoic era from 2.5 to 1.6 billion years. That's a whopping 900 million year interval during which a lot happened. There's atmospheric oxidation, there's the oldest unambiguous fossils of microbes, there are two huge pulses of banded iron formations, and the beginning of a long period during which much of Earth, at least the oceans and microbial life, really didn't seem to do much of anything new. This somewhat later interval is sometimes called the boring billion, from about 1.85 billion years to 850 million years ago. But those dates have only recently come into focus, and they just don't match the Proterozoic boundary. Then the Mesoproterozoic era is the 600 million year period from 1.6 to 1 billion years. During this time, there was at least one new supercontinent formed and broken up, and there were huge pulses of new minerals and major ore deposits as well. But other than being a nice round number, there's just nothing special about 1 billion years ago. We're getting closer to our own time with the Neoproterozoic era, the period from 1 billion to 542 million years ago. Though a much better starting point might be 850 million years ago, as we'll see when we discuss feedback loops in lecture 36. Anyway, a huge amount happened during that roughly 450 million year interval. Now, perhaps that's because it's more recent, so rocks are better preserved. but I think there really were unusually big changes. There were astonishing changes in climate, including periods when Earth was almost completely locked in ice from the poles to the equator, and then sudden shifts to a tropical globe. There were equally dramatic biological innovations, including the first multicellular animals, and there was another supercontinent formed and dispersed. So the Neoproterozoic was quite an alien time, but it was getting us much closer to the modern world. And finally, the last of the four grand eons, we have the Phanerozoic, the time that saw the emergence of the modern living world over the last 542 million years. Naturally, being closer to modern times and with a profusion of animal and plant fossils, we have a much more detailed picture of this last half billion years or so. That's why the relatively short Phanerozoic is divided into three eras, which are further divided into a dozen or so periods, which are further subdivided into smaller and smaller time intervals based primarily on important innovations in life, as well as a series of mass extinction events. We'll focus on those important events in the history of life in some of the later lectures. Suffice it to say that the closer we get to the present, the more richly woven is the tapestry of Earth's story. Let's journey backward in time and think for one last time about that transition from the early Earth, before 3.5 billion years, to the living planet of the Paleo-Archean era. Whenever that first life emerged, whether it was before 4 billion or after 3.8 billion years ago, those meager cells had little effect on Earth's ancient surface. The very first populations of microbes didn't have the chemical tools to alter the surface environment. They simply exploited the exact same chemical reactions that were already taking place at or near Earth's surface. From Earth's earliest days, lots of different chemical reactions were taking place because rocks and gases from volcanoes were more chemically reduced than those at the surface. The reason comes down to the distribution of electrons. Earth's mantle rocks have on average more electrons per atom involved in chemical bonding than rocks in the crust. That means the mantle is more reduced, the surface is more oxidized. It's a simple equation. When reduced and oxidized chemicals meet, for example, when reduced magma and gases from the mantle spill out onto the more oxidized surface in a volcanic eruption, that will inevitably lead to an energy-liberating oxidation-reduction chemical reaction. In the process, electrons transfer from the more reduced to the more oxidized compound, and a little bit of energy is released to the environment. A familiar example is rusting, in which iron metal reacts with oxygen. Iron metal is loaded with electrons. In fact, iron has so many bonding electrons that some of them are free to move through the metal and thus conduct electricity. So iron acts as a donor of electrons. Meanwhile, oxygen gas is so lacking in electrons that two oxygen atoms have to combine, they have to share their electrons to make an O2 molecule. The meager supply of bonding electrons is shared by both atoms, like rations on a desert island. So oxygen is the ideal electron acceptor, and iron is the ideal electron donor. When iron metal meets molecules of oxygen, an exchange of electrons occurs. Each iron atom gives up 2 or maybe 3 electrons. Each oxygen atom accepts 2 electrons. The consequence of this electron exchange is a new mineral, iron oxide, plus a small amount of energy. For example, 4 atoms of iron plus 3 molecules of oxygen can give you an red iron oxide called hematite plus a little bit of energy. The earliest microbes evolved to exploit all the abundant energy that was readily available in the form of reduced iron atoms and other food that was dissolved in the oceans of early Earth. Microbes learned to oxidize iron to form the black mineral magnetite, the rusty red mineral hematite that formed those layers in the earliest banded iron formations 3.85 billion years ago. Those mineral-forming chemical transformations released enough energy to support entire ecosystems on the ancient ocean floor. This pattern continued all over Earth for almost 2 billion years as massive banded iron formations formed in what are now cratons in Australia, in North and South America, in Africa, in China, in India, other ancient terrains. So all over the globe we find the leavings of what was in effect an epic microbial buffet that lasted hundreds of millions of years. Dozens of other oxidation reduction chemical reactions also would have occurred spontaneously at or near early Earth's surface. In addition to iron, there were several other common electron-donating metal elements, including nickel, manganese, and copper. All those metals were subject to oxidation. And then there were all sorts of simple carbon-based molecules that had been synthesized in those prebiotic processes that resulted in the primordial soup. So there was methane or natural gas, propane, butane, various other chemicals that will burn. What we use today as carbon-based fuels. Molecules of oxygen gas were pretty much absent in Earth's earliest atmosphere, but there were plenty of other electron-hungry molecules with oxygen on board, including sulfate, nitrate, carbonate, phosphate. All of them were available to accept electrons. And here's the key to understanding the role of early microbial life. Before the origin of life, oxidation reduction reactions occurred everywhere in Earth's near-surface environment. But they proceeded at a relatively leisurely pace. The first microbes learned how to shuffle electrons at a much faster pace. In many environments, including shallow ponds and along coastlines, in lagoons, the deep ocean floor, the microbes began to control the pace of these chemical reactions. You see, each oxidation reduction reaction provided a little bit of energy. Communities of microbes survived by accelerating oxidation reactions to produce minerals that would have formed anyway. They used the resultant energy to live, to grow, to reproduce. So planet Earth made iron oxides, but the first microbes made them fast and in a controlled way that laid down those beautiful banded iron formations. Those first microbes, in effect, helped Earth achieve its electron balance. And in that way, life began ever so slowly to alter both Earth's surface environment and its deeper interior. These events, though subtle at first, began what I describe as the astonishing co-evolution of the geosphere and the biosphere. It didn't take long for life to learn other mineral-forming tricks. Those earliest oceans were saturated in a variety of dissolved minerals, including the important carbonates of calcium and magnesium, the minerals calcite, aragonite, and dolomite. These minerals were from time to time deposited on the ocean floor by abiotic processes in great layers of giant crystals. Rather early in the history of life, microbes took advantage of the carbonate-forming chemical reaction, and in the process found another source of chemical energy. Carbonate layers also provided a safe and sturdy haven on which the microbes could anchor themselves. The early fossil structures called stromatolites are good examples of this innovation. Stromatolites are the result of microbes arrayed in mats, living on the energy and structure provided by carbonate. And microbes also used other minerals where conditions were favorable. They sometimes drew energy by forming phosphate and sulfate minerals from the mineral-saturated oceans. It was evolution by the process of natural selection that continued to drive all these mineral-forming strategies. Any microbial species that learned to use iron or carbonate as a food source, or conduct oxidation reduction reactions more efficiently, or tolerate more extreme temperatures or pressures, or to exploit some novel energy-producing chemical reaction, they would have had a distinct advantage and thus ensured their own survival. Inevitably, populations of mutating microbes discovered new enzymes that catalyze these energy-producing reactions more efficiently than the non-living environment. And so the results are preserved in the most ancient cratons as little stromatolite mounds of limestone, modest layered deposits of iron oxides. The rock record also holds subtle clues in its isotopes, pointing to a gradual increase in the processing of near-surface elements critical to biology, including carbon, sulfur, nitrogen, and phosphorus. But it's important to keep in mind that these earliest life forms on Earth did little more than mimic the chemistry that would have occurred on a non-living geochemical world. The era of this first life. Microbes that mimicked non-living geochemistry persisted for a long time. These cells dominated Earth's biosphere for perhaps 1.5 billion years, until about 2.5 billion years ago. That's when what was arguably the most significant biological innovation, other than the transformative origin of life itself, occurred. That's when cells learned to harvest sunlight, the innovation of photosynthesis. Most of us in the origins field suspect that the earliest life forms relied exclusively on the chemical energy of rocks. That was an abundant source of energy, especially in early Earth, but it greatly and increasingly restricted where life could make its home. Microbes either had to be anchored to a reactive mineral surface or else live in a place where water was not in equilibrium with its surroundings. All that changed when microbes learned to collect solar energy. Rather than relying primarily on oxidation-reduction reactions in the environment, these microbes could drive their own bioreactions with the energy of light. After all, solar energy is an abundant, cheap energy source available to any surface dweller anywhere on the planet. In its simplest guise, photosynthesis begins with sunlight and small molecules like water, nitrogen, carbon dioxide to make the carbon-rich biomolecules. It takes a fairly complex chemical apparatus, but given the right set of light-gathering molecules and enzymes, it's possible to manufacture all of life's essential building blocks: amino acids, sugars, lipids, the components of DNA and RNA, all that from nothing more than atmospheric gases and the sun's radiation. The first photosynthesizers were not like today's green algae and plants. They generated no oxygen. But we do have lots of modern descendants of these primitive organisms in the form of microbes that form a brownish or purplish scum on stagnant ponds. It's not such a stretch to imagine immense floating rafts of photosynthetic microbes, maybe unsightly brownish purplish splotches floating along the shorelines of the blue Archean oceans. You might wonder how we could possibly know. Microbes have no hard parts that can easily be preserved as fossils, and it's not obvious how floating algal mats would alter the rock record in any obvious way. But it turns out there may be a way to tease out evidence for some of the most ancient photosynthetic microbes. Light-gathering cells rely in part on distinctive molecules called hopanoids, which possess tough backbones of carbon atoms that form 5 interlocking rings. They sort of look like the Olympic logo. By the way, that term hopanoid came from a genus of resinous trees named for botanist John Hope. Well, long after microbes die and decay, the telltale hopanoid molecules can survive. And they can be preserved as a molecular residue in ocean floor sediments. Some of these molecular fragments, called geohopanes, when they've gone through a lot of processing, have been reported in rocks more than 2.5 billion years old. Now, any interpretation has to rest on some very tricky assumptions about more recent sources of contamination, and the paleontological community responds to every report of molecules that have survived for several billions of years with skepticism. Still, the geohopanes are there, and they may provide our best picture of the photosynthetic ancient biosphere. There can be no question that by our planet's 1 billionth birthday, 3.5 billion years ago, life had established a firm foothold on Earth's surface. For perhaps another billion years, this primitive microbial life had only modest effects on near-surface environments. The first microbes sped along oxidation-reduction reactions that would have occurred anyway, while a subsequent lineage of more sophisticated cells engaged in a primitive version of photosynthesis. So far, we found no evidence that life during those first 2 billion years resulted in any new minerals at or near Earth's surface. Cellular life simply made more iron oxides, more carbonates, more sulfates and phosphates that might have formed on a non-living world. Microbes constructed banded iron deposits of iron-rich minerals in the deeper ocean. They built protective stromatolite mounds in shallow coastal waters. But in the larger chemical sense, the living Earth of 2.5 billion years ago was not much different in character from the world a billion years earlier. But that was about to change. For Earth's primitive microbial population 2.5 billion years ago was poised to undergo a dramatic transformation. Microbes were about to learn the complicated new chemical trick called oxygenic photosynthesis. For the first time, cells gained energy from the sun while exhaling the highly reactive, dangerously corrosive gas called oxygen. Oxygen is the most abundant element in Earth's crust and mantle. Almost 2 of every 3 atoms are oxygen. But it took life and the emergence of the amazing process of photosynthesis to isolate oxygen into the molecule that we breathe. As a direct consequence of photosynthesis, more than 2 billion years ago, Earth's solid surface changed from a dull gray to brick red in a geological afternoon. We are learning about this critical transformation in Earth and in life from fossils of many kinds, impressions in rock, molecular remains, and isotopes. Oxygen-producing photosynthesis points to the growing influence of new kinds of algae and the consequent rapid rise of an oxygen-rich atmosphere. Many details of this epic transition, called the Great Oxidation Event, are uncertain and still matters of intense debate. Our best guesses regarding the timing of the Great Oxidation Event come from subtle changes in the rock record, which reveal a rise in atmospheric oxygen shortly after Earth's 2 billionth birthday, perhaps 2.45 billion years ago. And by 2.2 billion years, atmospheric oxygen had for the first time risen to more than 1% of its modern level. Today, oxygen makes up about 1 in 5 molecules of the air we breathe, about 20%. So 2.2 billion years ago, there were perhaps 0.2% of oxygen, and that was enough to forever change Earth's surface. This fascinating story of how Earth became a planet with an oxygen-rich atmosphere has only recently come into focus, and there's still a lot we don't know. But there is a scientific consensus about many important aspects as more and more new lines of evidence have emerged and new research directions have been tackled. It hasn't been an easy road. For the past 50 years of research in paleoatmospheres, it's seen a lot of competing ideas, many times with scientists coming to diametrically opposed conclusions. It's not an easy topic since the atmosphere is so ephemeral. How do you tease out the composition of gas from billions of years ago? But ultimately, the scientific method has a way of winnowing out the unsupportable theory and the false assumption. Of course, as with every aspect of early Earth, we don't have the whole story. And we'll always have some uncertainty, but we're getting a lot closer to a well-supported picture. And you might say that the emerging story is quite literally breathtaking. All the evidence for the Great Oxidation Event is locked in old rocks and minerals from around the globe. Most critically, there's a growing catalog of observations that span a vast interval of Earth's history from about 3.5 to 2 billion years ago. We find, on the one hand, that many rocks older than 2.5 billion years contain distinctive minerals that rapidly weather away in the modern environment because of the corrosive effects of oxygen. Geologists find pristine, unweathered, and rounded pebbles of pyrite. That's the common iron sulfide mineral, also known as fool's gold. And there are also stream-bed pebbles of uraninite, uranium dioxide, which is the commonest uranium mineral, but one that doesn't survive long in modern streams. These findings suggest there was an oxygen-free environment when those streams flowed 3 billion years ago. Similar evidence comes from rocks that represent ancient soil layers. These old surface deposits are preserved as sediments of silt, and when they date from before 2.5 billion years, they often have telltale chemistry. Now, compared to modern soils, they're unusually concentrated in some elements like the rare earth element cerium. That's element 58. In ancient soils, cerium has abundances comparable to other rare earth elements. But in modern day soils, cerium can be anomalously abundant or absent, either way due to the presence of oxygen interacting with other factors. Ancient soils are also strikingly deficient in other elements, most notably iron, but also molybdenum compared to today's soils. These chemical differences affect a variety of elements that are sensitive to oxidation-reduction reactions. So they point to an atmosphere completely lacking in oxygen. Rocks deposited at or near Earth's surface after about 2.5 billion years show a very different chemical pattern that appears to point unambiguously to oxygen. Most notable are the massive layered deposits of iron minerals called banded iron formations, or BIFs. You can recognize these dense rocks by their distinctive alternating black and rusty red layers. There are older versions of BIFs, roughly contemporary with the origins of life. But these new reddish layerings were deposited in absolutely staggering abundance between about 2.5 and 1.8 billion years ago. In fact, BIFs hold 90% of all the world's known iron ore reserves, and they're mined in gigantic open pits in several countries. There are also immense deposits of manganese oxides at about that same time. They suddenly appear in the geological record as thick layers of sediments that supply most of the world's manganese ores. And we'll soon see that many hundreds of other new minerals appeared for the first time after the atmosphere became oxygen-rich. They're colorful minerals of copper, nickel, molybdenum, cobalt, mercury, uranium. Many other elements also appear for the very, very first time in Earth's history after the Great Oxidation Event. That diversification of the mineral kingdom was just one more manifestation of the Great Oxidation Event. Of course, all these signs are subtle. You can't just look at a rock and see that it's older or younger than 2.5 billion years. You can't see the trace elements or the isotopes. What's more, the rock record is incomplete, and it can become altered in ways that are confusing and misleading. Nevertheless, new evidence kept building for a major transition in Earth's atmosphere more than 2 billion years ago. What many of us see as the smoking gun for the Great Oxidation Event came early in this century from isotopes. In fact, it was an unexpected source that's deeply buried in data on the isotopes of the very common element sulfur. Let me set the stage for this important discovery. Mass spectrometers are the essential analytical instruments for measuring isotopes. The 1990s saw significant improvements in the resolving power and the detection limits of mass spectrometers that could handle ever smaller samples. That was when it became possible to measure isotopes in individual zircon grains or even in individual living cells. And these new mass spectrometers could be tuned to any chemical element of the periodic table, hydrogen all the way to uranium. Sulfur is one of a handful of life's essential elements, and it proved to be a particularly interesting research priority. It turns out that there are 4 different stable isotopes of sulfur in nature: sulfur 32, 33, 34, and 36. All of these isotopes have 16 protons in their nucleus. That's the definition of sulfur, an atom with 16 protons. But the number of neutrons in these 4 isotopes varies from 16 in sulfur 32 to 20 neutrons in sulfur 36. Like all the elements, the distribution of sulfur isotopes is for the most part predictable based on the relative masses of the isotopes. The less massive isotopes vibrate more because of Newton's second law of motion, force equals mass times acceleration. Thermal energy applies a more or less equivalent force to all the sulfur atoms in a system, so more massive sulfur isotopes vibrate less. That means that in any chemical reaction, the less massive isotopes are more likely to move than the more massive ones. The result is that the reactants typically wind up with a ratio of sulfur isotopes that's different from the products. This process of refining the ratios of isotopes is called isotope fractionation, and it occurs any time sulfur atoms undergo a chemical reaction. And that's true whether the sulfur is in a rock or in a living cell. The case of sulfur isotopes is typical. Less massive sulfur 32 typically fractionates more than more massive sulfur 34, which fractionates more than sulfur 36, and ratios of these fractionation effects are usually directly proportional to the mass ratios of the isotopes. That means the fractionation of sulfur 36 and sulfur 32, which differ by 4 atomic mass units, is almost always twice the fractionation of sulfur 34 and sulfur 32, which differ by only 2 mass units. This is the basic physics that follows from Newton's second law. Smaller mass means a bigger acceleration. So under a given force, the sulfur 32 isotope vibrates more than sulfur 34, which vibrates more than sulfur 36. But there's something else going on with sulfur isotopes. That was a discovery made in the late 1990s by geochemist James Farquhar. Farquhar is now at the University of Maryland, but at the time, he was working at the scenic Oceanside campus of the University of California at San Diego. What he found was a profound and unexpected change in the fractionation of sulfur isotopes that occurred about 2.4 billion years ago. It it turns out that virtually all rocks and minerals younger than 2.4 billion years display almost precisely the mass-dependent trend that we all would have expected. The ratios of sulfur isotopes 32, 33, 34, and 36 depend almost exclusively on the ratios of their masses. But Farquhar and colleagues found a very different fractionation pattern for sulfur isotopes in many minerals and rocks that are older than 2.4 billion years. In some samples, there are wild deviations of several tenths of a percent, and that's a lot for isotopes. These samples seem to violate Newton's laws. So Farquhar and his coworkers asked, what could cause this mass-independent deviation? Well, the answer lies in quantum mechanics. Theoretical models and clever experiments showed that isotope behaviors can deviate from Newtonian behavior when molecules are exposed to ultraviolet radiation. It turns out that isotopes with odd mass numbers, like sulfur 33, can be selectively altered by ultraviolet radiation. So if a molecule of sulfur dioxide or hydrogen sulfide happens to hold a sulfur 33 isotope, and if that molecule is in the atmosphere where it absorbs an ultraviolet ray, then it reacts more readily. That process selectively changes the isotope ratios. Sulfur 33 experiences a mass-independent fractionation, and that fractionation skews the isotope ratios. Farquhar was able to explain why there's a mass-independent isotope effect. But what was the sudden change on Earth 2.4 billion years ago that turned off this effect? The answer is a change in that ultraviolet radiation that affected the atmosphere. The rise of oxygen led to the production of a new atmospheric molecule called ozone, which is a molecule made of 3 oxygen atoms. Ozone has been in the news a lot in the past few decades because it effectively absorbs ultraviolet radiation. It's Earth's natural sunblock. Today, a trace amount of ozone high in the atmosphere provides an essential barrier to the sun's potentially lethal ultraviolet rays. Basically, the way it works is high in the stratosphere, UV rays break up O2 molecules into 2 single atoms of oxygen. The single atoms bond with other O2 molecules to form O3, which is ozone. Ozone then absorbs ultraviolet rays and breaks back down into O2 and an atom of oxygen. It's kind of a cycle. Careful measurements taken over the past 25 years or so reveal that this so-called ozone layer has been significantly depleted, most likely because human-produced chemicals called chlorofluorocarbons, or CFCs, and other chemicals such as carbon tetrachloride, they can attack ozone and for decades after they're released. Loss of ozone could lead to a rise in skin cancers among humans and a variety of ecological stresses around the world. It's good news that a worldwide ban on CFC production has apparently led to a reversal of the previous trend and some restoration of the ozone layer, which was first created 2.4 billion years ago. Before the rise of photosynthesis and atmospheric oxygen, all those sulfur compounds high in the atmosphere were subjected to intense ultraviolet radiation. Compounds with sulfur 33 underwent mass-independent fractionation, and that process is reflected in rocks and minerals of the Archean eon. But after the great oxidation event, a protective ozone layer formed, and that layer acted to absorb the sun's UV radiation. That's why the odd isotope effect was effectively shut down after 2.4 billion years ago. There had been a lot of geological and geochemical evidence pointing to the great oxidation event before James Farquhar's findings. But as many labs around the world confirmed and expanded on Farquhar's discovery, the great majority of Earth scientists rather quickly accepted the reality of the great oxidation event. And this rapid change in thinking exemplifies the way scientific ideas often reach a tipping point, when one or more set of compelling data swings the majority to a new point of view. And unless scientists come up with some way other than ozone to block the sun's ultraviolet rays, the sulfur isotope data have established the beginning of the great oxidation event at about 2.4 billion years. There's now ample evidence that Earth's atmosphere contained a small but significant amount of molecular oxygen by 2.4 billion years ago. But where exactly did that oxygen come from? It's now common knowledge that plants and other organisms make oxygen by the remarkable process of photosynthesis. Photosynthetic cells combine water, carbon dioxide, and sunlight to make the energy-rich molecule glucose, from which serves both to form plant tissues and to power other biochemical processes. This chemical reaction is easy to write. You take 6 molecules of carbon dioxide, 6 molecules of water, and add energy, sunlight. You make a molecule of glucose, and a byproduct is 6 molecules of oxygen. One consequence of this reaction is therefore the production of oxygen in the atmosphere. So familiar is this chemical reaction that we now just take it for granted that plants play a central role in making our world a habitable place. But photosynthesis is not an obvious process. And the discovery of how photosynthesis works was one of the greatest advances in the history of science. And this history, like so many of science's key advances, was made sequentially in piecemeal fashion. The first breakthrough was the discovery of water's critical role in the 17th century. It had long been assumed that the woody tissues of plants must come from mineral-rich soil. So it was thought that soils must be consumed as plants grow. This assumption was tested in a simple experiment by Flemish physician John Baptist van Helmont, who lived from 1577 to 1644. Taking 200 pounds of earth that had been dried in a furnace, he planted a 5-pound willow tree. Now, 5 years later, after regular watering, his tree weighed 169 pounds, while the soil, suitably dried, weighed only 2 ounces less than when he started. His conclusion, therefore, 164 pounds of wood, barks, and roots arose out of water only. So, Van Helmont realized that soil is not consumed in any great quantity as plants grow. This discovery was a major advance. The water is not the entire story in photosynthesis. Fast forward 100 years, when English clergyman and naturalist Stephen Hales proposed that plants must rely on some component of the atmosphere as well as water. We now know that that component is the trace gas carbon dioxide, which combines with water to make the sugar glucose. And it's ironic that it was Van Helmont himself, a century before, who had discovered carbon dioxide gas in combustion and fermentation. But he didn't recognize CO2's central role in plant growth. By the mid-18th century, scientists knew that water and carbon dioxide were the raw materials of plants, yet the critical role of sunlight in the process remained uncertain. Indeed, it took another 200 years for all the details of photosynthesis to emerge. And surprisingly, it was advances in nuclear physics that paved the way. A new kind of particle accelerator called a cyclotron was used to produce the first reliable supply of the highly radioactive isotope carbon-11, which provided a very effective probe of biological reactions. It was in the turbulent late 1930s that Berkeley scientists Samuel Rubin and Martin Kamen fed plants with carbon dioxide that had been spiked with radioactive carbon-11. Rubin and Kamen used the radioactivity to trace carbon dioxide as it entered plant tissues. Now, carbon-11 has a half-life of only 21 minutes, so these experiments had to be done quickly. They weren't easy. But a real breakthrough came with Rubin and Kamen's discovery in 1940 of a way to make carbon-14, which is the famous radioactive isotope with a much longer half-life of 5,730 years. Creation of carbon-14 in the lab helped to revolutionize biophysics because researchers could follow the paths of radioactive carbon atoms molecule by molecule as plants made their tissues. For the first time, biologists could understand how plants use water, carbon dioxide, and sunlight to make sugar. At its most basic level, the molecule. 6 oxygen molecules are also produced as a byproduct. Here we see yet another example of a redox reaction, analogous to a burning fire or rusting iron. Here, electrons are transferred to carbon atoms in carbon dioxide. Those atoms are thus reduced. At the same time, oxygen atoms in water and carbon dioxide donate electrons. So oxygen atoms are oxidized. And the energy for this electron shuffle comes from sunlight. In its bare bones form, this chemical reaction is very straightforward. Carbon dioxide plus water combine to make sugar. Yet the details of photosynthesis turn out to be extremely complex, and some of the steps are still being studied. For instance, photosynthesis relies on a very ancient but complicated protein nicknamed rubisco that plays the central role in concentrating the raw materials, carbon dioxide and water, and absorbing the sun's energy. It also turns out that there are quite a few variants of photosynthesis. Different microbes harvest sunlight using slightly different chemical pathways. We're most familiar with oxygen-producing plants and algae, which typically use the bright green pigment chlorophyll. Chlorophyll looks green because red and violet wavelengths of light are absorbed. That's the energy that's being used, while green wavelengths represent wasted energy that's reflected off. In fact, if plants were 100% efficient, they'd have to appear black to us because they'd absorb all the different wavelengths of light. Other kinds of cells use different light wavelengths, and several variants of photosynthesis produce no oxygen at all. There are alternate light-absorbing pigments that result in distinctive red and brown algae, as well as purple bacteria and strikingly colored diatoms and lichens in a wide range of colors. There are even some microbes that use infrared radiation in their photosynthetic reactions. Those are wavelengths longer than visible light spectrum, so they're invisible to our eyes, but our skin can sense infrared radiation as heat energy. Many scientists study the nature and origins of photosynthesis. I've been especially impressed with the pioneering studies of Robert Blankenship, who is a biochemist at Washington University in St. Louis, and who also has a team of collaborators at Arizona State University. In fact, his work is so interdisciplinary that he is a member of both the chemistry and the biology departments at Washington University. Blankenship's research involves looking in detail at different photosynthetic pathways for several different kinds of photosynthetic microbes, including groups that are colored purple, brown, yellow, and green. And what he finds is that all of these organisms share some characteristics, but they also display important differences. The photosynthetic apparatus is intricate and consists of several components. For example, photosynthetic cells feature varied colored pigments that absorb light energy, and there are varied molecular sequences for the protein reaction centers where electrons shift from one molecule to another. There are even a host of different antenna systems because cells have evolved clusters of elongated molecules that behave just like tiny light-collecting antennas. What Blankenship finds is that life exploits a variety of photosynthetic strategies. It's clear now that photosynthesis didn't just evolve once, but at least 5 different times going back billions of years into Earth history. Historical details are murky, but Blankenship's best estimate is that the most ancient and primitive light-collecting chemical reactions probably date back more than 3.5 billion years. Those earliest forms of photosynthesis didn't produce oxygen at all. Some ancestors of those early kinds of cells still survive today, and they reveal that these most deeply rooted photosynthetic microbes lived without oxygen. Indeed, most of these primitive microbes don't even tolerate oxygen. Perhaps the most important discovery is the tendency of microbes to shuffle and swap their light-collecting genes. For microbes, this form of lateral or horizontal gene transfer turns out to be an important mechanism of adaptation and evolution. In the distant past, some single-celled organisms borrowed photosynthetic pathways from other cells in this way. Today, the oxygen-producing kind of photosynthesis that's used by almost all plants appears to be a coupling of 2 primitive chemical reaction pathways identified in the early 1960s and called photosystem 1 and photosystem 2. The 2 systems differ in many details, but each houses a few dozen chlorophyll molecules bound to proteins in a core complex, plus pigments in the so-called reaction complex. In most plants, the combination of these 2 pathways provides an extra energy boost. That's how today's plants exploit sunlight far more efficiently than did those earlier forms of photosynthesis. Even before photosynthesis, and even if photosynthesis had never gotten started on our planet, there were still non-biological ways by which Earth's surface would have inevitably produced a very subjected to breakdown by the destructive power of ultraviolet radiation and cosmic rays. Individual water molecules are split apart into fragments that ultimately make hydrogen and oxygen atoms. The hydrogen molecules are of such low mass, they're so light, and they move so fast that some of them simply evaporate into space. They just fly off and leave Earth. Oxygen, both in the usual molecule O2 that we breathe and in ozone, which is the molecule with 3 oxygen atoms, are a lot more massive, so oxygen can't easily escape Earth's gravity. That means that over long time periods, as hydrogen escapes, oxygen builds up slightly in the atmosphere. This process of hydrogen loss continues today. It's estimated that an amount of hydrogen equivalent to all the hydrogen atoms in a few Olympic-sized swimming pools escapes to space every year. The exact same process occurs on the much smaller planet Mars, with a lot less gravity to retain hydrogen. Mars had lost much of its water a long time ago. And as Mars hydrogen escaped to space over 4.5 billion years, iron minerals near the surface oxidized to the familiar rusty red color. And that's a key point. Almost as fast as oxygen was produced and released to the Martian atmosphere, it was locked away to near surface rocks. This process of oxygen production through hydrogen loss can't have had much of an effect on Earth's environment before the rise of life. Even if we take the most extreme estimates, there's probably less than 1 atmospheric oxygen molecule in a trillion prior to the great oxidation event. By contrast, today it's 1 in 5 molecules in the atmosphere. And that minute quantity of archean oxygen was consumed just as fast as it was generated at Earth's surface by immense quantities of iron atoms in the soils and in the oceans. Those atoms were available to donate electrons, to transfer them to make iron oxides. So it seems likely that even if photosynthesis never had evolved, Earth would eventually have looked like Mars with a reddish, weathered surface on all the older continents. But that reddish coating was just an external feature. It only affected the outer soil and rock layers. Even a fraction of an inch below Earth's solid surface, there wasn't a trace of molecular oxygen. And it's very likely that life itself contributed a small amount of oxygen even before the evolution of photosynthesis. It turns out that living cells have learned at least 4 different ways to make oxygen from their surroundings, in addition to photosynthesis. Of course, oxygen and photosynthesis is the huge process today, and it dwarfs all other ways to make oxygen. But these other biochemical pathways may very well have resulted in oxygen production for the past 3+ billion years. It's a recurrent theme in biology. Life is remarkable in its ability to scavenge energy from its environment any way it can. Life uses heat energy from volcanoes. It uses chemical energy of rocks. It uses sunlight. It even uses radioactivity in some special deep subsurface ecosystems. By far the easiest way to obtain energy while liberating oxygen is to start with a reactive molecule that's already oxygen rich. So microbes have learned to exploit hydrogen peroxide, or H2O2, which is produced in small quantities high in the atmosphere. It's certainly true there wouldn't have been much hydrogen peroxide before the rise of atmospheric oxygen. It's a trace chemical in any conceivable Earth scenario, and consequently, non-photosynthetic microbes can't have played any significant role in modifying Earth's early environment. There are other chemical approaches to making oxygen as well. A team of Dutch microbiologists recently reported what was perhaps a more significant oxygen-producing scenario for most of Earth's history. They reported on some microbes that obtain energy by decomposing the oxides of nitrogen, which can be produced by lightning and by burning fossil fuels with small amounts of nitrogen. Early in Earth's history, these so-called NOx, or NOx chemicals, were produced in small amounts through reactions with nitrogen gas with minerals. Today, even more NOx compounds are generated because of the widespread use of nitrogen-rich fertilizers that run off into lakes, rivers, and estuaries. Large microbial blooms include contributions from cells that are able to decompose nitrogen oxides into nitrogen plus oxygen. Then those clever cells use the newly formed oxygen in reactions with methane, which is also available in the environment. And those oxidation reactions provide life's energy source. course, all of these investigations of modern living cells and their biochemical processes must be supplemented by studies of ancient fossil organisms, including fossils of the earliest oxygen-producing life. And those studies represent some of the most revealing and at times dangerous research in our quest to understand the story of Earth. photosynthesis gets started. Of the several ways that Earth has learned to make atmospheric oxygen, photosynthesis is without question the champion. Green plants and algae pump huge quantities of oxygen into the atmosphere, so that today almost 20% of the air we breathe is that reactive gas. So how did photosynthesis begin? That question is in large part the domain of paleontologists, who study what turn out to be extremely fragmentary remains of the ancient microbial world. These scientists use every technique they can imagine to tease out connections between past and present life. In this lecture, I want to tell you stories of Archean paleontology, the search for signs of life in rocks older than 2.5 billion years. This is where we find the earliest evidence for any kind of photosynthesis, and we see hints of the initial transition to an oxygen-bearing atmosphere. Naturally, in their search for earliest traces of photosynthesis, fossil hunters concentrate on Earth's oldest rocks. As you can imagine, there are precious few fossil remains of the first photosynthetic single cells. Microbes have no hard parts like bones or teeth or shells, so they don't generally remain intact after they die. After billions of years of burial, heating, squeezing, and chemical alteration, almost nothing in the way of microbial fossils has been preserved, much less documented. What little has survived is typically baked and smushed. Colonies of presumed fossil microbes at best look like a smear of small black smudges. It takes a creative imagination and more to make any sort of biological interpretation, at least one that will convince other scientists. So it's not too surprising that every new announcement of microbial fossils more than 2 billion years old is met with a lot of skepticism. Let me give this skepticism an individual face. In every scientific discipline, it seems that there are individuals who have taken on the task of quality control inspectors. These researchers act as protectors of rigor to police what gets published and to point out questionable claims. And for the better part of half a century, paleontologist Professor J. William or Bill Schaaf at the University of California's Los Angeles campus has played that role for Archean fossils. After studying some of Earth's most ancient microbial fossils for decades, Schaaf developed a checklist of traits that are both necessary and sufficient to confirm that purported fossils represent actual remains of life. He developed his criteria by first focusing on more recent, well-preserved specimens, which are unambiguous. Schaaf was then able to push the fossil record farther and farther back into the past, more than 3 billion years old in some cases. Schaaf's criteria for old fossils are logical, they're convincing. He demands, for example, that fossil microbes must be preserved in properly dated sedimentary layers that were deposited in environments where microbes could have once lived. Fine-grained marine sediments are promising, but metamorphic or igneous rocks are not likely homes for these remains. If they're purported fossil microbes, they must show uniform size and shape. Microbes tend to come in large collections of nearly identical spheres or rods or chains, which are quite different from the nebulous black streaks and carbon-rich blobs that are found in many other old rocks. Schaaf and his students quantify these observations by employing statistical tools to analyze size and shape distributions. Those procedures, which included a checklist of perhaps a dozen characteristics, helped to remove some of the inherent subjectivity found in describing Earth's oldest sedimentary rocks. Now, the field really needed this kind of rigor, and Schaaf's quantitative catalog of essential traits for any purported suite of microbial fossils served him very well. Time and again, he published what seemed to others to be unassailable descriptions of new fossil finds. And he also cast doubt on some of the more questionable claims of ancient life that were submitted by competing researchers. His most public and newsworthy challenge occurred in August of 1996, shortly after NASA scientists announced that they had found microbial remains in a Martian meteorite. At a high-profile NASA-hosted press conference, Schaaf played the role of the lone dissenting voice, the only scientist to speak who rejected the claims of extraterrestrial life. And he had a litany of good reasons to suppose Martian fossil microbes are much too small. They're not even large enough to hold a single strand of DNA. The reports lacked the proper supporting chemical and mineralogical evidence regarding how the fossils were mineralized. And the microbes were in the wrong kind of rock type as well. It was a pyroxene-rich igneous rock, not sedimentary. Of course, most reporters went with the big story and seemed to ignore Schaaf's persuasive arguments. Given all that, it's more than a little ironic that Bill Schaaf himself was eventually subjected to the same kind of devastating criticism over a claim he had made a few years earlier to have discovered Earth's oldest microbial fossils from an Australian rock formation called the Apex Chert. These narrow layers of black rocks, rich in carbon and silicon, occur in a terrain that's almost 3.5 billion years old in a desolate part of northwestern Australia. Schaaf obtained many pieces of the Chert and then sliced them into thin, flat plates called thin sections that are transparent to light. His graduate students and postdocs were given the task of scrutinizing hundreds of sections in a microscope looking for anything that was suggestive of ancient life. They took lots of photographs of suggestive elongated black structures which could be interpreted as cell-like segmentation. Schaaf first published these results in 1993 in a high-profile science paper. The smudgy photographs were placed side by side with artistic line drawings to, quote, aid the eye, as well as photographs of similar-looking modern photosynthetic microbes that were cyanobacteria. Schaaf even went so far as to claim that the Apex Chert fossils produced oxygen, even though this was a full billion years before the Great Oxidation Event. Well, this was a discovery that really caught on. Within a matter of a few years, the most convincing Apex photos had achieved iconic status and were amongst the most reproduced paleontological images of all time. They appeared in many textbooks, each of which repeated the earliest fossil claim, often with an uncritical statement that the microbes were photosynthetic. Now, it's an old rule in science, often quoted by the great science communicator Carl Sagan, that extraordinary claims require extraordinary evidence. And it's equally true that extraordinary claims are likely to attract extraordinary scrutiny. All of Schaaf's Apex Chert fossil specimens reside at the British Museum in London, where they're carefully catalogued and preserved as thin, glass-mounted, transparent sections of rock. 7 years after the Schaaf paper in 2000, Oxford paleontologist Martin Brazier commenced a detailed re-examination of the Apex Chert fossils. Brazier employed new imaging techniques, and he came to a rather different conclusion than Schaaf. As it turns out, Schaaf's thin sections aren't so thin after all, at least not compared to the size of microbes. That means that under a microscope you can raise and lower the focal plane and see different slices of each section. That means that the job of relocating every one of the Schaaf's original images is rather difficult. If you can imagine, Brazier and his colleagues were eventually able to find most of the tiny objects, but they had to look through many, many thin sections to do this. So they found what Schaaf had photographed and published. And the big surprise was that many of the photographs were misleading because they showed a two-dimensional slice through a three-dimensional black object. Brazier's newer photographic technique produced three-dimensional montages and thus revealed a much more complex picture. If Brazier and colleagues set the microscope focus to the same depth of Schaaf's original photographs, then they could reproduce the classic textbook images of apex fossils. But if they raised or lowered the focus slightly, then what they had appeared to be legitimate elongated strings of microbial cells morphed into something altogether different. Wavy sheets, irregular blobs, sometimes with branching or folds that had nothing to do with biology. So Brazier and colleagues published a major challenge titled Questioning the Evidence for Earth's Oldest Fossils. That was in the March 7, 2002 issue of the prominent periodical Nature. They described Schaaf's fossils as nothing more than selectively chosen cross-sections. The real three-dimensional structures bear little resemblance to anything biological. Well, that wasn't the end of the controversy. As Schaaf fought back with his own article, Laser Raman Imagery of Earth's Earliest Fossils. It was published back-to-back with Brazier's piece in the same issue of Nature, and Brazier was furious. He claimed that his paper had been delayed a year to give Schaaf a chance to rebut that challenge. Schaaf's new contribution presented new microanalysis of the apex chair black cells. He showed that the isotopic composition, the atomic structures are consistent with biology. And he repeated that oldest fossil claim without any apology, although he didn't push the idea that the microbes were photosynthetic. Even though Schaaf fought back as best he could, for many of us the seeds of doubt had been sown. And the bar for claiming Earth's oldest fossils has clearly been raised. It's not surprising that 3.5 billion-year-old fossil microbes are rare, if they exist at all. Try to imagine what would happen to a colony of microbes when they die. Almost invariably, the microscopic collection of chemicals that was a living cell is going to fall apart. Larger biomolecules like proteins and cell membranes will break down into smaller and smaller molecular pieces, ultimately into water and carbon dioxide. Many microbes will be eaten or scavenged, and almost nothing will remain after a few months or years, much less millions or billions of years. Time is not kind to dead cells. There may be rare exceptions, but it takes extraordinary circumstances. Cells must be buried quickly in fine-grained sediments with absolutely no corrosive oxygen in the atmosphere. The host rock can't get too hot, nor can the rock be too deformed by pressure. Even so, only the hardiest carbon-based molecules can survive any length of time, and those molecules survive in an altered form. What's most likely to persist is the sturdy carbon backbone of molecules, perhaps up to about 20 carbon atoms total. Sometimes the backbone is a simple long chain with a few carbon atoms branching off to the sides. And sometimes it will be a hobanoid group of interlocking rings. You might think of these diagnostic molecular fragments as ultra-small skeletons. They're all that's left of much larger collections of functioning biomolecules that have been depolymerized, degraded, otherwise altered down to a resilient core. This is a new and different game in paleontology. We're talking about searching for the actual molecular pieces of once living cells. These are the atoms, the molecules that were once alive. It's really challenging, but if you can find such a molecular skeleton in old sedimentary rocks, and if you can convince yourself and others that it's not simply contamination from younger rock formations or from all the living microbes in our environment, then you might be able to claim discovery of a chemical fossil, the original atoms of a once living microbe. I'm fascinated by the contrasting lifestyles of this new breed of molecular paleontologists. On the one hand, the women and men who enter this field have to endure the rigors of field geology in some of Earth's most forbidding places, remote locations in Africa, Australia, northern Canada. It requires hiking miles across arduous terrain, excavating hard rocks by hand, carrying hundreds of pounds of promising specimens back to base camp. Other geologists work for months at drilling rigs because fresh drill cores are less likely to be weathered and contaminated by surface microbes and vegetation. These scientists face months of hardship, danger, deprivation. And then it's back to the laboratory for more months of clean room tedium. Once you have the rock in hand, a single thumbprint, even the slightest breath, can contaminate a precious 3 billion-year-old rock sample and lead to false results. It not only takes time and patience and exquisite care in handling specimens, but you also need an arsenal of specialized microanalytical apparatus to extract individual molecules from a rock. One of the pioneers in this kind of 21st century paleontology is Professor Roger Summons, an Australian who has set up a state-of-the-art lab at MIT's Department of Earth, Atmospheric and Planetary Sciences. The Summons Lab looks for molecular fossils in some of Earth's oldest rocks. Summons' most famous and controversial discovery was made in the late 1990s while he was working at the Australian National University. He focused on 2.7 billion-year-old sedimentary rocks from the ancient and unusually well-preserved Pilbara Craton in Western Australia. Summons and his colleagues were able to obtain relatively unweathered samples from a unique drill core that reveals a sequence almost half a mile long. There was an especially tantalizing section of black, carbon-rich shale, which is the kind of sedimentary rock that's most likely to hold original molecular fossils. And these particular Pell-Barrow rocks are especially interesting because they look like they haven't been very altered by high temperatures or groundwaters. So if there was any old rock where ancient biomolecules might survive, this drill core is a pretty good bet. Summons and his colleagues concentrated on finding those particularly distinctive and resilient class of molecules called hopanoids. Recall from 2 lectures ago, they have a multi-ring carbon backbone that's known in nature only from living cells. Each hopanoid molecule has its characteristic backbone of 5 interlocking rings, 4 of which are hexagons, each with 6 carbon atoms, and a 5th ring is a pentagon with 5 carbon atoms, and each ring shares 2 carbons with its neighboring rings. That's a total of 21 backbone carbon atoms in all. If you find hopanoids in a rock, then you have clear signs of life. In modern cells, these molecules play key roles in stabilizing cell membranes that protect cells, and because they only come from cells, they make very convincing molecular biomarkers. 2 extremely high-profile papers appeared almost simultaneously in August 1999 from Summons' Australian lab. The first one was in Science, with Joachim Brox, a PhD student, as first author. That paper described the oldest reported molecular fossils, 7-billion-year-old Pell-Barrow rocks, and that discovery would break the previous molecular fossil record by 1 billion years. And it was more than just a report of finding a molecule, because hopanoids come in varieties that can reveal a lot about ancient ecosystems. Different kinds of hopanoids have extra carbon atoms stuck off at various places around the rings. In this case, Brox and colleagues found a kind of hopanoid only known from more advanced cells called eukaryotes. These cells contain a nucleus that houses DNA, and they're the building blocks of all major types of multicellular life, including fungi, plants, and animals. At the time of their publication, the oldest known eukaryote fossils were only about 1 billion years old. All the more primitive microbes existing before 2 billion years ago were assumed not to have a nucleus. And you can imagine the surprise and the skepticism that met this interpretation. If the Summons Group discovery is true, then one of 2 conclusions is possible. Either eukaryotic cells evolved 1.7 billion years earlier than anyone had thought, and that would mean that life's early evolution was correspondingly accelerated much faster than anyone thought. Or this kind of hopanoid molecule evolved very much earlier than eukaryotes. Either case would require a rethinking of life's history. For many scientists, it was a lot easier to reject both conclusions and believe that Brox and colleagues were simply detecting contamination from much younger cells. The second article, this one published in Nature with Roger Summons as first author, made what was an equally surprising and some would say controversial claim that a nearby rock formation contained another variety of hopanoid. The rock is the 2.5 billion-year-old Mount McRae black shale, taken from a modest 3,300-foot hill in Western Australia. Mount McRae shale contains a kind of hopanoid with an extra carbon sticking off one side of one ring. Today, these 2 methyl hopanoid molecules are only found in cyanobacteria cells that produce oxygen by photosynthesis. So, someone concluded that photosynthesis was well established by 2.5 billion years ago, which was slightly before the Great Oxidation Event. For many paleontologists who read the paper, I suspect the prospect of probing the origin of photosynthesis with preserved molecular fragments was in part exciting, but also something to treat with caution. After all, there's no compelling evidence in the rock record that oxygen production began that early. And naturally, there were some pretty severe skeptics, just as there have been for every claim of the earliest fossil. Most troubling, even confusing to those of us on the outside, were grave doubts raised by Joachim Brox a few years after the publication of his own PhD work. Evidently, Brox had always harbored doubts about whether he was measuring something old, because young hopanoids are everywhere. Even the deep subsurface is swarming with microbes living in rocks, so contamination is inevitable. Even if the hobanoids and other molecular fragments are there, there's apparently no way to be sure how they got there. So I recently asked Roger Summons his current thoughts about what's the oldest known molecular fossil. He paused and said, well, I suppose it's 2.7 billion years, but a lot of people don't agree. And even more recent experiments at Summons' lab point to recent contamination in those very old rocks, so the jury is still out. But skepticism is probably warranted. It will probably take many years, more samples, refined separation methods, and new analytical techniques before the challenges facing this kind of research are fully resolved. The fossil record holds lots of clues related to the history of photosynthesis. We've discussed fossils of primitive cells, and algae, mound-shaped stromatolites, even possible molecular fossils. And then there are microbial mats, which may be at once the most obvious and the most overlooked fossils of ancient photosynthetic life. Today you can find microbial mats just about anywhere around the world, wherever shallow coastal waters or banks and slopes of slow-moving rivers and streams provide a foothold for algae. Given the chance, algae will form thick, tangled, carpet-like layers of intertwined filaments. These resilient coatings provide a kind of anchoring to loose, sandy sediments and ensure that the algae are stabilized in a wet, sunlit environment, a protection from the erosion of floods and waves. You might think that such fossils would be seen everywhere, but the paleontological community all but overlooked these fossil microbial mats before the discoveries of Nora Noffke. Nora Noffke is a professor of geobiology at Old Dominion University in Norfolk, Virginia, where she has amassed a research portfolio that establishes her as the world's leading authority on ancient microbial mats. I've had the good fortune to work with her on some of her findings since the early 2000s, and it's been obvious that her path to scientific prominence has been anything but easy. And this is a story that's been repeated over and over and over again for women in science. She enrolled as the only female undergraduate in geology at the Eberhard Karls University in Tübingen, Germany. There, and at her graduate department at the Karl von Ossietzky University in Oldenburg, there was not a single woman on the earth science faculty. And as you might expect, lab facilities and field trips were not geared towards co-education. On top of those challenges, Nora has chosen some extremely forbidding areas in the world to conduct her fieldwork, including remote and hostile rock formations in South Africa, in Western Australia, in Namibia, in the scorching Middle East, and frigid Greenland. But she brings to the field a steely determination and a remarkably keen eye for features that others have simply overlooked. Again and again, Nora has spotted the trace evidence that microbial mats have flourished on many of Earth's ancient sandy shores. Microbial mat fossils are important because they have to be associated with some kind of photosynthesis. That's not necessarily true of microbes that left fragmentary remains in black scherts or black shales. Those fossils could have come from deep, dark zones far from the surface, far from sunlight. A strong case can be made that shallow water stromatolites were formed by microbes that were photosynthetic, as the microbes are held in place right at the surface. Though it's also possible that this kind of mineralizing mound could simply represent a protective home in an otherwise harsh, wave-swept environment. But it seems logical that microbial mats must have been made by photosynthetic organisms. After all, why would a colony of microbes use all that energy to stabilize itself in a rough, shallow, tidal zone if it wasn't trying to collect the sunlight? Let me step back and place these contributions in some perspective. Scientists have been looking at ancient microbial fossils for about half a century. For much of that time, paleontologists focused on only three kinds of rock formation. First, you have the black cherts, which are silica-rich rocks like the controversial 3.5 billion year old apex chert that Bill Schaaf studied. In fact, old fossiliferous black cherts first made the news a long time ago, early in the 1960s, when Harvard's paleobotanist Elsa Barghorn recognized ancient microbial fossils in the 1.9 billion year old gunflint chert from northern Minnesota and western Ontario. when Barkhorn examined these thin, transparent sections of the gunflint, he realized that he was seeing ancient single cells preserved in exquisite detail. He did this work with geologist Stanley Tyler, who had actually been the first to observe these tiny sphere-like objects a decade earlier, but he wasn't sure what he was seeing. Barkhorn was able to describe amazing suites of cell-shaped like spheres and rods and filaments. Some of these were even fossilized in the process of dividing. It turns out that these fossils are still the oldest, absolutely unambiguous fossils of photosynthetic cells on Earth. There, of course, are older claims, but none that everyone accepts. So that's black cherry. Then there are carbon-rich black shales, which is the rock type studied by Roger Summons and colleagues. Black shales are very fine-grained and often come from deeply buried sediments. So they're perhaps the best source of ancient molecular fossils. Black shale typically represents a deep water accumulation of mud and carbon-rich debris that must have entombed ancient microbes. That's why thick sequences of ancient black shale from Australia, South Africa, lots of other localities are so carefully examined layer by microscopic layer. And we keep inventing more sensitive analytical tools so black shale will continue to be studied intensively. A third intensively group of studied microbial fossils are the dome-like structures called stromatolites. It might have been difficult to interpret these distinctive mound or sometimes cone-shaped structures, which are commonly preserved in limestone, but modern living stromatolites still form reefs in a few shallow coastal areas, most famously at Shark Bay in Western Australia. These odd layered structures form when a thin surface coating of photosynthetic microbes causes layer upon layer of minerals to precipitate. There are countless fossil stromatolite localities and boulder rocks all around the world, some in rocks about 3.5 billion years old. So, by about 1990, black chert, black shale, and limestone stromatolites were all well-established rock types in which to find evidence of ancient microbes. To this very limited list of Earth's oldest fossiliferous formations, Nora Nafke has now convincingly added a fourth rock type, sandstone. Now, it's easy to understand why sandstone wasn't embraced earlier. Microbial fossils are most easily preserved in very fine-grained rocks like chert or shale, or in limestone reefs, where the grain size is smaller than the microbes. That's why the focus on black chert, black shale, and stromatolites. Sand, by contrast, is relatively coarse, and the mineral grains are very much larger than most microbes. That makes it very hard to preserve small fossils. In addition, sand accumulates in the turbulent tidal zones of beaches, where sand patterns and most signs of life are quickly erased by waves. Fossils in sand are likely eroded away and dispersed. Nevertheless, Nora Nafke has spent more than 2 decades studying modern tidal flats and their rich ecosystems of tough, fibrous microbial mats. And one of the neatest things about these microbial mat structures is you don't need a microscope to see them. Nafke found that microbial mats impose all sorts of distinctive structures along shallow, sandy shorelines. For one thing, they imprint a crinkly texture to the sand surface, sort of like a wrinkled tablecloth. Mats also bind and trap sediment grains in a thick, resilient mass of algal strands, and they alter the pattern of ripple marks in the sand. Mats rip apart and fragment in storms by tearing into distinctive geometric chunks and rolling up like little Persian carpets. All of those features can be seen in the field if you know what to look for. Most sandstone outcroppings have none of these attributes suggestive of photosynthesizing life. They appear monotonously smooth or perhaps gently rippled, but they lack anything that's obviously biological. But Nora Nafke has an amazingly sharp eye, and she learned to spot the distinctive wrinkled and cracked surfaces characteristic of fossilized microbial mats in ancient rocks. This is classic field discovery at its best, and so in the next lecture, I'll begin by describing some of her most important discoveries with some of Earth's oldest microbial fossils. Research that's pushing the date for primitive photosynthesis back to more than 3 billion years. the last lecture, we saw how three rare and distinctive ancient rock types, black carbon-rich chert, black carbon-rich shale, and mound-like stromatolites, have provided compelling evidence for life on Earth more than 3 billion years ago. To these three sources, paleontologist Nora Noffke has added a fourth: the sandy shoreline rocks that were altered by thick microbial mats. Most sandstone formations consist of regular layers of sand, some lighter, some darker, that point to the gradual accumulations of small grains of rock. You can imagine how erosion from mountains, cliffs, bluffs inland are swept by wind and water to the sea, wherever so slowly they build up these layers. Nora Noffke began her studies of microbial mats by looking at modern sandy deposits. Most places you visit are like the beach, just wide expanses of tan sand where you can lie and soak up the sun and watch the water. But in select places where there are wide tidal flats and a sunny lagoon-like beach environment that's usually protected from violent surf, microbes can start to stake a claim. They grow thicker and thicker mats of interlocking filaments that bind and trap sand grains to form a cloth-like coating over the beach. It's usually pretty slimy and smelly, not the kind of beach you'd want to visit for your holiday, so most of us aren't aware of these amazing ecosystems. But Nora realized that such microbial mats could represent an extremely primitive ecosystem, one that's decorated Earth's shallow tidal zones almost since the dawn of life. And so she began her quest, looking at Earth's oldest sandstones for signs of wrinkled mats, of sand grains that had been subjected to binding and trapping of dried and cracked surfaces, and of mats that had been ripped apart and rolled up like little carpets during violent storm events. Nora developed a keen sense for these subtle features. She perfected her field techniques by starting with relatively recent sandstones that had little alteration, and then worked backward in time. And almost everywhere she looked, she spied subtle features pointing to microbial mats. These features must have been on view for previous generations of field geologists, but they had been completely overlooked. In 1998, when she was still a young graduate student, Noffke identified these diagnostic crinkly mat textures on the surfaces of 480 million-year-old sandstone rocks in a famous location in the French Alps, the Black Mountain. In 2000, after moving to Harvard University for postdoctoral work with the eminent paleontologist Andrew Knoll, she pushed the record of microbial mats farther back by identifying what to her had become familiar patterns in 550 million-year-old rocks of Namibia. I think it's safe to say that the paleontological community didn't pay a lot of attention to these findings. If you think about it, the fact that microbial mats may have existed 500 million years ago was not all that newsworthy. After all, every geologist and paleontologist would have agreed that Earth's atmosphere had become oxygen-rich by that time, and microbial mats must have been a part of that story long ago. Yet, even though the existence of ancient mats was probably obvious to most scientists, it appears that no one before Nora had taken the time to scrutinize a variety of modern mat systems, to systematize the kinds of features, the kinds of settings in which they arise, and then, the big step, recognize the similar kinds of traces preserved as unambiguous fossils in ancient sandstone rocks. And just 1 year later, the year 2001, came the big turning point for all her systematic work. That's when Nora Noffke made the first of what are now seen as groundbreaking discoveries in sandstone formations more than 3 billion years old in South Africa and Australia. Now, it's not all that surprising that microbes would have colonized coastal areas with sturdy mats after the Great Oxidation event. We know that filament-like algae are a major source of oxygen. We know they produced a lot of oxygen in our atmosphere, and we know they form mats today. But 3 billion years ago is a long time, at least 600 million years before the presumed Great Oxidation event. There was simply no reason to believe that oxygenic photosynthesis started much before 2.4 billion years ago, and so no one expected, indeed many paleontologists were probably highly skeptical of claims for an ecosystem that relied so heavily on sunlight so very long ago. But here's an important point. Black shale represent deep subsurface ecosystems where any microbes relied on the chemical energy of rocks to survive. Such microbes should have been around since the dawn of life more than 3.5 billion years ago. But there is really no reason to suspect photosynthetic surface life until about 2.5 billion years ago. Now, stromatolites are certainly surface deposits formed by layers of microbes. But the protection provided by these rocky mounds appears to be explanation enough. Stromatolites didn't have to be photosynthetic, though it now seems likely they were. Microbial mats are different. See, it takes a lot of metabolic energy to build up mat structures and bind up all that sand. The only logical reason to do so is to anchor yourself in a sunny environment. So most paleontologists agree that if you find a microbial mat fossil, you are finding incontrovertible evidence for photosynthesis. So the trick is to find the oldest microbial mat fossils, and that is an exceptionally difficult task. Microbial mat features are subtle. They involve slight irregularities in the surface topology of a sandstone outcrop. The outcrop has to be weathered to expose one ancient flat surface, and you can imagine how challenging it is to spot such features in the overhead glare of the midday sun of the South African or Australian deserts. But Norris told me of exhilarating moments of discovery late in the afternoon at the end of long and often fruitless days of searching as the sunlight streams across the barren rock. You've been staring at rocks for hours, seeing nothing. And then, all of a sudden, as the sun gets lower and light breaks across an outcrop surface, the telltale wrinkled sandstone markings stand out in stark relief. She told me how those structures seem to pop out everywhere. Once, she made one of her most unambiguous and thrilling discoveries at the final hour of the final day of an otherwise frustrating, arduous African field excursion. That outcrop eventually came to grace the cover of the prestigious scientific journal Geology. Nora Noffke first came to me in the year 2000 at the suggestion of her Harvard mentor, paleontologist Andy Knoll. Andy and I were in graduate school together, but he was in paleontology, I was in mineralogy, so our careers naturally took us in different scientific directions. But then we both became more involved in scientific efforts to understand the origins and distribution of life in the universe, and we had more and more to talk about. Andy realized that Noffke's scientific case for ancient microbial mats was based almost entirely on surface topographical features that, while suggestive of ancient life, admittedly at times required a pretty vivid imagination. For those of us who had not spent decades looking at modern mat structures, it was pretty easy to overlook or dismiss odd ripple marks or wrinkled rock surfaces. That's why Knoll pushed Nora to improve her case for mats by getting down to the microscopic level and adding analytical data on the minerals and chemicals and isotopes that were still preserved in those distinctive layers. So our strategy was to take very thin, polished slices of rock perpendicular to the presumed mat layers, and then use an arsenal of analytical techniques to look for traces of ancient carbon or concentration of distinctive minerals. We all felt that these analytical data could provide a kind of smoking gun for some of the oldest, yet what might seem to many scientists as ambiguous mat-like features. And here's an interesting aspect of the sociology of science. You can find a rock with clear mat-like features, at least clear to Nora, who studied them for 20 years. And many geologists who haven't been trained to see these fossils will just shrug. But if you provide a table with chemical analyses of unusual minerals or isotopes, then it somehow seems more scientific. And that's a real key to getting your ideas accepted by the broader scientific community. I have to tell you the story of the very first specimens that Nora brought to us. It was really an object lesson in why such analyses can be critically important if the outcrop data are somewhat ambiguous. So Nora is ambitious, and she's always expecting to find mat structures in old rocks. Quite naturally, she gets excited when a new potential mat fossil comes to light, especially if it could be the oldest example. Well, the first rock samples and thin sections I received were rushed by FedEx from Cambridge, Massachusetts to the Geophysical Laboratory. It was the highest priority. These thin sections contain thin, wiggly black layers in a sandy sediment that's 3 billion years old, and that would have been the record in the year 2000. Andy and Nora needed confirmation of two facts. First, that the black features are indeed carbon-rich, and second, that they have life's requisite isotopic signature that is about 3% less of the heavier carbon-13 isotope compared to the average crust. Our job at the Geophysical Laboratory was to analyze for carbon. Now, this isn't always the way research works, but Nora had already written up a paper for Science. It was sitting in Cambridge, Massachusetts, ready to submit, only awaiting those two numbers, carbon concentration and isotope ratio. And we were lucky that my Carnegie colleague, Marilyn Fogel, she was the carbon isotope expert at the Geophysical Lab. She was willing to help with the rush job. Marilyn looked at the sample, she told me the steps. First, you crushed the rock with those black bands, you grind it to a fine powder, then you put a few micrograms of the powder into tiny containers of pure tin foil. Weigh the samples, finally fold the foil cups into tiny balls the size of a little BB. The isotope machine does both measurements and it's easy to use. Just feed the samples, the carbon isotope standards, one by one into a furnace at the front end of the machine. The furnace vaporizes any carbon-containing compounds to carbon dioxide gas, and that gas flows into a sensitive mass spectrometer that separates and measures carbon-12 and carbon-13. The whole process only takes a few hours to obtain the total amount of carbon and the all-important isotope ratio. So you can imagine Nora was sitting in Cambridge waiting for our call. She was hoping for something in the -25 to -35 range, which mean less of the heavier carbon-13 isotope and be typical of some other microbial mats and at least consistent with biology. Certainly the value had to be about -20 or even more negative than that. But the machine told us a different story. The carbon isotopic ratio was close to 0. And that's a value that everyone agrees has nothing to do with biology. Rather, that value of 0 is the classic and unambiguous signature of inorganic carbon. It's the kind of isotope value that comes from fluids in the mantle and then is deposited as thin black veinlets of pure carbon graphite. So the bottom line was that the suggestive black features in Nora Noffke's samples were carbon-rich, but they were unambiguously not biological. Well, that episode proved to be an important object lesson for us. We proceeded very carefully to analyze thin, black, wiggly features in many other ancient sandy sediments, including rocks from South Africa, Australia, and Greenland. And many of those specimens were much more convincing. Over and over again, we were able to measure carbon isotope values in the -20 to -30 range, meaning about 3% less of the heavier carbon-13 isotope. We also found other convincing evidence that microbes had produced mats and flourished along the sandy shorelines more than 3 billion years ago. And of course, there's a lot more evidence than just black smudges or traces of biomolecules. You can see the evidence for microbial mats in the field at the scale of an outcrop. You can hold that evidence in your hand and carry specimens back to the lab. Our first collaborative paper published in the journal Geology in 2003 presented what was pretty compelling evidence for 2.9 billion-year-old microbial mats in sandstones of the Mozan group at a site about 30 miles southeast of Pretoria in eastern South Africa. The isotope and chemical analyses were presented side by side with photos of the obvious wrinkle structures at the scale of outcrops. Though there was only a trace of carbon, we found a convincing isotopic signature of -24, close to the conventional value of roughly -25 or 30. At the time, these were the oldest known microbial mat fossils, but that would soon change. 3 years later, we collaborated on a study of microbial mat fossils from the 3.2 billion-year-old Moody's group, slightly north of the Mozan fossils and quite near the town of Barberton. Nora included color photos of wrinkled surfaces and roll-up structures alongside the chemical and isotopic data, which showed a negative carbon isotope value of about -21. Again, this value is consistent with biologically processed carbon. And recently, we've been working on specimens from Western Australia and rocks almost 3.5 billion years old. The evidence is sketchier, which isn't surprising for rocks that old, but if there's something there, I suspect that Nora Noffke will find it. So microbial mats are the new evidence to watch. After all, there's no question that microbial mats were a common feature of shorelines on Earth more than 3 billion years ago, and it's certain that those microbes use sunlight as their energy source. But a key question remains. Do the mat-forming microbes produce oxygen? Or rather, did they use sunlight for simpler photochemistry? Modern microbial communities reveal the evolutionary history of a variety of sun harvesting strategies, and many of those mechanisms don't produce oxygen. In fact, it's likely that the very first microbes using photochemistry to harvest the sun's energy did not give off oxygen as a byproduct. That's why details of those 3 billion year old mat-forming microbes, how they use the sun's energy, is going to remain a hot topic for some time to come. What we can say for sure is that these fossils date not only the earliest appearance of photochemistry, but also some of the earliest appearances of life itself. Whatever new fossils are discovered, the big picture of Earth's gradual oxidation is widely accepted by geologists. The history is divided roughly into 3 parts. During Earth's first 2 billion years, prior to about 2.4 billion years ago, Earth's atmosphere was basically lacking in oxygen. As we saw 2 lectures ago, there are numerous lines of evidence that early Earth's atmosphere was devoid of molecular oxygen. There's mineral evidence such as the occurrence of unweathered pebbles of pyrite and uraninite. There's chemical evidence in the anomalies of such elements as cerium and iron in ancient soil deposits. And there's the smoking gun of sulfur isotope data, the sulfur isotope fractionation, based not on mass, but on UV radiation, that could only have occurred before the rise of oxygen and a protective ozone layer. Just about everyone agrees with this scenario. Then we see that rather sudden change in the characteristics at about 2.4 billion years ago, which has been interpreted at the time when oxygen rather quickly rose to a few percent of modern levels. Rocks younger than 2.4 billion years lack the mass-independent fractionation of sulfur isotopes. And that change parallels the rise of photosynthetic microbes, which caused the dramatic cumulative changes that are thought to have occurred between about 2.4 and 2.2 billion years ago. That was a key change. And so far, at least, it was an irreversible change that transformed Earth's near-surface environment and paved the way for even more dramatic changes in Earth's geology and biology. The next 1.5 billion years or so, the interval lasting to perhaps 700 million years ago, that includes almost the entire Proterozoic eon, is generally presented in graphs and tables as a time when the level of atmospheric oxygen stayed more or less constant at a couple of percent of modern levels. However, this is not a universally held idea, and a lot of my colleagues think oxygen contents must have gradually risen during that time, with smaller fluctuations up and down. After all, it's almost never a good bet that Earth did just exactly the same thing for 1.5 billion years. For example, Andy Noble at Harvard thinks the atmosphere just kept getting gradually more oxygen-rich, and I suspect that there were some significant swings up and down in total oxygen, depending on where the continents were with respect to the equator and how much rock weathering was taking place. You see, more rapid weathering can consume a lot of oxygen. So that long stretch of time when Earth's atmosphere is supposed to have had a stable 1% oxygen or more is a simple placeholder rather than a measured result. Finally, as we'll see when we turn to the second great oxidation event in lecture 38, the period between about 700 and 600 million years ago, and again between 300 and 200 million years ago, they're thought to be intervals when atmospheric oxygen spiked in concentration, largely as a result of feedbacks with the biosphere. The great oxidation event 2.4 billion years ago had many important consequences for Earth. Regardless of the timing and magnitude of the great oxidation event, I wanted to describe some of those consequences. In the year 2008, my longtime colleague Dmitry Svirgensky, who's a professor of geochemistry at Johns Hopkins University, and I presented a claim we've been building up to in this course, that the great majority of different kinds of minerals on Earth are the consequence of life. For centuries, really, for the entire history of mineral research, the tacit assumption had been that the mineral kingdom operates quite independently of life in that the minerals we see on Earth today have pretty much always been there. In sharp contrast to this view, the mineral evolution approach you've been learning in this course emphasizes that the geosphere, the rocks and minerals, and the biosphere, all kinds of life forms, have co-evolved. Indeed, it turns out that fully 2/3 of all known mineral species, and that number is now approaching 5,000, could not have formed prior to the Great Oxidation Event. That means that most of Earth's rich mineral diversity doesn't exist on any other body in our solar system and probably could not occur on a non-living world. This idea also transforms our view of some all-time favorite mineral species, such as the semi-precious stone turquoise, deep blue azurite, brilliant green malachite, each of which turns out to be an unambiguous sign of life. I'd like to present you with some concrete reasons for how we reach these conclusions, but taking a quick side trip into the field of aqueous geochemistry. In 1965, geochemists Robert Garrels of Northwestern University and Charles Christ of the United States Geological Survey published a now classic book, Solutions, Minerals, and Equilibria, in which they showed how to calculate what minerals can form under what near-surface conditions. For a time, this volume was required reading for all Earth scientists. But fashions in science changed, and I think it's safe to say that many of today's geology students have never heard of Garrels and Christ, much less studied the approach in that book. Their central idea is that each kind of mineral can only form under a limited set of chemical conditions. Some of these parameters are obvious. You can't form minerals of copper or uranium unless there's a significant amount of copper or uranium in the environment. You can't form carbonate minerals unless there's a supply of carbonate, that's CO3 ions in the environment. What is probably not so obvious is that any element that occurs in more than one oxidation reduction state is extremely sensitive to the amount of oxygen in the environment. So for example, recall that iron can occur in 3 different oxidation states: as a metal, or in the +2 state that often leads to dark green minerals, or in that +3 state that typically produces rusty red minerals. The amount of oxygen in the environment can be measured in many ways, but perhaps the most intuitive ways is with the fraction of total air pressure contributed by oxygen. What's known as there's about 2/10 of an atmosphere, which is just another way of saying that oxygen is roughly 20% of the atmosphere. And everyone agrees that the amount of oxygen early in Earth's history was much, much lower than our current 2/10 of an atmosphere. But Dmitry Svrjensky and I argued that the partial pressure of oxygen before the Great Oxidation Event was pegged at about 10 to the -72nd power. That's 72 orders of magnitude less oxygen than today. At first, the idea sounds crazy. But when you go to Garrels and Christ and look at their graphs, they immediately support this idea. What controls the amount of oxygen on early Earth is all the iron present in its +2 form. The oceans were loaded with +2 iron. So were the early soils, and all that +2 iron created what is known as an oxygen buffer. As long as there was ferrous +2 iron in the oceans and the soils, oxygen bubbled up when it contacted the surface. There was so much iron that it just dominated the chemical state of Earth's surface. So we just go to tables in Garrels and Christ and find that the oxygen levels were locked in at 10 to the -72 power. There's lots of other important mineralogical evidence that points to an anoxic early environment. And here it's evidence based on some of the minerals that did form at the surface. One notable example is the iron carbonate mineral siderite, or FeCO3. That's a mineral that commonly occurs in Earth's history, but rarely forms today. Siderite is the carbonate of +2 iron, and it can only form under extremely low partial pressures of oxygen, even lower than 10 to the -72. There's a useful graph in Garrels and Christ that outlines this point by showing the range of conditions under which siderite forms, given varying amounts of carbonate and of oxygen. And it's very restrictive. Only a small area in the plot where carbonate is enriched and oxygen is lacking. But those are the only conditions under which siderite can form. Their graph says that anytime we find iron carbonate in rocks, and we find it commonly in rocks older than 2.5 billion years, then the atmosphere contains essentially no oxygen. And the same kind of evidence can be extracted from many other minerals, from unweathered pyrite, from unweathered uraninite, from oceans rich in sulfide, from the presence of cerium in soils, from lots of other signs, if you know what to look for. The nice thing about Gehrels and Christ is there are lots of diagrams that reveal the conditions under which different minerals might form and are stable. One is a revealing graph of copper minerals that form under varying conditions of carbonate on the horizontal axis, oxygen on the vertical axis. So this graph is just like the one for iron under varying conditions of carbonate and oxygen. It's just wonderful how each mineral gets its own graph and has so much information conveyed in such a compact way. Anyway, the copper graph in Gehrels and Christ includes fields for two of my absolute favorite minerals, the copper carbonates azurite and malachite. On the graph, they're in regions of relatively high carbonate content. These are also two of the best-known minerals because they're extremely common as alteration products near copper mines. And they're extremely colorful. You can find both azurite and malachite used as ornamental stones and in jewelry, and they always make some of the most spectacular specimens in mineral museums. In addition, the graph shows three different minerals in the part of the graph that's carbonate poor. At the bottom, with the least oxygen, is native copper metal, the shiny copper-colored metal of pennies. Above that, with an intermediate amount of oxygen, is the copper oxide cuprite, Cu2O, with a 2-to-1 ratio of copper to oxygen. Since oxygen always has a valence of -2, that means the copper has a valence of +1 in cuprite. And above cuprite, with twice as much oxygen relative to copper, is another copper oxide tenorite, that's CuO, the 1-to-1 ratio of copper to oxygen, and thus copper is in the +2 valence state. That's copper's most oxidized state in nature. These two graphs, the one with iron carbonate and the one with copper carbonate, are broadly similar. They both have carbonate minerals stable on the right side and oxide minerals stable on the left side. They also have very similar scales on the horizontal axis for partial pressure of carbon dioxide. Copper and iron carbonates only form when the partial pressure of carbon dioxide is greater than about 1,000th of an atmosphere. Lower than that, and you enter the realm of oxide minerals. However, the vertical scale of partial pressure for oxygen is different for iron compared to copper. In the case of iron minerals, the scale is bigger and goes from 1 atmosphere pressure of oxygen at the top to 10 to the minus 100th power at the bottom. That's a huge range that takes you from oxygen-free iron metal at the bottom to the oxide of iron 3+, which is basically rust at the top. And recall that before the Great Oxidation Event, we're sitting at about 10 to the minus 72nd power. That's the buffer created when iron coexists in the 2+ and 3+ states at the same time. For copper, by contrast, the scale goes from 1 atmosphere of oxygen at the top down to only 10 to the minus 60th power at the bottom. That may sound like a terrifically small number, and it is, but it's 12 orders of magnitude higher than the oxidation state that was prevalent before 2.5 billion years. So that means that various minerals turn out to be impossible on early Earth. You can't form tenorite, the oxide of copper, in the 2+ state because it only forms above 10 to the minus 37th power of oxygen. You can't form cuprite, the oxide of copper, in the +1 state because it only forms between 10 to the minus 37th power and 10 to the minus 52nd power. And you can't form azurite and malachite because they require oxygen contents greater than 10 to the minus 35th power. In fact, the only copper mineral allowed turns out to be native copper metal. Let me emphasize the broader point. An important textbook published in 1965 and studied by a generation of mineralogists clearly describes the conditions under which various minerals are possible and impossible. That information, together with ever more precise data from paleochemists about conditions on Earth before and after the Great Oxidation Event, allows us to identify which minerals could coexist before that event and which could not. And the reasons for the limited mineralogical repertoire before the Great Oxidation Event are not difficult to understand. It turns out that these beautiful copper minerals, along with thousands of other mineral species, form in the shallow crust by interactions of oxygen-rich waters with pre-existing minerals. These waters resulted from the exchange of oxygen between the air and the water. We have arrived at the 2/3 mark in our survey, from the Big Bang to the dramatic changes of Earth's epic history. The time is 2 billion years ago. We're now well into the Proterozoic eon, and the diversity of mineral species on Earth is about to take its greatest leap forward. Earth now has some of its most important modern features. Our home is large, rusty continents bounded by blue oceans, and of course, Earth has become a living planet with abundant microbial populations, including great masses of slimy, green, photosynthetic algae and coastal waters. Nevertheless, Earth 2 billion years ago was a very different world from today, a very hostile world. The land was still utterly barren and lifeless. The sun's harsh ultraviolet radiation was virtually unhindered by the small amount of atmospheric oxygen and the tiny amount of resulting ozone. Without a breathing apparatus and a protective suit, any human time traveler would still perish quickly in that alien environment. What we find then is a planet in the midst of a long transition to the green, living world we think of as an Earth-like planet. Let's review where we are in terms of mineral evolution. 4.5 billion years ago, Earth had formed, and thus had incorporated all of the 250 or so mineral species that are still found today in the very meteorites that fall to Earth, the minerals of stages 1 and 2. Stage 3 of Earth's mineral evolution featured igneous processes, partial melting, fractional crystallization, crystal settling, and other processes associated with Earth's separation into the basaltic crust, the peridotite mantle, and the iron metal core. On a volatile poor world like Mercury or the Moon, these inevitable events lead to perhaps 350 different minerals. On Earth, abundant water led to more mineral richness with clays, hydroxides, ices, and evaporite minerals, upping the total to perhaps 500 different mineral species. And that was the state of our planet 4 billion years ago at the dawn of life. Stage 4 of mineral evolution depended on Earth's abundant store of inner heat. Unlike Mars or Mercury, our planet is large enough and thus has enough heat to partially remelt large volumes of basalt and thus produce granite. This process of remelting concentrates numerous rare and exotic elements: beryllium and boron, lithium and cesium, niobium and tantalum, uranium and fluorine, which ultimately generate hundreds of new rare and exotic minerals. Yet such selection and concentration of unusual elements takes a lot of time, more than 1 billion years by our estimates. So the distinctive pegmatite minerals of stage 4 probably didn't first start appearing until about 3.5 billion years ago, well after the origins of life. And then comes stage 5, plate tectonics, the subduction of immense slabs of wet crust into the hot mantle, and the subsequent partial melting of those deep penetrating slabs to generate massive volcanism at the surface literally changed the way Earth works. Before plate tectonics, heat flowed to the surface primarily in the form of great vertical plumes of magma rising from the deep core mantle boundary. These plumes transferred lots of heat in an efficient way, but I doubt they generated lots of new minerals. and that process may have dominated through Earth's first billion years. However, by 3 billion years ago, the new lateral tectonics had taken over. Subduction caused great volumes of crust to be reworked. The crust is where all the exotic elements concentrate, because they have nowhere else to go. So plate tectonics provides a means to rework those elements, select and concentrate them. Hundreds of new minerals appeared, for example, accompanying the massive metal sulfide deposits. They're the largest mining districts on Earth today. Thanks to granite formation and plate tectonics, by 3 billion years ago, Earth had achieved an inventory of minerals approaching 1,500 different species. Nevertheless, until the Great Oxidation Event, that was it. The rise of oxygen by photosynthetic algae changed everything. Earlier microbial life, what we call chemolithoautotrophs. It only speed up mineral-forming reactions that were already energetically favorable. Those reactions would have occurred anyway, and microbes simply catalyzed the process. But when microbes learned to harness the sun's energy, they could drive chemical reactions in totally new directions. They could employ Earth's abundant supplies of water and carbon dioxide. They could drive their biochemical reactions to make biological molecules, and oxygen was a waste product. That oxygen gradually built up in concentration in the atmosphere to change the chemical state of the surface. Given such a radical chemical transformation of Earth's outer layers, a mineral explosion was inevitable. In this lecture, I want to look more closely at the rise of mineral diversity in the Proterozoic eon. A few years ago, this lecture would have been based almost entirely on speculation. Informed speculation, to be sure, with sound theoretical grounding, but speculation nonetheless. But thanks to recent and exhaustive research, we're gaining a remarkable picture of exactly when and where mineral diversification took place, with two important conclusions. First, it took a long time, 1 billion years or more, for the mineral diversification to follow the Great Oxidation Event. And second, new minerals appeared not steadily, but during short episodes of intense activity associated with the formation of supercontinents. Let's look in detail at some of these new data to see the evidence. The first comprehensive mineral evolution survey of any chemical element was undertaken by my friend and colleague Ed Grew, who's a professor at the University of Maine in Orono. We met Ed briefly back in lecture 23 on pegmatites. Ed is the world's leading authority on the minerals of the rare element beryllium. Recall that beryllium is element 4 in the periodic table. It's surprisingly rare. It's the first of the so-called alkaline earth elements, right above the more abundant magnesium and calcium. Like magnesium and calcium, beryllium readily gives up 2 electrons to become a +2 ion in crystals. But beryllium is very small, and thus doesn't easily fit into the larger crystal sites with 6 or 8 surrounding oxygen atoms. Beryllium always wants to be at the center of only 4 oxygen atoms, and that means it needs its own distinctive crystal structures. In this respect, beryllium is what's called an incompatible element. It simply doesn't fit into ordinary rock-forming minerals, and so it becomes concentrated in the leftover fluids. And those are the fluids that form pegmatites during the gray earth of stage 4 mineral evolution. What Ed Grew has done for our understanding of stage 7 mineral evolution after the Great Oxidation Event was even more remarkable. First, he cataloged every known beryllium mineral. Turns out there are 106 approved species. Then he tracked down all the localities where each of those 106 minerals have been reported. And then he dove into the obscure geological literature in a dozen different languages to find out how old each mineral locality might be. This was a massive effort. The data are scattered through many hundreds of papers, many of them difficult to find. But Ed was able to produce a landmark graph, which he plotted age extending back 3 billion years on the horizontal scale, and the cumulative number of beryllium minerals that had appeared on Earth on the vertical scale. Now, had we been asked in advance to guess what we'd find, I suppose that we would have said a gradual, rather continuous rise in the diversity of beryllium minerals through Earth history. That's not what Ed found. Instead, he observed very distinctive pulses of mineral-forming events. The oldest known beryllium mineral found in rocks 3 billion years old is beryl. Recall from lecture 23 that beryl is an aluminum silicate that occurs in many pegmatites and is the principal beryllium ore. Aquamarine and emerald are prized colored gemstones of beryl. A few more beryllium minerals appear before a small pulse between about 2.8 and 2.6 billion years. Then a much bigger pulse occurred, a tripling of the number of beryllium minerals at about 1.8 billion years. Following that, there are additional episodes at about 1 billion years, and then a big increase during the last 500 million years. These intervals turn out to be very over 200 boron minerals. So this was a huge challenge to compile all that data. Like beryllium, boron does not easily fit into any common rock-forming mineral. It adopts a +3 charge like aluminum, but it's too small to fit comfortably into the crystal sites of most aluminum minerals. One family of boron minerals, the colorful tourmaline, stands out as the oldest mineral containing boron. We suspect tourmaline was first because it can form at relatively low concentrations of boron, but it's also a tough mineral that can persist as sand grains when most other minerals weather away. Anyway, the oldest dated boron mineral is tourmaline, which appears in rocks more than 3.5 billion years old. All other boron minerals are more recent than tourmaline. And just like beryllium minerals, we see pulses of mineral formation at about 2.8 billion and at 1.8 billion, as well as at 1 billion years ago. And then in the last 500 million years, boron minerals display a very rapid diversification, and that effect may be as much as anything a reflection of the fact that many boron minerals weather away quickly. In fact, dozens of boron minerals are water soluble and only occur in dry places like Death Valley, where former salty lakes like the Great Salt Lake in Utah have evaporated. You might recall old advertisements for 20 Mule Team Borax. Well, those ads were referring to big boron mining districts in the desert southwest of the United States. The point is that a lot of boron minerals just couldn't survive very long and appear only in relatively young rock formations. So, what do these episodes of mineral formation at 2.8 billion, 1.8 billion, and 1 billion years have in common? It turns out they're all times during which it's now thought that supercontinents were being assembled. Perhaps the most astonishing conclusion of the theory of plate tectonics is that entire continents shuffle about the surface of Earth, moving from one hemisphere to another, from poles to the equator, over times of hundreds of millions of years. An inevitable consequence of such continental motions is that from time to time, continents collide. Details of those collisions are preserved in many lines of evidence. Paleomagnetic studies of once molten rocks reveal the latitude and orientation of continents at the time when those rocks cooled. So we find that continents that are now widely separated appear to have been joined at earlier times. Fossils tell us the locations and ages of coastal beaches, of coral reefs, deep water environments, and certain distinctive fossil species like dinosaurs and land plants of a specific age are found on continents now widely separated, but which must have once been joined. And continental collisions themselves have profound geological consequences that can be mapped and dated, not the least of which are pulses of mineralization. What these varied studies reveal is that on perhaps 5 separate occasions in Earth history, most of Earth's continental material converged in a series of collisions into a single supercontinent surrounded by an even larger superocean. As you might imagine, the details of the exact position and shape of those supercontinents becomes increasingly uncertain the farther back in time we go. 2 lectures from now, we'll look more closely at this supercontinent cycle and the 5 major episodes of supercontinent assembly. Continental collisions produce minerals because collisions induce melting, and melting mobilizes mineral-rich fluids. Many of the most important ore deposits arise at these times and places of supercontinent assembly. Abundant granites in their associated pegmatites lie along these continental suture zones. Indeed, the larger and as yet unanswered question might be why we don't find more mineralized zones during the long intervening periods of supercontinental stability and then breakup. So what are these episodes that appear in Ed Gru's diagrams of beryllium and boron mineralization? The earliest well-documented supercontinent formed from about 2.8 to 2.5 billion years ago, when most, if not all, the continents clumped together to form the one gigantic supercontinent called Kennerland. Details are difficult to sort out because rocks of that age are sparse and generally quite altered by heat, pressure, and of course time, but mineral deposits, especially in Australia, South Africa, and Canada, paint a fuzzy picture of Kennerland. The supercontinent may have been stable for only about 100 million years, from 2.5 to 2.4 billion years ago. That's just before the Great Oxidation Event. And then the Kennerland breakup correlates with the Great Oxidation Event. Indeed, it seems likely that the increased coastline created by splitting Kennerland, and then the increased flow of nutrients from the newly exposed coastlines caused the immense algal blooms that then caused the oxidation. So here's a classic example of the geosphere and plate tectonics having an effect on the biosphere, which then has a huge effect on the geosphere. That's the coevolution of the geosphere and the biosphere. Next came the supercontinent of Columbia, also known as Nuna, which began to assemble about 2 billion years ago. It's thought to have been a stable supercontinent for about 200 million years, from 1.8 to 1.6 billion years ago. And then it broke up into separate continents, not unlike today's globe, for perhaps 400 million years. Roughly 1.2 billion years ago, the supercontinent of Rodinia began to form. By 1 billion years ago, Rodinia was stable and lasted for a quarter of a billion years. Another period of breakup and then isolated continents followed, starting about 750 million years ago. All this suggests that the supercontinent cycle is clearly implicated as a key factor in the diversification of Earth's near-surface mineralogy. Nevertheless, life and the rise of oxygen in the atmosphere is without any doubt the number one cause of mineral richness on Earth. I presented some of the quantitative evidence for mineral-forming power of oxygen in the last lecture. Most known oxide and hydroxide minerals simply cannot form without the abundant oxygen that's been produced by life. What about Mars? Some of my colleagues have countered with an observation of the red planet Mars, where some form of rusting has obviously taken place. Isn't that evidence that Mars has been oxidized and could possess a deep mineral diversity similar to Earth's? What's clear is that Mars has a small amount of oxygen in its atmosphere, and that's a consequence of the photodissociation of water, the sun's ultraviolet radiation causing the breakdown of water to hydrogen plus oxygen high in the atmosphere. Some hydrogen escapes to space, so oxygen builds up in the atmosphere. But the total amount of oxygen is trivial compared to Earth. Mars is red because it has a little bit of surface oxidation, like a very thin coating of red paint. The little bit of oxygen in the Martian atmosphere can't penetrate very deeply to the Martian crust. In fact, you may recall seeing the results when Curiosity rover drilled down into the Martian crust early in 2013. The surface is red, but even a millimeter below the surface, the rock is dull gray, not red. The crucial difference between Earth and Mars, and presumably other small planets like it, is that Mars can't experience the dynamic circulation of oxygen-rich subsurface waters that produces Earth's astounding mineral diversity. Not everyone agrees that the Great Oxidation Event marked a clear beginning of oxygen in Earth's atmosphere. Professor Ariel Anbar, who's a dynamic geochemist at the Arizona State University, has described ancient records rather differently. He titled a provocative article in the journal Science, this is in 2007, "A Whiff of Oxygen Before the Great Oxidation Event." To the average reader, that title explicitly claims that molecular oxygen was present in Earth's atmosphere, at least locally, by 2.5 billion years ago, or 100 million years before the Great Oxidation Event. Their claim was that a local concentration of algae created a microenvironment with atmospheric oxygen that modified the local minerals. Anbar and co-workers studied the abundances of various oxygen-sensitive trace elements that occur in a 200-foot thick sequence of black shales from Mount McRae in Western Australia, the same rock studied by Roger Summons in his quest for ancient biomolecules. These finely layered rocks were deposited in a relatively deep, offshore environment of an ancient ocean just about the time that Kinnerland was a stable supercontinent. The black shale appears monotonous to the eye, but these layers contain chemical surprises when examined closely. There's a 30-foot section of rock near the top of the shale that's enriched in two key elements, molybdenum and rhenium. Those elements tend to remain locked in rocks in their more reduced +4 state unless they're oxidized to molybdenum 6+ or rhenium 7+, and that oxidation can only occur if there's an eager electron acceptor like oxygen available. The key here is that they're more oxidized forms, both molybdenum and rhenium. They readily dissolve in water, and then they can flow down rivers and into the ocean where they concentrate in black shales on the ocean floor. All of us agree that these molybdenum and rhenium dating are telling us something about erosion 2.5 billion years ago. Molybdenite is the commonest mineral of molybdenum. And these will, as we're going to see, it often incorporates rhenium as well. I have a sample here with molybdenite layered on top of granite, which makes it look very sturdy, but molybdenite is actually an exceptionally soft and easily abraded mineral, similar to graphite. It's only 1 on the Mohs hardness scale. So suppose a molybdenite-bearing granite or ore body might have been exposed on an ancient mountain slope above the sea, where Mount McRae shale was deposited. Mechanical weathering could have produced microscopic bits of soft molybdenite that were carried to the sea and settled to the black, muddy bottom that became the Mount McRae shale. And even if the molybdenum and rhenium were oxidized at the surface, that doesn't mean that oxygen did the deed. Oxidation without oxygen might sound a little confusing, but Dmitry Sverdzenski and I have shown that there are plenty of ways to move and transform molybdenum, rhenium, and other elements without invoking oxygen. Such common molecules as sulfate or nitrate or even carbon dioxide could have done the electron accepting trick in the absence of any O2. So the more attention-grabbing storyline that a whiff of oxygen from early photosynthetic cells was modifying Earth's minerals even before the great oxidation event seems unlikely, especially given the evidence we've seen that there wasn't any atmospheric oxygen before 2.4 billion years. In fact, it turns out that even with significant atmospheric oxygen, as occurred after 2.4 billion years, that's simply not sufficient to increase mineral diversity right away. That's because subsurface waters, not air, are necessary to dissolve, to transport, to chemically alter, and otherwise modify the upper few thousand feet of rock. New minerals aren't formed primarily right at the surface, though there are certainly some new types that occurred as older rocks were weathered in air. But most of the numerous new minerals that arose for the first time after global oxidation formed underground in the upper mile or so of the crust. My group has cataloged long lists of minerals, more than 200 uranium minerals, almost 400 copper minerals, and hundreds more minerals of iron, manganese, nickel, mercury, molybdenum, many other elements that arise in this way. Many of these minerals form when oxygen-rich waters circulate through metal-rich ore bodies. We've also proposed that prior to the rise of oxygen, such mineral-forming reactions simply could not have occurred. That even long after the atmosphere had oxygen, the subsurface waters were highly reduced, and no new minerals occurred. Until recently, that statement was more of a conjecture than anything we could prove, but we now have new data that makes a convincing case for how very long it takes the subsurface to become oxidized and thus generate new minerals. And this data comes from the same two elements, molybdenum and rhenium, that Ariel Anbar and his colleagues measured in the Mount McRae shale. I'll look at this study in much greater detail in Lecture 38 when we explore some of the surprising consequences of biological feedbacks on the mineral kingdom. But here's a quick overview. It turns out that commonest molybdenum mineral, molybdenite, or molybdenum disulfide, that's MOS2, always contains a small amount of the heavier element rhenium. These are two chemically very similar elements. One is almost directly below the other in the periodic table, so rhenium easily enters the molybdenite structure. It turns out that the rhenium has a radioactive isotope that's ideal for dating individual molybdenite deposits, and that's information that ore geologists always want to have. So it's rather easy to go into the vast geological literature on molybdenum mines and extract information on both the ages of different molybdenite specimens and their rhenium contents. Our team gathered data on hundreds of molybdenite samples from around the world, and we found a remarkable correlation. The oldest molybdenite samples from the Archean eon before 2.5 billion years ago have very low rhenium contents. Samples from the Proterozoic eon, post-dating the Great Oxidation Event, have on average more rhenium, and molybdenite samples from the last 500 million years of the current eon have much higher average rhenium contents. The trend is obvious. Rhenium contents in molybdenites have increased dramatically over the past 2.5 billion years, and especially during the last billion years. But why? Well, this goes back to the fact that rhenium is only mobilized in an oxidizing environment. Rhenium will enter molybdenite if it's transported by subsurface waters in its 7+ state, and then joins molybdenum. And our data make it clear that subsurface oxidation didn't really get going until perhaps 1 billion years after the Great Oxidation Event. And that's what led to the majority of mineral species found on Earth today. And so we come back to life, and oxygen released by life is the key to understanding the mineral explosion. By Earth's 2 billionth birthday, our planet had changed irreversibly. The first dramatic changes had occurred quite a bit earlier on land as Earth's outermost exposed rocks rusted. By 2.4 billion years ago, oxygen-driven surface weather began to break down iron-bearing granite and basalt into brick-red soils. As Earth's near-surface environment changed, the land shifted its appearance from predominantly black basalt and gray granite to red. And from space, Earth's converging continents 2 billion years ago might have appeared something like the modern red planet Mars, though with big blue oceans and white clouds covering most of the surface. Rust was perhaps the most obvious and most superficial of many profound mineralogical changes that were taking place. We now estimate that the Great Oxidation Event paved the way for as many as 3,000 new mineral species. And all of these species were previously unknown in our solar system, indeed possibly unknown on any planet that has not evolved an oxygen-generating biosphere. We document hundreds of new chemical compounds of uranium, of nickel, copper, manganese, mercury, that simply could not arise on a non-living world. Many of the most beautiful crystal specimens in museums, blue and green copper minerals, purple and magenta cobalt species, yellow, orange uranium ores, and many more. They're signs of an evolving, living world. It's difficult to come up with any scenario by which these wonderful mineral species could form in an anoxic environment, and it's equally difficult to devise a way that significant oxygen can accumulate in the atmosphere of a dead planet. So life is directly implicated in the formation of most of Earth's more than 4,700 known mineral species. And this coevolution between geology and biology is not a one-way street. Remarkably, some of these new minerals provide life with new and unique environmental niches, and some of the new minerals formed by oxidation provided new sources of chemical energy for microbes. In this way, life has continuously co-evolved with the rocks and the minerals. Oxygen is an element of transformation, and it is the element of mineral diversity. The molecular oxygen that's pumped out of plants and algae by photosynthesis is always hungry for electrons. And so oxygen atoms react with all manner of minerals. Oxygen weathers away rocks and forms nutrient-rich soils in the process. The billion-year billion-year period after the Great Oxidation Event is also when the reign of simple, single-celled microbes called prokaryotes began to give way to more complicated, single-celled organisms called eukaryotes. This was when cells for the first time developed a nucleus, as well as a variety of specialized organelles. In fact, it's now widely thought that life's simple cells of the previous billion years may have combined to create the more complicated forms. For example, simple cyanobacteria capable of photosynthesis could have moved inside other cells to serve as chloroplasts, the organelle of photosynthesis in eukaryotic cells. Similarly, mitochondria, the so-called powerhouse organelle found in all eukaryotes, are thought to have originated as bacteria that moved inside the membrane of cells during this period. Both chloroplasts and mitochondria have their own DNA, and there's some thought that their move to symbiosis within a single cell may have been encouraged by a need to adapt to the increasingly toxic conditions of an oxygen environment. In a remarkable way, oxygen also paved the way for life's explosion onto land. When concentrations of atmospheric oxygen first rose to significant levels more than 2 billion years ago, all photosynthetic life forms had to live in the oceans. The sun's ultraviolet radiation was too intense, and lands were absolutely barren of life. But oxygen created Earth's ultimate sunblock, and thus paved the way for life's eventual expansion across the globe. You and I are not independent of oxygen's story either, for we all experience oxygen in the most intimate exchange. At this very moment, with every breath, molecules of air become part of us, even as a small part of us becomes the air, an unending series of chemical reactions with oxygen. Our tissues are replaced over and over and over again throughout our lives, just as Earth's atoms recycle constantly among air, sea, and land, and all its living forms. We are the beneficiaries of 2 billion years of co-evolution, a grand biological and geological solution to the challenges of oxygen.
After the dramatic changes of Earth's first 2.5 million years, what came next appears to be an extended time of stasis. For 1 billion years, very little seems to have happened. No major changes in climate, no glaciations, no major changes in near surface mineralogy, no major changes in atmosphere or ocean chemistry. Earth appears to slow down and take a nap.
It's hard for us to imagine a span of time that's as long as 1 billion years. That's roughly equal to 30 million human generations, an incomprehensible number. It's even harder to imagine a period of 1 billion years on Earth when nothing much happened. Yet that's exactly what some scientists have said about the billion-year time in Earth history, from roughly 1.85 billion to 850 million years ago. This was the middle of the Proterozoic eon, and by most accounts, our planet seems to have changed very slowly during that time, and in ways that are both subtle and as yet not fully understood. This vast interval has been dubbed the Intermediate Ocean by more conservative writers, but a lot of us prefer the more whimsical title, the Boring Billion. It's a period that's often skipped over, but there are important changes in mineralogy, in the oceans, the continents, perhaps the structure of life, changes that together make this a very pivotal stretch of time. For a flavor of how this period is usually seen, I love the comment made by the Australian field geologist Roger Buick, who specializes in the earliest rocks on Earth. He summed up a lot of this time period in the opening sentence 95 article, the dullest time in Earth's history seems to have been the Mesoproterozoic. Now, the Mesoproterozoic era spans the interval from 1.6 to 1 billion years ago, so it encompasses only the middle 600 million years of the much longer boring billion. Before and after things already look more interesting. The immediately preceding period, from 1.85 to 1.6 billion years, constitutes the tail end of the Paleoproterozoic era. And we already discussed in the last couple lectures how that era includes much of the more dynamic time of gradual global oxidation from 2.5 to 1.85 billion years ago. In fact, I argued that oxidation most likely continued underground until about 1.5 billion years ago. And after the Meso or Middle Proterozoic is the earliest bit of the Neoproterozoic era, the interval from 1 billion to 850 million years ago. Starting 2 lectures from now, we'll see how the end of the Neoproterozoic era, which lasted until 542 million years ago, saw some of Earth's most dramatic changes, including at least 2 episodes of global glaciation and other dramatic changes in the near-surface environment, along with corresponding changes in biological evolution. You can see how the eras of the Proterozoic eon can cause some confusion, because the timings of the 3 big subdivisions, the Paleoproterozoic, the Mesoproterozoic, and the Neoproterozoic eras, were defined before some key events in Earth history were discovered, so the timings don't quite match our present understanding of Earth history. In any case, with the boring billion, we have a vast chunk of Earth's history, almost a quarter of the story, and there are essentially no headlines, no big thwack, no formation of first continents, no inception of plate tectonics, no origin of life. You might ask why it would be surprising to have what appears to have been a time of relative biological and geological stasis. Why would we expect dramatic transformative events to take place throughout Earth history? And I suppose the answer is simply that Earth has so often been a planet of profound change. There have always been earthquakes and volcanoes, shifts in continents and oceans, and following the origins of life 4 billion years ago, continuous major transitions in life as well. Nevertheless, at first blush, the rock record of this interval reveals no epic, game-changing impacts or sudden climate changes. There are no obvious signs of glaciations, no mass extinctions. About the only thing going on was that the important interface between the ocean's more oxidized near-surface layer and the anoxic ocean depths may have gradually gotten deeper and deeper. On average, maybe a meter deeper every 100,000 years or so, this dropping fully 10,000 meters over the billion-year period. But no fundamentally new life forms are known to have emerged from that ocean. Nor is it generally thought that many new rock types or mineral species arose. At least that's the conventional wisdom. But I have to say from personal experience that boring is a risky term. I once made the terrible mistake in a public lecture of making a passing reference to the group of biomolecules called lipids, which include all the fats and oils. I said they were rather boring, as all the molecules had the same simple backbone of carbon and hydrogen atoms. Well, this remark was a mistake. Lipids are in fact amazingly diverse when you get into their nuances, as I learned from a chemist who had spent her entire career studying them and rightly took me to task. Lipids play all sorts of interesting roles in regulating life's chemical reactions and crafting its intricate nanoscale structures. Lipids define the insides from the outsides of most living things. Without lipids, life would not be possible. My point is that what we call boring may speak as much to our state of ignorance, our lack of sophistication in the nuances of a subject, than any intrinsic dullness. And so it is with Earth's boring billion. Earth scientists may underestimate biological changes. Biologists may be unaware of mineral evolution, and both may overlook the combined evolution of rocks and life. That long interval may, in fact, be somewhat analogous to human civilization's so-called Dark Ages. Now, it turns out the Dark Ages were a dynamic interval of great innovation and experimentation. As with every age in human history, there were inexorable and irreversible changes. The Dark Ages may be thought of as the gateway to the modern technological world, and yet it's a time span once largely ignored by scholars. As for Earth, I think all of us in the field would bet that some hints of dramatic transformations must lie hidden in rocks of the boring billion, and those stories are so far largely unread. Everyone in the business knows about some of those hints. Some of Earth's most valuable ore reserves, immense deposits of lead and zinc and silver from Zambia and Botswana in Africa, from Nevada and British Columbia in North America, and from the Czech Republic and southern Australia, they're found in rocks of ages smack in the middle of that billion-year interval. Many other important rock and mineral localities that formed at that time are rich in exotic minerals of beryllium, boron, and uranium. And the tectonic story is equally interesting and perhaps related to the valuable ores and exotic minerals from this time. Growing evidence suggests that Earth's continents clumped together into one gigantic supercontinent during the boring billion and then broke apart and then clumped together again in that most majestic of Earth's surface cycles. And biologically, this long period may not be boring at all. Throughout that billion-year interval are abundant, beautifully preserved fossils of microorganisms that reveal how life, though perhaps under great stress, still crowded coastal shallows and offshore environments. Though lacking confirmation from other lines of evidence, research using so-called molecular clocks has suggested that this period marks the first genetic divergence of precursor cells for fungi, modern plants, and animals. All of these organisms depend on eukaryotic cells. That is, their cells have a nucleus and specialized organelles. But the earliest differentiation into distinct types may have occurred at this time, along with the development of sexual reproduction and the first steps towards multicellularity. I think it's safe to conclude that we have much to learn about Earth's dark ages. Up to this point in the story of Earth's evolution, as we reach and pass the planet's 2.5 billionth birthday, the one constant theme has been change, with the first transformations occurring rapidly. There was the outrageously destructive impact of Theia, then an ocean of incandescent magma that encircled the globe, and the subsequent formation of our big moon. Within 100 million years, black Earth turned blue as hot, shallow seas covered almost all the solid surface. It's entirely possible that only 1% of Earth's surface was dry land, with only the tops of the tallest volcanic cones sticking above the waves. The nearby looming moon would have spawned wild weather, immense tides, the water world subjected to constant bombardment from above. Volcanic blasts from below made this earliest Hadean eon totally inhospitable, but the very intensity of those early conditions allowed for a stupendous amount of chemical experimentation, with microscopic life itself emerging very soon thereafter. While life stayed in the water, Earth's evolving surface was largely a saga of expanding the total extent of land. The first step was partial melting of mantle peridotite, which produced black basalt-covered land. The total extent of Earth's exposed surface in the first half billion years was probably no more than about 5%, compared to almost 30% today. And then partial melting of black basalt produced great mounds of gray, buoyant granite, which became the foundation stones of what were to become the continents. Even after 1 billion years of geological activity, those proto-continents of granite, maybe 50 to 100 miles in diameter, accounted for no more than about 10% of the ocean-dominated surface. It took even longer, perhaps another 1 billion years, for plate tectonics of the kind we see today to impose some order on the continent-forming process. It took that long for the chaotic swirling of the mantle to settle into more orderly, deep convection cells, which could then drive the stately plate tectonic conveyor belt. And amidst all of these geological changes, life emerged and evolved and ultimately became another major agent of change, particularly when cells learned to make oxygen. And I think we're getting the point that constant change was Earth's hallmark, something that set Earth apart from all of its planetary neighbors. 2.5 billion years ago, Mercury, Venus, the Moon, and even Mars were already more or less the way we see them today. But while those worlds were trapped in stasis, our planet kept reinventing itself over and over and over again at every stage age trying something new. And so I return to that central mystery of how could we have a boring billion? How could our dynamic planet have found itself mired in its own eon of apparent stasis? One possible answer is simply that Earth was not static. Perhaps change on Earth was still incessant, maybe just not as dramatic as a moon-forming impact or the Great Oxidation Event. After all, in biology, new generations of more complex cells, cells containing a nucleus, mitochondria, other organelles, they had to deal with new stresses while they developed new capabilities. Take sexual reproduction, which was not a feature of life's earliest microbes. Very incomplete evidence suggests that sexual reproduction and the cellular process of combining genetic material from two organisms by meiosis either began or stabilized during this period. Fossils of multicellular red algae found in Arctic Canada on Somerset Island have been dated between 1.2 billion and 1 billion years ago, with spore and gamete differences characteristic of sexual reproduction. Of course, such evidence is scarce and it's difficult to interpret, and the actual onset was probably somewhat earlier. But biologically speaking, this understudied stretch of time might someday be seen as the very opposite of boring. At the cellular level, almost a roaring billion. Anyway, perhaps a critical stretch of biological evolution that we do not yet understand. We do know that mineral evolution during this time led to new types of rocks and valuable ore deposits. Recent research reveals that this interval saw the first appearance of numerous new mineral species that had never before appeared anywhere in our solar system. And perhaps the most significant change was associated with plate tectonics, which just keeps churning. Geological evidence from every continent on Earth reveals that the Mesoproterozoic era was a time of inexorable shifts in the positions of continents. Probably the single most important geological discovery of the last half century is that Earth's familiar geography of oceans and continents is ephemeral. The globe that we all grew up studying and the locations we memorized are all temporary. All of the most recognizable features, including the Americas, Europe, and Africa framing the mighty Atlantic Ocean, the great eastward sweep of the Asian continent, the expansive Pacific Ocean with its plethora of southern islands, and the continent of Australia, and the polar world of Antarctica, all are but a momentary geographic state. And the continents didn't merely drift a single time and eventually lock into place. Go back 50 million years, or time travel 50 million years into the future, and either way you'll find a different, distorted globe that looks only vaguely familiar. 50 million years into the future, the Atlantic Ocean will be some 700 miles wider, while Africa will have finished colliding with Europe. Go back 50 million years before the present, and India was colliding with islands off the coast of Asia. Go back further to the Cretaceous period around 100 million years ago, and sea levels were 100 to 200 meters higher than today, with inland seas spread across North and South America, Europe, Russia, Africa, and Australia. Go backwards or forward 200 million years, and our modern borders would be unrecognizable. And that's just a tiny fraction, less than 5% of Earth history. The lesson is clear. Our globe's land and water have transformed in position and relative extent over and over again. Plate tectonics not only acts to assemble all the continents, but it also rearranges them by shuttling them across the globe, causing them to collide, to split apart. Plate tectonics is the engine of Earth's constant extreme makeovers. But how can we possibly know Earth's ancient geography? Isn't that knowledge lost to time and change? The job of reassembling early Earth falls to a mix of geoscience disciplines, which collectively produce remarkable, though admittedly approximate maps of past and future Earth. Fortunately, Earth has preserved numerous clues to help in the reconstructions. A key starting point is knowledge of how the continents are moving today, how fast they're traveling and in what directions. Year by year, scientists have employed satellites to measure the distance across the Atlantic Ocean. Thus, we have direct measurements of an increase of roughly 2 inches every year. We also see that Africa is splitting in two. And we can document how India smashes into China, which crumples the impact zone into the jagged Himalayan mountains, which are rising an inch or two every year. It's all happening in super slow motion, of course, but with changes occurring at a steady rate of an inch or two a year for 100 or 200 million years, these small increments add up to literally monumental changes. If we can play an imaginary videotape of those changes backwards and forwards, we might be able to guess the details of Earth's geography. If we try to look back much farther than 100 or 200 million years, then we need to invoke other kinds of geological clues. Longitude ceases to be something we can extrapolate backward with any precision. But important data about latitude come from fossil magnetism that's been locked into those volcanic rocks. Those paleomagnetic data have the potential to reveal the orientation of Earth's magnetic field long ago. Moreover, the dip of the field can also reveal the latitude of the continents at the time when those rocks solidified. Such subtle evidence frozen into solid rocks shows that rocks now at the equator were once at the poles and vice versa, and that information is complemented by evidence from fossils and sediments that point to former tropical lagoons in what is now Antarctica, or frozen tundra in what is now equatorial Africa. The sedimentary rock record adds vital data because different kinds of sediments accumulate in different environments. Sand accumulates in shallow seas, while black mud forms continental shelves. The steady laying down and compression of layers in a swamp differs from the windswept sediments of a rocky alpine tundra, and both differ from the daily cycles of tidal lagoons, the annual and multi-year cycles of glacial lakes, and the very long-term sediment patterns caused by the advance and retreat of glaciers, or the cycles of sea level rise and fall. The complex picture of shifting continents is clarified over the past half-billion years by the rich fossil record of animals and plants. Certain species are indicators of climatic zones, while the distribution of distinctive flora and fauna can point to widely separated continents that followed divergent evolutionary pathways. Familiar examples are the varied marsupials of Australia and the large flightless birds of New Zealand, which provide a convincing story of long zoological isolation. It's hard to use fossils much farther back because all we have before about 540 million years are a few jellyfish and sponges and single cells in the fossil record. Inevitably, farther back in time, the picture of Earth's geography fades from view, and any extrapolation from the modern world becomes much more ambiguous. Nevertheless, the experts in paleogeography have managed to bring many lines of evidence together to produce a coherent view of Earth back to at least 1.6 billion years ago, which is well into the boring billion. And there are now well-informed speculations about continental positions that have been pushed back much farther, all the way to 3 billion years ago. I find the results of these studies nothing short of amazing. It's easy to be biased by today's globe, on which the continents are widely dispersed across the globe. They're spread out east to west and from pole to equator. The Americas are separate from Eurasia, which is just touching Africa, and Australia and Antarctica are giant islands. But it hasn't always been so. According to the most accepted models, Earth has repeatedly experienced times when all of the continents were clumped together into one or two supercontinents, and these supercontinents have repeatedly broken apart and dispersed. If we start from the beginning, my view, and one that's supported by many, though not all geologists who study early Earth, is that it took a long time to make the first continent. Plate tectonics was the prime driver, both promoting the production of granitic crust and assembling bits of granite crust into larger and larger landmasses. The focal point of these continent-forming activities is the subduction zone, at the point where a subduction slab plunges down into the mantle depths. All of the unsinkable granite bits and pieces pile up, one after the next to make larger and larger, stable, long-lasting landmasses. At the same time, the subducting slab partially melts to make even more granite above the subduction zone. That's how the most ancient proto-continents form. Those earliest pieces of continents are the cratons, which we met earlier. And because cratons are made of tough, igneous and metamorphic rocks. Once a craton forms, it lasts a very long time and preserves a record of its history. Geologists have identified perhaps 36 more or less intact cratons on 6 continents. Some are as old as 3.8 billion years, and they ranged in size from 100 to more than 1,000 miles across. I love their evocative names. There's the Slave and Superior cratons in North America, the Kapval and Zimbabwe cratons in Africa, and the Pilbara and Yilgarn cratons in Australia. Each of these cratons has experienced billions of years of motion across the globe. They've been jumbled together, ripped apart over and over again, along with lots of smaller ancient fragments. And if we're ever to gain a picture of early Earth, it's the cratons that will provide the evidence, because cratons survive as the foundation stones of the continents. Let's take a closer look at the distribution of cratons, which will ultimately give us a sense of the supercontinent cycle. 3 cratons form most of Greenland. Half a dozen cratons make up a large region in North America, sometimes called the Canadian Shield, that includes not only central Canada, but also the Adirondacks in New York, as well as northern parts of Michigan and Minnesota. Moving to South America, large portions of Brazil and Argentina are underlain by several cratons. We also see 3 cratons forming big chunks of North, West, and South Australia, and other ancient pieces of continental plates called terranes that make up parts of Siberia, Scandinavia, and a large piece of Antarctica. Separate regions of East and South China, most of India, and also several swaths of West, South, and Central Africa. All of these cratons were begun more than 3 billion years ago, which is a time when a lot less of Earth's surface was dry land compared to now. Every one of these cratons holds information about Earth's early stages, but those records are warped. They're scrambled in ways that can make them almost impossible to read. Cratons provide the Rosetta Stones of Earth's earliest history. After all, today's oceans are too new to help in deciphering early Earth, and the atmosphere is even more ephemeral. And because the incessant conveyor belt of plate tectonics keeps swallowing up the salt at convergent boundaries, ocean floors can't help either. In fact, the oldest ocean crust is not much more than 200 million years. That means that anything old enough to tell us about early Earth must be preserved on the continents or not at all. The histories of the cratons are impossibly complex. Every craton has been pushed here and there across the surface, propelled by motions of the tectonic plates. Every craton experienced collisions with others to form larger landmasses called provinces, or supercratons, which in turn occasionally clumped into single giant landmasses. Those were the continents or even the supercontinents. Every time 2 cratons collided, they produced a new mountain range, along with a suture zone, which left behind telltale geological signatures. Each of these ancient mountain ranges provides compelling evidence for the ancient assembly of larger and larger landmasses. And what came together also had to rip apart. Each supercontinent enjoyed a period of 100 million years or so when it was more or less stable, but a supercontinent is like a heat-trapping lid. As heat builds up, upwelling magma forces new divergent plate boundaries to form, and the lands fragment. So each supercontinent eventually rifted apart and fragmented into separate ocean-bound island continents, and each time a continent split apart, a widening ocean formed between the diverging pieces, and when a new ocean opened up, thick piles of distinctive sediment were deposited. There were sandstones and tidal zones, then limestones representing offshore reefs, and in deeper water you get thick layers of mud and black shale. Each time we find a thick sedimentary sequence of this kind, it points to an episode of continental fragmentation. And the evidence, once again, is clear. Over and over for more than 3 billion years of Earth history, supercontinents have been assembled. Then after a few 100 million years, they've split apart. So imagining Earth history becomes something like an immense jigsaw puzzle, where you don't know what the picture looks like, and where the pieces constantly change their position and change their shapes. Given those complexities, how can we possibly reconstruct Earth's early past? What sort of evidence do we have to show that the 36 cratons have indeed moved relative to each other, much less to resolve the details of this exceedingly complex multi-billion-year wandering across the globe. As always, we must look to the rocks. Geologists must trek to the most remote places on Earth, map the rocks, collect samples, subject them to a battery of revealing laboratory tests. The number one target of opportunity is the cratonic core, where you find really old rocks, typically 3 billion years old or more. These are fragments of Earth's most ancient crust, and they represent a total of at most a few percent of Earth's total continental mass. Such old rocks are invariably baked by heat, by pressure. They're altered by the dissolving powers of subsurface waters, and they're often contorted by crustal stresses. Nevertheless, it's often possible to deduce the nature of the original rocks, whether granite-like intrusions or sedimentary layerings. Even so, if all that survived were the most ancient cratonic roots, then our task of deciphering Earth's early geography would be hopeless. Fortunately, the cratons are part of a dynamic crustal history. The story of each craton is punctuated by pulses of new magma, which penetrates the older rocks to form igneous rock bodies and veins and pods. New sedimentary deposits accumulate inland in lakes and rivers, as well as along the shallow, sandy coastlines. And whenever two cratons collide or rip apart, distinctive rock types and characteristic structures occur that can reveal the relative motions of two landmasses. So by carefully studying all the rocks and structures associated with a craton, it is possible to document pretty much the entire history of that craton. All of these younger rocks must be studied together to get a good picture of how a craton moved through time. The igneous rocks are important because they hold tiny magnetic minerals that, when they solidify, lock in the orientation of Earth's earlier magnetic field, and thus reveal the approximate latitude when the rocks cool. Those data don't provide GPS coordinates, but they do record relative positions of cratons through time. And the sedimentary rocks are important because they often hold clues about the climate and ecology. For example, sediments deposited in rapidly weathering tropical zones are quite different from those deposited in temperate lakes or the glacial deposits of higher latitudes. And some sedimentary rocks also incorporate tiny grains of magnetic minerals that can be used to complement magnetic data in igneous rocks. All this takes an enormous amount of work to achieve even a vague understanding of Earth's changing globe. Every one of the 36 cratons has to be scrutinized by armies of geologists. It takes decades of meticulous fieldwork and lab studies, and data from every part of the globe must be integrated. Then all those cratons have to be juxtaposed like bumper cars on a globe. And then we gradually play the imaginary movie of their wanderings backwards in time, starting from the known geography of the modern world. As you might expect, that movie becomes more and more speculative the farther back we go. Nevertheless, an astonishing picture is slowly emerging. According to the latest compelling interpretations, for at least the last 3 billion years, Earth has experienced a repeated cycle of at least 5 supercontinent assemblies, periods of stability, and then fragmentation. And so it appears that if we are to understand Earth, that great supercontinent cycle lies at the heart of the story. Our familiar world map will never look the same again.
This is a place to worship the Father. But you make it a den of thieves! You serpents! How will you escape being condemned to hell? What
By now, you've probably sensed that a lot of controversies swirl around the study of ancient Earth, the composition of the oceans and atmosphere, the timing and nature of life's origins, the extent of land versus water, and many other subjects provoke heated debates at conferences and in publications. And in this climate of uncertainty, the story of Earth's earliest land masses stands out. I doubt if anyone has the nerve to commit fully to more than a sketch map of Earth's surface 3 billion years ago. At least, not yet. There is some tantalizing evidence for the first continent-sized landmass, called that may have formed about 3.1 billion years ago from several scattered cratonic pieces of what are now South Africa, Australia, India, and Madagascar. It's also sometimes called Val Barra for two of its cratons, Cap Val, now in South Africa, and Pilbara, Australia. One interpretation of paleomagnetic data from all of these forming regions is that what are now separate cratons were once sutured together and remained that way for most of Earth's history. It appears that their movements across the globe were virtually parallel for more than 2 billion years, and thus they were probably all linked together. Indeed, magnetic data suggests that what was at least the core of the continent of may have persisted for almost 3 billion years, and only began to split apart about 200 million years ago. The earliest true supercontinent, that is the earliest single landmass that appears to have incorporated most of the cratons, has been dubbed Kennerland, after the ancient Kenoran Pluton that it incorporates. Kennerland is thought to have formed about 2.7 billion years ago from the continent of and lots of other smaller pieces. It's fairly easy to date this assembly interval because each time one craton collided with another, a suture zone was formed, while epic compressional forces pushed up a new mountain range and generated magmas that reveal rock ages. Numerous features are found clustered in rocks around the world with ages between 2.7 and 2.5 billion years old. This interval suggests a sequential growth of the supercontinent. Paleomagnetic data also reveal that Kennerland was at low latitude. It probably straddled the equator for most of its period of assembly and stability. Of course, large land masses with mountain ranges like Kennerland also mean episodes of large-scale erosion and the first great accumulations of thick sediment formations along the continental margins. The character of erosion 2.5 billion years ago was probably rather different from today. Most early Earth modelers describe an ancient atmosphere in which oxygen was totally absent, while carbon dioxide levels may have been hundreds or thousands of times greater than in our time. If so, then rain would have fallen as drops of carbonic acid that ate away at the land and transformed hard rocks to soft clays. Rivers carried these clay minerals into the shallow coastal slopes of the encircling ocean, where thick, delta-like wedges of soft, muddy sediments accumulated. By about 2.5 billion years ago, about the same time that oxygen began to accumulate in the atmosphere, Kennerland experienced the inevitable flip side of a supercontinent formation. Geomagnetic data revealed the divergence of from other cratons as Kennerland began its protracted period of fragmentation. The numerous cratonic pieces were scattered from the equator to the poles. Newly opened shallow seas between the diverging pieces led for a time to thick deposits of diagnostic shallow marine sediments. In many respects, with the breakup of Kennerland, Earth's geography 2 billion years ago was similar to today, in that the continents were widely dispersed around the globe with several intervening oceans. So it was that by 2 billion years ago, the supercontinent cycle was in full swing, and that made the boring billion a lot less boring. The next supercontinent episode, and one a lot more sharply in focus than Kennerland thanks to all of the younger and much better preserved suites of rocks, began about 2 billion years ago, at a time when Earth boasted at least 5 separate continent-sized landmasses. The largest among these was the Laurentian supercraton, which was a conglomeration thought to incorporate at least half a dozen cratons. Laurentia was thousands of miles across, and it encompassed much of what is now Central and Eastern North America. In fact, specialists in ancient landmasses sometimes refer to this clustering of cratons as the United Plates of America. A second large landmass separated from Laurentia by a substantial ocean was and the much smaller Baltica and Ukrainian cratons, which now form the core of Eastern Europe, and cratons representing what are parts now of South America, China, and Africa were also large islands approaching continental size. Paleomagnetic data and a number of mountain belts suggest that between 2 and 1.8 billion years ago, these varied lands collided at convergent plate boundaries. The resulting supercontinent has been variously named Columbia, or Nina, or Nuna, or Hudson Land, though my sense is that Columbia, which is a name based on persuasive geological evidence in the vicinity of the Columbia River along the Washington-Oregon border, that seems to be winning out. This vast, barren land, roughly estimated to have been 8,000 miles long from north to south and 3,000 miles wide from east to west, incorporated almost all of Earth's cratons. In other words, at the onset of the Boring Billion, virtually all of Earth's cratons were gathered within an area roughly the width of South America and the length of North and South America combined. Well, as you can imagine, the problem of arranging 30-plus cratonic fragments into one extinct supercontinent is daunting. Think about it this way. Today, the typical plate moves about 2 inches per year, and rates may have been significantly higher 2 billion years ago when Earth's interior had more thermal energy. So simply multiplying 2 inches per year times 2 billion years, that's 4 billion inches, or more than 63,000 miles. In effect, each craton has traveled a distance equivalent to 2.5 times around the globe, and each craton has taken a path that's different, erratic. That's why it's not at all surprising that multiple models compete for acceptance. In the case of the Columbian supercontinent, 2 rather different stories were proposed almost simultaneously in 2002. One model is published by geochemist John Rogers at the University of North Carolina and his colleague, Indian geologist Santosh Madhava, who is now based at Koichi University in Japan. They propose that Laurentia, what is now most of North America, formed the core of Columbia. In their view, the continent of was sutured to the west coast of Laurentia, while portions of Siberia, Greenland, and Baltica were positioned to the north. And parts of what are now Brazil and West Africa lay to the southeast. Remember, they had to keep track of the positions of more than 30 cratons. And then in the same year, Guoshun Zhao of the University of Hong Kong and several colleagues came up with a somewhat different configuration, in which Laurentia has Baltica sutured to its east instead of its north coast, while Laurentia's west coast has East Antarctica and China instead of Now, given the great age of Columbia and what must be seen as the preliminary nature of these reconstructions, the agreement between the 2 science teams is actually quite remarkably good. Nevertheless, I'm sure that many debates will arise as the locations of one craton or another are shuffled and debated. What most experts do agree on was that by 1.85 billion years ago, with the assembly of Columbia, the stage was set for the Boring Billion. Whatever the exact details of the Columbian supercontinent, we are fairly confident that the interior of the landmass was a hot, dry terrain with a great expanse of rusty red desert. There was no vegetation and certainly no animals, as multicellular life hadn't yet appeared. From space, Earth may have appeared as a strangely lopsided world with its one great reddish-colored landmass, surrounded by an even more expansive, as yet unnamed blue superocean. With all the continents concentrated together near the equator, it's likely that the poles held only modest amounts of ice. With minimal ice caps, the ocean levels would have been correspondingly high, maybe even high enough to invade some coastal regions with shallow inland seas. So, that's the great equatorial Columbian supercontinent, which is supposedly the starting point for the dullest time in Earth history. But what exactly does dull mean in this context? What characteristics of our planet were stable for so long? Was it global climate and rainfall? Or the nature and distribution of life? Or the composition of the ocean? Or the atmosphere? And if little change did occur over a very long period, more than 1 billion years ago, how could we be sure? What measurements would we make, and what uncertainties would remain? I want to tell you about the research of Professor Linda Kaye at the University of Tennessee in Knoxville, who is one of the few scientists who has chosen to specialize in rock formations that were deposited between 1.85 billion and 850 million years ago. She did her undergraduate degree at MIT working with John Grotzinger, who's a leader in the study of Earth's oldest rocks from before 2 billion years. Then her PhD advisor at Harvard was paleontologist Andy Knoll, who's made fundamental contributions to our understanding of life's evolution, particularly over the last billion years. So Linda Kaye was in a unique position to notice that the 2 billion year old Earth described by Grotzinger was strikingly different from the 850 million year old Earth described by Knoll. She concluded that something interesting must have happened during the boring billion. And so she has devoted a significant portion of her career to investigating the Mesoproterozoic era. That's the 600 million year span from 1.6 to 1 billion years ago. As Linda Kaye puts it, the boring billion is fascinating for one of two possible reasons. One possibility is that it was a time of big changes and we've simply missed something profound. If so, then we have much to learn about how to read those old rocks. We have to invent new ways to study Earth's geological record, because if Earth did evolve in dramatic ways, then some kind of record of those changes must have been preserved in the subtleties of isotopes or trace elements or distributions of minerals or maybe fossils. On the other hand, if the Mesoproterozoic is in fact part of a billion-year interval of little change, then that too is remarkable. We've seen that change is the central theme of Earth's story. So 1 billion years without any significant transitions in the near-surface environments would represent something unique. Is it really possible for Earth to experience 1 billion years when all the feedbacks of climate and life were in such perfect, harmonious balance? Linda Kaye's description of the Mesoproterozoic centers around Earth's dynamic surface and the fact that as plate tectonic shifts continents, Earth's behavior changes. It's not simply that as land masses constantly shuffle, collide, split, suture, our globe looks radically different every 100 million years or so. On the most superficial sense, oceans open and close up, mountain ranges rise up, they erode away, and the number and shapes of continents keeps shifting. What's really significant is what these surface changes do to alter dynamic processes at and near the surface. The boring billion began with the Columbian supercontinent as a lone and relatively long-lived supercontinent that persisted more or less intact from 1.8 to 1.5 billion years ago. However, just because there was one single large landmass, that doesn't mean that plate tectonics had stopped. One notable feature of supercontinents is that they continue to grow slowly around their edges because ocean plates subduct under their margins, and new volcanoes rise just inland near the coast. Today, a good example of this coastal expansion can be seen along the Pacific Northwest coast, where such majestic and potentially dangerous volcanoes as Mount Rainier, Mount Hood, Mount Adams, and of course Mount St. Helens are still active. So it's certain that some portions of the Columbia coastline were similarly active. And it's also certain that even more continental crust was added to Columbia as it experienced episodic rifting and ultimately breakup into smaller continents and islands. A big landmass like Columbia traps mantle heat and must eventually crack and fragment. About 1.6 billion years ago, the continent of Ur began to split off from Laurentia and the rest of Columbia, moving to the west. The newly formed ocean basin between Ur and Laurentia saw the deposition of a massive sedimentary sequence with layers of sand and mud that reached amazing thicknesses of more than 10 miles. You can see the remains of this epic deposit today as prominent layered outcrops that decorate much of western Canada and western Montana in the United States. This thick sequence of rocks is called the Belt-Purcell supergroup, and it underscores how new continental rocks are formed even as supercontinents split apart other consequences as well. Laurentia and were still more or less at the equator, and that means there were still no continents at the poles, which in turn means that there probably wasn't any significant ice buildup at the poles. We have to conclude that ocean levels were still relatively high. Indeed, based on sediments formed at that time, we know that much of Laurentia's newly exposed west coast was flooded by shallow seas. Unlike today, when about 30% of the globe is land, it's likely that less than a quarter of Earth's surface was dry, and that state persisted for perhaps 200 million years as thick sediment formations accumulated in shallow waters around the globe. No ice also means no glaciers. So the interval from 1.6 to 1.4 billion years lacks in such general glacial remains as piles of ice-rounded cobbles and boulders, layers of rock powder that are found in most other geological ages. So it's evident that as Columbia broke apart, supposedly dull Mesoproterozoics saw a great deal of change, even if those changes were geologically familiar. But that's not the end of the supercontinent cycle during the Boring Billion. The fragments of Columbia scattered across the globe for perhaps 200 million years, but a collection of continents can only diverge for so long before they start to converge once again. So it was that about 1.3 billion years ago, Laurentia, and other Mesoproterozoic continents began to reassemble into a new supercontinent called Rodinia, named for the Russian word for motherland or birthplace. The evidence here is strong. There's a worldwide pulse of mountain building events preserved in rocks formed between 1.3 and 1.1 billion years ago in Europe, in Asia, in North America. Each of those mountain ranges represents a suture where two converging continents collided and crumbled. You won't be surprised to learn that the exact geography of Rodinia is still a matter of some debate, but there are a lot of constraints on any model, including geological and paleomagnetic data and the arrangement of cratons on today's globe. One area of agreement is that the Rodinian supercontinent was located near the equator, with Laurentia, what is now most of North America, at the center. And significant fragments of what are now other continents accreted to the north, south, east, and west. One widely cited model has Baltica and portions of what are now Brazil and West Africa to the southeast, with additional fragments of what is now South America to the south, portions of Africa to the southwest. However, at this stage, I think it's safe to say that the relative positions of much of what is now Australia, Antarctica, Siberia, and China are uncertain. Rodinia seems to be distinctive in one important respect. All earlier supercontinents were probably incomplete. That is, there may well have been one or more large, isolated big islands, something like a smaller version of Australia or Antarctica. The evidence comes from minor sediments that represent coastal sedimentary deposits that formed during the period of Columbia's presumed stability, about 1.6 billion years ago. However, a curious lack of similar sedimentary evidence suggests that once Rodinia was completely assembled about 1.1 billion years ago, virtually all of Earth's land was clustered tightly together. This circumstance results in a 250 million year interval between about 1.1 billion and 850 million years ago, unlike any other in Earth's history, at least going back more than 2 billion years. Basically, there are no sedimentary rocks from that age range. That lack points to the fact that there were probably no shallow seas between continents of the type that saw the deposition of the 1.6 billion year old belt Herschel supergroup. That's why geologists have concluded that all of the continents must have fit neatly together, and that there weren't any large inland seas, so you can easily imagine a hot, dry, equatorial supercontinent of Rodinia with a desert-like interior, not unlike Australia today. Think of that. For 250 million years, the sedimentary rock cycle basically shut down. So now we see that from a plate tectonics point of view, the Boring Billion was pretty intense. Between 1.8 billion and 850 million years ago, two supercontinents, Columbia and then Rodinia, were assembled, each producing a dozen mountain ranges by continental collisions, and in between those two great gatherings of lands, when the Columbian supercontinent rifted apart, we find some of Earth's most impressive sedimentary rock deposits. That's a significant amount of geological change for a boring time interval. And so far, we've only looked at 1/4 of Earth's surface. That's solid land. Whatever the exact geometry of the continents, every expert is in agreement that the supercontinent Rodinia must have been completely surrounded by a much, much larger super ocean. This ancient globe-encircling body has been named Mirovia, after the Russian word for global. If, in fact, the Mesoproterozoic era was boring, then Mirovia is the principal reason why. Think back to the previous half-billion years, and the Great Oxidation Event, which was a pivotal geological transition, but was primarily a time of changes in atmospheric chemistry. Earth's atmosphere went from having essentially no oxygen to maybe 1% or 2%. That's an epic chemical change as far as the surface environment goes, but to Earth's vast oceans, such a change in the composition of the atmosphere was insignificant, because the oceans contain more than 250 times the mass of the atmosphere. A small change in the composition of the atmosphere, even a 1% increase in oxygen, a very long time for oceans to change. In this case, about 1 billion years. It's not possible to measure directly the composition of the ancient oceans, so geochemists who want to understand ocean history study rocks and minerals that formed in these oceans. They measure a host of chemical elements and their isotopes because the oceans hold at least minor quantities of almost every element in the periodic table. The details of all that chemistry can be quite overwhelming, but we'll focus on 5 key elements, each of which tells us something about how oceans change through time. The main storyline is provided by oxygen, sulfur, and nitrogen, all of which are found in the atmosphere and play key roles in life, as well as the metals iron and molybdenum. Let's put this in perspective by thinking about what came before and just after the boring billion. Prior to the Great Oxidation Event 2.4 billion years ago, the oceans were rich in dissolved iron. But iron could only have been maintained if the water column was utterly devoid of oxygen or other oxidants, because oxidants would have caused iron oxides to precipitate. The oceans also had to be low in sulfur, because sulfur and iron would have precipitated out as the iron sulfide pyrite. The atmospheric changes 2.4 billion years ago altered the ocean's iron cycle in 2 significant ways. Some iron must have been removed as iron oxides in shallow coastal waters, both directly by reaction with oxygen or indirectly as oxidized weathering products washed into the sea from the land. In addition, atmospheric oxygen rapidly weathered and eroded sulfur-bearing minerals, which flowed into the oceans and also reacted with iron. In combination, these chemical changes triggered the massive deposition of so-called banded iron formation, commonly known as BIFs. We discussed these distinctive ocean floor sediments when looking at how the living Earth of 3.5 billion years ago already featured layer upon layer of red and black iron minerals. You may have seen them used as ornamental stone, and they represent most of the world's easily accessible iron ore reserves. BIFs didn't form all at once. 2.4 billion years ago, the oceans held a lot of iron. So BIF deposition continued episodically for another 600 million years or so. Anyway, by the time we get to the boring billion, 1.85 billion years ago, the oceans were still anoxic, but they had lost most of their dissolved iron. Now, let's fast forward about 1 billion years and compare. By 800 million years ago, it appears that Earth's oceans were pretty much oxygen-rich from top to bottom. The crux of the boring billion is what happened to the oceans in between. That's the reason this time has been called the intermediate ocean. In 1998, geologist Donald Canfield of the University of Southern Denmark offered the fascinating proposition that sulfur, not oxygen, played the central role in Earth's changing ocean. In fact, lots of us in the field now refer to a sulfur-dominated Mesoproterozoic ocean as the Canfield Ocean. Canfield's clever thesis appeared in the December 3rd issue of Nature after almost a year's delay by initially reluctant reviewers. It was titled, "A New Journal for Proterozoic Ocean Chemistry, and that short paper transformed the way many of us think about the nature of Earth's oceans through deep time. The basic idea is simple. First, the Great Oxidation Event produced enough oxygen to influence gradually the distribution of many oxygen-sensitive elements, including iron, which was rather quickly stripped out of the water column and deposited as BIFs. But there wasn't nearly enough oxygen in the air to change the chemistry of the oceans all at once. One of the first big chemical changes was that enhanced weathering and oxidation of minerals on the land, and that introduced lots of sulfur in the form of sulfate runoff into the oceans. Hence, the intermediate ocean lost its iron, was still poor in oxygen, unlike today, but gradually became enriched in sulfur. And it took 1 billion years for oxygen from the atmosphere to displace the sulfur. Once you know what to look for, there's lots of evidence to support this idea. For one thing, the fossil record reinforces the view of a static intermediate ocean with equally static biological evolution. I find it wonderful that some rocks deposited between 2 and 1 billion years ago preserve microscopic fossils of amazing quality. In North America, we have the 1.9 billion-year-old Gunflint Chert. In northern China, the 1.4 to 1.5 billion-year-old Gaozhang Formation, and in the Ural Mountains of Russia, the 1.2 billion-year-old Avsean Formation, all contain minute fossil microbes that are so perfectly preserved that you can see some in various stages of cell division. These cells look exactly like modern living cells, but in spite of their amazing preservation, there's absolutely nothing novel about the life from that time in history. Cells from that billion-year interval look the same as those that came long before and those that came long after. And I think that's because the long period of the anoxic, sulfitic, intermediate ocean brought both good news and bad news to life. On the one hand, the influx of sulfate was a positive thing, as it provided an excellent source of energy for some microbes that gain energy by reducing the sulfate to sulfide, which is a molecule of nothing but 2 sulfur atoms. Many hints persist in the fossil record, including distinctive molecular biomarkers and sulfur isotope data that point to thriving coastal populations of green and purple sulfur bacteria in the Mesoproterozoic era. Now, similar sulfur-eating microbes persist today in some anoxic environments where they produce organic sulfur compounds that, by the way, they just smell awful. Linda Kay likes to joke that the Mesoproterozoic was the smelliest time on Earth. That's kind of a riff on Roger Buick's dullest time on Earth line. When was it smelly, I once asked her, and she replied, I think it was smelly the whole time. Well, the really bad news for life was its absolute reliance on the element nitrogen. The only readily available source of nitrogen on Earth is nitrogen gas. That's N2 in the atmosphere. About 80% of the atmosphere today, and an even higher percentage 1.5 billion years ago. The problem is that life can't use nitrogen gas. Instead, cells require nitrogen in its chemically reduced form called ammonia, or NH3. Out of necessity, life has evolved a clever protein, an enzyme called nitrogenase, which takes nitrogen, the gas form, and converts it to ammonia. But there's a big problem. The nitrogenous enzyme depends on a cluster of atoms containing sulfur plus a metal, and that metal is either iron or molybdenum. But neither of those metals was widely available in the intermediate ocean. Iron had been almost completely removed during the formation of BIFs. And molybdenum, which is readily available in the modern ocean, has an affinity for sulfur as well as oxygen, and is only soluble in water when the water is relatively oxidized. And during that anoxic time of the intermediate ocean, effectively during the entire boring billion, both molybdenum and iron were only in the oceans along weathering coastlines in relatively shallow water. Don Canfield's Sulfide Ocean has been followed by a stream of publications linking Mesoproterozoic geochemistry, paleontology, and tectonics. A couple of decades ago, specialists in those disciplines didn't always have a lot to say to each other, but today the fields are inextricably linked. And we now see the core reason why the boring sulfur and starved for nitrogen under intense pressure to adapt, barely hanging on in the narrow coastal zone of the continents. Next time, we'll see how a complex collection of causes, including moving continents, microbes, and sedimentary rocks, finally brought the boring, smelly billion to an end. Earth often undergoes change at a stately pace, measured in hundreds of millions of years. We've just seen how that still mysterious interval from 1.85 billion to 850 million years ago provides ample evidence for the vast scales of time and space that we have to embrace if we're going to understand Earth history. That boring billion-year interval also underscores the inexorable processes of the ever-so-gradual changes that have characterized every stage of our planet's evolution and which continue to operate today. What's obvious from the geological record is that by 850 million years ago, Earth's near-surface environment had changed irreversibly from its state a billion years before. The increasingly oxygenated ocean margins of the fragmenting Rhodinian supercontinent teemed with algae and other microorganisms, while the dispersing continents were poised to burst with new life. The mysterious and not so boring billion holds important lessons for us today. Earth certainly has the potential to settle into stasis. For 100 million years or more, our planetary home can find a stable and benign balance of its many competing forces. Many factors have come into play: gravity and heat flow, sulfur and oxygen, water and life, and all of those factors can find and maintain a stable equilibrium for hundreds of millions of years. But it need not always be so. If pushed too far, Earth can become unbalanced and reach tipping points with consequences to climate and to life that are difficult to anticipate. Growing evidence suggests that rapid changes may disrupt the near-surface environment in a matter of years. And that appears to be exactly what happens next. The Proterozoic eon, which encompassed most of the second half of Earth's history, nearly 2 billion years, from 2.5 billion to 542 million years ago, was a long time interval of sharp contrasts. In its first half-billion years or so, was perhaps the most newsworthy, as it witnessed the great flourishing of photosynthetic algae and the consequent rise of atmospheric oxygen. Oceans transformed from their ancient iron-rich state as the immense banded iron formations were deposited on the ocean floor. The living world of cells also transformed with the innovation of complex cells with nuclei, the precursors of all plants and all animals. The middle billion years of the Proterozoic eon was much less eventful, though far from downright dull. And then we come to the final frenetic 300 million years, which constitutes the tail end of the Neoproterozoic era. That was perhaps the most dynamic time interval of all the Proterozoic, with continental breakup and assembly, repeated radical climate swings, epic shifts in ocean and atmospheric chemistry, and the rise of animal life. And you might wonder how such radical changes could have all taken place in a few 100 million years, when the previous billion years was so uneventful. It turns out that feedback loops hold the key to understanding such surprising changes. Earth's systems of water, rock, atmosphere, and life are complexly interconnected. Air, water, and land may appear to us superficially as separate spheres, which change over very different scales of time. After all, the weather report varies daily. Ocean shorelines change over millennia. Rocks cycle over millions of years. And supercontinents take hundreds of millions of years to assemble and break apart. Yet every Earth system affects every other in ways both obvious and also ways hidden from view. The This realization brings us to what ecologists call the law of unintended consequences. Namely, when you're dealing with a complex system, you can't change one characteristic without changing other aspects, and often in ways that are difficult to predict. Let me tell you about 3 recent examples of the law of unintended consequences. The most amusing of the 3 has to do with the rare flowering plant, the Peters Mountain mallow, that's only known from the forested southwestern part of Virginia. In an effort to preserve the dwindling population of these plants, the Forestry Service did everything it could to prevent forest fires from wiping out the remaining few examples. But they couldn't stop one fire from sweeping through the area, and it appeared that every last Peters Mountain mallow was destroyed. The assumption was that, in spite of their best efforts, the plant had gone extinct. That was until the next spring when the forest was covered by new mallows. You see, it turned out that the Peters Mountain mallow requires the heat of a forest fire to germinate the next generation. By preventing forest fires, the well-meaning forestry officials were actually disrupting the ancient life cycle of the plant. It's now widely realized that forest fires, far from being destructive, can be essential to the health of forest ecosystems. For example, by keeping tree falls and underbrush under control. Preventing forest fires for many years can also cause much more destructive blazes, fueled by the accumulated piles of fallen dead branches. A second, more serious example of the law of unintended consequences occurred in the Aral Sea, which is a large body of water located in Central Asia. In the mid-20th century, the Aral Sea was ranked among the 4 largest lakes in the world, with a total surface area of more than 25,000 square miles, or about the size of the state of West Virginia. 2 large rivers feed the Aral Sea in a region where the land is largely arid desert. In the 1960s, the government of what was then the Soviet Union decided to divert some of the water in those rivers to irrigation systems that they hoped would produce large crops of cotton for export. I suppose they thought that taking a little water from 2 big rivers wouldn't have much of an effect, but it was a disaster for several reasons. First, the irrigation system was poorly designed. The water flowed through unlined ditches, and it just disappeared into the ground, with estimates that as much as 75% of the water was lost. Then, to save the cotton farms, more water was diverted, and the Aral Sea began to shrink. To make a long and sad story short, by 2007 it was only 1/10 the size it had been a few decades earlier. The results of the shrinkage were striking. The Aral Sea fishing industry, which had employed tens of thousands of people, simply disappeared, with dozens of fishing boats stranded high and dry in the desert. What's more, industrial waste and agricultural runoff that had been carried into the sea became incorporated into the large salt flats that were left behind by the receding waters. And these dangerous wastes were picked up by the wind and breathed in by people living in the area, causing major health problems. In 2010, the Secretary General of the United Nations declared the Aral Sea one of the planet's most shocking disasters. Fortunately, in the 21st century, the countries in the region began a program to restore the Aral Sea, and the results of their efforts are encouraging. A system of dams has allowed water levels to increase. There's been a modest restoration of the fishing industry as well, but it's pretty shocking to think that one of the world's largest lakes can disappear in a matter of decades through seemingly small changes. The third and most sweeping environmental disaster is also the poster child for the law of unintended consequences. That's the Lake Victoria disaster. This episode has even become the focus of a documentary film called Darwin's Nightmare. Now, go back to the optimistic boom times in Central Africa in the 1960s, when beautiful Lake Victoria, as the largest lake in Africa, was becoming a prime tourist destination. The millions of people who live on the shores of Lake Victoria know firsthand about that law of unintended consequences, because what was once a rich fishing ground and the source of most of their protein has been radically altered by the introduction of a single new species, the Nile perch. Sport fishermen seeking a greater challenge for the growing tourist market introduced this large, aggressive predator into the lake. The perch thrived and rapidly ate up populations of smaller fish that not only provided an essential part of the local diet, but also controlled populations of algae and parasite-bearing snails. Unchecked, live algae spread over the lake surface, while dead algae sank, decayed, and consumed oxygen in deeper water where fish used to live. Snails have also multiplied and have become a serious health hazard because they carry parasites that can affect humans. Native fishermen now rely on Nile perch, which weigh up to several hundred pounds each, rather than smaller fish. But this change carries its own ecological consequences. Unlike the small fish that were sun-dried, Nile perch must be roasted over fires. Lake Victoria's shoreline, each year stripped of more trees for this purpose, is suffering extensive soil erosion and further unanticipated changes to the lake's ecosystem. A single new species has thus drastically altered a vast ecosystem. Okay, we've looked at 3 examples of complex systems and the law of unintended consequences: the Peters Mountain Mallow, the Aral Sea, and Lake Victoria. What do they have in common, and what lessons can we learn about Earth? Well, first of all, they were all set in motion by human actions, and that clearly didn't happen to our planet hundreds of millions of years ago. But more generally, in each instance, a complex system was disrupted by changing just one thing. And that one change, something as small as introducing one new species or diverting a part of a river, led to a cascade of consequences. It's possible to analyze these kinds of system change in terms of positive and negative feedback loops, as well as tipping points. Let's look at a house, which serves as useful, though not an exact metaphor for our home planet. Like Earth, a house is a complex system with many interconnected parts. And when you buy a house, you should find out many things. When was it built, for example? As well as the age and configuration of any additions or major renovations. You want to obtain details about the materials used in the construction of your house, as well as information about their installation from the foundation to the roof. Of course, it's essential to learn about the plumbing system and the source of water, as well as the air handling system, the furnace, the air conditioner, and their sources of energy. If you're a smart home buyer, you'll also find out about all kinds of potential risks, from fire, from carbon monoxide, and there's termites and carpenter ants, there's radon, asbestos, leaks, mold. You may have noticed that this homeowner checklist is a good metaphor for the way geologists think about Earth. We want to understand Earth's origins and major transitions, the nature of the rocks and minerals, the movement of water and air, the sources of energy, the risk, geological hazards. Your house also displays many of the same complex behaviors that we see at the scale of Earth, because different systems are interconnected in sometimes surprising and unexpected ways through negative and positive feedback loops. These 2 terms mean almost the opposite of what you might guess. Consider the familiar example of a cold winter day. As temperature drops below your comfort level, the thermostat responds by turning on the furnace, and the temperature rises for a time. Once the house warms up, the thermostat senses that the change is complete and the furnace shuts off. By the same token, on hot summer days, the air conditioner trips on if the inside temperature rises too high and then shuts off when things have cooled down. These are negative feedback loops, where changes in your house's temperature are linked to processes that mitigate the changes. So in a negative feedback loop, change is met and canceled out by the negative of the initial change. In a similar way, Earth operates through the operation of many negative feedback loops that help the planet maintain climate in a more or less narrow range of conditions of temperature, of humidity, composition at and near the surface. So, for example, warming oceans result in more clouds, which reflect sunlight back into space and cool the oceans. Likewise, rising concentrations of atmospheric carbon dioxide cause global warming. The warming accelerates rock weathering, but rock weathering gradually consumes excess carbon dioxide and leads in turn to cooling. On the other hand, houses occasionally display self-reinforcing or positive feedback. When when the increase or decrease in some environmental condition is amplified. Ironically, these so-called positive feedbacks often have very bad or unpleasant consequences. Perhaps the most familiar example is a fire that starts to burn out of control. As long as a fire is confined in a fireplace, it behaves in a more or less stable and predictable way. However, if uncontrolled, the growing heat of a raging fire causes the fire to spread even more rapidly. And a similar effect can occur with cold. Imagine what happens if your heating system fails on a cold winter day. The water pipes can freeze and burst, which causes cold water to flood your home, making the house even colder and less livable. Many of the greatest uncertainties regarding Earth's changing climate today focus on this kind of potential positive feedback loops, where one change might trigger even bigger cascading effects. Eventually, such a complex system out of balance can reach a so-called tipping point, where a set of reinforcing changes push the entire system into an entirely new state. So, for example, rising sea levels will lead to coastal flooding, which might result in more evaporation and more rainfall, which in turn might cause even more coastal flooding. A warming ocean is likely to cause the widespread melting of methane-rich ice at and beneath the ocean floor, which could add the greenhouse gas methane to the atmosphere and cause even more warming, which could release even more methane. It's difficult to predict when and how extensive such climate tipping points might be, but we have only to look at the runaway greenhouse effect of our neighboring planet Venus with its thick carbon dioxide atmosphere and 900-degree Fahrenheit surface temperatures to see the potentially catastrophic effects of positive feedback. Now, Venus likely reached its methane tipping point very early in this history, perhaps within the first 100 million years, and it has never recovered. Like a house, Earth can enjoy long periods of relative stability and gradual drift, or it can experience sudden and dramatic change that may disrupt ecosystems worldwide. The boring billion, to the extent that it was really boring, must have been a consequence of many negative feedbacks that more or less moderated the near-surface environment and held major changes in check. Naturally, change did happen. Nothing in Earth's surface could stop plate tectonics, which is driven by the second law of thermodynamics and the imperative that heat must find a way to move from Earth's hot core to the cool surface. Nevertheless, in spite of ongoing plate tectonics activity, including the great slow-motion migrations of land masses and the assembly and breakup of supercontinents, Earth's climate during the interval that encompassed the Mesoproterozoic era seems to have been fairly stable. There's no evidence for great ice ages. It appears that the chemistry of the oceans remained both anoxic and sulfur-rich. The paleontological record similarly shows nothing that would suggest that life evolved in any new characteristics with planetary consequences comparable to photosynthesis. Scientists who specialize in studying rocks in this age conclude that there weren't any major tipping points to alter the atmosphere, the continents, or the oceans between 1.85 billion and 850 million years ago. That age of stability was about to change with the breakup of Rodinia about 850 million years ago. Earth was about to reach its first tipping point in a long time, and the next few hundred million years experienced some of the most remarkably rapid and extreme near-surface fluctuations in our planet's history. About 850 million years ago, most of Earth's many continental masses were still clumped together near the equator in the dry and utterly lifeless Rodinia supercontinent. The immense ocean of Mirovia, perhaps only punctuated by a few isolated arcs of volcanic islands, surrounded this denuded, rusty red megacontinent. The inhospitable atmosphere contained only a small fraction of today's oxygen budget, too little to form much of an ultraviolet protective ozone layer. So if you were to travel in time to that ancient red land, and if you had a reliable supply of oxygen and very strong sunblock, you might be able to survive along the coast, and you'd have a bland diet of algae. But be assured that life would be desperately difficult on that desolate Neoproterozoic world. Like all supercontinents before and since, Rodinia could not last. The great equatorial land mass was like a heat-trapping lid, and thermal energy continuously built up, melting and thinning the crust and eventually rifting the supercontinent into more manageable fragments. In the aftermath of the breakup, a combination of events conspired to push climates to previously unknown extremes. For most of Earth's history, the climate has been moderated by negative feedbacks. Climates have varied throughout Earth history, to be sure, with warmer times of limited ice caps and glaciers and high sea levels, and other times of extensive glacial ice and low sea levels. But there's no evidence that these fluctuations reached life-threatening extremes prior to 850 million years ago. However, beginning about 850 million years ago, several changes disrupted the former equilibrium and pushed Earth to a climatic tipping point. The most important global transformation was the gradual fragmentation of equatorial Rodinia. The first of several rifts was 850 million years ago, when the Congo and Kalahari cratons, what are now parts of southern Africa, began to separate to the southwest of the otherwise intact supercontinent. About 800 million years ago, a second small rift zone isolated the West African craton, which appears to have moved in a southerly direction from the main landmass. Rodinia's breakup had accelerated by 750 million years ago, when extensive volcanism and flows of basaltic lava reveal major new cracks in the crust. The supercontinent basically split down the middle, north to south, as a great rift zone separated to the west, and continental clusterings of Laurentia, Baltica, Amazonia, and other smaller cratons to the east. Rifting on a global scale had huge consequences. With rifting came tens of thousands of miles of new coastline and an associated acceleration of coastal erosion and sedimentation. Dynamic sedimentary basins formed in the growing seas between diverging continents. And for the first time in a long time, the rock record picks up again. That almost complete cessation of sedimentary rock deposition that had begun in the Mesoproterozoic era had lasted almost 250 million years, that is, for the entire lifetime of Rodinia. And with the new pulse of sediments came mineral nutrients, and with nutrients, photosynthetic microbial life, green and purple and brown algae flourish in the shifting, fragmenting world. The ocean, which had long limited life's expansion by its meager store of phosphate, molybdenum, manganese, iron, other essential elements, experienced a blossoming as never before. Paleontologists tell the story of a time of shallow, sandy tidal zones with thick mats of slimy green filaments and offshore waters choked with smelly algal rafts. The tectonic events associated with Rodinia's destruction conspired to alter Earth's oceans, atmosphere, and climate. And here we see the dramatic and unexpected intertwined consequences of change. Atmospheric oxygen rose in part because of the profligate coastal algal blooms, but also in a positive feedback because increased production of algal biomass led to rapid burial of organic carbon. Okay, there's a tricky sequence of causes and effects here. Throughout Earth's history, carbon-rich biomass has been one of the most important consumers of oxygen. The more biomass that's produced and decayed, the faster oxygen is consumed. You can think of modern forest fires as representing an unusually rapid and efficient way of how biomass that isn't buried can also consume oxygen. By the same token, as carbon-rich black biomass, that is, materials like coal or oil, are buried more quickly, the more quickly oxygen levels also rise. Think of it this way. There's a certain large number of oxygen atoms in the crust available to make rocks or to make atmosphere. Those oxygen atoms can be bonded to carbon atoms in the forms of carbon dioxide gas in the atmosphere and limestone in rocks, or they can bond to each other as atmospheric oxygen. The more carbon atoms that are buried as black biomass, the more oxygen atoms are left over to bind to themselves and form the oxygen molecules we breathe. But how can we possibly know if biomass was buried and if oxygen levels rose 800 million years ago? Rocks almost never preserve a record of the atmosphere and trapped gas bubbles, so there's no direct measurement possible. But it turns out that limestone, which precipitates as carbon-rich mineral layers on the shallow ocean floor, preserves a subtle, telltale record of the atmosphere. It's the stable carbon isotopes in the limestone that point to changes in the production rate of algae. Life's essential chemical reactions, such as the conversion of water and carbon dioxide to sugar in photosynthesis, almost always concentrates the lighter isotope carbon-12 relative to the heavier carbon-13. Consequently, the carbon in biomass, and in the Proterozoic eon, when I say biomass, I'm really saying algae, whether it's dead or alive, is always isotopically light compared to the inorganic carbon in limestone. During normal times, when microbial life flourishes and light carbon is depleted from the oceans, limestone from this time displays a complementary heavy isotope signature. At times of unusually rapid biomass burial, as more of the lighter carbon isotope is systematically removed from the oceans, the leftover carbon that makes limestone is even heavier on average. Sure enough, limestone deposited along the shores of fragmenting Rodinia 790 to 740 million years ago is unusually heavy, in some cases more than 1% more massive than in ordinary times. That means that algae must have bloomed far and wide and been buried at an unprecedented rate. And here we see the feedbacks that ultimately affected Earth's climate. The climate that had been stable for 1 billion or more years, microbial life consumes that greenhouse gas, carbon dioxide, which is constantly pumped into the atmosphere by volcanoes. In normal times, CO2 inputs to the atmosphere from volcanoes and other deep sources pretty much balance the carbon dioxide that's consumed by photosynthetic life, plus the weathering of rocks, plus the uptake of CO2 by the oceans. That's a global balance that keeps atmospheric carbon dioxide concentrations relatively constant. It's not always a perfect balance. Just over the past century, for example, atmospheric CO2 has been rising steadily. However, during the Neoproterozoic era, the opposite happened. Pulses of rapid algal growth consumed carbon dioxide at unprecedented rates, so CO2 levels may have dropped to their lowest levels in more than 1 billion years, indeed possibly the lowest levels in Earth history up to that point. This change rapidly reduced the contributions of carbon dioxide to greenhouse warming. For a time, warming would have enhanced rainfall and coastal weathering, which added more nutrients to promote even more algal growth. So that's one feedback loop that ultimately had the effect of reducing the amount of atmospheric carbon dioxide and thus cooling the planet. There were probably a number of other climate-altering feedback loops as well, each of which interacted with the algal bloom story in ways that aren't yet completely obvious. One of these that may have accelerated Earth's cooling is a fascinating and rather convoluted feedback loop related to both plate tectonics and to CO2. The rifting of Rodinia must have resulted in tens of thousands of miles of new seafloor volcanoes, not unlike the 40,000 miles or so of mid-ocean ridges on Earth today. These volcanoes manufactured hot ocean crust that's less dense and therefore more buoyant than old, cold ocean crust. Now, such hot, relatively buoyant crust must have significantly raised sea levels compared to before. It follows logically that the period after 750 million years ago, when Rodinia was fully broken up and rifting was proceeding all around the globe, was probably a time of extensive flooding and shallow inland seas. And here we need a chain of causes and effects. Inland seas mean more evaporation and increased rainfall on the continents. More rainfall leads to more rapid weathering of exposed rocks along the shoreline and the burial of those weathering products in offshore sediments. But rock weathering rapidly consumes the greenhouse gas carbon dioxide, and those lower CO2 levels in turn can lead to more global cooling. And here we see how integrated the Earth system is. Changes in plate tectonics, in ocean chemistry, in sedimentation, in microbial life, and in climate are interdependent. You simply cannot study any one attribute of Earth in isolation from the others. It must be obvious that these stories of the distant past, stories of a planet that would be all but unrecognizable to us if we could visit its alien surface, hold powerful lessons for us today. Feedback loops have been very much in play throughout Earth's history and remain so in our modern world. The details of such complex feedback loops hundreds of millions of years ago are still being resolved, and new, ever more intricate chains of causes and effects are being proposed all the time. But it's clear that the Neo-Proterozoic Earth, after its long period of stability, was poised for epic changes.
A giant snowball travels through space. Earth's surface and atmosphere has cooled, and ice covers virtually the entire globe. It's about 1 billion years before the present, and Earth is in a period of extreme glaciation. Most continents are positioned near the equator, with surface rocks now insulated by ice. Carbon dioxide from volcanoes begin building a runaway greenhouse effect in the atmosphere. Earth is at a tipping point.
For most of the Proterozoic eon, Earth's near-surface environment shifted only gradually, with no obvious periods of extreme global warming or cooling. Yet for a combination of reasons that are still being revealed, 750 million years ago, around the middle of the Neo-Proterozoic era, Earth entered a period of extreme climate instability, the likes of which had never been seen before. This unsettled interval began with a brutal ice age. Geologists deduce the timing and intensity of these changes because glaciers leave an unambiguous suite of sedimentary features. First and foremost of these glacial leftovers are thick, irregular layers of diagnostic rocks called tillites. Tillites preserve chaotically jumbled piles of sediments that are carved out in, concentrated by the action of ice flowing over rock. That includes sand and gravel, as well as angular rock fragments and fine rock flour. Glaciers also alter the landscape in very diagnostic ways. They leave behind characteristic rounded and elongated outcrops of bedrock that have been shaped by what might be called rivers of ice. That ice also carries along rocks and boulders which scratch and polish outcrops of bedrock in very distinctive ways. Other geological clues to glaciers are thick deposits of finely layered, barbed sediments, paper thin, alternating light and dark layers representing seasonal runoff deposits into glacial lakes, coarser in the spring, finer in the fall. Added to these sedimentary features are erratic boulders and mound-like accumulations of gravel called moraines. It's this diverse combination of features that points to regions of ancient glaciation. As a geologist, you're trained to spot such evidence when you go into the field. And indeed, field geologists around the world have discovered that these glacial features occur abundantly in rocks of ages between 580 and 740 million years old, just about everywhere they look around the world. These data have piled up for more than half a century. Evidence for extensive glaciation is found on every continent and at latitudes from the equator to the poles at more than 50 localities, and the list keeps growing. As a result, the geological community has come to realize that an ice age far worse than anything we had imagined once gripped the entire globe, beginning roughly 740 million years ago. This evidence for an abrupt and drastic climate change started about 740 million years ago. It didn't come all at once. In fact, it's been accumulating for decades when geologist Paul Hoffman and 3 colleagues at Harvard and the University of Maryland published a short scientific paper entitled A Neo-Proterozoic Snowball Earth. That was in the August 28, 1998 issue of Science. And let me tell you, that was an electrifying moment for those of us who study early Earth. Lots of scientists have thought about ice ages when the polar ice expanded to lower latitudes, perhaps south into what is now Midwestern United States, for example. But Hoffman and co-workers made the extraordinary leap that at least twice during the interval between 740 and 580 million years ago, Earth had experienced what was not simply an ice age of expanded ice caps, but that our planet had completely frozen over from the poles to the equator. They based their extraordinary claims in part on all those field studies, including their own meticulous field observations of a sequence of rocks from the skeleton coast of Namibia. These Namibian deposits were crucial because, unlike many of the other reports of Neoproterozoic glaciation, the glacial features were made quite close to the Neoproterozoic equator. They documented thick deposits of tillite, which is the sedimentary rock created by glaciers and composed of grains of all sizes side by side with paleomagnetic signals that the glaciers covered the land at about 12 degrees latitude in what today would be tropical conditions. What's more, these weren't alpine glaciers of the kind that form in cold, high altitudes of lofty mountains. These glacial tillites were clearly deposited in the shallow waters of a coastal setting right at sea level. That means the climate must have been correspondingly frigid, cold enough to build up thick accumulations of ice and snow near the equator. That's a sharp contrast to Earth's most recent ice age 20,000 years ago, when advancing glaciers never got farther south than about 45 degrees latitude, and when the fossil evidence clearly points to a relatively warm tropical zone with coral reefs, even during the maximum extent of ice. You know, most of us quickly bought into the Snowball Earth scenario because the Harvard team had accumulated what seemed to be unassailable evidence for massive buildups of glacial ice at sea level close to the equator. Part of the beauty of the Hoffman et al. Article was that they included both obvious geological evidence from the field and more subtle geochemical data from stable isotopes. Indeed, for many scientists reading the Snowball Earth article in 1988, carbon isotopes provided the smoking gun that persuaded us to accept the case for a sudden and catastrophic change. Here's the story the isotopes tell. During the tens of millions of years prior to the first presumed Snowball Earth episode, before about 740 million years ago, as the supercontinent of Rodinia would continue to fragment and shallow inland seas nurtured primitive life, the rapid growth of algal biomass concentrated isotopically light carbon. We've seen how the contemporaneous limestones deposited in the coastal waters around the broken pieces of Rodinia are correspondingly heavy. But you can turn this argument on its head. If microbially produced limestone and so forth slows down or stops completely, then the carbon isotopes in the limestone must become, on average, much lighter. In other words, as life sequesters less and less of the lighter carbon-12 isotope, then that lighter isotope must enter the limestone. And that's exactly what Paul Hoffman and his colleagues found in rocks from 740 million years ago. There was a huge decrease of more than 1% in heavy carbon in limestone that were formed just before the Great Snowball event. And then there was a break when no limestone or sediments of any kind other than glacial deposits are known. And then just after the appearance of glacial deposits about 700 million years ago, more limestone with extremely light carbon, suggesting a sharp decline in life. So that's the evidence for global glaciation. But it really raises more questions than it answers. For almost 3 billion years, Earth had existed without any global ice event. So what happened? Why was the time 740 million years ago different? The model that's emerged relies on a sequence of nested feedback loops, each of which drove Earth to a colder and colder state. One feedback depended on continental weathering, which was accelerated in hot and humid tropical zones. Rocks simply weather faster in warm and wet zones, and that pulls more and more carbon dioxide from the air. Another feedback was triggered by the massive blooms of photosynthetic algae, which scavenged even more CO2 out of the air. The drop in carbon dioxide weakened the greenhouse effect, and and as Earth's atmospheric greenhouse weakened, its climate cooled. That means that ice caps began to form and grow larger at the poles. Now, this fresh white ice and snow effectively reflected lots more sunlight into space, so that solar energy was also lost, creating a positive feedback that cooled Earth even more rapidly than before. So we have an unstable situation, which ice sheets were spreading to lower and lower latitudes from both poles, while the still warm equatorial continent and the profligate algal growth continued to remove more and more carbon dioxide from the skies, further weakening the greenhouse effect. The net result was that Earth's climate was at least temporarily skewed out of balance. So it reached one of those unpredictable tipping points. Earth cooled quickly. More and more sunlight was reflected into space, more ice formed, the global greenhouse weakened, and ultimately white ice converged from both poles toward the equator. Eventually, in the most extreme, hard snowball version of this story, ice may have completely encircled the globe. In this scenario, the one promoted by Paul Hoffman and his colleagues, estimates are that average Earth temperatures plunged to 50 degrees Celsius below zero, while a mantle of ice up to a mile thick surrounded the entire globe. Think about the profound implications of the snowball Earth hypothesis. According to this model, for many millions of years, Earth was almost completely encased in ice, or at least slush. The white snowball Earth was unable to soak up solar radiation. It must have seemed forever locked in an icy shroud. Temperature almost never rose above freezing, so the water cycle was greatly slowed down to a process of sublimation of ice and snowfall. And the global ice age would have shut down almost every ecosystem. Earth's formerly abundant microbial life, including all that green algae, was all but wiped out. Indeed, we suspect that life survived primarily in those isolated refuges at or near volcanoes and their associated hot springs. It's certain that some microbes would have persisted in the perpetual darkness of ocean floor hydrothermal vents, particularly near mid-ocean rifts, where new basaltic crust was being formed. So those ecosystems probably have been around for billions of years and aren't much affected by the surface environment. It's also possible that other sparse surviving populations of photosynthetic algae found their homes in sunlit zones of cracked, thin ice or shallow open water near the warm flanks of volcanoes. We find such microbial communities even today in the coldest parts of Antarctica. So it's easy to see how once the snowball Earth events reached the tipping point, that things would settle into a very long time of cold. What might be harder to understand is how could Earth possibly have recovered from that seemingly static, icy state? And here it's pretty easy to find an answer in the inexorable power of plate tectonics. Indeed, so many aspects of Earth's changeable surface are literally rooted in our planet's much deeper ceaseless churnings. Nothing occurring at the surface of our planet, and certainly not the white veneer of ice and snow, could stop plate tectonics. The key link between the deep interior and the surface is the global network of volcanoes. Constant volcanism, along with constant emission of volcanic gases like water vapor and carbon dioxide from hundreds of black cones that must have poked through the ice, slowly tipped the balance. Carbon dioxide and water vapor are the dominant volcanic gases, so CO2 once again began to build up in the atmosphere. And with the land entirely jacketed in ice, there was no way to remove that CO2 by rock weathering. And with the microbial ecosystem all but shut down and photosynthesis all but ceased, the carbon dioxide wasn't removed by life either. That means the carbon dioxide concentrations must have gradually risen, and probably to levels not seen in more than 2 billion years. It's likely that CO2 concentrations increased eventually to perhaps several hundreds of times modern levels, and that rise in greenhouse gases must have triggered a new positive feedback, a runaway greenhouse effect. Here we have the snowball scenario in reverse. Sunlight still scattered off the white landscape, but carbon dioxide in the atmosphere bounced that radiant energy right back to the surface, inexorably warming the planet. As the atmosphere warmed, small patches of equatorial ice melted, perhaps for the first time in many millions of years. As the darker land became exposed, more and more sunlight was absorbed by rocks and soils, and the warming accelerated. The oceans, too, began to clear of their white covering as positive feedbacks between the sun and the surface caused Earth to become warmer and warmer. So far, the Snowball Earth story seems like a pretty neat and tidy package, but a central mystery remains. The Snowball Earth episodes were by no means the first periods of glaciation on Earth, nor would they be the last. But the Neoproterozoic snowball intervals stand out in history. To the best of our knowledge, never before and never since have such extreme cold spells occurred on Earth. Why should that be? We've seen that almost every aspect of Earth history repeats itself. Furthermore, the preceding billion-year interval was a time of exceptional global stability. So how can one relatively brief period of Earth history have been so different from any other? The contrast is made starker by looking at the two earlier periods of glaciation, which were evidently a lot less severe. The earliest known ice advance was a relatively brief event revealed by tillite deposits on ancient South African cratons, which occurred about 2.9 billion years ago in the middle of the Archean eon. That it should have taken so long for Earth's ice caps to expand from poles toward the equator is in itself something of a mystery. Astrophysicists tell us that early in Earth history, the sun was much fainter than it is today, or than it was in the Proterozoic eon. In fact, 4 billion years ago, the sun had only about 70% of its present radiance, and it was not more than about 80% of its present energy output during that first mid-Archean glaciation. Why no Snowball Earth episodes back then? With so much less energy coming from the sun, there must have been other warming mechanisms in play. Many scientists suggest that much higher levels of greenhouse gases, including carbon dioxide, methane, and perhaps an orange hydrocarbon haze, were critical at moderating influences that held off cooling, glacial forming events. It's also certain that early Earth experienced much higher heat flows from the turbulent deep interior, so greater volcanic outputs must have played a role. Ironically, Earth's first glacial episode, 2.9 billion years ago, may have been the result of too much greenhouse gas. If the atmosphere's methane content rose to high enough levels, as it may well have done before the rise of oxygen, the chemical reactions high in the stratosphere would have produced more and more of the big hydrocarbon molecules that may have given early Earth a hazy orange sky. But if that haze became just a little bit too thick, then some of the sun's energy, which was formerly trapped by the greenhouse effect, would have been blocked in the upper atmosphere, and Earth's surface would have cooled somewhat. But let me emphasize that whatever the cause of Earth's ice age almost 3 billion years ago, it was nowhere near the extent nor the severity of the Snowball Earth interval. There was a second, somewhat longer and more severe cooling episode that was marked by extensive glacial deposits between about 2.4 and 2.2 billion years ago, which followed the breakup of equatorial Kinnerland supercontinent. And here we see some familiar causes in operation. Atmospheric modeling suggests that increased weathering and sediment deposition along newly formed coastlines gobbled up much of the carbon dioxide. At the exact same time, the rise of oxygen in the atmosphere by photosynthesis caused the destruction of atmospheric methane, which was perhaps the dominant greenhouse gas at the time. The fainter sun, which had an energy output perhaps 85% of water levels, was simply insufficient to maintain as effective a greenhouse effect, and a protracted cold period ensued. Nevertheless, that ice age wasn't anywhere as severe as the Neoproterozoic Snowball Earth. And for the next 1.4 billion years, that's almost a third of Earth's entire history, there is no trace whatsoever of an ice age that's been found in rocks anywhere on Earth. For all that time, Earth's climate seems to have remained in a remarkable balance, never getting too hot, never getting too cold. Looking at the previous glacial episodes at 2.9 and 2.4 billion years, and knowing of the coming cycles of snowball hothouse crisis, it's difficult to explain such a long time when changes were litany of possible negative feedbacks, all of which may have contributed to stasis, but it's hard to pinpoint the single cause, especially when there's no obvious effect. So what was unique about that time 740 million years ago? Naturally, scientists have ideas, and I'd like to share a mix of these speculations, including my own. Let me warn you that what I'm about to say is not necessarily the correct explanation, but this is how the science of ancient Earth progresses. We look at the limited fragmentary data, we see correlations, and we come up with possible explanations. The first factor, and the one I find especially compelling, has to do with ocean geochemistry and its effect on life. All life has certain chemical requirements for survival. One of those basic requirements is a steady supply of the element nitrogen in a form like ammonia. That's NH3, with a nitrogen atom bound to 3 hydrogen atoms that can be used to make amino acids and many other key biomolecules. But the only abundant source of nitrogen at Earth's surface is nitrogen gas, the molecule N2 that makes up 80% of the atmosphere. The problem is that nitrogen gas is exceptionally unreactive with anything. That's why it's hung around in the atmosphere for billions of years without reacting with rocks or the ocean. Life solves the nitrogen problem with that clever enzyme called nitrogenase, which we met 2 lectures ago. Nitrogenase starts with nitrogen gas and water and makes ammonia. In order to work, this enzyme needs a little energetic boost from a cluster of atoms that includes either iron or molybdenum atoms. So all microbes in the Proterozoic eon needed a reliable source of iron or of molybdenum, and that's the key. During the entire period of the Boring Billion, after the deposition of those massive banded iron formations, the ocean had become completely stripped of iron. They've been that way iron poor ever since. Today's oceans have a significant quantity of molybdenum, which is soluble in water that's oxidized, but molybdenum was lacking in the oceans throughout the entire Boring Billion. Okay, so for a billion years, the oceans were poor in both of the essential nitrogenase elements, iron and molybdenum. Paleontologists have concluded that algae could only have flourished right along the coastlines where weathering and river runoff supplied both the iron and molybdenum needed for life. So how does this relate to climate change? Limited life meant limited consumption of carbon dioxide. So there was no dramatic drawdown of the greenhouse gas. Only since 850 million years ago was microbial life able to grow unimpeded. Add to this growth all the new extensive coastlines and shallow inland seas, and Earth suddenly experienced an explosion of carbon dioxide consuming life. Another part of the explanation for the uniquely radical consequences of the snowball Earth rests on the distinctive positions of continents and oceans just prior to and during Rodinia's breakup. The key here is the sharp contrast between oceans and land in their ability to reflect or absorb sunlight. Darker oceans have a correspondingly low albedo. That means they soak up most of the sun's energy and warm up in the process. Dry, barren land, by contrast, is much more reflective. It bounces more of the sun's energy back into space. A dry and desolate supercontinent like Rodinia, sitting as it did on the equator, would have bounced much of the incident sunlight back into space. Such a juxtaposition of polar oceans and equatorial continents would have exaggerated any global cooling event, since the equator receives much more solar energy than the poles. It's extremely unlikely that our modern world would experience the same kind of cooling because we now have 2 major oceans straddling the equator and significant land masses at high polar latitudes. What's more, unlike 750 million years ago, we now have a terrestrial biosphere with forests, fields, other vegetation that significantly decreased the land's albedo. That means much more solar energy is absorbed by today's green landscape than during the barren Neoproterozoic. That doesn't mean Earth can't undergo new and severe climate changes. It just won't do so in quite the same way as that topsy-turvy Neoproterozoic world. So we don't have all the details nailed down, but I think it's possible to come up with a pretty plausible set of explanations for why the period immediately after the Boring Billion saw such dramatic swings in climate, and I'm not done with those changes. When we left the snowball Earth about 700 million years ago, climate was changing fast. Carbon dioxide had built up in the atmosphere from continuing volcanism in the absence of algal growth or continental weathering. Greenhouse warming had started to melt the equatorial ice. As dry land and open oceans began to emerge, more of the sun's radiant energy was added to Earth's total budget. A sudden release of the potent greenhouse gas methane from shallow deposits of hydrated methane called clathrates may have contributed to the warming as well. In a geological blink of an eye, perhaps much less than 1,000 years, the climate lurched. The snowball Earth transformed to the hothouse Earth as temperatures soared to what may have been record levels. For a long time, perhaps as long as 30 million years, a warm climate prevailed, but the hothouse ensured its own demise. Some of the greenhouse gas was removed by reactions with rocks. The denuded land was exposed to rainfall laced with corrosive carbonic acid. That was another consequence of high atmospheric CO2, so it weathered rapidly. The influx of mineral nutrients coupled with the resurgence of sunshine also led to explosive algal blooms that consumed the greenhouse gas. And as with the snowball Earth, all of these events are duly preserved in the carbon isotope record. For the next 150 million years, Earth cycled between these extremes of climate, not just once, not twice, but at least 3 times the ice gathered and circled the globe, and then at least 3 times it retreated. The global climate swung drunkenly from Arctic to tropical and back again. It's taken geologists quite a while to sort these details out. It's tricky in part because during the actual snowball Earth episodes, there aren't many rocks being deposited, so it's a matter of teasing out part of the story from a lack of evidence. The first episode, which is well documented now, is called the Sturtian glaciation. It began about 740 million years ago and reached a maximum about 720 million years ago. Climate swung to hothouse levels by 700 million years ago. Then came the second big snowball event called the Marinoan glaciation at 650 million years ago, which was followed by another hothouse interval, and finally came the less severe Gaskir's glaciation, which occurred at 580 million years. Now that we've seen this pattern emerging multiple times from the rock record, the picture is becoming ever clearer. Thick accumulations of rock in a dozen countries reveal more and more details of this dramatic climatic cycle. As ice retreated, the glaciers left behind huge piles of plucked up boulders, ground up rock, lumpy tillites composed of all grain sizes, and polished, rounded bedrock. Soon after the warming cleared most of Earth's surface of ice, thick crystalline deposits of carbonate minerals covered the tillite layers. Carbonates on top of tillite is another telltale sign of the dramatically warming oceans. In fact, the carbonates form so rapidly in the CO2-saturated seas that giant crystals several feet long blanketed the shallow ocean floor. These distinctive calcium carbonate deposits tell us of a time when Earth's near-surface environment had swung wildly from its chemical equilibrium. For a time, following Paul Hoffman's 1998 publication of the Snowball Earth model, geologists everywhere embraced the novel scenario. But I have to say that the mood has shifted significantly. Try as they might, the climate modelers have found it exceedingly difficult to find any combination of circumstances that could encase all of planet Earth in ice. Their calculations suggest that even at times of the most significant global cooling at the poles, the equator should remain a rather temperate zone with little ice. What has changed the consensus viewpoint are new observations by field geologists who now find evidence of moving ice and surface waves, and ocean currents that persisted during what was thought to be the maximum deep freeze. Those are clear signs of at least some open water, so Earth couldn't have been completely encased in ice. That's why, for most geologists, this hard snowball model has been replaced by a more benign slush ball scenario. The slush ball with an only partially ice-encased Earth is the new model to beat. Paul Hoffman is retired now, but he still promotes his original model and counters that it's hard to date those signs of open water and that the slush could represent conditions just before or just after the glacial maximum. How might we tell the difference? One of the more intriguing emerging lines of evidence supporting a hard snowball is a striking, short-lived pulse of banded iron formations laid down about the same time as the ice is thought to have covered the globe. Now, it's hard to explain such iron deposits because the oceans have been stripped of their iron more than 1 billion years earlier, before the start of the Boring Billion. So how is it possible that the oceans become recharged by iron and triggered a new pulse of banded iron formations? Well, one persuasive model suggests that the snowball episode sealed the ocean, cutting off all oxygen to the ocean water column. Meanwhile, seafloor hydrothermal vents continued to pump fresh iron from the mantle into the deep ocean. Gradually, iron concentrations rose, only to be rapidly deposited as new banded iron formations when the glacial episodes ended. Such controversies are nothing new in science, and they tend to focus energy and original ideas on solving interesting problems. And I must say that the snowball versus slush bowl debate has remained very low-key and a lot friendlier, with a lot more goodwill and humor than most. As Paul Hoffman retired, a new generation has taken up the challenge, but the answers still lie hidden in the rocks. So, keep watching the news. New discoveries will be made, and the last chapter in this story of Earth's global ice ages hasn't been written quite yet. The leading surface mineral on Earth, roughly 3/4 billion years ago, was ice. This is also the start of a second great oxidation event, and in this lecture we'll see how ice and much higher levels of oxygen transformed the planet once again. To be more precise, the Neo-Proterozoic era featured a time of snowball episodes, followed by hothouse episodes, not once, not twice, but at least 3 times between 740 and 580 million years ago. And together, these episodes raised the level of oxygen close to modern levels. The living world had to be dramatically affected by such extreme global changes. Think about all the consequences. During the global winters lasting millions of years, the lands were covered by thick ice, so that very little erosion could occur. Without erosion, essential mineral nutrients couldn't flow into lakes and oceans, so microbial life was greatly limited in extent. It's very likely that life was restricted to those few places where mineral-rich hot waters spewed out of volcanic zones. By contrast, after each glaciation, the melting ice and exposed continental shores must have contributed pulses of essential mineral nutrients to every coastal ecosystem. The element manganese, which is required for photosynthesis, was one such vital mineral supplement. And molybdenum, which was used by many cells for processing nitrogen, was also available in much greater quantities. There were also new pulses of iron, nickel, copper, and vanadium, all of which are employed in various metabolic roles. Like iron, these are metals that form not only metallic bonds, but also covalent bonds, or ionic bonds capable of joining organic molecules. But of all of the many chemical elements that were available in only limited supplies during global glaciation events, phosphorus may have been the most important in those freshly exposed Neo-Proterozoic seas. Just to remind you, the element phosphorus is the 11th most abundant element in Earth's crust, where it's concentrated by pegmatites. It's also the 6th most abundant element in the human body, and absolutely essential for all life. Phosphate, the 5-atom group of 1 phosphorus surrounded by 4 oxygens that gave rise to hundreds of new minerals inside pegmatites, also helps to form the backbone of those familiar genetic molecules DNA, the double helix, and RNA. In addition, phosphorus helps to stabilize many kinds of cell membranes as part of phospholipids, and phosphorus bound to oxygen atoms plays a key role in storing and transferring chemical energy in small molecules called ATP, or adenosine triphosphate. Those small energy-rich molecules are found in every cell in your body. The ancient story of phosphorus and its effects on life has been a long-time fascination for Dominic Papineau, who comes from Quebec and was for a time my colleague at the Geophysical Laboratory. What Dominic Papineau has discovered is that some Neoproterozoic ecosystems, including the coastal ecosystems of the fragmented Rhodinian supercontinent, phosphorus might have been the most crucial limiting nutrient. That is, the total biological productivity, the mass of all the cells, may have been directly tied to the amount of phosphorus that eroded off rocks on land and was carried into the sea by runoff. Dominic imagines times between each global glaciation when there was an unprecedented amount of phosphorus flowing into the shallow coastal seas of the Neoproterozoic era. That's because the exposed land can be rapidly eroded by the big buildup of carbon dioxide in the atmosphere, causing carbonic acid to rain down on the land. And that was at the same time that all the ground-up rock flour produced by the glaciers was rather suddenly released, providing even more phosphorus for life. So life thrived at this time as cells gobbled up every bit of phosphorus, and then those phosphorus-rich cells died and settled to the bottom. The mineral they formed is called phosphorite, which can refer to any mineral with a substantial percentage of phosphate. Well, it turns out that some of the world's largest deposits of phosphorite are composed of thick layers of sediments laid down as phosphorus-rich cells when they died and they settled to the bottom. And they're concentrated in the same time intervals as those snowball hothouse cycles. Stagnation of the oceans during snowball events was followed by periods of vigorous circulation conducive to production of phosphorite. Some of the largest examples are in China, along what used to be a continental margin. Dominic has traveled the globe in search of these ancient phosphorite deposits in northern Canada, in Finland, in Africa, and in India. In each locality, he studied their distinctive geological settings, their associated fossils, and their fascinating chemistries. Major deposits dated to this period are known on every continent except Antarctica, and in each case, they're found on top of glacial related sedimentary rocks. One key consequence of this phosphorus increase was the production of massive phosphorus-driven algal blooms along the coast. You can imagine the shallow seas around all the continents choked with green algae spreading miles in every direction in smelly, thick mats that pumped atmospheric oxygen up to new levels. By some estimates, the atmosphere rather quickly jumped from only about 1% of today's oxygen to more breathable concentrations close to modern levels. So algal blooms produced unprecedented amounts of oxygen. Under such conditions, surface rocks quickly weathered. They oxidized and hydrated to all sorts of minerals that formed much more easily than before. Microbes quickly learned to exploit these chemical reactions for their own energy source. The more oxygen meant it was easier to gain energy from oxidation reactions. What's more, life could creep onto land for the first time because the increased oxygen budget meant that more ozone was produced high in the atmosphere. Remember, ozone is the molecule with 3 oxygen atoms that acts as a natural sunblock against harmful ultraviolet radiation. So the rise in atmospheric oxygen that was caused by the blooming of algae along the shores triggered positive feedbacks that increasingly protected life on land from radiation and allowed new ecological niches. Yet paradoxically, rotting clumps of dead algae that settled to the ocean floor consumed every bit of oxygen in the deep waters. So algae in the Neoproterozoic acted much like runaway algal blooms in many areas today, where excess fertilizer runs off into coastal waters. Photosynthetic oxygen-producing cells cause deep waters to return to a deadly anoxic state. As a result, the great resurgence of microbial life following the snowball Earth episodes may well have led to a newly stratified ocean, with a living, oxygen-rich layer near the surface and dead, anoxic waters below. The strong parallels between the algal blooms 600 million years ago and those of today, triggered by large fluxes of phosphate from fertilizer runoff, provide an important incentive to study the kinds of dramatic changes that affected ancient ecosystems. And this story of the intimate connections among global climate and atmospheric chemistry and near-surface mineralogy and microbial life underscores a critical point about our planetary home. Everything is interconnected, often in surprising and even paradoxical ways. This realization is relatively new, and it's changing the way many Earth scientists approach their work, not to mention science education in departments of geology. Indeed, even the names of those departments have changed. In the 1960s, almost all universities had departments of geology. But now you're more likely to find departments of Earth and environment, or Earth and planetary science, or even Earth systems science. When I began my graduate studies in mineralogy and crystallography in the 1970s, the predominant viewpoint was that studies in biology were all but irrelevant to geology. Geologists study rocks, and the grand cycles of igneous, sedimentary, and metamorphic rocks were widely viewed as absolutely separate from the cycles of life. Even as plate tectonics came to be accepted doctrine, the roles of moving plates in the distribution of life were only dimly seen. And that was primarily life on land or shallow coastal regions where fragmenting continents could effectively isolate different populations. There certainly was no obvious connection between life and plate motions themselves, nor did anyone talk about life having a big influence on the formation of minerals. So it's not surprising that when I asked my thesis advisor whether to take a biology course as my final elective, he persuaded me to take quantum mechanics instead. "You'll never use biology," he assured me, and his advice, I suppose, made a lot of sense in the context of the 1970s. That view has almost completely changed. Now Earth scientists realize that all and every aspect of Earth's evolution, from geochemical origins of life 4 billion years ago to the present day, life's influenced geology, geology's influenced life. I want to give you a sense of this new mindset by describing 3 relatively recent ideas that have been proposed about how life has changed Earth's near-surface geology and mineralogy. The first of these intriguing ideas was described in 2006 by geochemist Martin Kennedy, who teaches at the University of California's Riverside campus. Kennedy and 4 co-authors devised a particularly novel, albeit speculative, scenario for the codependence of rocks and life. The title of their article included the phrase, "the clay mineral factory," and it appeared in the March 10th issue of Science. The hypothesis is that life greatly accelerated the production of clay minerals, hence the clay mineral factory. And the clay minerals in turn had important feedbacks to life. Specifically, the rise of atmospheric oxygen from a few percent to its present level was accelerated by positive feedbacks between microbes and clay minerals. I think this is a pretty clever idea. Here's how it works. First, recall that clay is a generic term for a large group of dozens of different minerals that consist primarily of ultra-fine-grained microscopic particles that soak up water and form sticky, gooey masses. We met clays in their uniquely sticky properties during stage 4 of Earth's mineral evolution, at a time when the first granite protocontinents were just beginning to appear. The principal mode of clay mineral formation on land is weathering, especially weathering by chemical alteration under the wet, acidic conditions of the kind that predominated during the late Neoproterozoic era. Carbon dioxide was still abundant, so a rain of carbonic acid would have been too. That's why Kennedy and co-workers suggest that the rapid post-glacial weathering of the continents between about 700 and 580 million years that produced an order of magnitude more clay minerals than before. Added to chemical weathering or biological processes, there's a lot of growing evidence from the fossil record that microbial colonies began to colonize the coastal landscape at about this time. And it turns out that microbes can be especially efficient at turning hard rock into soft clay. It's not entirely clear how they do this trick, but scientists in Japan and France and the United States have shown that all sorts of common rock-forming minerals, especially feldspars and micas, break down as much as 10 times faster when they're attacked by microbes. And the minerals that are most commonly produced are clay minerals. So 600 million years ago, huge quantities of clays were being generated both by chemical weathering and by microbes. Among the most important characteristics of many clay minerals is their ability to form strong chemical bonds to organic biomolecules. Clay minerals often develop a slight electrostatic charge on their surfaces, which complements the polarity of many organic molecules. Those molecules, like water, have positive and negative ends, so the molecules stick to the clays. The greatly increased production of clay minerals, coupled with the extensive blooming of algae, would have sequestered huge amounts of carbon-rich biomass. large volumes of clay minerals washed into the oceans, they would have sequestered those biomolecules in thick piles of fine-grained carbon-rich sediments. Now, recall that burial of organic carbon is equivalent to releasing oxygen into the atmosphere. It's just like photosynthesis, which takes carbon dioxide and turns it into biomass while releasing oxygen. So, according to the Kennedy clay mineral factory scenario, burial of carbon tied to clay minerals led to the rise of oxygen, which further accelerated weathering and the chemical production of clay minerals on land, which led to even more carbon burial. That's how complex feedbacks among weathering, microbes, clay minerals, and the atmosphere may have contributed directly to the rise of atmospheric oxygen and the evolution of the modern living world. The second of our three examples of feedbacks between biology and rocks relates to the rare and toxic element mercury. The mineralogy of mercury is a fascinating story in itself, but here I want to focus on one biochemical process that may have profoundly influenced Earth's mercury cycle. Living cells, whether in algae or in people, simply cannot tolerate much mercury. The mercury binds strongly to key biomolecules and disrupts their functions. So sometime in the history of Earth, probably after the initial great oxidation event, microbes developed a very clever and sophisticated method of eliminating mercury by binding it to a methyl, or a carbon plus 3 hydrogen group. The resulting chemical compound, called methylmercury, is very soluble in water and is easily passed through the microbial cell membrane and thus voided from the cell. Today, numerous kinds of primitive microbes are able to tolerate mercury-rich environments by producing and excreting methylmercury. So, what does the microbial production of methylmercury have to do with geology? Well, this is just speculation on my part, but we recently discovered that Earth's mercury cycle appears to have completely changed about 1.8 billion years ago, right about the beginning of the boring billion. Prior to that time, there were quite a few mercury mineral deposits around the world. But rather suddenly, at 1.8 billion years ago, mercury mineralization just seems to stop. In fact, for another 1.2 billion years, there are simply no known mercury mineral deposits, right up until the last of the snowball events we've been discussing. That's a really strange thing, because mercury should have been continuously recycled by plate tectonics and concentrated in hydrothermal fluids and released in mercury ore deposits when those hydrothermal solutions cooled near the surface. As I say, this is speculation, but it may be that the microbial invention of mercury methylation suddenly changed the mercury cycle. If microbes started pumping lots of methylmercury into the oceans, then very slowly the ocean's mercury concentration would have risen, while this new reservoir essentially took up any excess mercury that previously went into mercury mineralization. It's just one more possible example of feedbacks between life and rocks. A few decades ago, such thinking would have been radical, implausible, but today it's almost mainstream, and it's really fun thinking across disciplines in this way. Topics that used to be studied in isolation: oceans, microbes, ore deposits, plate tectonics, atmospheric composition, weathering, so much more, are now essential parts of a well-rounded earth science education. Never again will a mineralogist be advised to ignore biology. And now to a third example of the remarkable feedbacks that can occur between life and rocks. And in many ways, this example is the least obvious and the sort that's most hidden from view. I want to explain some of the evidence for the conclusion that oxidation below Earth's surface probably lagged, perhaps for hundreds of millions of years later than the appearance of increased oxygen in the atmosphere. This example involves studying the kind of subtle change in a mineral record that would probably never have been recognized before the rise of this new geobiological paradigm. Two rather scarce metal elements that are very sensitive to the oxidation state of their surroundings were key: molybdenum and rhenium. Molybdenum, element 42 of the periodic table, is a member of the column that includes the somewhat more familiar elements chromium and tungsten. Like chromium and tungsten, molybdenum finds important uses in the steel industry for making special alloys of great strength and hardness. We've already discussed molybdenum as an important element for creating the enzyme that allows plants to take nitrogen from the air. Let's review molybdenum's two common valence states in nature. Under more reducing conditions, such as those of the mantle and prior to the great oxidation event, it adopts a +4 charge. This positively charged state is very insoluble in water, so molybdenum 4+ is not easily mobilized or transported. This is why molybdenum wasn't available during the Boring Billion. By contrast, the more oxidized +6 form of molybdenum is highly soluble, and thus it concentrates in hydrothermal fluids, which can dissolve and mobilize molybdenum 6+. When fluids rich in molybdenum 6+ encounter more reducing conditions deep underground, for example, conditions caused by buried carbon-rich organic matter, the molybdenum will revert to its insoluble +4 state and precipitate out as molybdenum minerals. That's how most of the major molybdenum ore deposits are formed. Okay, the other element in this story is rhenium, element 75 of the periodic table. This extremely scarce metal element is present at only about a part per billion in Earth's crust. Its principal uses are in high-temperature alloys, such as those employed for thermocouples for measuring extreme temperatures, where other metals melt. Rhenium's geochemical behavior is remarkably similar to that of molybdenum. Like molybdenum, rhenium has two common valence states in rocks. Like molybdenum, the more reduced +4 valence state is very insoluble in water, so it stays locked in rocks and minerals. And like molybdenum, the more oxidized form of rhenium, in this case it's rhenium 7+, is easily dissolved in water. So rhenium 7+, like molybdenum 6+, is concentrated and transported by hydrothermal solutions. Now by far, the commonest mineral of the molybdenum is the sulfide mineral we've seen called molybdenite, that's MOS2. Most molybdenum mines exploit molybdenite, so it's a very well-studied mineral. And in addition to a few dozen major mining districts, there are thousands of known molybdenite localities that don't rise to the level of economic deposits. So there's a lot of data on molybdenite in the mineralogical literature. Rhenium is never so concentrated that it forms its own mineral species, but chemically, rhenium 4+ is very similar to molybdenum 4+. That means that virtually all specimens of molybdenite contain trace amounts of rhenium. And that's handy because rhenium has a radioactive isotope, rhenium-187, and it decays to osmium-187 with a half-life of about 42 billion years. Rhenium-osmium dating is perfect for determining the ages of any molybdenite sample. Okay, so that's a pretty long preamble to a research project that my group recently completed. Because rhenium is mobilized and concentrated in more oxidizing fluids, I made a simple prediction that more recent molybdenite samples would display higher levels on average of rhenium than those before the Great Oxidation Event. My colleagues Joshua Golden and Melissa McMillan, who at the time were both graduate students at the University of Arizona, then dove into that vast ore geology and mineralogy literature to find reports of the analysis of molybdenite specimens that happen to include both the age of the mineral and the rhenium content. And let me tell you, that was a huge undertaking. They found more than 350 sample descriptions and hundreds of scientific papers in a dozen different languages. Melissa also analyzed another 80 samples in her lab, so we wound up with more than 400 data points from 154 localities spanning the last 3 billion years of Earth history. So we plotted up all the data on a graph of age on the horizontal axis and rhenium content in parts per million on the vertical axis. And the rise in rhenium over time was immediately obvious and quite striking. The first thing you see is that every specimen before about 1.5 billion years ago has relatively low rhenium content. The average value for samples of Archean age, those molybdenites that are greater than 2.5 billion years old in our study, is about 130 parts per million, and no Archean specimen has a rhenium concentration greater than about a part in 1,000. By contrast, during the Mesoproterozoic and Neoproterozoic eras, from about 1.6 billion years to roughly 550 million years ago, the mean rhenium concentration is more than 350 parts per million, with a maximum value of several parts per thousand. So we see a distinct rise between the Archean and the Proterozoic. And rhenium content keeps rising after that. The mean rhenium concentration for Paleozoic air samples, those deposits between 542 and 251 million years ago, it's almost 400 parts per million. And then Mesozoic era specimens with ages between 251 and 65 million years old, they have a mean rhenium content of 444 parts per million. And then the concentrations really soar over the last 65 million years with a mean of more than 600 parts per million. And the highest individual rhenium content of any recorded sample comes from Mexico. It's over 10,000 parts per million. So there's a significant and systematic increase in the average rhenium content in molybdenite from the Archean time before 2.5 billion years ago all the way to the modern era. And we would argue that this striking increase reflects a gradual oxidation of deep water circulating in the crust as a consequence of mobilizing rhenium through enhanced deep weathering processes. That is, there was a gradual oxidation of the subsurface environment following the Great Oxidation Event. What really took us by surprise, though, is the timing of the subsurface oxidation. Remember that the first Great Oxidation Event occurred roughly 2.4 to 2.2 billion years ago. And the second oxidation occurred about 800 to 600 million years ago. Yet our data suggests that the subsurface environment didn't become more oxidized until many hundreds of millions of years after those atmospheric changes. So why did it take so long? Almost a billion years for subsurface oxidation to reflect the changes in atmospheric composition. Recall that the oxygen content of Earth's atmosphere following the Great Oxidation Event has been estimated to be about 1 or 2% of present levels, so maybe just 0.1% of the total atmosphere. And that's roughly similar to the amount of argon in today's atmosphere. If you do the math, it turns out that equals a planet-wide total of about 10 to the 19th grams of oxygen. And that might sound like a lot, but it's roughly equivalent to the oxygen contained in a layer of rock at Earth's surface that's only about half an inch thick. That's only the tiniest fraction of the quantity of oxygen that would be required to oxygenate the upper mile or so of Earth's subsurface waters. And so it's also only a tiny fraction of what would be required to trigger significant mineralogical changes. For Mars, it's a similar calculation. The atmosphere of Mars has a tiny oxygen content of about 0.1%, equal to 4 times 10 to the 13th grams of oxygen. That's amount equivalent to the oxygen contained in about 100th of a cubic mile of rock, or a layer of the Martian surface that's perhaps 1/1,000,000th of an inch thick. The bottom line is that it took a very long time, at least hundreds of millions of years, for low levels of atmospheric oxygen to penetrate down into the subsurface zone where molybdenum and other ores form. By the way, it might be possible to gain even more information on the rates of subsurface oxidation because molybdenite ores are commonly hosted by granite. And it turns out that the grain size of granite can be a very sensitive indicator of the depth of formation. Granites that form near the surface in the upper half mile or so tend to cool quickly, so they're relatively fine-grained, with quartz and feldspar crystals generally no more than 1/8 of an inch across. The deeper the granite, the slower it cools, and so the bigger the average grain size. Our data don't yet incorporate information on the depth of molybdenite formation, but we're working on that. It's plausible that deeper crustal zones on average took longer to experience that influence of atmospheric oxidation. And that's because of the circulation of oxygenated groundwaters. So a systematic trace element survey that also incorporates depth information might point to a gradual increase in the depth of subsurface oxidation that increased rhenium contents in molybdenite, which in turn might hold the key to the timing of Earth's mineralogical diversification from the first Great Oxidation Event to the second. As we peer into Earth's past, to a time 800 million years ago, we find Earth nearing the end of a comfortable and seemingly stable middle age. For a billion years, the planet had been remarkably stable in its climate and life. But then, as Rodinia fragmented, Earth reached that climatic tipping point normal times, steady sunlight and heat-trapping carbon dioxide keep our planet temperate. But as carbon dioxide was rapidly consumed by the weathering of equatorial continents, and as reflective ice spread from both poles to the equator, Earth's temperatures plunged into the first snowball episode. Then, after millions of years, steady carbon dioxide buildup, perhaps amplified by the rapid release of methane from the ocean floors, triggered an equally rapid runaway greenhouse effect. Cumulatively, the snowball hothouse cycles amounted to a second great oxidation event in the history of Earth, which raised the level of oxygen close to modern levels for the first time. But climate is another matter. Perhaps more than any other events in Earth's history, Earth's wildly erratic snowball to hothouse cycles reveal a planet knocked out of kilter. Climates shifted in a matter of decades, while almost every living thing died. Although life at this time consisted of microscopic organisms leaving no detailed fossil record, we can probably assume that major extinction events occurred during this time. But major change on Earth has often led to new opportunities. The flip-flopping Neoproterozoic climate led directly to an unprecedented rise in atmospheric oxygen. That transition paved the way for the first animals and plants, and the colonization of the seas and continents. Having considered oxygen, we turn next time to carbon, the most useful and chemically flexible of all the elements, and to recent efforts to understand the full carbon cycle, from methane and carbon dioxide in the atmosphere to the abundance of life and other types of carbon found not only on the surface, but deep inside the planet. How much carbon does Earth hold? What are the repositories of Earth's carbon? And how does carbon move among those reservoirs? And how have those cycles of carbon varied through deep time? These seem like simple questions, but full answers turn out to offer a great deal of insight into our planet. Carbon is the fourth most abundant element in the universe, according to data from stars and observations of our solar system. But in Earth's crust, at least a dozen other elements are more abundant than carbon. Carbon seems to be missing from Earth's crust. So what's going on? Well, we don't know yet, but plate tectonics and subduction are cycling at least some of Earth's carbon deep into the mantle. And if so, that raises questions about what kind of carbon is down there. Diamonds? Carbonate minerals? Vast new petroleum and natural gas reserves? Or maybe even extremophile life? In this lecture, I want to discuss efforts by the Deep Carbon Observatory, a 10-year, billion-dollar research project to get to the bottom, so to speak, of carbon on Earth. Then, after looking at a range of key unanswered questions about carbon, I want to focus on methane, an important greenhouse gas throughout Earth's history, which is a timely and surprising example of how it's so useful to understand carbon far below Earth's surface. The Deep Carbon Observatory was initiated by the Alfred P. Sloan Foundation. Alfred P. Sloan was president and then chairman of General Motors during the time it became the largest car company in the world. Anyway, he made a lot of money, and he used some of that money to establish the Sloan Foundation in 1934. At any given time, the foundation officers are likely to have one or more big 10-year science programs that adopt an international approach to big global questions. To give you an idea, one amazing recent program was the Census of Marine Life. Ultimately, the Census of Marine Life engaged 2,700 scientists from 80 countries. The idea was to organize a truly international effort with countries around the globe cooperating in an effort to document what lives in the oceans, from the equators to the polar regions. They set about surveying every every sort of life form, from coral reefs and fish to microbes and planktons, and in the process they made wonderful discoveries, including thousands of previously unknown species of sea creatures. In 2007, Sloan was thinking about their next 10-year program, their next big thing. And I happened to be in New York presenting an after-dinner talk on our NASA-sponsored research to investigate the possibility of a deep subsurface origin of life. Now, by good fortune, Dr. Jesse Ausubel, a program officer from the Sloan Foundation, decided to attend that presentation, and it triggered an idea. He then read my 2005 book on the subject Genesis, The Scientific Quest for Life's Origin, and a short while later, I got one of those unexpected phone calls you never forget. Jesse called me. He introduced himself as representing the Sloan Foundation and asked if I'd consider developing a plan for a 10-year international scientific program to study the deep origins of life. Now, he made it clear this was a big program in the hundreds of millions of dollars range, and he offered an exploratory grant of $400,000 just to see if the international scientific community was interested. And that's a pretty big incentive. After some thought, I countered that a big program on the deep origins of life was too narrow, but that a global effort to understand the element carbon from crust to core had real potential for fundamental discoveries. And here's why. Carbon is arguably Earth's most important element. It's key to understanding Earth's variable climate and environment. Carbon has long been and continues to be the central element in our quest for energy. Carbon is also the crucial element of life, and by extension, it's the core element in the design of new drugs and myriad other products. Carbon is a well-studied surface cycle of oceans, atmosphere, rocks, and life. But we remain woefully ignorant of many of the most basic aspects of Earth's deep carbon cycle. Well, the Sloan Foundation agreed, and in May of 2008, we held a workshop-style conference in Washington, D.C. with more than 100 scientists from a dozen countries to see if there was sufficient interest in a cohesive set of scientific questions to warrant a huge investment of time and money. In short, the opinion was unanimous. The role of carbon in Earth is of fundamental importance. The result is the Deep Carbon Observatory, launched in the summer of 2009 and now in full swing with about 1,000 researchers in 40 countries taking an active role. The Carnegie Institution's Geophysical Laboratory is the headquarters of this ambitious 10-year program to understand carbon in our planet. And our resolve is to achieve a new level of understanding of carbon in Earth's deep interior. There are so many things we want to learn about Earth's carbon. Most basically, we want to know how much carbon our planet holds. And it's amazing to me that at this point, we don't know Earth's total carbon budget to a factor of 10, or maybe even a factor of 20. That's because we don't know if there's much carbon in the lower mantle or the core, or even a few parts per million carbon would add up to much more than all the known carbon in the crust. Now, current estimates of Earth's total carbon content range from less than 0.1% to more than 2%. But scientists of the Deep Carbon Observatory are starting to refine that number, and some of our latest estimates have been published in an open access volume called Carbon in Earth. In this 700-page review, we suggest that Earth's metallic core may hold anywhere from 1/4 to 1% carbon. And the mantle might hold even more carbon, some in the form of diamond and carbonates, but maybe as a trace element in much more abundant deep silicate and oxide minerals as well. So many of us now think that Earth's total carbon budget is at least 1% of the planet's total mass. One of the most amazing hidden repositories of carbon is deep microbial life. It turns out that just about anywhere you dig or drill into Earth's crust, whether on land or at sea, there are microbes living in the subsurface. Microbes have been found in drill cores as deep as 3 miles. And they seem to thrive in deep sediments and solid rocks anywhere there's subsurface water, as long as the temperature is below about 130 degrees Celsius. Now, this deep life is sparse, typically with no more than about 1 million individual cells per cubic centimeters. Soils on the surface, by contrast, can easily have 1 billion cells per cubic centimeter or more. But if you integrate all those cells over all of Earth's upper crust, the number of cells is absolutely enormous. By some estimates, the biomass of living cells beneath the surface may be as much as 30% of all the life we see at the surface. Deep microbes, though largely hidden forever from our view, may thus represent a significant fraction of all life on the planet. Now, I have to say that all of that subsurface life, indeed all of life, is only the tiniest fraction of carbon on Earth, but it's a really fascinating fraction. Now, if deep microbes are a surprise, deep viruses are nothing short of astonishing. There's now a lot of evidence pouring in that the subsurface also holds a vast amount of viruses that live, so to speak, beneath the surface. There is debate over the extent to which viruses are actually living, since they lack those typical cell parts. They can't reproduce on their own. They don't quite have a metabolism. They're just strands of DNA or RNA encased in a protein. That's why they are far smaller than bacteria. 5,000 viruses put end to end might equal only the width of a fingernail. Yet viruses on Earth are so numerous that their total length placed end to end has been estimated to equal the length of the Milky Way galaxy times 100. Deep viruses play a couple of key roles that are only just now coming into focus. For one thing, deep viruses have a significant effect on carbon turnover. That is, the rate at which carbon atoms are reworked from one reservoir to another. When viruses kill cells, their carbon atoms get reprocessed by other cells. The deep turnover rate is thus many times greater than previously thought. What's more, deep viruses play a key role in evolution by shuffling and swapping genetic material among microbes. So microbes are constantly evolving by this lateral transfer of genes. And that's because of the way viruses manipulate DNA. Viruses introduce new genes, alter the structures of microbes, and break them down completely into molecular fragments. And they have an absolutely cosmically stunning amount of genetic material to work with. The Deep Carbon Observatory has all this and more among its many objectives. But what's perhaps most important to me are several legacy projects. Those are research efforts that we hope to start, but which will continue long after the DCO has ended its 10-year program. For example, we have begun an effort to instrument every one of the approximately 500 active volcanoes on Earth. We envision a time when anyone can go to the web and find out what their favorite volcano is doing. Video feeds, gas analyses, seismic events, and so forth. School classrooms, interested amateurs, and first responders could follow a volcano and even try to predict eruptions. Then we have a legacy project called the Global Census of Deep Microbial Life, which we imagine hooking up to something like Google Earth, so you can click on any spot on the globe and find out what's known about the diversity of microbes beneath the surface. Other legacy projects involve building reference collections of diamonds, which have been notoriously difficult to obtain from the big diamond companies. That's why cooperative international effort is needed. Diamonds are important to understanding Earth because they are the deepest objects we can hold in our hands, and they hold a treasure trove of information about Earth's interior. Some diamond crystals hold deep Earth minerals, other types of minerals, minerals that reveal the rocks, and minerals from as much as 1,000 miles down. What's more, some diamonds display carbon isotope values that suggest biological processing. I mean, how's that possible? The idea here is that the carbon-rich remains of life are subducted deep into the mantle, where they're reprocessed into diamonds, and when those diamonds come back and reach the surface, they complete a carbon cycle that can last 1 billion years. That's why amassing a research collection of diamonds is so important. And the Deep Carbon Observatory also wants to develop a big data infrastructure so that researchers everywhere have immediate access to key data, not just on carbon compounds, but all Earth materials. And finally, we have a legacy program to design and construct new instruments. And that takes us back to the methane question, because discovering the origins of Earth's hydrocarbons is a centerpiece of the DCO's mission. Let's turn to the lightest of all hydrocarbons, methane, which is a good way to see all this come together. In each of the last 3 lectures, I made passing reference to the gas methane, CH4, which is a powerful greenhouse gas that may have played an important role in the history of Earth's variable climate. Now, when you hear the phrases greenhouse effect or global warming or climate change today, the first chemical that comes to mind is probably carbon dioxide. That's because atmospheric concentrations of carbon dioxide have been increasing year by year, and there has been a great deal of attention to humans burning large quantities of carbon-based fossil fuels like coal, petroleum, and natural gas that produce CO2. The problem that you'll commonly hear expressed is that fossil fuels that took hundreds of millions of years to accumulate in what are now deeply buried layers of sediment are being burned over the space of centuries. Relatively rapid increases in carbon dioxide in the atmosphere might cause global temperatures to rise, which would in turn cause significant shifts in climate, more severe weather, and rising sea levels. And all of those changes could have an adverse effect on human populations. Well, it turns out that carbon dioxide is by no means the most effective greenhouse gas. In fact, methane, or natural gas, that's the smallest hydrocarbon molecule with a central carbon atom surrounded by 4 hydrogen atoms. It's molecule for molecule about 7 times more effective a greenhouse gas than CO2. A sudden release of methane, therefore, would be expected to have a much more pronounced effect on climate than a comparable amount of carbon dioxide. Moreover, part of the concern is the potential positive feedback caused by any methane release. Much of the methane stored near the ocean floor is trapped in a fascinating compound called methane clathrate, which is an ice-like crystalline mixture of water and gas that forms under moderate pressure and cold temperatures. This freezing cold methane ice is amazing stuff. It actually burns. You can check out videos on YouTube. Methane clathrate outcrops on the continental slopes and forms large deposits beneath the ocean floor. Vast quantities of methane, by some estimates, several times all other known methane reserves combined, are locked into these methane ices. The methane in the methane ices must have formed as gas rising from below, either from deeper microbes or from the mantle, and it reacted with cold ocean water. There's also a lot of methane locked in methane clathrates in Arctic permafrost, soils in parts of Siberia, northern Canada, other polar regions that have been frozen for centuries are now thawing and releasing methane at an increasing rate. An extreme positive climate feedback might occur when ocean waters or tundra warm even slightly, which causes the shallowest clathrate deposits to melt. They can release copious amounts of methane gas, and this methane adds significantly to the greenhouse effect, which causes the oceans to warm even more. Some scientists now point to a possible catastrophic neoproterozoic release of ocean floor methane as a way to accelerate global warming, perhaps flipping Earth from cold to hot in a matter of decades. A warming ocean is likely to cause the widespread melting of some of those methane-rich ices that are now found in huge quantities beneath the ocean floor, and which would inevitably add to the greenhouse methane to the atmosphere. Increased methane would increase the greenhouse effect, causing even more warming, and warming could release more methane. That's a positive feedback. Looking back to the Neoproterozoic hothouse Earth episodes, many scientists suggest that a sudden release of methane from shallow clathrates contributed to the warming in exactly this way. In a geological blink of an eye, perhaps much less than 1,000 years, the climate lurched. If we're to understand the potential for this kind of sudden methane release, we need to understand the sources of that methane. For billions of years, methane has accumulated in ocean floor sediments, and the growing evidence now suggests that the methane is coming from 2 contrasting sources. The first process, or rather set of processes, relates to biology. There's no controversy that some methane deposits result from methanogenic microbes that release methane as part of their normal metabolic cycle. These methanogens thrive in oxygen-poor ocean sediments that are found near many known methane reserves. Some very large and and shallow natural gas deposits are thought to have formed by the sustained action of these microorganisms. So, microbes can produce methane, but there is another important biological source as well. When biomass is deeply buried and subjected to temperature and pressure, methane is often produced as a byproduct. This so-called thermogenic methane is very commonly associated with both petroleum and with coal deposits. You've probably seen pictures of a flame high atop some oil wells and refineries. That's where relatively small, non-commercial amounts of methane are being burned off. And you've also heard of coal mine disasters that occur when a spark ignites underground methane seeps. The methane can become trapped in pockets and suddenly released during mining operations. In both cases, the methanogenic and thermogenic methane, it's clear that much of the deep natural gas is a byproduct of biology. Recent experiments in my lab and elsewhere point to additional non-biological sources of methane from a much deeper source that doesn't rely on biology at all. It now appears that in the deep crust and upper mantle, where extreme temperatures and pressures prevail, water and carbon dioxide can react with common iron-bearing minerals to produce methane. Experiments at high temperatures and pressures mimic these suspected deep Earth reactions. In one study conducted in 2004 at the Geophysical Laboratory, my colleague Henry Scott mixed 3 common crustal ingredients: the mineral calcite or calcium carbonate, which is a common carbon-bearing mineral of limestone, an iron oxide mineral FeO called wustite, which is thought to be one of the 3 most common minerals in the mantle, and water. Scott sealed these ingredients in a diamond anvil cell in which 2 gem-quality diamonds act as tiny anvils to compress reactants to pressures thousands of times greater than the atmosphere. He used a laser to heat the sample to more than 1,000 degrees, which matches conditions found in the upper mantle. The diamonds of the diamond anvil cell are transparent, so you can observe the sample in the process of reacting and changing. Henry Scott could see tiny bubbles of methane forming in the sample chamber. It turns out that the hydrogen of water had reacted with carbon from the calcite to form natural gas, with lime and magnetite as other byproducts. Now, lots of other laboratories have duplicated and expanded on this result. Experiments in Russia, Japan, Canada, and elsewhere in the United States have documented the synthesis of hydrocarbons under a range of conditions that represent deep Earth conditions. The bottom line is that experiments show that methane can form and accumulate in Earth's crust both through biological and non-biological mechanisms. These experiments have real relevance to the Neoproterozoic global warming, for deep methane may have contributed to the particularly strong positive feedback. This Neoproterozoic warming scenario depends strongly on the sources of methane. If microbes and thermogenic alteration of biomass produce most of the ocean's natural gas, then clathrate production probably slowed during the snowball episodes, and methane release may not have played such a major role in the subsequent warming. If, on the other hand, a significant fraction of deep methane comes from the lower crust or mantle by non-biological reactions, then stores of natural gas would have built up continually throughout any global cooling spell, even a snowball Earth. That methane buildup could have triggered a much greater feedback. So we want to know where that deep methane comes from. The chemical rationale for deep abiotic methane production is supported by a growing number of experiments. Water plus carbon dioxide plus minerals react under a whole variety of conditions to make methane at high pressure and temperature. Nevertheless, the idea that such reactions contribute significantly to Earth's crustal methane reserves has not met with universal acceptance by the oil and gas industry in the United States. Conventional wisdom in the States, and much of the rest of the world for that matter, points to a biological origin of virtually all hydrocarbon fuels. The history of this question is politically charged. In the mid-19th century, the famed Russian chemist Dmitry Mendeleev, who's known for his ubiquitous periodic table of the elements, he proposed that petroleum comes from a non-biological source. He wrote, quote, "The capital fact to note is that petroleum was born in the depths of the earth, and it is only there we must seek its origin." Mendeleev's hypothesis was promoted in Soviet Russia and in the Ukraine in the second half of the 20th century. And to this day, it informs Russia's successful oil and natural gas industry. Some Russian geochemists still argue that virtually all petroleum derives from deep, abiogenic sources. In their view, some very productive oil wells may be renewable resources, at least on geological timescales. These fields would continuously refill from below from those vast mantle reservoirs. American petroleum geologists don't agree. They have the experience of generations of research on North American deposits to back their claims, and they cite a litany of evidence for an exclusively biological origin for petroleum. For one thing, oil is only found in sedimentary horizons of an age and locality where life once thrived. Petroleum is always loaded with distinctive molecular biomarkers, and the isotopic composition of oil is uniquely lifelike. The trace elements of oil, rich in nitrogen and sulfur and phosphorus, also point to a living source. For many North American petroleum geologists, there's nothing more to talk about. Whatever you think of this strong evidence, the debate between biogenic and abiogenic origins of oil was revisited in North America by the iconoclastic Austrian astrophysicist Thomas Gold, known to his colleagues as Tommy. Tommy Gold taught at Cornell University and continued research and publication until his death in 2004 at the age of 84. He was best known for his realization that rapidly oscillating radio sources in deep space, the so-called pulsars, are in fact rapidly rotating neutron stars. Well, Gold speculated on many other areas of science, from the physiology of hearing to the consistency of the powdery lunar surface. But his most notable publications outside of astrophysics were on the genesis of petroleum and natural gas, and he was an unabashed champion of non-biological origins. Petroleum looks biological, he argued, because there are abundant communities of microbes, what he called the deep, hot biosphere. Those deep microbes use abiotic hydrocarbons as their food, and so microbes overprint abiotic hydrocarbons with their distinctive biochemical markers. Based on this hypothesis, Gold advocated petroleum and natural gas exploration in unconventional, igneous, and metamorphic rock hosts. He was persuasive. Based on his recommendation, a Swedish company drilled exploratory wells into solid granite at the Siljan Ring complex. That's the site of Europe's largest known meteorite impact, dating from over 360 million years ago. That project yielded intriguing, though commercially unsuccessful results, and a lot of unhappy investors lost their money. The answer to this hydrocarbon question, the origin of hydrocarbons, is not yet resolved. And here's where the Deep Carbon Observatory's instrumentation program comes in. How can we tell if a methane deposit on the ocean floor was produced by a rock or by a microbe? Geochemist Ed Young and colleagues at the University of California in Los Angeles think they have a way. Theoretical calculations point to a subtle effect in the distribution of isotopes that might be the key, but not with any ordinary measurement of heavy versus light isotopes. Ed Young and co-workers want to measure isotopologues. Isotopologues are molecules that are chemically identical, but that differ in the arrangement of their isotopes. For example, methane has one carbon atom and 4 hydrogen atoms, so it comes in several different isotopologues. Recall from our discussion of mineral isotopes in Lecture 5 that 99.8% of all carbon atoms are the less massive carbon-12, while 1 in every 500 carbon atoms is the more massive carbon-13. And hydrogen also comes in a less massive version, technically hydrogen-1, but always just called hydrogen, and the more massive hydrogen-2, which is always called deuterium. The typical hydrogen to deuterium ratio on Earth is about 1,000 to 1. It follows that about 1 in every 500 methane molecules incorporates carbon-13, while about 4 in every 1,000 methane molecules holds a deuterium. Okay, measuring trace amounts of either of these two heavy isotopes is hard enough, but Ed Young and colleagues want to do something much more difficult. They want to measure the doubly substituted methane isotopologues. That is the roughly 1 in a million molecules of methane that holds both a carbon-13 and 1 deuterium, that's denoted 13C H3D, or else 2 deuterium, so that would be 12C H2D2. According to their calculations, the ratio of these two rare isotopologues in any given sample of methane depends on the temperature at which it formed. If a methane deposit formed at temperatures below 200 degrees, then it must be microbial. But if it formed at temperatures above 1,000 degrees, then it's most likely abiotic from the mantle. This idea sounds terrific. Just measure the ratio and we'll know how the methane formed. But there's not an instrument in the world that can determine that ratio. Conventional isotope mass spectrometry can't distinguish the two isotopologues for two very good reasons. First, these two isotopologues differ by only a tiny fraction of a percent in mass. So the instrument has to have superior mass resolving power. Second, the isotopologues are present at extremely low concentrations that can't be measured by conventional analysis. So Ed Young and colleagues have designed a new instrument that enhances both the mass resolution and the molecular sensitivity. One of the first actions of the Deep Carbon Observatory was to help fund a $2 million prototype instrument in England specifically to measure the isotopologue ratios of methane. And it will take years to complete this spectrometer and find out if it works. But many scientists think the time and effort is worth the risk. And if, as some scientists suspect, a significant fraction of Earth's deep methane does come from the mantle, then that might just help explain why the neoproterozoic climate shifted so far and so fast. Of course, carbon shapes not only the environment for life, but also the very composition of life as well. Carbon is capable of forming multiple bonds with itself and more than 80 other elements, making it an unmatched building block for chemical behavior. In the next lecture, we'll see carbon usher in a 10th stage of mineral evolution centered around biomineralization. And we will see how biominerals, in turn, allow for the invention of animals.
The snowball hothouse cycle has ended, leaving behind an unprecedented amount of atmospheric oxygen. Mineral evolution gives way to biomineral evolution, as multicellular animals invent hard mineral shells, diversify, migrate, and find their way to every corner of the world.
We've journeyed through almost 90% of Earth history. We've experienced epic changes on land and in the oceans. But we have yet to meet a single animal, or any kind of land plant for that matter. Thanks to parallel advances in geology, geochemistry, and paleontology, we now understand both how and why it took so long for animals to emerge. Animals and plants also set the stage for the next chapter of mineral evolution. Indeed, the rise of the animal kingdom as we know it today would not have been possible without minerals. Conversely, the mineral species of the 10th and final stage of mineral evolution turn out to be equally dependent on life. Animals evolved, as did minerals, and this time the two kinds of evolution are even more closely related than before. As we know, by about 650 million years ago, the concentration of atmospheric oxygen had climbed to near modern levels. Those elevated levels of oxygen, in turn, are likely to have had a direct effect on the rise of complex multicellular life. That's because the only way for organisms to adopt the active, energy-demanding lifestyles of jellyfish and worms was to have a concentration concentrated energy source for rapid and reliable metabolism. Increased oxygen in the atmosphere, and by extension in the ocean's water column, would have provided chemical energy in a form that was much more effective than any oxidant that had come before. Indeed, we see a strong correlation between the timing of the second great oxidation and the earliest known multicellular organisms, which appear in the fossil record about 630 million years ago. So that's just after the second global snowball glaciation and one of the intervals when oxygen is thought to have spiked. To understand this startling, sudden rise of animal life in the Neoproterozoic era, we have to look much further back in time. In fact, more than 1 billion years earlier, but just before the beginning of the Boring Billion. The fossil evidence is sparse, as you might imagine for microbial life, but some of the rare fossils that are preserved point to the rise of a wholly new kind of cellular life at perhaps 2 billion years ago. Before that time, which is in the Paleoproterozoic era, all organisms appear to have been single-celled life, and these forms consisted entirely of cells without internal structures, such as the cell nucleus. But before 2 billion years ago, cells were simpler in their architecture, and the DNA was not isolated into a separate compartment. In many modern cells, by contrast, a central nucleus holds the critical genetic information package in the form of strands of DNA. The difference this innovation makes is that replication of the genetic material in the nucleus is separated from translating the genetic material into proteins outside of the nucleus. This separation allows cells to share the same DNA in the nucleus, but to express that shared genetic material in an increasingly wide variety of new proteins, such as collagen for animals and pectin for plants. This more complicated kind of cell begins to appear in rocks about 2 billion years old. For example, in the Negaunee Iron Formation in Michigan, where one finds exceptionally well-preserved fossil microbes with clear evidence for that nucleus. That's the internal structure that holds the DNA. Not only can you sometimes see the nucleus as a sort of shadow cell within a cell, but these organisms are much, much larger than most of the previous generations of single-celled organisms. So how did that cell nucleus arise roughly 2 billion years ago? According to an originally controversial but now widely accepted idea, first expounded by biologist Lynn Margulis, who spent much of her career at the Amherst campus of the University of Massachusetts, one cell swallowed a second cell whole. Normally, the bigger cell would simply digest the smaller one, but in this case, the bigger cell incorporated the smaller one in a symbiotic relationship, perhaps in order to provide more protection to the vital DNA. This rise of a new kind of cell, the eukaryotes or true nucleus cells, forever transformed life on Earth. I have to tell you a little bit about Lynn Margulis, who was such a creative powerhouse and original thinker. She died still in her prime of invention in November of 2011 at the age of 73. She exemplifies the kind of wildly creative scientist who's constantly coming up with new ways of looking at nature and then proposing hypotheses that most of her colleagues think are a little bit wacky. And while most of the time her most extreme ideas were probably wrong, once in a while she hit upon a really transformative approach. Margulis' scientific career was devoted to understanding how groups of sometimes very different organisms interact with each other and thus co-evolve. A central theme in her work is symbiosis, by which two or more species merge their lifestyles to make one integrated communal organism. And one fairly obvious example is the lichen family, which consists of a fungus that attaches strongly to a hard surface like rock or tree trunks, and then algae that provides chemical energy through photosynthesis. The fungus can't generate food by photosynthesis, while the algae can't attach strongly to rocks. So the two species intertwine and live their lives as one entity, the lichen. Fungi are multicellular eukaryotes that may have appeared long before plants and animals, so their symbiosis with algae could have begun correspondingly early as well. Many animals have symbiotic relationships with bacteria. A termite eats wood, but can't digest cellulose of which the wood is made, while microbes that live in special organs inside the termite can't survive isolated in wood, but can break down cellulose into individual glucose glucose molecules. So the microbes survive on the wood the termite eats, and the termite survives on the glucose that the microbes leave behind. Similarly, and even more surprising, the Human Microbiome Project, sponsored by the National Institutes of Health, has found that bacteria hosted by a healthy human body account not only for 1 to 3% of our mass, but for 360 times more protein-coding genes than the human genome itself, leading some researchers to suggest that microbes contribute more genes responsible for human survival than humans themselves contribute. All biologists agree about these and many other symbiotic relationships, but Margulis saw symbiotic relationships and the sharing of biological inventions as an even more pervasive theme in life's history. In a very real sense, she saw nature as one extremely complex, intertwined, symbiotic network that extended even to non-living parts of Earth. She became well known for her acceptance of aspects of the Gaia hypothesis, by which Earth itself is a kind of living system that responds to its own environment. And I have to stress that she wasn't some New Age mystic. She saw very concrete feedbacks between the geosphere and the biosphere, some leading to global scale changes, others tending to mitigate rapid and extreme changes in climate or in chemistry. These and other ideas stirred up quite a few controversies, in large